Hello and welcome to Intellipaat's data science course. Let's be very honest, data is everywhere around us. From the moment you wake up and check your phone, your sleep tracker, your weather app, your calendar reminders, all of that is powered by data. When you scroll through Instagram, binge watch a show on Netflix, ask Alexa to play a song, or even get a notification about a sale on the shirt you were browsing last week, it's not a coincidence. It's all happening because of data. Gone are the days when companies made decisions based on the gut feeling. Today, every major decision is backed by data. And across industries like finance, healthcare, retail, and even manufacturing, businesses are using data to move faster, make smarter decisions, and get ahead of the competition. According to US Bureau of Labor Statistics, job in data science are expected to grow by 36% between 2023 and 2033, making it one of the fastest growing career paths. Plus, nearly 97.2% of companies have already started investing heavily in data and AI. That's how big this field is becoming. So, if these numbers excite you and you are someone who wants to be part of this fast growing, high impact field, then you are in the right place. We have designed this course just for learners like you. Whether you are a complete beginner or switching careers, this course will guide you step by step, starting from the fundamental of data science all the way to advanced topic in machine learning and artificial intelligence. You will not just understand theory, you will actually get hands-on with real tools, work with project, and build job-ready skills. So make sure you stick with us till the very end, because this course might just be the beginning of your new career. Are you someone who dreams of becoming a data scientist? Keep watching, because we are going to show you how data science works in the real world. Meet Alex. He's a data scientist. Let's take a quick look at what his day looks like as he works on a supply chain optimization project. The first step in solving any problem is understanding the problem itself. And for this, Alex gets in a meeting with the operation team. He asks questions, digs deeper, and figure out what exactly need to be solved. He creates actionable questions such as, is the goal to reduce cost, improve delivery time, or manage inventory better? He also checks if there are any current issue with the system. Once the business goal is clear, Alex moves to the next step, which is data acquisition. This means collecting the right data for machine to learn from and make smart suggestions. Think of it like cooking. Just as you need the right ingredient for cooking, similarly, you need the right data for a data science project. And this, the process of gathering useful information from different sources, is called data acquisition. Alex collects data from inventory system, order management platform, warehouse logs, and third-party suppliers, APIs. And yes, finding the right data takes time, patience, and attention to detail. So once the data is collected, Alex moves to the next step, which is data preparation. Raw data in its natural form is very messy and unstructured. You can't jump into analysis or modeling until the data is structured. And once it is structured, the job is still not done. We still need to clean it, transform it, and organize it. Alex here needs to check the empty row, duplicate entries, missing delivery timestamps, and ensure that there are no inconsistency in the data set. This step is often the most time-consuming part of the entire process. Why? Because here you are making sure that you have the right information needed to solve the actual business problem. So once the data is clean and structured, Alex moves on to exploratory data analysis, or EDA, a very critical step where he identifies the feature that really matter. But why is this important? So let's say you're trying to predict delivery time. Would features like product cost, payment mode, or ID help? Those are basically the order details. They have no influence on the delivery time. So keeping them in our data science process doesn't make any sense. If we include them, we might weaken the model or introduce unnecessary noise. Think of it like cooking for one person. You don't grab everything from the fridge, just the exact ingredients you need. That way you don't overcook or waste time. EDA helps you do the same in a data science project. Focus only on relevant features so that your model is efficient, accurate, and purpose-built. Next comes the step 5, where a data science model will be prepared. Alex already have a clean data at hand. Now he trains this acquired data with machine learning algorithm that fit best to the business problem. He can apply model like random forest, k-means clustering, and linear regression. He trained these models and evaluate their performance. To do that, he used metrics like accuracy score or confusion metrics. These metrics help Alex understand how well models are able to perform on test data after they are trained. Alex usually prefers Python for this, though he also uses R or SQL depending on the requirement. Now you might think that we have accurate model, that means the job is done. Well, not true. Alex now needs to present his finding to business stakeholders again. Alex meets with the business team again to communicate his finding in a clear, straightforward way. He uses tools like Tableau, Power BI, and Excel to create visual reports and dashboards, which are self-explanatory and easy to understand for business leaders. Once Alex gets the approval, he then moves to the next step, which is deploying the model. Once it is deployed, Alex monitors real-time metrics using dashboard and continues fine-tuning the model's performance. And this is how Alex completes a data science project. Every data science project generally starts from business problem, data acquisition, and then come stages such as data preparation, EDA, modeling, reporting, and end with deployment. With Alex's journey, now we have a clear picture of entire data science project lifecycle. So let's move forward and look at how data science is transforming industry today. In retail, it helps forecast demand and prevent stockouts during peak sale periods. In logistics, it finds the most efficient delivery routes and reduces fuel uses. In HR, it helps predict employee turnover and improve team retention. In healthcare, it accelerates diagnosis and powers personalized treatment. A data scientist can take on many roles. You can become a business analyst, machine learning engineer, data engineer, or a specialized supply chain data scientist. In 2025, the average salary ranges from $100,000 to $170,000 depending on your skills and industry. Whereas in India, they earn between 7 lakh rupees to 18 lakh rupees as per Glassdoor. So are you ready to begin your journey as a data scientist? If yes, start today because the world of data is only getting bigger and it needs people like you.
It doesn't matter whether you have a computer science degree in hand or not. Neither does it matter whether you have programming experience behind your back or not. When it comes to getting a job in data science domain, all that matters is whether you have got the skills. It's true that for many aspirants back in the day, acquiring data science skills was only possible with master's and PhD degrees. Considering the fact that data science need mastery over 4 different things such as statistics, programming, machine learning, and business acumen. But what if I tell you that now you can attain this feat and become a data scientist within a year? What if I tell you that you don't necessarily need a master's background to become a data scientist today? Well guys, bear with me till the end of this video and I'll answer how you can make the above 2 things happen. With this video, I'll provide you with the success mantra, the roadmap that will help you become a data scientist all by yourself. But before we begin, make sure to enable both the subscribe button and bell icon for the Intellipaat YouTube channel. Now, first of all, let's discuss why you should consider a career in data science. When it comes to choosing a career domain, you need answers to 3 questions. Does the domain have high demand right now? And will it be relevant in the coming years? Number 2, are there better job prospects available? Number 3, are the salaries lucrative enough? Okay, let's try to break all these 3 questions one by one. First of all, let's talk about question 1 and 2. Right now, if you just go over to the Google search and search for data science jobs available, you'll get to know that on just the LinkedIn job board, there are 7 lakh plus jobs available. If you consider the other job boards, the number of data science jobs available might be even more substantial. Now, that's one thing. Consider this as well. In the last 2 years, 400,000 employees have been laid off by IT companies. And according to the Economic Times report, almost every job was impacted by these layoffs. Some were impacted severely, whereas some faced a less backlash. But consider this, 27% of laid off employees were from an HR background. 22.1% were from software development background, whereas just single-digit amount of people were from data science backgrounds. What that means is AI did not harm the data science jobs at all. Also, since both AI and data science go hand in hand, there are predictions that both these job roles together will produce 80 million jobs by the end of decade ahead. What that means is for data science, both the present and future is quite bright. What about salaries, you may ask? Well, let me tell you that data science salaries are one of the highest in the IT industry. Even the junior data scientist earns an average pay between 7 lakh rupees to 19 lakh rupees in India and $92,000 to $200,000 in the USA. You can see that data science as a career clears all the checkboxes that we set out in the beginning. Hence, definitely data science is a great career option you can go for. Now, having said that, let's move forward and discuss how you can become an employable data scientist all by yourself. Basically, to make it happen, you have to be very strategic about what you learn and how you learn it. After doing a thorough consultation with data science trainers and industry experts associated with us at Intellipaat, we have formulated a roadmap that not only will provide you with the necessary skills, but also will prepare you for data science interviews at top companies. So ideally, the very first thing you need to do is go through the concepts of statistics. See, the term data science itself suggests that you'll be dealing with a lot of numbers. If you lack the fundamental math knowledge, doing so will become very difficult. Even if you were to carry out a simple analysis, let's say you want to know if YouTube changes the color of the subscribe button to green, what will happen? In that case, statistics will be important for you to understand the noise in data, to understand what parameters is critical for captured data, even the basic concept or fundamental ideology behind machine learning like neural network is born out of mathematics. That's why we want you to dedicate a month and a half to revising critical mathematical concepts for data science. See, if you have done engineering and 10 plus 2, you'll already be acquainted with ideas like probability, normal distribution, charts and graphs, etc. All you need to do is revise those concepts and learn few more critical concepts such as mean, variance, bias, Bayes theorem, sampling, hypothesis testing, standard and normal distribution, t-test, etc. To help you do that, we have created a free statistics for data science course. You can just search for the free Intellipaat statistics for data science course over Google and you'll come across this course page. I'll also be dropping it in the description below as well. See, you don't have to become a mathematician here. You just need to understand enough of math to learn and understand the data science concepts. Once you have done that, it's time we get started with the next dependency, that is learning the programming language. For data science, primarily there are two languages to choose from. First one is R programming and second one is Python programming. I would prefer learning Python since it is large-scale programming language and it doesn't just stop at data science. Again, you don't have to become a Python developer. You just need to learn enough of Python programming to be able to do data science course. Here is a list of concepts you'll have to master. For this task, you can dedicate 2.5 months. Getting acquainted with programming language is not going to be as difficult as it might seem to you right now. Once you get started, you'll realize that you have got it. Next up, you need to go through the libraries such as NumPy, Pandas, Seaborn and Matplotlib. Basically, you'll be doing the exploratory data analysis as the first task in any data science process. Hence, exploring these very basic libraries is a must. Learn to create the data frames and NumPy arrays, how to carry out the mathematical operations on them, and learn about different Pandas and NumPy functions. Also explore the different charts available in Seaborn and Matplotlib. Understand what each chart resembles. Basically, comprehend the language of charts and graphs. You can spend 15 days doing this particular activity. Once you have understood how to use these libraries, it's time you grasp the SQL basics and art of exploratory data analysis. Learning SQL is very important because without it, you'll not be able to interact with data systems and gauge the data that you need. Tasks like wrangling are done with SQL itself. So try to gather the fundamentals of SQL and databases. You can dedicate one complete month to learning and practicing with SQL. Also, since we have already dedicated the time to learn statistics and 4 Python libraries, mastering the EDA will not be a difficult task. Basically, you'll discover how to load data, clean it, figure out descriptive statistics and analyze the important attributes, etc. I would recommend you guys to go over the Kaggle, explore many notebooks and figure out how people understand the data. Then try to analyze different sorts of data sets on your own. We can spend 1 month practicing different datasets on Kaggle every day. Doing this activity will give you a boost in confidence as well as help you understand why you did what you did till the point. Next up, you have to take on machine learning algorithms. This is the area where most of the data science aspirants or beginners give up. They try to learn the workings of machine learning algorithms and their logic, but don't comprehend how to apply these algorithms to data and when. They fail to understand a problem in mathematical format and propose a solution using logical reasoning and machine learning algorithms. This is the challenge we need to address at any cost. So, what I would recommend is you should learn machine learning algorithms with a hands on approach. Let's say you understand a certain ML algorithm after watching a video on YouTube, then you need to go onto Kaggle and go through the sample exploratory notebooks based on the very same algorithm. Take pen and paper and jot down what you understood about the exploration. Learn about feature selection techniques, how fine tuning can be achieved, etc. Keep on doing the Kaggle notebook exploration until you gain a knack for picking patterns in dataset. To do this, we would recommend you spend 3 to 4 months. Once you have a deep understanding of machine learning, walk the extra mile and learn about deep learning, natural language processing, computer vision, etc. For this, you can dedicate an extra 3 months. By fulfilling step 6, you'll acquire all the beginner level data science skills that can get you a job. Although it would take 9.5 months to do so, the efforts will definitely pay off. Next, you'll need to work on building your portfolio as a data scientist. You need to have some good projects under your belt. You can get them done by participating in Kaggle competitions and showing off your skills to the world. Not only will this help you build some awesome projects, but it will also provide you with awards and employment opportunities as well. Mention the projects and competitions you have participated in over to your LinkedIn profile. You can spend 2.5 months working on projects and building your LinkedIn presence. If you follow all these 7 steps and dedicate 7 to 8 hours of learning time every week, you'll be able to master data science for sure. I know that keeping track of what we have covered might come as a challenge. So we have prepared a year-long slow-paced study plan for all of you guys. The link is available in the description. Visit it and get started on the data science learning journey. I hope you guys are clear with the data science roadmap. Remember guys, learning skill takes time. There is no shortcut. And if someone commits that it is possible within a shorter duration, please don't follow along. Give time and prepare well, and you'll become the best professional that every company out there is looking for.
If you're new to machine learning, linear regression is the easiest algorithm to understand and implement. In fact, this is the first algorithm you're going to learn at the very start of your machine learning journey. Even though it might seem like a big task, within this video, this concept has been covered in a way that even a high school student can understand it easily. For starters, let me help you visualize what linear regression is all about. Let's say I have some data on the heights and weights of a few people, and I want to use this same data to predict the possible weight of a new person provided his height. Now from this given data, we want to find a pattern that allows us to predict the weight of a new person for a given height. This makes our weight column the target variable and the height column as our input variable. Now how can we imagine the relationship between these two features? Simple thing, we can plot them and understand their relation. Now the simplest way to find this pattern is to assume a straight line relationship between height and weight. This is also called linear regression. The line follows the formula y is equal to alpha into x plus beta. Here y is a predicted weight or predicted feature. X will be the height. Alpha is the slope of the line. It shows how much weight changes with height. And beta is the intercept, that is where the line starts. To make the best predictions, we need to find the values of alpha and beta so that the line fits the data as closely as possible. Now what do we mean by this? Basically, the line should try and touch maximum of the data points. To achieve exactly that, we will minimize the difference between actual and predicted weights. Okay, this might sound a lot, but it's not. Let me hand over the proceedings to one of India's best data science trainers. He's right now leading the AI development team in one of the world's renowned fintech companies. And after he's done teaching, I am 100% sure you will never have to retouch upon this concept of linear regression.
Imagine you have a data set like this. You have weeks and sales, right? So week, W-E-E-K, week, okay? This is the first week, the second week, the third week, the fourth week, and the fifth week. Example. You have 5 weeks, okay? And the number of cars you have sold so far is like this, right? So the number of cars you have sold could be n number, right? So you have, Let's take it like this, right? You have week in one of the variables and the number of cars you have sold so far in those weeks could be 2, 4, 5, 4, 5, some numbers, right? This is the data that has been given to me. Sir, can we mathematically understand in depth how does linear regression work? What does it actually do? And how does it make our life easier? Okay. In order to understand how linear regression works, first we need to plot this data. Okay. We need to take the data and we need to plot it in the XY graph. How do we do that? In a very simple sense, I'm going to take the variable like this. I'm going to take a straight line and I'm going to pass it like this. Okay, I'm going to have this. So this is my x-axis and this is my y-axis. Okay, I'm going to point it out like this. So what is going to be my x-axis? Will week be on the x-axis? Can I say this is 0, this is 1, this is 2, this is 3, this is 4, and this is 5. Can I say it like this? This is the 5-week data. So this is 5, week is X. Okay. What is going to be my Y? The number of cars sold. So can I say this is 1, 2, 3, 4, and 5. So 0, 1, 2, 3, 4, and 5. Anybody has any confusion in what graph did I plot? No, right? It's a simple graph. Nothing complicated. Very good. So in the first week of my graph, how many cars did I sell? I sold 2 cars. So can I have the red pointer point like this? Good. In the second week, I sold 4 cars. So this is 4 cars. In the third week, I sold 5 cars. Okay. So I sold 5th car like this. In the fourth week, I sold 4 cars. So this is 4th car again. And in the 5th week, I have sold 5th car or 5 cars. So, like this. Is this the data that has been given to me with the weeks versus the car sold part? This is the data that has been given to me. Okay. My people, let me ask one question to all of you. Isn't it possible that there is infinite number of lines possible for this particular data? Meaning a line like this is also possible, 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 meaning to solve this problem, infinite number of lines are possible that will pass through the data point. Agree or disagree? I want to identify which line is the best line. Which line represents the best line for this particular data. In the previous example, I said line will pass, but what line? Which line? How do we identify that? We don't know anything. So in order to solve this problem logically, isn't it best to first understand where the line would pass from? Meaning, I'll give you guys an example. Listen to me. Suppose I have a point like this, a single point in a 3-dimensional space. Is this line possible in a 3D space? Is this line possible? Is this line possible? Is this line possible? Is this? Basically, infinite number of lines are possible through one single point. Yes or no? Okay. But will the point move if I fix the point? Meaning, if I tell you this is the fixed point, the point won't move, correct? Only the lines are possible through that point. Agree? Yes or no? Okay. So listen to me. Can I not do one thing that is a guaranteed good point? I mean, the point that I'm recommending right now is a good point. What do you mean? In your x-axis, what is the mean of your x-axis? Can somebody tell me what is the mean of x-axis? Basically, the mean x bar of mean and x bar or y bar of this. What is the mean of x-axis? Is it going to be 3, the number 3? And what is y bar? What is the mean of y bar? 4. Agree, disagree? The minute you plot the data, the first thing you should do is take the mean and take the mean of x and take the mean of y. So can I say that the mean of x is 3? So it is going to pass here. I'm going to take a different color. Give me 1 second. I'll choose purple. I'll choose peach. Yeah, peach is good. Okay. So control Z. Give me 1 second. Is this the mean of x-axis? This peachy line that you see? Very good. What is the mean of y? Is this the mean of y? The minute you took the mean of x and mean of y, did you get a point for reference where the line should pass from? The minute you took the mean of x and the mean of y, you kind of got a reference via which a line could pass. Agree, disagree? But in this scenario also, listen to me. In this scenario also, isn't this line possible? Isn't this line possible? Isn't this line possible? Oh, it's complicated. So many lines are possible, but it's okay. We'll solve a problem one step at a time. Is this step clear to everybody? Take the mean of x and the mean of y. Step number 1. Take the mean of x and take the mean of y. Okay. Now, what you need to do is this. Okay. Your weak data, I'm going to take it as x. So what is the x data that has been given to me? 1, 2, 3, 4, and 5. Everybody agrees? This is my x-axis data. Very good. What is the y data? It is 2, 4, 5, 4, and 5. Okay. This is my x-axis data and this is my y-axis data. Okay. What you need to do right now, the minute you calculate this part, x and y, so can we take first data point and try align with connect points? You will calculate something called x minus x bar. Hey, what is x minus x bar? Is this data point called x? This particular data point called 1 minus 3. From the perspective of 3, I want you to understand from the perspective of the number 3. Is this number 1 called x value and this is the x bar? This point is called x bar and this point is called y bar, yes or no? So basically, aren't you calculating that 1 is deviating from 3 by how much? 2 is deviating from 3 by how much? 4 is deviating from 3 and 5 is deviating from 3 by how much? Are you calculating this exactly? Yes or no? So tell me, x minus x bar meaning 1 minus 3. What is 1 minus 3? What is 1 minus 3? Minus 2. Very good. What is 2 minus 3? Minus 1. What is 3 minus 3? 0. What is 4 minus 3? 1. What is 5 minus 3? 2. So tell me, from the mean value, is this 1 point not in the negative 2 direction? Isn't from the mean this point 2 in the negative 1 direction? From mean, the mean itself is at 0 distance, meaning it is within calculation of itself. Then this number at 4 is 1 positive distance and this number to 5 is a 2 positive distance. Did it not give me the spread? The information, not exactly spread, but did it not give me the information of the deviation I have in the data? Minus 2, minus 1, 0, 1, and 2 with the number format. Is everyone clear? We kind of got the idea of how much is this part. Okay, because you did this with x, don't you need to do this with y also? So you need to calculate something called y minus y bar. Y minus y bar. So tell me, what is 2 minus 4? What is 2 minus 4? Minus 2. What is 4 minus 4? Is it 0? What is 5 minus 4? Is it 1? What is 4 minus 4? Is it 0? And what is 5 minus 4? It is 1. Is everybody clear what we did here with the calculation of x minus x bar and y minus y bar? What did we do with this? Why did we do it? to understand how far off my data lies from the actual mean value. Are we clear? Are we clear until here? Okay, good. The next thing that we do, okay, is there any reason to take x equals to 3? What you have to do next is x minus x bar, the whole square. You know why should you take the whole square? Because isn't -2 and +2 cancelling each other out? If I want to add them together, will I be able to add them together? Will I be able to add them directly together mathematically? The minus will nullify the plus value. Agree or disagree? So that the nullification does not happen, what do? We take x minus x bar the whole square. Doing squaring of a number, what does it make sure? That the number is always positive. Agree, disagree? If you take -3 and if you square it, won't the answer will be 9? And if you take 4 square, the answer is 16. So squaring will make sure that the number is never negative. So nobody will get cancel each other out, right? So what is x minus x bar the whole square? -2 square. Can I say that is 4? -1 square. Can I say it is 1? 0 square. Can I say it is 0? 1 square. Can I say it is 1? And 2 square. Can I say it is 4? Yes? Now, if you take the summation of all the values, what do you mean by summation? Addition of all the number. So tell me, what is 4 plus 1 plus 0 plus 1 plus 4? 8, 9, 10. Can I say it is 10? Can I say that the summation of x minus x bar into y minus y bar is this? Okay. Until here is everybody clear. Until here is everybody clear. The next thing you calculate is what we called as x minus x bar into y minus y bar. Now listen to me carefully. Can I say that this data point and this data point distance is called as x minus x bar? From this data point to this data point is called x minus x bar. Now listen to me carefully. Listen to me carefully. Can I call this also x minus x bar? This distance can be called as x minus x bar. Yes, good. Can this distance be called as y minus y bar? If I multiply x minus x bar into y minus y bar, essentially what I'm doing is, this is x minus x bar, this is y minus y bar. Multiplying them together gives me this answer. If I have an area of a rectangle, length into breadth gives me the entire area. Yes or no? This point, this line is nothing but x minus x bar. This line is y minus y bar. Am I not doing x minus x bar into y minus y bar? If I do x minus x bar into y minus y bar, can somebody tell me what is x minus x bar? Is it -2? Is the answer x minus x bar going to be -2? Yes or no? Multiplied by, what is y minus y bar? -2. What is the answer? Is it 4? Very good. X minus x bar is -1. Multiplied by y minus y bar is 0. Is the answer 0? Okay. What is x minus x bar? 0. What is y minus y bar? 1. Is the answer 0? What is x minus x bar? 1. What is y minus y bar? 0. Is the answer 0? What is x minus x bar? 2. What is y minus y bar? 1. Is the answer 2? If you sum the numbers together, 4 plus 2, what is the answer? 6. Are you clear so far? What did you do here while the calculation of this x minus x bar, y minus y bar? You have a line equation called y is equal to mx plus c. Yes or no? This is the line equation. Everybody agrees? Do you know the value of m so far and the value of c so far? Are you clear with the value of m and c? The answer is no. Isn't this the first thing you need to calculate? What is the m, what is the c, so that we can find out the line that can cross? Okay. To calculate the value of m, to calculate the value of m, using mathematical derivations. Do you understand what is derivation? You start with the base equation, you solve, and you get some answer. So, mathematically speaking, to get the value of y-intercept, or sorry, to get the value of slope, the formula is summation of x minus x bar into y minus y bar divided by summation of x minus x bar the whole square. Do we have the values for this? What is the value of summation of x minus x bar into y minus y bar? What is the answer? Is it 6 divided by summation of x minus x bar the whole square? Can I say it is 10? So the answer is 0.6. Did you just get the value of m, the slope of your line? We just calculated the slope of the line. Now listen to me carefully. Sir, how did we get this formula? Did someone calculate it? Yes. Somebody has already calculated this using mathematical derivation. If you want, so first of all, I don't think you should learn derivations because somebody has taken enough effort to solve the derivation. Me teaching you the derivation is only going to take time, but it is not going to be important for you to know. What's important for you to know is to remember the formula. I can teach you derivation also. It's not a very complicated thing. It's a simple mathematical process. But the problem is that derivation will have no importance to you. Am I making sense? What formula it is, you need to understand that clearly. How you arrived at it can always be learned eventually over a period of time. But first, you need to understand what is linear regression, how it is applied, how can I practically implement it, then giving your energy to how did the derivation occur, who wrote it for the very first time, what is the history. I think you should focus on your priorities slightly differently. So did you understand why I wrote down the formula straight up for you so that you don't get confused? It is arrived using a derivation. This mathematical derivation is slightly complicated, slightly simple, but we have the formula, okay? Here we are squaring the number and denominator. Yeah, I mean, this is the summation value. We are not squaring anything. It's summation of x minus x bar into y minus y bar by the summation of x minus x bar, the whole square. This will give you the y-intercept. The logic is pretty simple, but in the derivation, you will see why we do the division because this goes on the left side of the equation. So we put it in the bottom. Okay. Anyways, this is the value of y. Now, between y is equal to mx plus c, what did we calculate? Did we calculate the value of y? It is now calculated. But do we have the value of c? No. We don't have the value of c. So to calculate the value of c, how do we calculate it? The formula to calculate the value for c, you have to use this equation. Y bar is equal to mx bar plus c. Now tell me, in this formula or in this equation, do we have the value of x bar and y bar already given to us? What is the value of x bar? X bar is equal to 3 and y bar is equal to 4. Yes or no? So you have this equation called y bar is equal to mx bar plus c. Okay. To calculate slope of any line, mathematically, you have to calculate the delta, the difference. Meaning, if you have a line here, right? This difference in y and this difference in x will help you calculate this. And while the derivation of linear regression was done, right? So, पहली चीज क्या है ना, हर फॉर्मूला मैथमेटिकली सेंसिबल हो ये जरूरी नहीं है. लेट मी आल्सो टेल यू व्हाई. आप पहले सुनिएगा ध्यान से और समझने की कोशिश कीजिएगा और फिर मेरा तर्क समझिएगा कि मैं क्यों ऐसा कह रहा हूं. एक मैथमेटिकल डेरिवेशंस में क्या होता है, जो डेटा होता है, जो नंबर होता है, वो किसी फॉर्मेट में होता है. जैसे आपको एक एग्जांपल देता हूं मैं. हमने इनिशियल एग्जांपल जब किसी डेरिवेशन का लिया तो वो डेरिवेशन में हमको बहुत सारे अजम्पशंस लेने पड़ते हैं. लेफ्ट हैंड साइड, राइट हैंड साइड को 10 से डिवाइड कर दिया. लेफ्ट हैंड साइड को लॉगरिदम, नेचुरल लॉगरिदम से डिफरेंट बेस लॉगरिदम में कन्वर्ट कर दिया क्योंकि वो नंबर्स मैच नहीं हो रहे हैं. तो क्या होता है, इवेंचुअली हम किसी डेरिवेशन को जब स्टार्ट करते हैं, स्पेसिफिकली ये लीनियर रिग्रेशन की जो डेरिवेशन है ना, आपको अगर मैं पूरा डेरिवेशन सिखाऊंगा तो आपको समझ में आएगा कि क्या हो रहा है कि इनिशियली जब हमने स्लोप को लिया था, जो स्लोप का एक्चुअल फॉर्मूला है हम उसी को कंसिडर करते हैं। बट इवेंचुअली जब हम इसको ना सॉल्व करते हैं, मतलब सॉल्विंग फॉर द लेफ्ट हैंड साइड एंड राइट हैंड साइड, जब हम सॉल्व करना स्टार्ट करते हैं ना, तो हमको रियलाइजेशन होता है कि मे बी लेफ्ट एंड राइट में ना कुछ और ऐड करना पड़ेगा ताकि वो बैलेंस आउट हो जाए। करते 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 जाते हैं तो इवेंचुअली वो जो फॉर्मूलाज हैं वो थोड़े डिफरेंट फॉर्म में कन्वर्ट हो जाते हैं। फिर हमें क्या करना पड़ता है, m के लिए ऊपर वाली वैल्यू को नीचे लेके आना पड़ जाता है। तो क्या हो जाता है कि आपका ये जो समेशन ऑफ x माइनस एक्स बार द होल स्क्वायर है ना, ये लेफ्ट हैंड साइड में आता है, और ये जो समेशन ऑफ x माइनस एक्स बार ये राइट हैंड साइड में आएगा। तब क्या होगा, ओवरऑल जब हम सॉल्व करना स्टार्ट करते हैं ना, तो ये समेशन वैल्यूज जो है, जो ये आपको ये फॉर्मूला दिख रहा है, इट स्टार्ट्स सॉर्ट ऑफ फॉर्मिंग इनटू दिस पर्टिकुलर फॉर्मूला। जो आपको ये दिख रहा है ना, ये इस फॉर्म होना स्टार्ट होता है। एक काम करते हैं, व्हाई डोंट वी सॉल्व द डेरिवेशन आल्सो सामने ही। इफ यू रियली वांट टू अंडरस्टैंड मशीन लर्निंग, the point is, if you want to deeply understand machine learning, like when I'm talking about deep, because here is the thing, when I started machine learning, right, I have implemented each algorithm, every algorithm in machine learning from scratch. I have done that. That is when my knowledge in machine learning increased 10 times, because when you do not use any packages, any libraries, understand the core mathematical concepts, you should be able to like build anything because you now understand the basis behind it, right? Just like that, learning the core mathematics is important. The reason I am not going ahead with the derivation and explain you logically how did we arrive at this conclusion is because it will end up taking a lot of time. Number one. Number two, the mathematical reasoning that it takes to arrive at this solution is also going to be very, very complicated for few people. So that's why I said, if you start with machine learning right now, you guys are just starting with machine learning, right? Focus on how to apply machine learning, then learning the foundational logic. But because if the question is, how did we arrive at this conclusion? We can always go back and learn the derivation also. So it's up to you guys. I mean, if derivation is also something that we can look at, we can also look at this. The derivation will make sense. Why are we taking this area x minus x bar the whole square will start making sense, because it is directly related to residuals. So now that we've understood, right, slope of the line using the data point or variable, which is one independent, one dependent, we are able to calculate the equation, slope using this particular formula. Now that we've understood how we calculated that using the slope, the next thing that's pending is for me to calculate the y-intercept, okay? Because y-intercept cannot be calculated directly, I need to manipulate my equation slightly differently, like y is equal to mx plus c. Because we don't have m and we don't have c, right? We don't have c, sorry, y and x. We calculate y bar and x bar. X bar is already given to me as 3 and y bar is already given to me as 4. So tell me, what is the value of y bar? Is it 4? Is equal to, what is the value of m? 0.6. What is the value of x bar? Is it 3 plus c? So mathematically, if I solve this, 4 is equal to, what is 0.6 into 3? Is it 2.2? Okay, that's good. 2.2 plus c. Now, listen to me. In mathematics, when you jump equal to signs, you convert the sign from positive to negative or negative to positive. Meaning, if this 4, if this 2.2 needs to jump to the other side of the equal to, what will it become? Will it become 4 minus 2.2 is equal to C? Yes or no? Whenever you change the number from one part of the equation to the other part of the equation, if it is a, so what will be the value of C? What will be the value of C? 2.2. Wait, 0.6 into 3 cannot be 2.2. I don't know if it makes sense to me, because 6 threes are 18. It should be 1.8, right? If I'm not wrong, 6 threes are 18. Point difference is 1.8, right? Yeah, this should be, I think the difference is 2.2. I think this is what you mean. Yeah, I think I got the concept. Okay. This is 3.2. Yeah, D is 2.2. Exactly. So tell me, Did you get the equation y is equal to mx plus c? And now you have an equation for the line 0.5 into x plus the value of c will be 2.2. Did you get the line equation for your data using the steps that we have done so far? We got the equation called y is equal to mx plus and we got the line. But our job is not yet done. Until here, is everyone clear? Until here, is everybody clear? What exactly did we do to solve until here? Everyone got the concept until here. 0.5 or 0.6. But there is so much more to achieve. Meaning, you got the line equation 0.6x plus 2.2 something, something, something. My people, based on the linear equation graph that you see that I have plotted for you like a while ago, which is this. Okay, give me 1 second. Let me copy the graph. Give me 1 second. Let me just go ahead and copy this and paste it here. Give me 1 second. Copy this and paste it towards the bottom. My people, we got the equation of the line equation as y is equal to something, something like this. Like, so we got a line equation that passes the data like this. But observe very, very carefully that the distance between your actual data point, is this my actual data point? AP is my actual data point. AP is the actual data, the real data. And the line is the prediction. Agree or disagree? This is my predicted data and this is my actual point and predicted point. Can I say it like this? Do you see there is some difference between it? Some distance, some error? Yes or no? This error exists here also. This error exists here also, here as well, and here as well. There is some distance between this, and this. The data points are distance. This distance or difference is called as residual. What do we call this? What do we call this? Residual. Tell me, the point is very simple. When you make linear regression line happen, or when the linear regression line has been calculated, do you want the distance between data point and the actual point to be the least as possible or to be the maximum as possible? What should your intention be? Your intention should be to minimize, right? Your intention should be to minimize the residual, but your life and your job is not that simple. Let me explain why. Let me explain why this is not simple. Listen to me carefully. I'm going to erase these data point, okay? The line point, and I'm going to show you guys an example. Mathematically, also sensibly, it should make sense to you. Okay, give me 1 second. Let me copy this graph and paste it so that I don't ruin the graph. Give me 1 second. Why am I not able to copy? Okay, this is the copy, is it? Okay, fine. Yeah. So listen to me carefully. I'm going to erase the middle line for a second so that you guys don't get confused, okay? X bar, Y bar, I'm going to remove. My people, now we have a line that passes through the data like this, okay? It is passing through the data point like this. Listen to me carefully. And it is passing through the line like this. Like this is the line that we have calculated, okay? This is the distance between the predicted data point. This is the predicted data point, and this is the actual data point. Okay. So tell me, isn't this data point the data point which is predicted versus this is the actual data point? This is the data point which is actual, that is, this is predicted, that is actual, this is predicted, that is actual, this is predicted, that is actual. So listen to me carefully. This is the error, also called error number 1. Can I call this difference as error 1 E1? Yeah, can I call this error as E1? Okay. Can I call this error as E2? Can I call this error as E3, this error as E4, and this error as E5? Can I call this E1, E2, E3, E4? So the best possible line for me to claim that the line that I have has the best fit. It's fitting the data points in the best possible way. So shouldn't that be possible that E1 plus E2 plus E3 plus E4 plus E5, this number should be the most minimum number as possible? Yes or no? the number E1 plus E2 plus E3 plus E4 plus E5 should be the most smallest number possible. But the problem here is some data points are following in the positive direction, meaning in the bottom, and some number are at the top. So isn't it possible that E1 and E2 will also cancel each other out because the directions are different? Does that make sense? See, from this data point to this red data point, it is in the negative direction, but E2 is in the positive direction. So if I don't square them, won't they also cancel each other out? And the actual answer will be terribly wrong. So rather than combining E1, E2, E3, E4, E5, do we not take E1 square plus E2 square plus E3 square plus E4 square plus E5 square? Agree, disagree? Now listen to me carefully. Listen to me carefully in a most simplistic sense. Okay. If I take this line and rotate it a little bit more, the line that we have calculated it just for practical purposes, just to test something, can I rotate it a little to the left and a little to the right? And when I rotate it 2 times to the left, one left, one right, I got the value of error, ERROR, TOTAL, total error as 1.6, 1.2, 1.9, and 2.3. When I rotated the line, which line gave me the least amount of error? In this 4 rotation that I did, 2 to the left, 2 to the right, did this give me the least amount of error? That line is your best fit line. Did that logically make sense? Did that logically make sense? Okay. Can I show you an example? Can I show you an example practically to show you how in reality in linear regression, how it works? You guys want to have a look? Have a look at this, okay? Linear regression, best fit line, okay? Fit line. Look at this, my people. This is my linear regression data. Can you see what's happening to the line? Did you see what happened? Did you see what happened? See, I'm going to rotate the line, okay? I'm rotating the line. Is the error increasing and decreasing? Are the errors increasing and decreasing because of the rotation? Have a look at this also. See, this is the best fit line. Do you see the mean of X and mean of Y? Do you see the mean of X and mean of Y? We took the red color line. On that point, are we rotating the line that we just calculated Y is equal to mx plus c? When the rotation when we do that rotation, isn't it possible that we can get the value of multiple different error types? And whichever error has the least possible error, that line is the best fit line. Did you understand the logic behind how linear regression is able to calculate the least amount of error? And that line is going to be the best fit line for your example. Is everyone clear what we did in linear regression? First, we plotted the data. Then we took the X bar and we took the Y bar. Sir, we have to code for this. It's too long. The entire linear regression code is 15 lines of code. 15 lines. Without any library. Without any library, it's 15 lines of code. Do you think it's too much? Point being, first we plotted the data, then we took the mean X, mean Y. From that point, we passed the problem or we passed the line, and now we are rotating the line a little bit to check whether the data or the line is the best fit line. Did you get what exactly I was saying? What line rotation is showing exactly? Line rotation shows you the distance between the error. Meaning, suppose if this is the graph that I have, okay, this is the graph that I have, this is line number 1. Is it not possible for me to rotate the line slightly and have another line like this? If I rotate the line, the distance between actual data point and your prediction data point, does it not change? And your job is making all the errors together, E1 plus E2 plus E3 plus E4 plus E5, all the errors together, Don't we want a number, a value of the line where all the errors together is the least number possible? That is why you rotate the line. Rotate the line, the only thing you need to change in your equation is m, right? Because y will remain the same. Or no? To rotate the line, what do you need to change? Both m and c, right? You need to change both m and c together for the line to rotate, right? So multiple values of m and multiple values of c will give you the answer. Isn't this like the initial guess of the line? The initial guess of the line, is it the best fit line? The first product you buy, is it the best product? No. We just made a guess on the y, axis equation. We did that. But is that line the best fit line? Are you sure that is the best fit line? Can you be sure? No, right? In order for us to understand which is the best fit line, we take the line that we just calculated and we rotate it a little bit. Based on the rotation, whichever error value has the least error, that is the best fit line. Now, my question is, how many of you got this and how many of you did not get it? Let me take up a quick poll. How many of you got it? Yes, yes, yes. How do we calculate it? How do we do it? I'm going to teach you all of that. How many times to rotate? The higher you rotate, the better chances of best fit line it is. The higher you rotate or the longer you rotate, the better the chances you will find a best fit line. If we rotate, are we not changing the C 2.2 which we calculated? Yes, we calculate both the L, M and C, we change and we check for multiple C and M. Okay, let me explain. How do we rotate? How do we rotate? Let's understand. Let's understand the rotation. Is this my line with some value of M and C? Yes or no? You first please tell me that. Is M is equal to, is the value of M 0.6 and the value of C 2.2? Yes or no? If I want to rotate, this is the line, okay? This is the line which will give me this y m is equal to 6.6. If I want to rotate it by one degree, 1 point, increase m and decrease y, can I do this? Or decrease m, increase y, can I do this? Are you getting what I'm trying to say? This is my xy graph. This is my y point on which the line is plotted. And this slope of the point is 0.6. Make it 0.5 and make the intercept here. Will the line now rotate by some point here? Increase point number 1 by one more point, decrease the slope by 1. Will the line rotate now? Same thing, keep doing. Increase the point by 1 and decrease the point. Did you now rotate the point slowly, slowly, slowly by changing this decrement by 1, increment by 1? And now if you do the reverse operation, it will go in the opposite direction. Agree, disagree? Am I making sense? In this part, at least in this part, 1.1 increase. Won't you be able to calculate for multiple values of y, like the line will rotate? This is the line equation that we calculated. Listen to me carefully. Based on the data, what did we do? Based on the data, what did we do? Did we calculate the y is equal to mx plus c equation? That was the first thing that we did. Yes or no? Y is equal to mx plus c was the first thing that we calculated. The line equation that you calculated, y is equal to mx plus c. How sure are you that that line is the best fit line? Can we be sure that the line equation that I calculated, y is equal to 0.6 into x plus 2.2, this is the line which is the best fit line. What do you mean by best fit? The line passes through all the data point in the most perfect way. Are you sure that this is true? Should you not validate that? We are not sure. Should we validate? The answer is yes. You need to validate. In order to validate, how do we validate if something is good or not? Mathematically, we need to have some foundation for it, right? How do we identify somebody is a good ranker, somebody is a bad ranker? Shiv Kumar, who spoke to me a while ago, is a Bihar topper. How do we know he's a Bihar topper? He must have gotten good score. His percentage would have been higher. The number would have been bigger. If the number is smaller, does it equally mean that the person did not score well? Yes or no? this is called mathematical quantification, meaning some number is trying to give us the idea. So tell me, suppose I have a line called line number 1. This is my line. This is the line. My people, this red color point, is it my actual data point? Is this the actual data point that was available in the data? Good. But using the line, did you predict another data point, which is your prediction? This point on this line is your prediction. This is not the actual data. This is your prediction. Yes or no? Can I say the distance between the prediction versus the actual value is -2? Example. For example, it is -2. Can I say this? Good. The distance between this data point, the red actual data point, and this data point is +2. The distance between the red data point and this data point is +3. The distance between this data point and this data point is -3. And the distance between actual data point versus this predicted data points is -2. Example. So far, the total error in the program is nothing but the difference, right? Difference between the actual and the predicted is what the error will be, right? So -2 +2 +3. Okay, so -2 +2. Let me expand it and write this, okay? So let me say -2 +2 +3 +3 +2. If I add them together, will this not be the actual difference, the error in my program? Isn't this going to be my error? But -2 will cancel 2, +3 will cancel 3, and the answer is -2. Is the answer actually -2? No. Even if they are not equal, even if the numbers are not equal, okay? The problem here is mathematically, if this number was -2 and this was -2.1, won't the answer be 0.1, which is also not correct? The numbers don't need to be equal, but they cancel each other. They take a portion of each other. We don't want that to happen. So rather than taking errors like that, don't we square them, the errors? Yes or no? So rather than taking the answer like this, if I want to quantify the number, can I not take -2 square plus 2 square plus 3 square plus -3 square plus -2 square? The answer will be 4 plus 4 plus 9 plus 9 plus 4. Can I say now this will be some number that represents the error? Are we clear until here? Dipankar, even if it's not equal, it does not matter, my dear, mathematically. It won't make difference also. If one direction it's -2, other direction it is unequal number, errors will still get added together, right? At the end of the day, you're adding the errors together. It does not matter if you have 10 rupees, 15 rupees, 19 rupees. It does not matter what number you have. The errors at the end of the day are getting added together, but you're trying to nullify them. I am not nullifying them. I am taking the difference between the actual data point and the predicted data point and square them. I am saying that you should square it. I am not saying nullifying it. I am saying square it so that nullification does not happen. I know positive and negative predictions. That's why I'm saying squaring them will convert it into a positive number, and all the positive numbers you can add together. You got, this is a very simple thing, my dear, not a very complicated thing. -2 and +2, if you square, -2 square is 4, +2 square is 4. If you add them together, did you get the value 8? 8? Agree, disagree? Yeah, okay. Even if you have 15 points, 1500 points, whatever points you have, the distance between the actual versus predicted data point, you need to square them in order to get the error. So tell me, what is 18 plus 12? What is 18 and 12? So 8, 9, 10. This is going to be 30. So did we get the error? The total error using the line is 30. Yes or no? We are not nullifying anything. We are trying to get some number. Okay. Now tell me, I'm asking a very simple question. Very simple question. Are you sure this is the best possible line in the entire data that you have? No. If I rotate the line slightly to the bottom, isn't it possible that that total error now will be 29? Slight rotation gave me the error as 29. And we want the error to be as minimum as possible. So will you choose line number 1 or will you choose line number 2 as the best fit line? If this is my line, okay. Do you guys know that in mathematics, you can take a range between 0 to 10? I can take 0, 1, 2, 3, 4, 5, 6, 1 point at a time. This also is possible between to reach 0 to 10. Okay. 0 to 10 can be reached by 1 unit distance, meaning between 0 to 10, I can reach 10 by exactly how many steps? 10 steps, correct? Taking one at a time. Agree? Yes or no? If I want to count from 0 to 10, but I want to take one step at a time, so can I take from 0 to 10, making only one step at a time, I'll be able to reach 10 times. But same 0 to 10, you can reach in 20 steps by taking 0 0.5, 0, 0 0.5, 1, 1.5, 2, 2.5, 3. Can I say you can reach from 0 to 10 using also 40 steps by taking 0 point, I don't know, 25? How much to rotate? Should it not depend on how much you want to increment your MNC? Am I making sense? Your y is equal to mx plus c. Your value of m was 0.6 and your value of c point 2 was 2.2. Your m can be 0.65, meaning 0.05 times your increment one step, one step, one step, one step, one step. Or you can also do 0.1. So 1, 1, 1, 1, 1. Does it not depend on the user how much you want to rotate? Does that make sense? And because it is a computer program, we can make it do millions of rotations. That line could be rotated in the positive direction and in the negative direction. And let me ask you a question. Let me ask you a simple question. Did we not calculate the mean of x and the mean of y like this? Did we not calculate the mean of x and mean of y? Should you even rotate it beyond this and beyond this? Meaning, should the line go beyond this point and beyond this point? It should be between the points, right? If it goes beyond, are you even calculating anything? I hope you got the concept. Did you get the concept of rotation? How exactly linear regression is able to do that? How are we able to find the best fit line? Exactly. Exactly. Thank you. Are we clear with what exactly is the definition of linear regression? How it is able to do it? It is a very simple machine learning algorithm that's able to do it. And based on that, and based on the best fit line, we will be able to make a prediction in the future because that line has the least amount of error. So if the prediction in the future is that for 4,000 square feet house, it is 2 crore, meaning it actually in reality is 2.2, but R isn't 2 crore nearer to 2.2, meaning with some error, we were able to very closely identify the answer. That is why linear regression is used. Concept of what is R square. Okay, my people, in linear regression, R square represents a very simple information, and that information is R square tells us how well the line predicts or fits the actual point, or how well the line predicts the actual point. This is technically more correct. So R square tells us, okay, R square tells us how well, how WELL, the line predicts, okay, predicts the actual points, POINTS, okay. R square is a way to tell yourself that your model is doing a good job or your model is doing a bad job or your model could do better. Okay. This is a way to quantify it to yourself. Now you can ask me one thing, sir, why don't we have a quantification already with something called residual error? We do. The problem is linear regression has a very big problem, and that problem is outlier. If you have a line of a linear regression where you have one data point here, one data point here, one data point here, one data point here, and one data point here, this is known as the best fit line. Okay, the red color thing is gonna be my best fit line. But by mistake, if your point is somewhere here, right, then your best fit line would go somewhere like this. So tell me, does outliers affect the output of your linear regression model? Does having an outlier create problems? Sir, 100% it will create problems. If you don't know, I'm telling you this right now. So removing outliers from your data should be an essential part of your EDA. Have you all heard of something called EDA? Has anybody heard of the concept called EDA? The full form is called exploratory data analysis. It's called exploratory, okay, data analysis. Are we clear? So now that we have spoken or learned about R square, what exactly is R square? Take a line. Listen to me carefully. Take a linear regression line. Okay. So for example, if this is like the y-axis and this is like the x-axis. Okay. If this is my x-axis and this is my y-axis. And suppose you have data points like 1, 2, 1, 2, 3, 4, 5, right? Like this. One. Suppose if you have a data point like that. R square, most simplest form I'll explain. Okay. It is nothing but the distance between and the distance between. Okay. There are two distances we will calculate. The actual value minus mean value, the estimated value minus mean value. When we did linear regression code, okay, when we wrote this graph in front of you, right? I'm not sure if I can copy this, but I'm gonna try my best. Give me 1 second. Oh yeah, I can. Control X. Yeah. Okay. You see this graph? We did this graph. Whoever does machine learning well, their level will be the best, is what I meant. You know what I think? Listen to me. Listen to me. Okay, listen, because this is a very important concept. Here's what I think. I think all of you need to make a Google sheet. A Google sheet. In that Google sheet, just write down your name and your address. Your name and your address. And what I'm going to do is I'm going to have a deal with Swiggy. And I'm going to be like, look, 7 o'clock I start my class. 6:45 I want you to send tea or coffee based on whatever preference you have to all my students so that they wake up. But before delivering the copy, take a hot water and just like on their faces so that they are up. Yeah. We'll speak about that. I think this is a good startup idea as well. It's a very simple idea. I am teaching you the concept of R square. R square tells you how good your model is or how good the estimation. What do you mean by estimation? Prediction only, right? Estimation is prediction only, right? You have some actual data point. You having actual data point is called ground truth. Remember, in machine learning, this is a very important term. Ground truth. GROUND. TRUTH. Ground truth means your actual data. It is a very important technical term. Just like how in marriage, I am sorry works every time. It's an important keyword. Ground truth is an important keyword. It represents all your actual data point. Okay. So now Your ground truths are your actual data points, and your line is the estimated data points, basically the one that you have estimated, right? So tell me, do you have something called the Y bar? This thing is called as the Y bar, the mean of the Y, the Y mean, okay? On this particular plane, what two things do you see? One is the Y bar and the other is the actual data point, correct or not? There are two things on the graph right now. One is the Y bar and the actual data point. Can I plot a line, a regression line like this? So now what do you see? You also see the predicted line. Now there are three things on this particular graph. Make sense? Now there are three things in the graph. The distance between actual data point and mean. Listen to me. The distance between actual data point and the mean value. Is this the actual data point? The red dot? The distance between actual data point and mean. So can I say this is the distance between actual data point and mean? This is the actual distance between data point and mean, and rest is on the same tribe. So this distance is what we are calculating first, the actual distance between data point and mean. Yes or no? Good. Then the next difference we calculate is estimated minus mean. Meaning, can I say these is the actual data point, the red one, and the yellow one is the estimated data point. This is the estimated data point. This is the estimated data point. And this is the estimated data point. The next thing you do is you calculate the distance between estimated minus mean, estimated minus mean, estimated minus mean, which is this much, okay? Estimated minus mean and estimated minus mean. Did you get what I'm trying to say? The distance between actual data point minus mean data point and estimated minus mean. And when you want to do their comparison, this comparison is what we call as R square. Are we clear? It's not a very complicated topic. Everyone got the concept, right? You got the concept very, very well. So tell me, can I expand your knowledge now on how to do this mathematically? Again, I am not showing you how the formula has come up into picture, but like we have to take y-axis mean only because y is enough base for comparison. You got what I'm trying to say? Y is also an axis, which is a mean value. X is also a mean value. Taking from y makes more sense because you are doing y prediction. I hope you got what I'm trying to say. Your equation is y is equal to mx plus c, right? So y becomes a solid base. Okay. R square is the distance between the actual data point minus the mean data point. You compare against the estimated data point minus the mean data point. No confusion here, right? It's a comparison, simple comparison. It does nothing else. I'm going to show you mathematically what it does. Okay, good. I am going to take the X and the Y from the code. Give me 1 second. The X and the Y. Copy. Is this the value of X and Y that we have? Tell me, what will it mean if I do this? Y minus Y bar. What do you mean if I do Y minus Y bar? Is this line actual minus mean? The actual data point minus the mean is going to be called as Y minus Y bar, yes or no? This is simple logic. You guys must have learned that by now. So tell me, what is Y minus Y bar? 2 minus 4. What is 2 minus 4? 4 minus 4. 5 minus 4. 4 minus 4 and 5 minus 4. What is the answer, everybody? What is 2 minus 4 minus 2? What is 4 minus 4? 0. 1. 0. 1. Can I say this is the answer for actual minus mean, y minus y bar? Can I assume my understanding is correct? Because the numbers could be both negative and positive, we don't want that. What do we do with those numbers? Whenever the number starts becoming negative, very good. So do we take y minus y bar the whole square? So does it become 4, 0, 1, 0, 1? Now, tell me if I sum the number up, if I calculate its summation, what will be the answer? If I sum them up, 4, 5, 6, 6. Let's calculate something called y hat. Y hat is nothing but, what was the equation that you got? What was the value of m that you got here? 0.6 and 2.2. 0.6 and 2.2. 0.6 into x. What is the value of x? 1 plus 2.2. Can somebody tell me what is the answer? 0.6 into x is 2 plus 2.2. 0.63 plus 2.2. 0.6 into 4 plus 2.2. 0.6 into 5 plus 2.2. Am I predicting the estimated data point here using the y hat? Yes or no? This would be 2.8. 1.2, 2.2. What? This should be 3.4, right? If I'm not wrong. Right? 4, 4.6. Yeah, that's true. And that would be 5.2, right? 4.6 and 5.2. I'm assuming this is correct because it is at a very standard difference. Is it correct? Is my y hat prediction correct? 2.8, 3.4, 4, 4.6 and 12, 5.2. Correct? Okay, good. Did you all understand what is y hat? Y hat is the estimated data point. Using the equation only we calculated the estimated, right? Using the equation only we will calculate estimated, correct? So tell me, my people, I have actually taken something called actual data point, actual point minus mean I have taken. What am I remaining with? What is remaining? What is missing here? Which point is remaining? Estimated minus mean, correct? See, actual data point minus mean is taken. Estimated minus mean is not taken. What is your estimated value? Y hat. What is the mean value? Y bar. So what is the estimated value, my people? 2.8 minus what is the y bar? Is it 4? What is y bar answer? Negative 1.2. 2.8 minus 4 will be negative 1.2, correct? You know what? You do the hard work. 3.4 minus 4. 4 minus 4. I will write the answer. It is easy. Minus 4 and 5.2 minus 4. Come on, give me the answer for all of these. What should be the answer? Negative 1.2, negative 0.6, 0.6, and 5.2 minus 4 is going to be 1.2 because similar answers. Aren't these answers in plus and minus? Do we like answers in plus and minus? Do we like the answers in plus and minus? No. So what do we do? Y hat minus y bar the whole e square. What is whole e square? Everybody, what is 1.2 the whole square? It becomes 1.44. What is 0.6? 6 twos are. Nah, it's not done like that. It's going to be 0.36. Yes or no? 0. 0.36 and 1.44. Now what do we do? If I sum the number, what answer do I get? What is the answer? If you sum them together, 3 point. Is it correct? Is the summation going to be 3.6, everybody? That's good. That's good. Once you have calculated this, your R square formula is very, very simple. Your R square formula is summation of y hat minus y bar, the whole square divided by summation of, what are you comparing it against? Estimated minus mean is compared against actual minus mean. What is the actual minus mean? The actual minus mean, the whole square. So tell me, what is the number that we got? Is it 3.6 divided by 6? What is the answer? What is 3.6 divided by 6? What would be the answer? About 0.6. Remember one thing. R square is a number between 0 and 1. What is the number R square? R square is a number between 0 and 1. If your R square is closer to 1, the fit is good. If your R square is closer to 0, the fit is bad. What R square did we get? What R square did we get? Closer to 1. So what does it recommend? Is it recommend, or is it recommending something that my fit is good? But R square has a problem. You know what is the problem? I'm going to show you what is the problem. R square formula. You are going to be very much confused when I show this formula, right? Have I taught you the formula like this? Okay. Did I teach you the formula like this? Y minus y hat the whole square, y minus y bar the whole square. Is my formula different from this formula in what way? Copy image and paste it here. Okay. What's the difference in my formula and this formula? Please, somebody tell me fast. Nope. Look at the numerator and look at the denominator. Y minus y hat. And here I have y hat minus y versus y minus y bar. Okay. Actual minus predicted and estimated minus mean. Okay. Two things. I'm also going to show you guys one more formula. Okay. I'm going to show you guys it like this. Okay. Give me 1 second. Copy image and paste it here. Is this visible to all of you? Is this image right there visible in front of you? Listen to me carefully. Do you see this thing called SSRES? SSRES. The full form of this is sum squared residuals. Residuals. And the third is SS tot. Sum squared total error. Okay. TOTAL. Now, I don't want you to get very much confused with this concept that, oh my God, what is this new thing? It's nothing. It's nothing. Literally nothing. Okay. The formula that I gave you, okay, the formula that I have given you, which is this formula, here R square is nothing but sum of squared residuals divided by sum of squared total. Sum of square residual divided by sum of square total. You have to think of it like this. In R square, okay, while calculation of R square can be expanded in multiple different forms, like sum of square residuals by sum of square residuals plus sum of square error. Okay, that becomes sum of square total. When you rearrange the terms, you get an answer like this: 1 minus, okay, summation of y minus y hat, which is the actual minus estimated, actual minus, actual minus predicted, which is y hat, and actual minus mean. When you say you're comparing, you're basically dividing one comparison with another comparison, and you're taking something called as a ratio. Now, I am going to ask you guys a very simple thing. Do you know what is the meaning of the word ratio in mathematics? Let me give you guys a very simple example. Very simple example. Tell me, if you had 4 chocolates and 2 people to share it with, per person will get how many chocolates? 2. Reverse the situation. You have 2 chocolates, but 4 people. How many will each person get? About 0.5. Agree, disagree? Okay. This number represents the power of the method, meaning when you divide a larger number by a smaller number, you get a number which is significantly different. When you divide a smaller number by a larger number, you get a significantly different result. What do I mean by that is, does the answer of the division represents the equal parts for that particular division? For 2 people, you get 2 chocolates. For 4 people, you're going to get this chocolate. Division of A divided by B will give you some value called X. B times X is always going to be A, right? X into B will always be A. It will always come back to A. The value X represents equal portions for the value at the top, or sorry, equal portions with the value at the bottom, meaning sum of squared total, right? You will get some answer called X has a relationship with this number. This X number represents the equality among the equation, or equality among the uh, among this particular division, meaning whenever you take R square and the number is larger to 1 or closer to 1, whenever your R square is closer to 1, what does that represent with numerator and denominator? What should it represent? Under what condition will be the number closer to 1? If the numbers are closer to each other, or if the numbers are far away from each other, meaning you have a value called A, you have a value called B. Between A and B, if the number of A and B, if they are closer to each other, will that become 1? Or if they are far away from each other, will that number be 1? Please think and answer, okay? Please think and answer. If the numbers are closer to each other, meaning, let's take the example 3.6 divided by 6. 3.6 divided by 6. What is 4 divided by 6? Very much tell me, what is the answer? What is 4 divided by 6? This is not a very hard calculation. What is 4 divided by 6? 2 2s are 4, 2 3s are 6. What is 2 divided by 3? 0.67 approximately. What is 5 divided by 6? What is 5 divided by 6? 0.83. What is 5.5 divided by 6? 0.92. Let me ask you guys a simple question. When your sum of squared residual error, which is sum of square residuals divided by sum of square total, when both the errors are very close to each other, is your R square saying that the model is a good fit? Listen to me. But what does that mean in the graphical format? The closer the lines of estimated n minus mean or actual minus mean are, the better the R square. Meaning, when all the distance between the actual minus mean and estimated mean is as less as possible, the numbers will be closer to each other, and hence the R square will be bigger. You got the concept? If the distance between the actual minus mean and the estimated minus mean is as closer to each other, the numbers will be as closer to each other, and the R square will be equal to or closer to 1. And that will represent a good fit in the model. Did you guys get the logic behind it? You got the concept behind it, right? Why R square is preferred for the choosing or for the recommendation that my model is good or not. Are we clear? Is everyone clear until here? You guys got the concept? Okay. Now listen to me. Do you see this formula? Do you see this formula right in front of you called adjusted R square is equal to 1 minus R square into n minus 1 by n minus p minus 1? You see this formula a lot? Okay. So just listen to me, okay? Just listen to me. If you do anything wrong in your house, do we get punished? I'm not sure if the kids nowadays or the parents nowadays even hit their kids, but yeah, I mean, I was the champion at my time, right? Like anybody used to just, but you do anything wrong, you get punished, right? In machine learning, this technique is called penalization. What do we call this? What do we call this technique as? Penalization. I have a very simple question I want to ask you. This question is going to come in your interview. It's going to be asked in your interview. This is not a 5-star. This is a 100-star question. My people, what is the difference between a machine learning model where you have A, B, C, and D and a target column? How many independent columns exist here? In technical term, they are called as features. Features. So from now on, do not call it independent column, call it feature. How many feature columns are there? 4. How many target column are there? 1. Correct or not? If I want to run machine learning on a model or on a data where the number of features, FEATURES, is 100 columns and the target is 1, do you think that machine learning should have no problem in running 4 feature, 1 target, 100 feature, 1 target? Or do you think the machine learning model will get a problem? My question is, if the number of features increase, listen, this is a very important question I'm asking you. Trust me, this is very important. If the number of features increase in linear regression or any machine learning model, okay, not just linear regression, if the number of features increase, does that cause problem in the machine learning modeling? The answer is yes. The answer is 100% yes. I'll tell you why. Listen to me why. For the prediction of some answer, for the prediction of some target variable, I'll tell you why this is a problem. Listen to me. Listen to me. I'll tell you why this is a problem. Suppose you have a column called age. You have a column called salary. You have a column called blood group. You have a column called civil score. You have a column called DPDs, days past dues. Oh, XYZ, XYZ. And the target column is whether this person should be given loan 0 or should be given loan yes or no. Tell me, for the prediction of the loan, will the age column also will be like a person? Hey, you should consider me also for your prediction. Then there will be one more person called salary. Hey, you have to also consider me for the prediction. Then the background will be like, hey, I am also existent. Civil say I am also here. DPD say I am also here. More the column, won't there be more chaos because so many people are saying prediction should be 0, prediction should be 1, and the machine learning model will be confused. More the columns, more the people are talking. All the columns are saying you have to listen to me, you have to listen to me, you have to listen to me. Won't the model be confused? Who do I listen to get my prediction? Right? And it is good to be wrong. My people, when I started machine learning, okay, and when I learned machine learning from my instructor used to also ask me questions the way I'm asking you. And I used to also say no, and then I used to say yes. It's okay. It's a fun part of the game. That's the beauty of learning together, right? The point is, the more the columns you have, the higher the chances of something called overfitting. Okay, I have not taught you what is overfitting, underfitting, but more the chances, more the overfitting. So tell me, does it not mean that by default, if a model, a machine learning model with 4 columns exists and a machine learning model of 100 columns exists, because the numbers of columns are higher, R square will always be closer to 1 because the number of columns are so many. So don't we want a true measure of R square? Even if the columns are 2000 tomorrow or 100 or 4, you give me the proper value of R square. Yes or no? You got what I'm trying to say? If the numbers of column increase for a linear regression model, higher the columns, R square will always be pointing to 1. But is the real value of R square 1? No, sir. It's because more the columns, more the representation. So don't we need to adjust our formula in such a way that even if the number of columns are higher, it will give us the right value of R square. That formula is called adjusted R square because the R square formula that I taught you, is it adjusted? No, it is not adjusted. It is not fixed. This is the formula that is fixed. So what is the formula of adjusted R square? Is R square nothing but your sample R square that you normally calculate the way I calculated? Yes. Absolutely correct. But you divide the equation by total sample size. Can you see I'm dividing this by total sample size n? The sample that I have taken for the consideration of R square, that sample. At the same time, can you see number of independent variable here? This is nothing but the number of features. If your data is working with 100 features, am I not dividing and subtracting it with n? So I am penalizing the model saying that if you take more number of features, your division also will be larger. You got what I'm trying to say? If your column is 100, Suppose if your feature set is 100, I will divide you by 100. So the number also will be that much smaller. But if your column is 10, I will only divide by 10. So be careful. Don't get overconfident and take too many columns. You got what I'm trying to say? That's the logic behind the R square formula. If the number of features are higher, R square is likely to be near 1. Of course, 100%. If the number of features that you have taken are very, very large, what happens in your R square? Because each individual column will start saying that you have to listen to me, you have to listen to me, you have to listen to me. What happens in that situation? What will happen in that situation? I mean, think about it. More the number of dimension, more the number of models complexity increase. What will happen with that? If the model's complexity increase, what happens to the model? Will it get confused? So closer to 1. That is your answer. It will basically overfit itself. It gets so overconfident on the training data. On test, it basically performs nothing. Is everyone clear until here? This is the formula for adjusted R square, meaning you penalize it more. If you want to take more columns or features, I will divide you by that number of size and you will be equally reduced in your R square. For more number of data or less number of probability of getting a good fit is high. See, let me answer this in this way. Sometimes when you do machine learning, listen to me, I'm asking you a simple question. Sometimes when you do machine learning, do you want more and more columns, more and more features? That is the requirement of my machine learning modeling, but are anyway trying to get R square closer to higher. How is it a problem? We never try to get the R square closer. And just focus on this part of the piece of code. Just be here, okay? I want to ask you guys a very simple question, okay? What data did we take for our prediction? What answer did we take for our prediction? Or what answers have we take? What data did we take week versus something, right? So what I'm going to do is import pandas as PD. Can I do this? Import numpy as NP. Can I do this? Import matplotlib.pyplot as PLT. Do I say these are the most basic kind of, I don't know, the most basic kind of approaches whenever we are writing any code? Okay. Exactly. That representation of R square is not good because anyways, more the columns are adding and making the R square closer to 1. That is not a true reading. I'll give you guys a knowledge. Okay. Give me 1 second. So tell me, when you cook tea or when you make tea, you don't cook tea, you make tea. TEAT. For 4 people, the amount of sugar you add is 2 cup or maybe 2 spoons or 3 spoons. Agree, disagree? When you make a tea for 100 people, will the amount or the quantity of sugar that will go will be larger? This behavior is normal and is common in the human system, ecosystem, right? If you are making a tea for 100 people, of course, the sugar is larger. You make a tea for 4 people, the sugar quantity will be lesser. If you reverse this situation, what happens? Disaster. For people, you want to make 4 cups of tea, adding 100 cups of sugar. And for people, 100 cups of tea, you make 2 cups of sugar. Is it disaster? Okay. So according to the size and the quantity of the data, should you adjust the sugar size? Larger the feature set, do I need to penalize it, control it, maintain it, so that the R square value that I get is not a number closer to 1 by default? That is not the true number. That is not the true representation of the number. I hope you got what I'm trying to say. That R square is not the true representation. The actual R square should be adjusted because automatically when the number of features are larger, it becomes overconfident and says that R square is 1. But in reality, R square is 60, 0.60, 0.70. It shows 0.9. Not good. Penalize. The logic is clear. Why we do this? That's why we do this. Have I taken all the packages? Matplotlib, NumPy, Pandas, and all of that. Weeks underscore data. Tell me, how many cars do I get to sell in a week? 1 week, second week, third week, fourth week, and fifth week. I only took till fifth, right? If I'm not wrong, I only took till fifth week, correct? Right? Okay. Then the sales underscore data. Sales data is, what did we take? I don't even remember the code. What was the sales value? 24545. Okay. 2, 4, 5, 4, and 5. Is this my weeks data and my sales data that I have taken as per what we did in the coding? Very good. So tell me, listen to me carefully. df equals to pd.data frame. If I want to convert all of them in data frame, do I take it in a dictionary format like this? Like take a dictionary like this, a single dictionary? Can I say it like this? Weeks, colon. What do I pass? Weeks data. Bracket, sales. Now listen to me carefully. Everything will start making sense a little bit more to you, okay? In machine learning, whenever you do in the production, whenever you're writing code, how you cut your birthday, right? How you cut your birthday cake. Just like that in machine learning, you need to do two cuts, okay? Two cuts, C-U-T-S. Sir, what are those cuts? I'll tell you. Imagine this is your data, okay? This is your column data, your Excel data, your, good looking, beautiful looking Excel data, okay? The first cut you need to do is separate target and feature separately. Suppose I have a column called feature 1, feature 2, feature 3, feature 4, and target. Where is the first cut you will draw? Okay. Where is the first cut you're going to do? You are going to separate your target and your feature separately. Am I making sense? Your first cut should be to separate your target and your feature separately. Usually in machine learning, target is taken as X and the feature or your actual feature, sorry, your feature is taken as X. Okay. Your feature is taken as a variable called X and your target is taken as Y. Did it become clear? Your features will be separate, your target will become separate. So tell me here, can I take something called X equals to df of, specifically df at weeks? Can I say all the values of the weeks will be converted to X? So if I print X, all the 1, 2, 3, 4, 5 value of the weeks are separated in X. Yes. And your Y value will be, your value of Y will be df of sales dot values. So what did you do? Did you take your X and Y separately? Did you take your X value and your Y value differently, your variable separately? So you have done that. The second cut you're going to make is separate something called as training versus testing. I'll explain the concept. You make a cut like this. Okay. This much data is training data and this much data is testing data. Okay. I'm going to explain this concept a little later to you. I'm going to keep this graph in the next. Did I first make the first cut as per what I had done? X and Y is separate. The first step that we do is calculate the mean of X and mean of Y, correct? In the mathematical example also, I calculated the mean of X separately, then mean of Y. Mean underscore X equals to NP dot mean of, what do I pass? X. Mean of Y is going to be NP dot mean of Y. Did I take the X separately and the Y separately? The mean of X and mean of Y? N is equal to length of X. Basically, I am taking another variable called N where I am understanding how many X parameters do I have, meaning how many independent feature sets number do we have. N will represent that. NUMER, numerator is equal to 0, denom is equal to 0. What have I done here? What have I done here? What is the concept here? Numer is equal to 0, denom is equal to 0. Have I taken something called as a counter? In Python programming, this is also called as a counter. This is counter. I have initialized the number to 0, correct or not? This is a counter that I have taken. Okay. In the mathematical terms of doing the R square calculation, sorry, in the calculation of y is equal to mx plus c calculation, numerator is nothing but x minus x bar into y minus y bar. Agree? X minus x bar into y minus y bar. X minus x bar into y minus y bar. Please tell me, for I in range of n, how many data points am I going through? All the values of x? Am I looping through all the values of x? 1, 2, 3, 4, whatever values of x is, I'm going to calculate its x, x bar, y, y bar. I'm going to calculate all of that. Okay. Can I say numer, NUMER, plus equal to, numerator plus equal to, keep on adding that number is x of I, which is the actual value of x minus mean of x. Is this x minus x bar? Is this code, as simply put, nothing but x minus x bar into y minus y bar? So y will be taken like how? Y of I into mean of y. Is this x minus x bar into y minus y bar? I am simply looping through the code. I am simply looping through the code. How many? First, I will take row number 1, then row number 2, then row number 3, then row number 4, then row number 5, then row number 6, then row number 7, and it goes and on and on and on. I'm sorry. What? Isn't it minus? What is minus? What did I do? Where did I make mistake? X minus X bar into, oh, sorry, Y minus Y bar. Yes, sorry. X minus X bar into Y minus Y bar. Correct. Okay. So X minus X bar, Y minus Y bar. Numerator is done. What do we need to solve for next? What do we need to solve for next? X minus X bar is done. Denom. Denominator plus equal to, what is going to be denominator? Look at the formula. Denominator was X minus X bar the whole square. X minus X bar the whole square. So how do you write X minus X bar? X minus X bar the whole square. Can I say this? This is X minus X bar the whole square. Okay. If I come outside the loop to calculate the value of M, do I need to divide numerator by denominator? Numerator divided by denominator should give me the value of M, correct? M should be equal to numerator divided by denominator. Agree or disagree? Okay, that's good. And what will be the value of C, my people? What will be the value of C? I have written the formula right here. Can you see? Y bar is equal to mx bar plus C. Y bar, sorry, give me 1 second. Y bar is equal to mx bar plus C. So can I say C is nothing but mx bar, sorry, y mx bar plus C. So if I move y bar minus mx bar, can I say it like this? Can I say this is going to be y minus mx bar? So if I write it like this, mean of y minus m, whatever value of m I have calculated from top into mean of x. Can I say it like this? If I print f double quotes of m is this. And the value of c is this. Did I get the value of m and c? Now we make plots. So now I'm going to do some plotting. Why plotting? Because we just calculated y is equal to mx plus c. Yes or no? We have the value of m and c. We just need to put the value of x. So if I say max underscore x equals to, just try to understand the code I'm writing, okay? np.max of x plus 1. Min of x np.max, np.min of x, because it is the min value, I'm going to take -1. Okay. Who knows what this np.linspace? Have you all used the method called linspace? Have you all heard of something called linspace? Comma, max of x, right? You guys have heard about something called this, right? Mx plus c, correct. That would be 1, 2, 3, 4, 5, 6, 4 and 4, and then mx plus c, right? That should be fine. That's my equation, correct? From min to max, which is correct. Okay, fine. See, I'm very sure you must have studied something called linspace you guys did do something called NumPy, right? You guys have studied something called NumPy, correct? I'm assuming that NumPy is done. Okay. Or maybe, I don't know. Let's take a little maroonish color like this. Yeah. Let's come to this part of the code and change this to hashtag this. Color is done. I can change the label also. X and Y in color. Okay. And you guys have studied matplotlib, correct? So what I'm doing here is I'm writing a label because this is going to be sort of like my regression line. Okay. Regression line that we have just calculated from that particular thing. Okay. Line style will be, I'm going to keep it actually dashed so that you guys understand dash dash. That's more than enough. I will take no alpha if you guys don't want it. Plot dot scatter. Okay. Inside the scatter plot, I want to plot the original values. So I'm going to take x comma y, the one that I had originally. Okay. So the color is equal to, let's take sky blue. Sky blue. And the label I want to add, because I want to add a legend, legend later on. Label is equal to the actual scatter point or the actual data point. You can call whatever you want. Point, right? Actual data point. And actually I can make them bigger or smaller. I think I can make them bigger. How do you make the points bigger? Actually, there is something called width. Yeah, I think I have to check it. So plot is done, plot dot scatter is done. I have taken two specific plots. Okay, so plot dot x label. So let me first take an x label. On the x label, I will say the number of weeks that have elapsed. Okay, weeks. And plot dot y label will be, the actual sales of the cars that have been done. So I will say sales. And plot dot title. I'm going to take the title of the plot to be, demo of linear regression or whatever it is. Linear regression demo. Okay, demo. And then we are going to do plot dot grid. Let's make it true because we want it to look good. And we will say plot dot legend, and the location will be equal to best, right? So the lock will be equal to best, upper left, upper right, depends on how you do it, right? Okay. Let's not make it sky blue. Let's make it black. Yeah. Okay. Not even black. It's not looking good. How do I make it lighter yet darker? Oh, I think this is darker color. This is like a good looking dark color. So I'm going to take this copy. I'm going to come to this code. We're going to go to hash and paste. Let's make the grid a little less lighter. Alpha 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 equals to, let's make it 0.5. Now let's make it little 0.3. Let's also make it line style is equal to, let's make it dashed, right? Let's make it like this. Please tell me if you're better. Looks good. Now let's make the alpha better. 0.4. Good. Okay. Do you see what has happened here? We have 4 data points. 1, 2, 3, 4, 5. 5 data points. The red color line is what is actually called as the fit line that we have observed. Yes or no? The red color line is the actual y is equal to mx plus c line, and the blue dots are the actual data points. You got what I'm trying to say? Let's make it a little bigger if you want. Please tell me if the code is correct. No. Is it capital S? I'm not sure. S is equal to 40. Oh, I think I'll get an error. Or small s equals to, let's make it 70. Yeah, okay. Now listen to me carefully, okay? What have I done here and how am I basically printing these values, okay? See, predominantly, I want you to understand just one thing, okay? I have taken something called max of x is equal to np dot max plus 1 and minimum of x is np dot min minus 1, okay? The largest number of the value of x, is it 5? Plus 1 will be how much? And the most minimum number in x is what? 1. Minus 1 is 0. I want to make a plot. Where the x-axis will start at 0 and end at 6. Did you get it? Limitation on the x, the direction of x. Okay. Now what did we do? X equals to np dot linspace min x and max x. Do you know what does linspace method do in NumPy? Everybody? Do you know what linspace does? Everybody? You guys are clear, right? What linspace or this line space does? It's actually spacing. It's for spacing. You guys are aware. So I don't need to teach you this, correct? I don't need to teach this x equals to this, create equal spacing. Very good. I have taken something called y is equal to mx plus c. I plotted x comma y with a different color with a label and a line style. I plotted the scatter plot x and y, the actual data point, color, label. I did the x label, y label, title. I've put the grid in the background. Alpha is the intensity. How do you want the intensity to be darker or lighter? Line style is the style of the line. And then legend is basically regression line and data point. And I plotted this data. Yes or no? Are we visually clear on how this particular thing works? Are we visually clear with the concept of something called how does the whole thing work? It's good. Very, very good. You got what I'm trying to say? You don't know what is grid and legend. Okay, so you don't know what is grid and legend. Do you see the background grid? Okay, let me make it alpha 1. Alpha 1. Alpha equals to 1. Okay. Do you see the grid in the background image? Let me show it to you like this. How about now? Is there any grid in the background? No. Correct. But the minute you say plot.grid and pass inside the parameter called true, it will make the grid for you. If I run this answer, this red color line is what? The blue color points are what? We don't have that information. If I don't have that information, then the plot looks incomplete, right? I want to label it in the plot. So if you do plot.legend and print it, can you see the red color thing is called regression line and the blue color points is called data point. This difference is what we call as legend. How it figured out without giving figure size. Matplotlib has everything by default. If you don't give any figure size, it won't give you error. It will still run. I thought you guys knew this by now. Nobody takes figure size. Nobody in real practical applications takes figure size. Figure size is very illogical and also irrelevant because if you take more than 5 plots, subplots will take care of by itself. What max x and min x does is a very simple thing, right? When you plot any graph, you want to know how long do you want your x axis to go and where do you want to start your x from. You want your starting point for the x axis to start at some value. Now it so happens that not every time the x and y graph will start at 0, 0 only. Sometimes a graph can also start like this, right? A graph can start -3, -2, -1, 0, 1, 2, 3. Sometimes graph can start like this also, right? Not necessary that every time they start from 0 to 0. So what I did is I took the X column, which is this weeks column, and I calculated what is 5 plus 1 because the maximum of weeks is 5. Plus 1 will be 6. So it will plot a graph where the ending point will end at 6. And the starting point will be minimum value, which is np.min. The most minimum value of X is 1. 1 minus 1 is 0. So it will start at 0, go all the way till 6. And then I can plot whatever y value I want. So to restrict the columns, sorry, the values on x, I did that. So now tell me, let me ask you guys one more question. Sir, if I do it like this, 100%, let's take minus 10 plus 10 and run this. What is your access value? What is your access value here? Minus 15 to 15. You got what I'm trying to say, right? Plus 10 and minus 10 were added to your data. So your actual data point got shifted below. Can you see the points are now closer to each other? Let me copy paste this. Sorry, not copy paste, and move this. And do you see the answer called 2.2734, 2.34, 2.42, 2.49? Okay. Y is equal to mx plus c. You will be like, there are so many values in this, right? There are so many values. Is that the question that you have? That y has so many values? Tell me, okay. Print length of y. Okay. Length of y. Tell me, what is the length of y? 50. Okay. How many data points does y need if I calculate y is equal to mx plus c? In actual y predicted value, what answers am I supposed to get just for the prediction of y hat? Y is equal to mx plus c is supposed to give me 5. Okay. Tell me one thing, right? When you print y is equal to m into x plus c, okay? Did I break my actual x into multiple different data points here? This is not the actual x, the capital X. It is the small x. You didn't understand. Okay. Is this y is equal to m capital X, which is the actual data point plus c, or I had to take linspace because I had to plot the value for line also? You didn't get it. I had to print the value for each individual line, correct? So have I not taken x is equal to np dot linspace, and it divides the whole data into 50 different points. And that's how I got a straight line. You got what I'm trying to say, or is there confusion? Did everybody get the concept or no? Okay. How many data points do we have in weeks? Okay, listen. How many data points do I have in week? 5. The name of the variable, is it capital X or small x? Is it capital X or small x? It is capital X, not small x. When I did y is equal to mx plus c, is it small x or capital X? When I wanted to plot the point, I wanted to show the line for the entire data point, right? For all the 0 to 6. For all the values of 0 to small value, I wanted to show. So tell me, if I did x equals to np dot linspace, if I print x, how many values of x did I get? Equal portion. 0 to this is one portion. This to this is one portion. This to this is one portion. This to this is one portion. Haven't I divided my value also into multiple small points? Meaning your x-axis also got divided into so many smaller points, equal spaced value. Yes or no? Now, don't I need to do a line equation for all small points? So that is why I have not taken capital X, I have taken small x. That's why the line will go from the 0 all the way till 6. Longer line. Why are we doing it? If you don't do it, will you be able to plot a line? If I don't do it like this, will I be able to plot a graph like this? Like the line going all the way from here to here. That line, that red line going from left to the bottom, will it go? No. Line will start here, it will end here. Correct or not? The regression line will be so small, it won't be visible. That's why we are doing it. If you don't do that, you're pretty much done. You will not be able to plot. Then you will be having only y is equal to mx plus c. That's it. Like you will have 5 different answers. You will get this answer. Y predicted is equal to this, but you will not be able to plot it. This value, y hat. 2.8, 3.4, 4, 4.6, 5.2, and you're done. So what it did is it created some values and then connected the dots to create a line. Yes, that is what it is doing. If I take the values to be more and more, the line will always be visible. The line will not become shorter and longer. It will always be visible. The regression line will always be visible. That's why we did it. I hope you got the concept. In reality, it's only calculating 5. That's it. That's all it does. It's not a very complicated thing. So what if we have only 7 data points and not 50? Still, we will be able to plot. You can do it, Piyush. It's not a very complicated thing. If you want to plot only is equal to y mx plus c, write a loop, write x of I, and you'll be able to calculate it. Shouldn't be a problem. It's not going to be a problem at all for you to calculate it. What value of x's do I have? Do I have the value of x's like this? X is equal to, let me show you. What is the value of x do we have? Is it an array? So if I do x of 0, will it give me the value 1? So tell me, for I in range of, listen to me, for I in range of length of x, will this run the loop 5 times? If I print x of I, will this give me the value of each number 1, 2, 3, 4, 5? Now that you have 1, 2, 3, 4, 5, can I do this? Y is equal to m into x of I plus c. Can I do it like this? And close it and close it. And if I go ahead and print y, each time that the y happens, I print it. So 2.8, 3.4, 4, 4.6, and 5.2. Can you not take this in an array and plot it? You can, na, sir. Of course. It's a simple method. You know how to plot this, right? You guys know how to take two array values and plot them, right? You must have done that like multiple times. If you take another array, arr underscore new is equal to an empty array, and take this arr underscore new dot append. Okay, inside that append, what do? We append the value of y. If I run this, what is my arr underscore new value? Did we get the answer? Take this and plot it. Done. Now, my people, let's talk about the calculation of R square. How did we calculate R square? What did we do in R square? Sum of square total, sum of square residual, all of that stuff. We'll be talking about that. Okay. So as you guys already know, we calculated something called R square, right? To calculate R square, sum of square total, SS underscore TOT total. Okay. Is it going to be empty? It's going to be 0. Sum of square residual is going to be 0. Okay. I have taken two separate counters, sum of square total, sum of square residual. Listen to me. For I in the range of, how much do I need to run the model? How many times do I need to iterate? N times, because I've already taken the value of n on the top. Y underscore pred. For calculation of R square, I want the value of Y predicted values. Yes or no? For the Y predicted values, I want the values of Y pred. So can I say Y pred is mx? X is nothing but x of I and plus c. Can I say it like this? So sum of square total plus equal to, based on the formula that we wrote, y minus y bar the whole square. Listen to this. Y minus y bar the whole square. The whole equation is reversed. That's why we do 1 minus. I'll show you. Y minus y bar the whole square. So can I say the equation will be written like this? Y of I minus mean y the whole square. Y minus y bar the whole square. This is my sum of square total. My sum of square residuals value plus equal to y minus y pred the whole square. Opposite. Y minus y pred the whole square. So y of each individual point, actually this is capital Y, okay, because we are taking from the actual value. Y minus y of I minus y pred the whole square. I have taken the value of sum of square totals and sum of square residuals. Based on this, my R square answer that I got is 1 minus sum of squared residuals, right? So sum of squared residuals divided by sum of squared total. If I run this and print, go ahead and print F double quotes R square is going to be R square. If I run the answer, what answer did we get? What answer did we get? 0.6. What answer did we get here? The only difference in this formula and that formula is sum of square total and residuals are opposite. Agree? They are numerator is denominator, denominator is numerator. So if you do 1 minus the reverse case, is it the same thing? In mathematics, when you want to reverse A by B with B by A, you just take 1 minus of sum of square total by sum of square residual, and your answer is pretty much the same. I hope you got what I'm trying to say, everybody. So tell me, did we use any library in this? But we got the value of R square and Y is equal to MX plus C. Can we validate? Do you understand what is validate? If I would have used a machine learning library like sklearn, scipy, what answers are they saying and what answers do we get? Can we validate it? From sklearn dot linear model, I'm importing something from sklearn dot linear model. I will import something called linear regression. Can you see I'm importing something called linear regression? I'm importing a model called linear regression. I've imported x equals to, now remember, the problem is when you use a library like linear regression, sklearn, stuff like that, it needs the data to be in two-dimensional format. So your x value should be reshaped. I'm going to reshape the value to -1 or n comma 1. So if can I take it like this, n comma 1? What does this do? Do you guys know what reshape does? N comma 1. The value that we had, was it not a single array like this? The x value was a single array. If I print x here, is it not a single array, one-dimensional array, one bracket open, one bracket close? But in sklearn, you cannot run like that. You need to have the data, even if it's 1D array, it should be in what format? It should always be in what format? 2D format. So this reshaping, I converted the entire form into a 2D array. Are we clear? We converted the whole thing into a 2D format. Now that the whole thing is converted into 2D format, let's take this as a small x, not a capital X, because there will be a lot of confusion. So let's run. Okay, x value should be equal to this. The problem is what you need to do. You need to call the library. Regression is equal to linear regression. Close the bracket. Regression is equal to regression dot fit. And inside the fit, you will pass something called the actual value of x and the actual value of y. Did I make a mistake? I did make a mistake. I think there is a shape. Oh, I took it as a small x, correct? I did take it as a small x. Yeah. What did I do here? This 2 lines of code has run the model. The model has run, meaning linear regression has occurred. You don't need to do anything else now. Your value of y_pred, y underscore pred value, the predicted value that I want to calculate is going to be m into x plus c. If I do, you know what, let's take it in x format only because I'm taking it separately. So there is no confusion here. Okay. Mx plus c. My people, if I calculate the y_pred value like this, mx plus c, right? And if I run that value directly, suppose if I want to just run the value of y_pred straight up, because I'm using the package directly, if I have reshaped the value, or maybe, you know, maybe I'll do it like this. Until here, is everyone clear? Let me run this once again. Until here, is everyone clear? I have run the linear regression part. This part is called linear regression. I have just used the method. Why do we need to reshape y? We never reshaped y. We only reshaped x. We only reshaped x. We never reshaped y. Where in this code do you see reshape y? Where in this piece of code have we reshaped y? Why not? Okay. When we run machine learning or when we run machine learning code, y is only for prediction, right? But the actual mathematics is happening with the feature numbers, right? Y is not even getting involved there. Does that make sense? Your x value, which is the feature value, your x is being crunched. Your mathematics is only operating on x. Y is just a number that can be compared. Suppose if the y value was 4, y_pred is 3, the maximum you do is y minus y_pred. Agree, disagree? The entire operation is running y is equal to mx plus c. The x is being multiplied with m and then added with c. All this operation happens on the x value, correct? So the reshape has to happen only on x, never on y. All of you got the question that features are the one that goes through a lot of mathematics. Target just sits. It has no operation. The maximum it will do is y minus y pred. Done. Everyone got what I'm trying to say? What did I do here? I took a value, I reshaped X, and I'm running linear regression. Basically, this value here is running linear regression. Agree, disagree? This particular value is running your linear regression. That's it. You've run. Now, if I say y pred value, whatever is your y pred value that you want to score or you want to calculate. So if I want to calculate the value of, say, r square, you want to calculate the value of r square. If I say r square is equal to, just r square is equal to reg, because I have taken everything in the small reg dot score, SCORE, pass x comma y directly. And if I print r square like this, what answer did we get? What answer did we get? 0.59999. Is it 0.6? What answer did we get for r square? We got an error of 0 point or 10 to the power of minus 12 with least significant digit of 10 to the power of minus 12. Did you understand? I ran a model, a linear regression model. By the way, this is not modeling. Modeling, I will teach you how to do that. But when I ran the algorithm, the actual library versus our code, we got the same exact answer. You got the concept, my people, on how we wrote linear regression from scratch, how we implemented it from library, the numbers match. If R square is matching, M and C also is the same answer. The point and the plot is also the same answer. Everything that we've done is calculated. Did we get the concept clear? Now, in the formula of R square, did I not take the value here, the formula? Y hat minus Y pred the whole square. This formula, I have taught you this formula. This formula is already given. All I did, sum of squared total was Y minus Y bar, the whole square, and Y minus Y pred the whole square. We had taken opposite, but in actual R square formula, we take 1 minus of this value. When we take it like this, whatever formula we get on, whatever answer we got then, we got the same answer here. Validate part is confusing. It will be confusing. Have you ever used a method called linear regression or linear model ever? No. This is not for your understanding. This is only to show you that the answers are same. Even if you don't understand the code, it's okay. This is to show you the difference. Linear regression formula, library, and our way of written, we got the same answer. Is going to be a very simple thing, right? I'm going to be importing something called import pandas as PD. Now, I'm going to ask you all a very simple question. This is not the first or a very new library for you, right? I'm very sure you must have implemented this library and you have learned this library, so I don't have to teach you. Okay. Hiding internal implementation and use of existing libraries as and when needed instead of rewriting the code. Yes, absolutely correct. The abstraction in object-oriented programming is different from the abstraction that I am talking about, but you got the logic correct, right? So encapsulation, polymorphism, injection of control, dependency injection, adaptee, adapter. These are all object-oriented principles, SRP, single responsibility principles. These are all object-oriented principles. They are very technical in nature. What I'm talking about is the basic concept of abstraction, but I'm very glad that you got it. Knowing object-oriented skills, programming skills is very important, right? So now what we've done, we've imported pandas as PD. I want to load a data, right? So I'm gonna keep this thing as import all other OTHER libraries here. Okay, import all other libraries here. Here, I'm gonna load the data set. I'm gonna load the data set. Okay, let's load the data set. Data is equal to PD dot. Now, I already have an API or a method which is given to me, using which I can load the data set, right? So pd.read CSV. And my people, I'm going to give you guys certain tricks. I'm not sure if you know them or not, but I'm going to do it. See, in pandas, you have a trick of loading the file directly, right? So if I want to load it directly, I have this. See, now my data is loaded. Okay. So I have loaded pandas and I have loaded the data set. Now, let me tell you the trick I use to load a certain file faster. Okay. Every computer has a structure called folder. Yes or no? You create your own folder. You can create your own folder. Inside that folder, listen to me carefully. Inside that folder, how many files are there? To find that out, you can use a trick called dot and forward slash. A dot and a forward slash. When you use dot and a forward slash and press on tab, you can see all the files. So you see this headbrain.csv. Now I have loaded this file. So basically, a method called dot read CSV reads the file called CSV. Now, what is CSV? It's comma separated value. Now let me tell you two different things. You guys are currently learning machine learning on a tool called Jupyter Notebook. Like Jupyter Notebook, there is something called Google Colab. Like Google Colab, there is another tool called Visual Studio Code. These are platforms on which you can write the program. This CSV is the format of the file on which you work. Sometimes you work with Excel format. So the extension will be .xlxs. If you work on something called Apache Parquet, so you will have Apache Parquet, Apache Parquet, right? If you work on Hadoop distributed file systems, then you will have a different kind of data set that's given to you. If you work on Carrot file, it'll be different for you. Remember, in machine learning, you can use as many different kind of structures as you want. Depends on what is the file structure that you have, okay? It is so if the same folder available to, no. Dot slash only gets you the file from the same folder on which your file ml_ff is written. Your folder needs to be same. If the folder is not same, it's not going to go beyond that to get it for you. Okay. What is the difference between Jupyter Colab and Visual Studio? See, Visual Studio is something that you will appreciate a lot. Like if I show you a Visual Studio code, I'm not sure if I have it with me. I mean, not here, Visual Studio code. Okay, I'm going to show you the difference between Colab and Visual Studio Code. Actually, you should really know the difference between Visual Studio Code and this. So you see, right now, this is inferential stats that I was teaching a while ago. This is extension. Give me 1 second. Let me go ahead, and I think I had a folder somewhere. I'm going to open it up for you guys. Give me 1 second. Desktop. And I have A to Z. I think I was teaching. Yeah. Let me see if this is the, yeah. So this is like a small data structures code that I was teaching to a recent batch right now. So see, this is written in an IPYNB file. This is how Visual Studio is going to look like for you. So you see, it has a certain theme. So I'm just going to expand it a little bit, right? So I'm going to, show it to you. So what happens is basically, if you run a portion of this, so for example, how do you find the second largest and the second smallest thing from an array? So you have a certain way of doing this. So what happens in Visual Studio Code is, Visual Studio Code can help you write any kind of program with a proper and a beautiful file structure. So you can maintain and work on the database together, files together, multiple different stuff like Docker, Kubernetes. If you want to build a Docker container for your, code, if you want to do a blue-green deployment. So you can do all of that in one place. Jupyter Notebook is more like for beginners. If you're a beginner, you're just starting with your machine learning journey or starting with your programming journey, people usually prefer Jupyter Notebook. But Jupyter Notebooks are not predominantly used for deployment, meaning you don't take a Jupyter Notebook file and you're going to be use it for deployment. Some people do that using Amazon Web Services and Kubernetes services, but usually it's not preferred because you have to do load testing, stress testing, pen testing. It's like regression testing. That's like crazy amount of stuff you have to do. Okay. For VS Code, we need to create environment for Jupyter, or you can use it directly. It's directly. All you need to do is just download Darwin. So VS Code Darwin, if you just just download Darwin, you should be able to work on it. Or just write Visual Studio Code, right? Like VS Code, depending on your computer, MacBook, or whatever it is, download. That's it. Just download, install the kernel, you're done. Okay. Colab is just like that. Colab is exactly like Jupyter Notebook, but it works on cloud. So if I go to Colab for you guys and show you just one example, I have a pro version. So I'm going to show it to you differently. So see, this is the code of large language model like GPT. If you want to make your own GPT, this is a code for that. I'm using something called Microsoft 5 3.5. So see, for example, if I want to chat with my model, so if I ask a question like, like, hey, can I extract some image information from from a given image or something like that? So see, I use something called as Google Colab Pro. The difference in Pro is I get an opportunity of connecting with something called A100. A100 is a very expensive GPU. So you will not have this option. I have this option. You will only have CPU or GPU or TPU. In Google Colab, what happens? You are able to load your data in a separate file called file structure to the left. So you have files here, so you can load your data there. That's the only difference. It's just like Jupyter Notebook, but the way it is done is slightly different. Okay. So Jupyter Notebook is same, Google Colab is same, and all of that is same. It's just that you can use a lot of, you can do a lot of fancy stuff with Google Colab. GPU for image processing. GPU for large language models, for inferencing. When you write a query to a GPT model, you need the answer to be as fast as possible. For that, we use GPU. Okay. So now coming back to the point, right? I have loaded the data set. I want to test my data set. How do I do that? Data.head of 5. And if I run this, what data do I have right in front of you, my people? Let's look at it. I have 4 columns. Those 4 columns are, I have gender, I have age, I have head size, and the size of the brain in weight. Okay. So this data set that is available right in front of you, you guys are able to see the, okay, how about now? Is this more clear? Much better? I've zoomed in for a better clarity. Okay, good. So the data set that I have right in front of you is a very simple data set. It has 4 different columns: gender, age, head size, and brain weight. Basically, I want to predict using linear regression that does increase in the size of the head increase the weight of the brain? Basically, if the size of the head is larger, does it mean that there exists a relationship between the weight of the brain? Meaning, larger the head, larger the brain, smaller the head, smaller the brain. To us, it looks like, I think it's common sense, but I don't know. There must exist a relationship, and we will calculate that using linear regression. So in order for me to implement it using linear regression, I need to identify one thing, understand one thing. Okay. And I want to teach you this very, very clearly. Okay. So see, I have taken this example right in front of you: gender, age, rank, whatever, XYZ, right? I'm going to come over here and I'm going to paste it in front of you. Okay. So give me 1 second. Cut. And I think, why don't I paste it in a view sheet? Okay. Are you guys able to see this original data set right in front of you? Okay. This data set is what I would like to call the OG, the original data set. Okay. Now I will tell you how important is data scientist's job. My people, look at the data and observe carefully. How many variables or columns are categorical variables and how many variables are continuous variables? How many variables are continuous variables and how many are categorical? First of all, let me ask you all one question. See, my people, in statistics, you guys must have learned something called continuous variable, categorical variable, ordinal variable, nominal variable. I'm going to revise that concept to you, okay? See, whenever a number is continuous in nature, for example, temperature, can temperature be 47 degree, 37.19 degree, 97.26 degree, meaning it can belong to any range of negative infinity to positive infinity. A number that exists continuously and can be any number between negative infinity to positive infinity. This kind of variable is called continuous variable. What do we call this? What kind of variable do we call this? This variable is called continuous variable. Let me show you an example. Between age, gender, head size, and brain weight, which number is any number that is continuously going on? Isn't head size and brain weight continuous? I'm asking everybody, whoever I taught you, both head size and brain weight are numbers between 4512, 3738, 4261, 3777, 4177, 1530, and all of that, and all of that, and all of that. Listen to me carefully. Data of just gender. If I just take gender, dot value counts, okay? Dot value counts, and run this. The gender column has only two kind of people. If you are one, it means you are a male. If you are two, means you are a female. So tell me, in the column of gender and age, let me also take age very, very quickly. Paste, remove gender and say age. And this. Do I also have the same category like 2 and 1? It's like category. Either this or that. Is it continuous by any chance? Everybody, whoever did not know the difference between categorical variables and continuous variables. So, head size and brain weight are continuous variables. You will find numbers which can belong from negative infinity to positive infinity. But when you go to columns like gender and age, do we have infinite amount of genders available in this planet? No. So this value becomes categorical variable. What variable will it become? Categorical variable. So now that you have the clarity, this variable and this variable, gender and age, is it categorical? And head size and brain weight, is it continuous variable? And the answer and the distinction is clear. Am I making sense to everybody? What is the difference between a continuous variable and a categorical variable? Did you guys get the clear, your differences clear, everybody? In the most simplistic sense, I hope everyone is clear. Is there yet anybody again who has confusion? I don't believe there should be, but I am asking. No. Okay. The answer is clear. Okay. For implementation of linear regression, we have no use of gender and we have no use of age rank or range. We don't need them. It's not needed for my analysis. They are not helpful in any perspective. So I need to remove them from my original data. Now, here is what I want you to know and listen to me carefully. Sir, does that mean whenever I implement linear regression, I should never take categorical variables? I should only take continuous variable? The answer is no. If you want to implement linear regression, listen to me carefully. I'm telling you, this is very important. If you want to implement linear regression, your target variable should be continuous in nature. What variable it should be? Your target variable, whatever you're trying to predict should be continuous. Your features could be a combination of continuous, categorical. That's okay. Did that make sense? Whenever you want to implement linear regression, the rule is, the law is, the target variable that you will take will follow what variable? Should be of what kind? It should be a continuous variable. You cannot take a target variable where the data is categorical. This is not allowed for linear regression. Very good question. See, this is what I want to know. But gender and age might also have an impact on the head size and weight. It does. But the problem is, in machine learning, can I say that your gender, age, and head size is going to be my feature data set and the brain is my target? can I split my data set like this? Can I do this? Okay. Meaning, using head size, I can predict the brain weight. Okay. Given the size of the head, I can predict the size of the brain. Okay. In machine learning, you can do something called feature engineering. What do you mean by feature engineering? Is gender important for my calculation of brain weight? Is age important for the calculation of brain weight, or head size is important for the calculation of brain weight? And then the machine learning will only tell you, don't give me gender, don't give me age. They are not adding any value. Just give me head size. And when I did that and when I ran that, it says only head size has more correlation with the prediction of brain weight versus gender. Now, why am I not showing you feature engineering? Because that code is very, very large and you haven't yet come to the concept of feature engineering. So now did everybody understand why am I asking you to drop gender and age? Because these are not adding any value to the final prediction. Hence, we are going to be dropping these columns. But I will be teaching you how to do this calculation all by yourself. How to take a feature set of multiple different columns and identify which columns are important and which are not. In specifically linear regression, what variable cannot exist for target? Tell me, if you are implementing something called linear regression, your target variable should be not of this type. What is that not? Categorical. What it should be? What it should be? It should be continuous. Number one. So tell me, what do we do? What do we do here? First of all, I took something called gender. I took something called age. I got something called head size. I will be only using the data set from the original data set. What I'll do, I will take my original data set, okay, which is this, and I am going to, I'm gonna duplicate, okay, come to the bottom. And what I'm going to do is I am going to remove these two columns, age and gender. And now I will be left with this two columns. So originally, what did I do? I had this data, but what did I do in between? I dropped dropped, dropped some columns, and I got the answer called, I got the data set as head size and brain weight. Agree, disagree? This is my original data. Now, this was my original data, but this is my data now because I no longer have needs of these two columns. Taught you the concept of something called as in machine learning. Okay. Just listen to me carefully and everything will make sense. Just like how we humans need to be shown some things for us to understand, machine learning also requires training. When I say training, it needs to go through something multiple times for it to get the idea. So tell me, my question is very simple to you. If I teach you 4 plus 5 is equal to, that's correct. 3 plus 2 is, reinforcement is different, Kalpesh, right? Reinforcement will be a different thing. But yeah, reinforcement also is like you have to train the model and get the idea. It's absolutely correct, right? So it's also going to be, it's also going to be same. You will get the concept. Okay. So imagine you have been taught how to do addition. 4 plus 5 equals to 9, 3 plus 2 equals to 5, 1 plus 2 equals to 3, and 2 plus 2 equals to 4. I taught you this. I taught you mathematics, okay, addition, where 4 plus 5 is 9, 3 plus 2 is 5, 1 plus 2 is 3, and 2 plus 2 is 4. I taught you this. If I now want to test, have you learned mathematics or not? Or have you learned how to do addition or not? What two numbers will I take? You didn't understand. Let me explain. I taught you how to add two numbers, 4 plus 5, 3 plus 2, 1 plus 2, and 2 plus 2. I taught you how to add using these numbers. Okay, good. If I want to test your mathematics skills, should the numbers be different from what I taught you? Because if I give you the same number 4 plus 5, 3 plus 2, 1 plus 2, you can also cheat. You can also cheat, right? You can also memorize. My question was very simple. I said that when I taught you mathematics, I taught you using four numbers, 4 plus 5, 3 plus 2, 1 plus 2, and 2 plus 2. If I give you a number called 2 plus 2, wouldn't that be cheating? Because you can always memorize what was 2 plus 2, 4 and write it down here, but you did not really understood math, correct? You can cheat like this. So what if I, for testing, give a number like this, 3 plus 6 equals to whatever this answer is, right? I think it'll be 9. Yeah. You understood what I'm trying to say? And then if you're able to answer 9, then I know you have learned math, correct or not? Agree or disagree? Machine learning works exactly like this. I'll tell you why. Imagine you have an entire data set of all these numbers. 4 plus 5 equals to 9, right? 3 plus 2 is 5. 1 plus 2 equals to 3. 2 plus 2 equals to 4. And 3 plus 6 equal to 9. This is my entire data set. Okay? This is my entire data set. To train my machine learning how to do addition, what will I do? I will divide my data set like this. All this from the top will be used for training my machine learning model, but I will keep this number separate. Why will I keep this number separate? Because I want to test my model also. Hey, model, did you learn mathematics? The model will say, yes, sir, I learned mathematics. Okay, let me give you a question. But the question I'm going to give you, you have never seen it in the training. This question is unique, one of a kind. You have not seen it. But because you say you have learned everything from the training, you should be able to solve the problem. Is this logical? Is this a logical approach to test whether something who says that I have learned, to test whether this person has already learned or not, actually learned or not? If I want to test your mathematics skills, if I want to test your mathematics skills, should the numbers be different from what I taught you? Because if I give you the same number 4 plus 5, 3 plus 2, 1 plus 2, you can also cheat. You can also cheat, right? You can also memorize. My question was very simple. I said that when I taught you mathematics, I taught you using 4 numbers, 4 plus 5, 3 plus 2, 1 plus 2, and 2 plus 2. If I give you a number called 2 plus 2, wouldn't that be cheating? Because you can always memorize what was 2 plus 2, 4 and write it down here, but you did not really understood math, correct? You can cheat like this. So what if I, for testing, give a number like this, 3 plus 6 equals to whatever this answer is, right? I think it'll be 9. Yeah. You understood what I'm trying to say? And then if you're able to answer 9, then I know you have learned math, correct or not? Agree or disagree? Machine learning works exactly like this. I'll tell you why. Imagine you have an entire data set of all these numbers. 4 plus 5 equals to 9, right? 3 plus 2 is 5. 1 plus 2 equals to 3. 2 plus 2 equals to 4. And 3 plus 6 equal to 9. This is my entire data set. Okay? This is my entire data set. To train my machine learning how to do addition, what will I do? I will divide my data set like this. All this from the top will be used for training my machine learning model, but I will keep this number separate. Why will I keep this number separate? Because I want to test my model also. Hey, model, did you learn mathematics? The model will say, yes, sir, I learned mathematics. Okay, let me give you a question. But the question I'm going to give you, you have never seen it in the training. This question is unique, one of a kind. You have not seen it. But because you say you have learned everything from the training, you should be able to solve the problem. Is this logical? Is this a logical approach to test whether something who says that I have learned, to test whether this person has already learned or not, actually learned or not? Okay. Do we need to clean data by removing any duplicates? We don't want to do that yet. The point I'm saying is, you will take your entire data set and divide the data set into 2 different portions. One data set is going to be called as training data set, and the other data set is called as the testing data set. Is this concept clear to everybody? Now listen to me. From the original data set of 100% data set, can you control how much percentage I want to use for training and how many percentage I want to use for testing? I can control that ratio also, meaning from 100% of the data set, can I use 80% of the data for training and 20% for testing? Should you have this control? Yes or no? Very good. Very good. Now listen to me carefully. Everything will make sense. This is my original data set, correct? Head size, brain weight, and all of that stuff. Yes or no? You should always do how many cuts in a data set? How many cuts will you do in the data set? 2 cuts. The first cut will separate the feature from the target. So can I say that head size is the feature X and brain weights is the feature or target Y? Sorry, feature X and target Y. Can I say this? So the first cut I'm going to do is where the first cut I'm going to do is on my original data set, which is this data set. So how do we cut it? Duplicate it. Give me 1 second, my people. You know, I am not very fast. Give me 1 second. So what I'm going to do is I'm going to make a cut. How do I make a cut? Actually, let's copy and let's make a copy of it somewhere here safer later on. Okay. So what will I do here? I will make a cut here. Basically, this is going to be my feature. I'm going to say, okay, my feature set is separate. And now I am taking another cut, which is going to be called as crop, which is going to be my target variable separately. So what did I do? I separated my feature and I separated my target. I did this. I separated them together. The entire feature set has the name of the variable as x equal to. So this is x equal to this and this is y equal to this. Agree, disagree? This is called as the first cut, separating the feature from target. The second cut you need to do is in the X and in the Y. You know why? Because between this data, you need to decide how much percent you want to take for training and how many percentage you want to take for testing. So can I do this? Listen to me. Okay, so let me explain. First of all, the data set that we have loaded has what? How many data do we have in it? 234. Okay. This is only 5. For example, it has about 200 data set. So tell me, the first cut I made was this cut, separating the X and the Y. And the second cut I made was separating this. You know why did I do the separate cut? Because this entire data set is going to be used for training and this entire data set will be used for testing. Did you understand what I did? I first separated the X and Y and then I separated the X separately and Y separately and I called them training and testing. Okay. For example, I have taken about 80% for training and 20% for testing. Agree, disagree? My people, this variable here, this variable, does it belong to X or does it belong to Y? Does this belong to X or does this belong to Y? This belongs to X. Underscore. Does this belong to training or does it belong to testing? So this variable is going to be passed in machine learning model as which variable? X train. This part of the data 4512, 3718 and 426 will be going to the machine learning model as X train. Now tell me, is this Y or X? Is this Y or X? Y. Y. Underscore. Is it training or testing? Training. So this will become my Y train. What is this? This is X. Is this training or testing? This is testing. So this is X test. What is this? This is Y. This is Y test. Did you understand? What did you do? You divided your data into 4 separate parts. X train, X test, Y train, Y test. Is everybody clear? We will be doing this in the example. But is the concept clear? Why do we do this? Is everybody following with me? You need to do this. You cannot escape this in your life of deep learning, generative AI, machine learning, statistics. You have to do this. So did you just divide your data set into 4 parts? Training, X training value is different, Y training value is different. X test value is different, Y test value is different. Agree? Once you divide all this data like this, how do you know your model has performed good or not? So I am asking you a simple question. This part of the data will be used for training. Agree, disagree? This training part of the data, both X and Y will be used for the training. Agree, disagree? The one that I have highlighted, both X and Y will be used for training. Whatever model has learned, machine learning model has learned, should I not create another folder or another column called y underscore predicted column? Meaning, using the training example, if I give it the test example 37774177, it will predict some number like 1200 1500. This is the actual value 1282 and 1590. This is the actual value and this is the predicted value, yes or no? And comparing the difference between these two columns, I will be able to say that, oh, okay, I am off by 2%, 3%. This is your entire machine learning. Is this concept clear to everybody? If the concept is clear, remember one thing. I am coming over to my data set right now. Is this my original data set with which I'm working on? This data set called data.head of say 10. This is the data that I have. My people, your machine learning model has done a good job or bad job. How do we know this? How do we know if the machine learning model has done a good job or bad job? By seeing the results, correct? But to see the result, you need to be able to compare it with something, right? Let me give you guys an example. When we were young, our parents used to tell us how good the neighbor's son is. Because neighbor's son got 90% and you got 80%. Example, I'm giving you an example. They had a comparison to do it with, right? Like you had somebody to compare it against. If you have nobody to compare against, can you do comparison? And by the way, I am Sharma. So, you know, Sharma ji ka ladka. So you get the concept. You have something to compare it against. So tell me, in the entire data set, how many data set did we take for testing? How many data set are we taken or have we taken for testing? 2 points. 80% is training, 20% is testing. Agree? 80% of my data will go into learning the module, meaning for training the machine learning model. For training the machine learning model. The machine learning model will learn from the training data. But now I want to test my module. I want to test my module. Okay. I want to test my answer. To test my answer, don't I need to give it the value of X for it to give me the prediction of Y? If I give it the value of X, it will give it, the machine learning model will give me some prediction. Oh, I think it will be this much. Correct or not? If I give the value of X test, it will give me some Y value, no? That Y value is called Y predicted value because this prediction is actually from the machine learning model. But the prediction is 1200 grams, 1500 grams. This is the prediction of the model. But don't we have the real value, the actual value that the model, the actual value in the data set, which is the Y test value? So won't you compare Y test with Y pred? You are comparing the Y test value with the Y pred value to compare and see, oh, okay. My algorithm is off by 80 points in this data point and 30 points in this data point. This will let us know how the algorithm is performing. Did you get it now? How you got Y test value? It's good, dear. Y test value comes from the original data, my dear. This is my original data set. I split the data into 4 different parts. So can you see what I did? The Y test value came from this part. I took the value of Y, I took the value of X, I split Y into 4 parts. Part 1, part 2, part 3, part 4. The fourth part is the Y test value. We need why do we need why predicted value is, for example, Anaga, you work in a very big bank, example, bank, PDFC bank. You want to build an algorithm by yourself that so that any customer can come to your bank's website and can ask and add the details like what is that person's age, what is that person's salary, what is that person's CIBIL, and you will give the prediction. Your machine learning model will give the prediction that, hey, come over to the bank, will give you up to 5 lakh rupee loan. Example. To build this model, you must have used 10,000 data points to train the model. Model needs to do prediction for millions of customers for the future use of also from the same data set, the model, how well did it learn? How good of a job did it perform? To
Okay.
test that also, you need to hide some questions from the model. That
Okay.
data set is called testing data. Because we already know in real life, in
Mhm.
actual life, for somebody whose brain size or head size is 3,700 centimeter square, the actual answer that we got using the using the calculation, actual answer was 1,282. But because our model has made prediction, our model will make prediction, the model's prediction is this and the actual answer is this. So can we also not compare and see how good our model has performed on
Okay.
the data set itself? My question is, we don't have actual y-test data in real time. We always have y-test value. I think you guys are slightly off by some points. Let me explain. Let me get the clarity. When you're training your machine learning model on 10,000 data points, you can only test on those data, correct? Okay, let me explain. Suppose you have 10,000 data set. Your data size is 10,000. How much is it? Ignore everything. I want you to answer my question. I have 10,000 data points, Baba. कितने data points है मेरे पास? 10,000. What is 80% of 10,000? What is 80% of 10,000? Is it 8,000? And what is 20% of 10,000? 2,000? Now tell me, is my model good or bad? I can only test on the 2,000 data points and validate, correct? Yes or no? If I make future predictions, my future predictions, I don't care if I have the y-test value for that or not. No. I am testing for the given 10,000 data point. How did it perform on the two? That's it. My accuracy, my model's performance will be judged only on the 2,000. On the 2,000, if it did a good job, I will use it for feature prediction because I know it's going to perform well. Did you understand why do we take test data? Test data is only to test. If it performs good in test, the point is it will perform good everywhere else also. You got it? Everybody? If the model performed good on the 2000 testing data, meaning while I tested from the 2000, it answered 93% correct. So isn't the chances if I use it for future 93% it will do good? That's the point. So is it the test data the basis of Vipred? Yes, of course. If you give it the X test value, it will perform Y test. That's it. If prediction is not accurate, do we not give it more data to train? Yes, if that's exactly the point. If the testing is not good, we try to feed more data or we change the algorithm. You got it? If the answer that you want is not arriving well, then you either change the algorithm or add more data. Are we clear now? This graph is clear to everybody. Have any confusions? You please let me know now. Is it clear? Okay, now listen to me carefully. This is my data.head. How we arrived at ypred. Yeah, I'll show you how ypred is calculated. I will show you how ypred is actually calculated. I'll show you how ypred is calculated. Is that cool? In the practical part so that your knowledge will be clear. Is this my data that I want to run machine learning on? Okay. I want to take a variable called x equals to data of which variable do I want my x to be in? I want the head size to be my x variable. Agree, disagree? I have already taught you this. I want my x to be the head. I want my y variable to be what? Or let me take it one point at a time. Values, okay? dot values. If I run this and if I print x, have I taken x separately? All the values 4512, 3738, 3261, whatever all the values of x is now separate. Now it is in the format of an array, a single array. It is become an array. Agree? Okay. What do I do next? I take another variable called y. Okay. I take another variable called y. Which portion of the y do I need to pass? Do I need to pass data of something called as, what do I specifically pass inside the y? I pass brain weights. I copy this and I paste it here. Dot values. So what kind of answer did I get? I got all the values of y as an array. Agree or disagree? So have I separated the x and the y now? Have I separated all the values of x and y now? I did. Now, to implement linear regression, I need to import some libraries. These libraries are already given to us from sklearn dot linear model. Using sklearn.linear model API, I'm importing something called linear regression. Did I import linear regression also? This function will help me run linear regression. I don't care how it is written. I just need to call it. Agree, disagree? Yes or no? From sklearn.model selection, import train test split. Have I done this? From sklearn.model selection, I'm importing something called train test split. From sklearn.metrics, import mean square error. Okay. Import mean squared error. And I'm also going to import R square error, right? R2 score. So tell me, what did I do? Did I import the libraries? I'm not even using them. I have just called them. I have just called them. I am making them sit on the chair. I have not asked them to do anything. Agree, disagree? So far, I have only called them. I have not done anything with them. Okay. Because I have taken the x value separately and I have taken the y value separately, the x value currently is in what dimension? Is it in one-dimensional data or two-dimensional data? One. That for sklearn, your data should be what dimensional data? Two. So can I say x equals to x dot reshape? Inside the reshape, if I pass this comma this, and if I print x again, did it become 2D? If I print x dot ndim, the answer is 2. The number of dimensions have become 2. From one dimension, I converted that into 2 dimension. Remember, you don't need to do this with y, only x, because x is the data that is being crunched by the model. Y is only for comparison. Only x needs to go through this process. Are we clear? Yes or no? Until here, is everybody clear? Oh, you don't know how reshape works? Okay. Have you ever done something called reshaping in NumPy? Have you ever performed something called reshape in NumPy? Okay. Okay. Sure. Sure. Okay. Okay. Listen. Array is equal to, listen to me. Listen to me carefully. Array is equal to np.array and pass any number inside it. 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever it is. 1, 2, 3, 4, 5, 6. There is a name of a method called array.reshape. So if you change that like okay. Did you understand this is how you declare an array in NumPy? This is how a NumPy is declared. Array is equal to np.array 1, 2, 3, 4, 5. This is an array. Okay. What is the dimension of the array? Is it a 1D array or a 2D array? Is it a 1D array or a 2D array? Okay. The shape of the array is 1D. Agree? If I want to reshape this, reshape bit array is equal to reshape RESHAPED underscore array is equal to r reshape. Whatever you want to reshape it on, if I pass like this 2, 3, and if I just print reshaped array, okay, and run this, did I just convert my original array into a different array format? Did I do this? Did I just reshape the array into a different format? Okay, let me show you one more example. Array.reshape of If you add the number -1, 2, what happened in the original shape of the array to this? What does -1 do? What does -1 do? Let me explain that clearly for you. What is the concept of -1? Why do you use -1? No, no. Listen, in NumPy, if you are not sure about the shape of the array, meaning if you don't know whether the conversion of the shape will happen properly, meaning you don't know if the conversion of the columns or the rows will happen properly. So first of all, when you say 2 is what? 2 is the row order. Agree? 2 is the row order and 3 is the column order. Is this clear to everybody? 2 is the row order, 3 is the column order. If you're not sure about the row order or the column order, you don't know. You just want to make sure that the row should be 3. Because tell me one thing, depending on 1, 2, 3, 4, 5, 6, if I take one more number called 7, can this happen? Will the answer pop up 7? No. But because you don't know how many numbers exist, even number or odd number, I don't know. But if I do it like this, what happened? Array.reshape cannot reshape array of size 7 into shape 2 because you have given the column order 2. Yes or no? Agree? If I cross and put -1 and -1 here, it will still not be able to do. But what if I do 7, 8, right? And if I come over and do it like this, okay, let's change this to maybe 3. Right? Give me 1 second. 1, 2, and 3. What happened here? -1, 3 cannot reshape an array in the size of 8. 8 values, can it have some number of row which we don't know, but 3 columns? If I change this to maybe 2, 1, 2, 3, 4, 1, 2, 3, 4. But automatically, did I tell it how many rows it wants or how many rows it should have? But did it do it automatically? At the same time, did it convert the dimension from 1D to 2D? Just like that, how many number of data point does X have? Do we always know? Will we always know the size of the X? No, because we don't know. And also we want no errors and we want to convert it in 2D, always put -1, 1. So have I put only one column and one row, which automatically it gives, but in 2D format. So this is reshaping the whole array. So what did we do now, right now? Did we reshape the array? What if we have more than one feature? So do we have to make all the feature into 2 dimension? Always. Does not matter you have 100, 200, 300, 800 features. It will always be 2D. It should be nested array. It will be nested array. Does not matter. It has to be 2D. Otherwise, sklearn does not consume this. Are we clear until here? Are we clear until here? Now that we have reshaped the array, if I take it like this, x underscore train, comma, x underscore test, comma, y underscore train, comma, y underscore test. Call this method called train test split. And inside this, pass the value of x and y. Okay, so the values of x and y, you can pass inside it directly. At the same time, I can say test size is equal to 0.20. What happened here is, did I import a method, a function called train test split here using the library called sklearn.model_selection? Am I using the library's method called train test split? I am. I have just called that particular function here called train test split, and I'm passing the original value called x and y. And I'm taking the 100% of the data, but for testing, how many percentage will I use? 20%. If I make this 0.30, how much percent will this be? So training will be how much percent? Training will be how much percent? 70%. Testing will be 30%. Tell me, how much will be the training percent now? Did you get it? What happened? It automatically, this function called train test split automatically calculated the value of x train, x test, y train, y test in the data and gave the test data set to be 25%. Are we clear? I'm going to keep it only 20% and split the data. Also split the data. So did we get the value of X train, X test, Y train, and Y test? Just what I taught you a while ago. Run this code. Your answer is done. That's it. That's all you had to do. The concept I had to take was so long, but it happened in one single line. Done. Now you want to implement logistic regression. Okay, some random and nums. Okay. Return nums. Okay. Okay. Some random of 1,2, 1 minute रुक जा हाँ just give me 1 second 2, 3, 4, 5, 6. Okay. Or I can do this. Okay, I can do this. Some random function of a comma b. Okay. Return a plus b and return a minus b, return a into b and return a divided by b. Okay. मैंने एक फंक्शन लिखा है. I wrote a function called some random function. ठीक है? In front of you. If I call this function called some random function, and if I pass in the number 4, 5, is it giving me 4 different answers? Can I say that addition is this, subtraction is this, addition is this, subtraction is this, multiplication is this, and division is this is equal to some random functions, and I will pass the value of 4, 5. If I write the addition, 4 plus 5 is how much? 9. Subtraction kitna hua? -1. Multiplication 20 and division in Python. Yeah, good. No, you got what I'm trying to say. And write functions that can return 4, 5, 6, whatever values. This function called train test split is returning X train value separately, X test value separately, Y separately, Y test. So when I wrote all the variables, each variable got its own answer. So did we take the X train value, X test value, and all of that stuff? Okay. So I'm going to take linear regression is equal to linear regression. Did you all implement something called classes and functions in Python? I am using something called object, a variable LR is equal to linear regression, and I'm calling a class called linear regression. I will use, or I will tell the Python program that, hey, I'm using a variable called LR. It is nothing but my model. Your model, your machine learning model is called what? What is the name of the model? LR. But what have I called the variable name? What have I called the variable name? LR. So I will tell the model that take the model, dot fit it. What do you mean by dot fit? Run the model. But will it run now? No. Because did I pass the train data? No. Did I pass the Y train data? No. Now it will run. Now I have passed the data, it will run. Do you see this blue color box in front of you? This blue color thing? This shows that the model has run. Your model has run, and the name of the model is called what? What is the name of the model? LR. You can give it whatever you want. I have named it as LR, and your model has run. Are we clear? Your linear regression has run. Now, I want to know how my model performed on the testing data. So I will take another variable called ypred equals to, don't you want to make prediction on the test data to compare? What is the name of your model? LR dot predict. LR dot predict. This dot predict comes from sklearn only. You don't have to program it. It comes predict. So will I give it all the values of Y test? Because all the Y test value will tell me what is the Y predicted value. No, you can't do that. Because Y test is for comparison. You need to give it the value of X test for it to give you the value of Y test, which is Y pred value. So I need to, rather than X, test value, I need to give it the value of X test. Now I have all the values of Y predicted, calculated for me. See, the values of Y predicted values that the model has calculated for the test data is now created. So basically, I have created one more column called ypred in front of you. It's right there. Agree, disagree? Now I want to know whether my model did a good job or a bad job. So can I say R2, R square is equal to R2 score, R2 score of what do you pass inside it to compare whether your model did good or not? Won't you pass Y-pred and Y-test because you want to compare them together? Y-test and Y-pred will be passed to see how good they are, how close they are to each other. Yes. So tell me, in the R2 square, will I say Y underscore test comma Y underscore pred and we will get some answer R2 is equal to 0.71? Is the model closer to 1 or farther away from 1? Closer. So did our model do a good job in prediction? Is our model doing a good job in prediction? 100% it is doing a good job. I will show you how it is doing a good job. Plot dot plot. Inside this, I will pass X test comma Y test value. Just the X test value and the Y test value, comma, you can take whatever color you want. So let me take color is equal to black. Okay, BLACK. And the label that you can give this is the actual data. Okay, the actual data point. Plot dot plot, because you want to also print your X test value with the Y pred value. I'll tell you why. Okay, I'll tell you why. X test value with your Y pred value. What will this give me? X test comma Y test will tell me the actual data point. X test with Y pred will tell me the predicted data point. So I will say color is equal to, I don't know, you can take red, black, whatever you want. I have taken red. Label is equal to predicted value, right? Predicted value. I have taken two different plots and I'm going to run this. Okay. I'm also going to give you, give me 1 second. Did I make a, tell me before plotting, what should you make sure for? Your X test and Y test value are scatter plot, not an actual plot value, correct? Yeah, this makes sense because this is the data point that I wanted to plot. This data point, the black color line that you see, the black color dots that you see, that is your what data point? So if I plot dot legend, okay, plot dot legend legend. Okay, if I do this, what are the black dots? Oh, you can also do grid. You can also do grid. Plot dot grid. And inside this, pass the parameter bool called true. Yeah, plot dot grid. Let me make the alpha as 0.3. Yeah. The black points are the actual data point and the red line is the predicted line. Yes or no? Do you see that the fit is good? Are we able to see that the fit is good? Please listen to me carefully. Listen to me carefully. The machine learning model has learned from so many different data sets that if your head size is 3,777 centimeter cube, how much is the weight of the brain? 1,282 grams, meaning 1.2 grams, 1.2 kg. Agree, disagree? Yes or no? Sir, I want to give my number. I want to give my number. I want to give weird number. I want to know if my machine learning model is able to predict my number or not. If you want to do that, use only one function, lr.predict. Now, you know that machine learning model like sklearn can only take a two-dimensional data. So give me a number like this, like if the head size is 4,177 centimeter cube, the answer is 1590. Give me a number like that. I will make the prediction in front of you. 6,000. 6, 1, 2, 3. What answer did I get? If your head size is 6,000 centimeter cube, what will be the weight of the brain? According to the linear regression model, it will be 1,883 grams. If you want me to give 4123, what answer did it give? If your weight is 1,406, it is 4,123, it's 1,004. We did take that. Did we not take all the values of X test here and we calculated Y pred? This is how we took, right? Did we not take all the X test value and created Y pred value and then compared Y test with X test? Now you got the concept. We took the values from the model itself and we tested how good it performed from the original data. And that's why the answer of R square came up to be 0.71. Can we try 377? Oh yeah, 100%. See, 3777. What is the answer? 1282, correct? 1282 is the answer. See, look at this. 1318. Is it closer to 1282? You got what I'm trying to say? For the answer 37777, see, look at this answer. 3982. What is the answer? 1375. Okay. 1375 is the answer. 1375 is the answer. The prediction is 1370. You understood what happened? The R square that I made you do was from scratch. The R square that I did teach you was from scratch. Will you be implementing things from scratch in life? No. You will be using the function that is being called here. Can you see I have called a function called R square? You don't need mean square error now. R square. Do you see I have used this R square? That's it. That's all you need to implement. This is the machine learning code to predict whether somebody's weight will be given or not. How many lines of code minimum did we use here? Not even 10, 15, maybe 12. This is the power of Python. This is the power of abstraction. You don't need to worry about anything. Everything else is taken care by itself, and you're able to use the library and build your machine learning model. Some of you were asking me question, but sir, how will we predict? How will we predict? Did you see? Call the model and call the method called dot predict, and you will be able to get the answer. Are we clear? Did we get the concept? Is it clear until here, everybody? How did we learn the machine learning code and how did it implement and how did we write it? Okay, okay, good, good, good. My question to you is very simple. If we take one value from X train and it should predict exact Y train because we feed the value. What I taught you doing the concept of machine learning using actual prediction code was from scratch for your idea. But this is how you actually implement. Can you explain about LR.predict? Okay. Y is equal to mx plus c is the equation of the line. Agree? Some value of m must be calculated like 0.8. Some value of c must be calculated for 9. So won't the LR.predict do nothing but the actual value of y will be 0.9, 0.8 into what is the size of the head did we take? 3982. So it will take 3982 plus some value of C, 9 will be taken. That's why the answer came up to be 1370. Did you understand? LR.predict is doing nothing complicated. What it is doing, it has created some equation called y is equal to mx plus c. It knows the value of m, it knows the value of c. The minute you take 3982, it is able to calculate the answer 1370. This is what this function is doing. This is what that prediction is doing. Same code can be used for Swiggy. This code is reusable wherever you want to use it. Is it also fitting best possible line? Yes, Ravish. The model fits the line to the best of its abilities and then it gives the answer. Are we clear? It will automatically do all of that for you. Linear regression code runs that and gives you the most optimal answer. Don't you see the line passing through exactly in the middle, meaning the most optimal way fits? It's not even off by certain points. So it does. Because you had question in reshape, my dear, if you want to convert a data or any dimensional data into two-dimensional data, one-dimensional data into two-dimensional data, dot reshape. When you want to reshape your answers into something, you have to first pass the row and then you have to pass the column. Are you clear? The two will represent that create an array of size 2 and the answer 3. May you share the data set? Answer the row value and the column value and it will reshape the answer. The concept of -1 is you don't care about how many rows it will form, but you for sure want only 2 columns. And I want NumPy to take care of how many ever rows it will give me, you give me. But I want only 2 columns. If that happens and you don't care about how many rows will form, just put -1 there. Can you guys do some research and on the same data set print the value for adjusted R square? The answer will be same, by the way, because one feature, one target. But still, will you give it a shot? Will you guys give some try? Okay, let me tell you something. Do you think 2 hours of machine learning with me is more than enough for you to learn machine learning? I don't think so. This is possible forever. Don't you think you want to do your own research sometimes? Maybe validate whatever I teach. Hey, is Rudra teaching correctly or not? I want to check. He taught me linear regression. Let me learn linear regression from somewhere else also. Oh, no, no, no. Rudra is correct. Should you not do this? Should you not validate? You should not have faith in me. Make sense? You should always get it validated. So don't you think whatever code I taught you, you will implement it on your own? Also print extra value like R square, adjusted R square, and see if you're getting the answer. Do your research. If you guys are incapable, I'm not going to say incapable, but if you have a problem, let me know. Can we look into examples where multiple features are invoked? Sure, Reena, if you want to do that, I can also do this. Since it's almost 9, I will take care of that example also. But it's not going to be very challenging, Reena. You will understand once. I mean, not multiple, like I can take hundreds of columns. It's not going to be a very complicated thing. Why don't you give it a shot, Reena? And let me know if you face any trouble. If you want to implement machine learning algorithms, right? I have a folder created for guys like you. If you go to my GitHub page, right, you will find a repository called ML codes, right? In this ML codes, you will, under the ML folder, you will find something called linear regression. See here, how do I teach you? Yeah. Can you see multivariate linear regression? Can you see? I'll show you the example. See, do you have area of the house, bedroom of the house, age of the house, and price of the house? Is it multivariate, meaning multiple features? If you go to my code, look at what I did. Listen to me. Just have a look at this data. Is this the bedroom? Yeah. Do we have this equation? Listen to me carefully. Do I load the data? df is equal to df.read CSV? Yes or no? df.read CSV. I'm going to zoom it. Yes. Okay. Do I have something called linear regression is equal to regression.fit? Can you see? Regression model dot fit, but I am dropping price as the part, meaning I am taking area, bedroom, and age in my regression model, but my y variable will be what? What will be my y variable? My target y. That's it. You just have to do regression is equal to linear model. X will be equal to area, bedroom, and age, and price will be separate. Now, what did I do? I run the coefficient. See, I'm doing regression dot predict. If my house is 3,000 square feet, what is the next thing? 3 bedrooms and 40 is my age. What will be the price? 49 lakh, sorry, 4,98,408 rupees or dollars. Did you get the idea? See, I'm able to predict also now. Did you get what I'm trying to say? Here, what I did is I have just dropped y variable because I don't need y variable. In X, I have taken both area, bedroom, and age. Doesn't need to be in caps. It just, you can do it in small also. Can I confirm my understanding? There are R2 here, test train, and they indicate the line is best fit or not. But none of them tell us that we have selected all the right features or not. No, that isn't feature selection, Kishle Sinha. That's different. That is using chi-square and different techniques to validate that. That is not taught by R square. R square tells you how good the fit is. But data can have null values as we are working on data before data cleaning. Will the ML give issues? Yes. If your data has null values, your answers will be wrong. Fortunately, whatever data I'm teaching you today with has been cleaned with any null and none values. So you don't have to worry about it having null or non issues, right? So you see, gender has no null value, age has no null value, head has no null value, and brain weight has no null value. So basically, if you run this method called data.isNA.isNull anything.sum, it tells you the null values. It has 0 because I cleaned it before for you. Because I'm thinking first you guys should learn how an algorithm works. Then slowly we'll go to EDA, make the data, clean the data, fix the data, mend it, and then we will do implementation of that. Everything happens step, step, step.
Just a quick info, guys. Intellipaat offers a data science course which will help you master Python, SQL, machine learning, AI, and Power BI. Get a data science certification from IIT Empower, an innovation hub of IIT Madras. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given in the description and take the first step towards the career growth with the data science course.
Now we've covered one type of algorithm in machine learning, that is linear regression. But there exist other algorithms like logistic regression, support vector machines, that is SVM, and decision trees, which are also known as classification algorithms. Here's a quick introduction to these topics.
In our last video, we covered the linear regression algorithm where the goal was to predict the continuous values by drawing a straight prediction line. But what if we need to predict categorical values instead of numbers? That's where logistic regression steps in. At first step, the name might trick you into thinking it's related to linear regression. But in reality, logistic regression is totally different. It's designed to classify things into distinct groups. If you have understood linear regression, this concept is going to be a no-brainer for you. Let's try to understand it with a simple intuitive example. Imagine you're working for a bank and you need to build a system that predicts whether a customer will default on a loan or not. The data you have includes the income of a customer, his age, and loan default status. Here, the loan default column is what we are trying to predict, which contains values like yes or no, which means our target variable is categorical, not continuous like before. So if we draw a straight line, we'll get a terrible classifier. But what if we draw a shape like this? This S shape seems to do really well, right? This is what is called as the sigmoid curve. And this is the equation that helps us achieve it. Right now, it looks bizarre, but don't worry. Just understand that this predictor classifies things in binary class, either 0 or 1. And in this particular example, if the data points lies above 0.5, we classify it as yes. And if it's less than 0.5, we classify it as no.
Now the next fundamental algorithm that you will learn in your machine learning journey is SVM. It might seem tricky at first, but by the end of this tutorial, you will see how simple and effective it really is. To make things easy, let's start with an example. Let's say there's a basketball coach handling a bunch of players and he wants to categorize these players as tall or short based on their height. Here's the data he collected. Now your goal is to help this coach draw a line or a boundary that best separates the tall players from the short players. This is exactly where the SVM algorithm comes in the picture. It finds the best possible boundary, also called a hyperplane, that separates different categories in your data. So we know that SVM finds the optimal boundary for categorizing data, but how does it exactly do so? It works by maximizing the gap between the two categories. Think of it like placing a fence between two groups so that the fence is as far as possible from both sides. Mathematically, the boundary is chosen in such a way that the margin, that is the distance between the closest points of each group, and the boundary is maximized. The points closest to the boundary are called the support vectors. These are the most important data points that define the boundary. But what if the data is not perfectly separable? That is, real-world data is often messy and we can't draw a straight line to separate the groups. In such cases, SVM uses something known as a kernel trick to transform the data into a higher dimension where it becomes separable. This allows SVM to handle even complex data sets. It might sound like an advanced concept, but in reality, it's just about drawing the best possible boundary between different groups in your data. So far, we've explored linear regression, logistic regression, and SVM. Now let's dive into another powerful algorithm, decision trees. So let's break it down with a simple example. Let's say there's a restaurant owner and he wants to predict whether a customer will order dessert or not. He has collected some data based on the past orders. Now your goal is to build a model that can predict whether a new customer will order dessert based on their age and whether they ordered a main course. Now your first instinct would be to use logistic regression because it's used for classification problems like predicting yes or no. But here's why it's not the best fit for this case. Logistic regression works well when the data is perfectly separable.
That is, logistic regression relies on a linear decision boundary in feature space. But in our case, the data is not perfectly separable. Look at customer B and D. They both ordered a main course, but one had dessert and the other did not. This suggests that the decision might depend on a more complex interaction between age and the ordering behavior, something that logistic regression is likely to struggle with. A decision tree, on the other hand, works by splitting the data into smaller and smaller groups based on certain conditions, just like how we make decisions in real life. For example, let's say we first check whether the customer ordered a main course. If yes, then we check their age. If the age is below 30, they are more likely to order dessert. If the age is above 30, they are less likely to order dessert. This forms a tree-like structure where each decision leads to a new branch, eventually leading to a prediction. But how does a decision tree decide where to split? The algorithm tries to find the best question at each step to separate the data into the most pure groups possible. It uses a mathematical concept called information gain or Gini impurity to determine the best splits. The idea is simple. The cleaner the split, meaning all items in a group belong to the same category, the better the decision. But real world data is often messy and complex, and sometimes a decision tree can become too complicated by making too many splits. This is called overfitting, meaning the tree learns the training data too well but struggles with new data. To avoid this, we prune or cut down unnecessary branches, keeping the tree simple and effective. I hope this explanation made things clear. Since these topics are also important parts of machine learning, we've covered all of them in separate detailed videos. You can find the links to those in the description below as well as in the eye icon on the top right corner of your screen. Alright, now let's dive into naive Bayes and clustering algorithms and see how it helps us group and understand data in a whole new way.
We had a training data, right? And in the training data, we have a special type of situation here, which is we have a column, which is message or email, and another column, which is spam or not. This is our output column. This is also categorical. And the message email column, which is there, which is our input column, that was in not just category, but it is in complete text. It's a statement kind of data, right? Now that statement can have any number of words. It can have just 10 words, or it can have 50 words, 100 words. So every message or email can be of different length, and we have a very unique type of situation here. So for that, we said that if we provide this data to naive Bayes classifier in machine learning, then the naive Bayes classifier will have the responsibility of learning which words have more chances of being in spam message and which words have more chances of being in non-spam message. So when you provide this data set to naive Bayes classifier, then it will make a trained model which will be ready for classification. And once it is making your trained model, which is ready for spam classification, then it will take the future message and classify them as spam or non-spam on the basis of pattern it has learned from the training data, right? Then we talked about few steps here that if I have to encode a statement kind of data, then we have to do something like this. We have to take a statement, tokenize it, means we have to create a list of words given this statement, and that we have to do for every statement, every message, every email. We have to do this thing for every one of those one by one individually. So we take an email, we take a message, and then we first tokenize that, convert that into a list of words. That is what we do. Then we remove the stop words from that to reduce the number of words that we have to process later. So we keep only the important words of every message, right? And then we do the vectorization. Vectorization was whatever words you are left with, pick all the unique words and put all the unique words as a column name, and then represent zeros and one for whatever message is there in your data set. So vectorization was that process where we converted our text into numbers, right? Then when we were talking about the working of naive Bayes classifier, then we saw that it works on the basis of a Bayes theorem. Bayes theorem is a proven fact kind of thing in statistics, which is very much used by the statistician for their day-to-day work. But this Bayes theorem is this formula basically. And using this formula, we try to do classification of the email, which is spam or not spam, on the basis of the Bayes theorem. So Base because it uses Bayes theorem, classifier because this model will do classification, and naive because I've explained one reason for which I'll show you again. So this is the formula. And in that formula, it is probability of a class given a message. So we have to find out what is the probability that a message is a spam or not spam. So we have to find out the probability that given this X, which is nothing but our message, list of words in that message, given these words, we have to find out whether that message is a spam or not. So the probability of what is higher for that particular message. So what we try to do, we try to see every word one by one in that message. And we try to find out every word has how much possibility of being in the spam versus non-spam, right? So this probability we have, we would get from the training process. When the training will be done, then the algorithm will try to understand basically that in the training data set, how many times the word we was in spam messages, how many times the word can was in the spam messages. So training process in the naive Bayes classifier is learning these probabilities from the training data set. And once you know all of these probabilities, then we can utilize that for final prediction process, right? So let's say that we have to find out probability of a spam message given these words. So we were finding out all of these things into probability of spam divided by all these words. So when we have multiplied everything and divided with that, then we saw that we got this type of probability, right? This kind of probability. But this probability is not actual probability, right? Then because of that, we found out that we have to find out the probability of non-spam given this message. Because this is not the actual probability I was looking for. It is, you can say, a scaled down version of probability, right? It is not the actual one. So it should have given me probability, but because of some reason, we are not getting the actual probability. It is giving me another form, a scaled down version of probability, right? So I was expecting a value like 0.3, 0.45, 0.87, something like that. If it would have been that number directly between 0 to 1, then I would have treated that as probability. But it is very small number, which is not representing probability in this case, right? So that is why we have to also find out the probability that given this words, it is a non-spam. We have to also find that, right? And the same thing, probability of can given non-spam into probability of we given non-spam, probability of have given non-spam. We found all these things multiplied by probability of non-spam divided by probability of each word separately. Then as we did all of these process, so suppose we found that we have a probability of spam given this message, this much, and probability of non-spam given this message, this much. So why these were not actual probabilities? Because you can see, if these numbers were actual probabilities, then if this number was this, then this number would have been 0.99999, right? Something like that. But this is not 0.99 because the probability of these two has to be 1. When you add both the probabilities, it has to be 1. That is how the concept of probability works. So given that message, either it will be spam or not spam. So when you talk about these two cases that can happen, so you will have such a probability number, which when you add them should give you total 1. That's the feature of the probability, correct? So since these numbers are not actual probability, what we do to get the actual probability from these numbers, what we do is we take the first number, divide by both, right? Then we take the second number, divide by first plus second. And then we got a number like 0.18, 0.82. So we have 0.8 means 18% possibility that this message is a spam given those words, and 82% possibility that it is a non-spam given those words, right? So the message was, can we have a quick meeting 5 p.m.? So it is like obviously a non-spam message. So it has 82% probability of being non-spam like that. And these all numbers which I'm showing you, those are like example, assumed numbers. These are not actual numbers. But it will work like that. It will have a numbers like this. The numbers will change, but these are assumed values for you to understand this thing. Right. So once you have found this thing, that is your answer. Your final answer will be, given this message, its predicted output is what? Non-spam. That is what we have to do in machine learning. Given an input, we have to predict its output. Correct. And why these probabilities were not actual probabilities? Because when you multiply 5 into 5, then you get 25, a bigger number. But when you take like 0.5 into 0.28 into 0.0095095, if you multiply lot of numbers which are less than 1, then that multiplication will give you a very small number, right? And that is how the multiplication works. If you take the number which are greater than 1, and if you keep multiplying that, it will exponentially increase. Correct. Any number which is greater than 1, and if you keep multiplying a lot of them, it will exponentially increase and it will become a very big number after some multiplication. Same way, if you take any number or multiple numbers which are less than 1, and if you keep multiplying them, then it will exponentially become a very small number. And because of these multiplications of very small number, the value which we were getting was not an actual probability. It was a scaled down version of that probability. From that, we have to get the actual probability, and then that was our final answer. Now, what is naive in naive Bayes? Or the question is, what is naive about naive Bayes? Why it is called naive? The reason for that was, in the case of naive Bayes, we are using every word, and we were using every word to find some sort of probability. What is the probability that this word exists in non-spam? What is the probability that this word exists in non-spam? What is the probability that this word exists in non-spam? Since we are treating each word separately, thinking that they are not at all related to each other, and they will not be related to each other in any case, that gives us wrong answer, right? So here, in many of the situations, when we take multiple words together, and using multiple words together, if we try to find out probability of something, then that makes more sense. That gives us the correct idea about whether it is spam, not spam, whatever. So all the time, single words will not give you the correct answer, whether it is a spam, not spam, or whether it is a positive review, negative review, that kind of thing, right? So sometimes we have to use multiple words together, and whatever probabilities I was calculating, we should sometime take multiple words together, which we were not taking. So this assumption that all the words are independent of each other in any message, that assumption in naive Bayes makes it naive, right? This is not a clever thing to do. This assumption which it is making, it's not a clever assumption which it was making. And because of that, it is known as naive, which is known as the k-means clustering, okay? And in the k-means clustering, what kind of task we do and what is that, we will be talking about that in very much detail. So it's a very interesting topic, and it's a little different from what we have been doing till now. It's a special case, or it's a different kind of learning algorithm. Now we are going to start. So for now, let's have an idea about unsupervised also, so that you can understand this scenario too, that what kind of problems do we face in unsupervised learning. We know very well now that what kind of situations we face in supervised. So once we know that what kind of situation we faced in unsupervised, then we will have much more clarity about the problems we can solve in the field of machine learning. In supervised, there are a lot of algorithms. There is no limit, like 40 plus, you can say, algorithms are there. Small modified version of multiple existing algorithms, lot of are there. But as a fresher, you don't need to know like 40 plus. Initial 7-8 algorithms are there, which you need to know. I'll mention their names and that's all as a fresher. Because all the algorithms are not used in every industry. There are specific type of algorithms which are used in specific industry a lot. Correct. Now, like us, basic idea is that logistic regression and linear regression, you will see being used in finance industry a lot. Logistic and linear, right? Because whenever financial kind of data is given to us, then we want to work on that in such a way that model is trained faster, and whatever model is created, that should be able to do the prediction faster. Okay, that model should be able to catch if any fraud is happening on a real-time basis. It should be able to catch it quickly. It should not be like a very heavy model that takes too much time, and in the meanwhile, the transaction has happened, the fraud transaction has happened. Right. And in the financial industry, the data is also huge. So we want a simple algorithm which can do the training fast, but it should be good enough that it learns the pattern also well enough from that huge financial data set. Then when you talk about other type of industries, let's say where you deal with a little larger data set on a regular basis. So in those cases, you will see that one, the data is large. Second, their main motive is to get, you can say, a high accuracy score, right? They are okay if the model is taking more time for prediction, but they want that the accuracy should be very high. Correct. Like there are many companies who work on insurance approvals, right? Insurance approvals. So let's say I have a car and I have taken insurance of somewhere and I met with an accident. So that company has to see the images of the car which has been through the accident, and it has to identify whether it was the mistake of the driver or it was actual accident, which was not the mistake of the driver. And on the basis of that, insurance has to be provided. So here we are not in very hurry to get the predicted output of something, that was this a genuine car accident or the mistake of the driver kind of thing. We are not in a hurry. We have time. So our model can take time, no problem with that. It can study the images properly. It can take time, but we want a very high accuracy because we have to process the insurance for different customers. So in those cases, when we care about more accuracy, then we have random forest, XGBoost. These are the two algorithms which will be very popular in that case. They will take more time because they are very complicated and they use hundreds of trees in the background to make a model. So they will take time, but their accuracy will be also higher. So it depends upon the industry, which kind of algorithm they are using on a regular basis. So you don't need to know all of them. There are many in supervised. You just need to know 7, 8, which are the most fundamental ones. And after that, if you know those, then learning any other version of those supervised learning algorithms will be very easy for you. We are going to talk about unsupervised learning and how unsupervised learning is different from the supervised learning. In the case of machine learning, we have different types of learnings. Okay, and why we have different types of learning? Two reasons: because our data is very different in many cases, and the output we are expecting is very different in many cases. So if I show you, see, so the three most popular type of learnings are supervised learning, unsupervised learning, and reinforcement learning. Reinforcement learning is a very advanced technique. And on the basis of this reinforcement learning itself, you must have heard about DeepSeek, which is the new AI tool which has been launched, and it created like a storm in the market on the day it was launched. So DeepSeek was totally trained on the concept of reinforcement learning, and this AI tool has been created, right? So this concept is a very complicated, and you will be working on that after 4 or 5 years of experience in the field of data science, at least after 4 or 5 years of experience, and not as a fresher. The DeepSeek and other AI tools also which are created, they use reinforcement learning very frequently for their training, right? So what happens in reinforcement learning? In the start, you will teach a AI something, right? In the start, AI is like, you can say, a child, correct? AI is like a child who has a very high capability of learning anything. But at the start, it does not know how it should learn, in what way or what roadmap it should follow to learn something. So in the start, what we do, we train it on the basis of supervised. We teach it that what kind of thing it should do, what it should learn. And after it has got some idea what it should do, then reinforcement learning um, gives it a capability of learning from rewards and feedback. If it does something right, it will do something, and if it does something right, we will give it reward in the form of code, and if it does something wrong, we will give it uh, you can say a penalty. So on the basis of rewards and penalty, it will learn itself after a certain period of time, right? So let's say if I talk about self-driving car. So in self-driving car, we teach the car manually. There will be a person sitting, and that person will be driving a car for, let's say, starting 100,000 kilometers. And on the basis of that, the car is learning how we are performing on the road, what kind of decisions we are taking. But in the real world, there are millions of situations, correct? Millions. So after a certain period of time, we say that we as humans will not be teaching it further now. It knows enough about the scenario, how it should act in the real world. It knows enough. Now we will let it do something, means let it drive itself. If it will make some mistake, we will penalize it through the code so that it knows that it has done something wrong. And if it keeps doing the right thing, we will keep rewarding it. So it will keep doing that thing more and more. So on the basis of this, we don't have to include a human in the training process. It will be kind of automated, and we just have to see whether it is doing something wrong or right, and we just let it do if it is doing something right. For now, you will be mostly focusing on these two, supervised and unsupervised. Supervised, we have seen that it is a scenario where you have input columns and output column. So most of the problem statement that you see around yourself are specially of supervised type, correct? Where we are given input and output in the training data set. On the basis of that, the algorithm is learning and it is making a model. And then that model will do that kind of prediction in the real world, correct? So after that, you have unsupervised learning, right? In unsupervised learning, how it is different from supervised learning? The difference is in the data set. In this data set, we have input only, right? There is no output column, and that type of data we used in unsupervised learning, correct? And that type of data is known as unlabeled data. So output is like labeling for something, right? Why it is labeling? Because let's say this is my first row, and these are the features of a house. Then it is mentioned 1.323 million, let's say. Now this is the label that given these features of the house, this was the price of the house. So this is considered to be the label, which we call as our output, correct? But in the case of unsupervised, we don't have any output. We just have the input here. And only using the input, we have to make such kind of model which will do something. So if output is not there, then what kind of task we will do? That is what we will be talking about. And it's very interesting. You all have been using the application of unsupervised learning or very frequently on day-to-day basis, but you did not know. Now you will know those applications here. So let's get started and let's see what kind of task we will solve in the unsupervised learning. Where is it going to be helpful if there is no output column? So for example, let's say we have data of Amazon. Amazon has their own marketplace where we go and purchase something, and it is on a global scale. Now, Amazon suppose have 100 million customers just in India. For Amazon, we have 100 million customers just in India, correct? And what kind of information Amazon has about this 100 million customer? These information like the name of the customer, address of the customer, gender of the customer, from what date they are customer on Amazon, what purchases they have made in the last 3 months, 1 month, 6 months, 1 year, and other things they know about these customers. So these are all the information which the Amazon would have about these customers. For each customer, all these information. Now, in this case, all the columns are input. We are not trying to predict anything in this case. All of these are just inputs, the features of a customer or like the details related to a customer. These all things. And right. And these are known as the input columns, which we have to use. But what kind of task we do? So let's say that we have detail about 100 million customer. We have to do what in unsupervised learning? We have to divide all the data points, or we have to divide all the customers into various groups, segments, and clusters. Correct. So either you say groups, or you say segments, or you say cluster. It means the same thing. So our main task in unsupervised learning is to take the data and divide that among multiple groups. So currently we have the entire data somewhere together. And we have to first identify that how many groups exist in our data set. So first we have to identify that. Then we have to divide our data, entire data, into that many groups. So that will be our main task or main focus in unsupervised learning. Now, when you're dividing all the customers into various groups or segments or clusters, the groups will be based upon some similarities between the customers or the data point. Here, every row is a customer detail, and you can call every customer as a data point. Correct. Because when you make a graph, if you make a dot, this dot is representing a row always. So in every row, I have a customer detail. So every dot is a customer or a data point, anything you can say. Right now, so when I divide the customers into multiple groups, in each group, you will have similar type of data point. You will not put dissimilar data points into the same group. That is not our task. So we have to put, if I'm putting, let's say 1 million customers into one group. So it means that those 1 million customers are somehow similar to each other. Either their gender is same, their age is same, their city is same, their country is same, right? So some sort of similarity must be there in the customers on the basis of which you are putting them into one group, right? So again, we have data about 100 million customers, and we have these information about every customer. So 100 million rows are there, 100 million data points are there. So first we have to divide the customers into various groups, and or you can say clusters. Clusters is the main term we will be using, which means nothing but groups. So we will divide the customers into multiple clusters or groups, and each group will have similar data points to each other, right? And there is one very important property you should know about these clusters. All the data points within one group should be very, very similar to each other. Correct. The data points which are within a group should be as similar to each other as possible. So if I have made one group and if I put some customers here into this group, so these, all the customers should be very, very similar to each other. Correct. So we'll be talking about what do I mean by similarity. But these customers should be similar to each other in some way, very, very similar. And if I have another group, and in this also some data points are there. So these data points should be very similar to each other. But if I pick one data point from this and one data point from this, then they should be as dissimilar to each other as possible. The higher the dissimilarity between them, the more stable the group we have identified. Correct. So there are two properties we have to follow. And on the basis of that, we will be able to identify correct number of groups. So if I have 100 million data points, I can make 10 groups, 100 groups, 1,000 groups, even 10,000 groups. But how much groups are enough, right? So that will be decided on the basis of these two factors. That in all the data points within a group should be as similar to each other as possible. At the same time, a data point from one group should be as dissimilar to a data point from another group as much as possible. Both of the factors have to be followed at the same time, and then only we can make more stable clusters in our data set. Correct. Now, what kind of similarity am I talking about? So Amazon can make one group where we have young customers who like to spend high, right? They spend too much on Amazon and they are young customers, like till the age of 25, let's say. Then we can have another group where we have young customers, but they spend less. They don't spend anything above 1,000 rupees. They don't like to spend much. Correct. So in this group, we can have all the customers who are young, but spend less. Then we can have another group where we can have mid-age people and they spend less. Then we can have another group where we have mid-age people who spend high. Then we can have old customers who spend less and old customers who spend high. And here I'm just considering two factors, right? That they are young and they like to spend a certain amount. Only two factors I'm just considering to make these multiple groups. If I consider third factor, four factors, fifth factor, then the quality of the groups will become better and better if I take more and more of these factors. But the factors which I take should be good. And what do I mean by that? Let me show you that with an example. They have to be dissimilar. First group and second group has to be dissimilar in some way. Some way they have to be dissimilar. So these both are young people, but these are high spenders and these are low spenders. So that makes them different, right? That is what that makes them separate. So one data point from this group and one data point from this group should be very dissimilar from each other. That is what we are trying to make sure. So let us see that what could be the factors which are better for making the clusters. Okay, let's have a look at that. So let's say another example that I have Intellipaat, and 1,000 learners come to Intellipaat for enrolling into the data science course. Now Intellipaat once receives 1,000 applications for data science course. They have to divide these 1,000 people into different batches. Right. One thing they can do is they can put all the 1,000 students in one batch. But the problem will be that it will not be manageable for Intellipaat also. It will be not manageable by the instructor also to handle 1,000 people in one batch. So whenever we have a certain amount of data, we have to see if I put everything into one group, will it be manageable? So that way, if Amazon put all the 100 million customers in one group, is it manageable by them? So they'll say, no, it is not manageable because there are too many data points and they have a lot of dissimilarity among them. So we don't know what to do with that data since they are so much dissimilar. So we have to divide the data points into multiple groups so that we can serve them better as a company. So one thing the Intellipaat did, they thought that let's divide the customers on the basis of gender. For example, let's say they said 500 learners we will put into one group or one batch, and 500 we will put into another batch, all the female learners, right? Now, is this going to make a good quality cluster for them? Is it going to be any help to that company or anywhere? Is it going to be of any help? Not at all, right? Because either you are putting them, those 1,000 people into one batch, or you are dividing them into on the basis of gender into two batches. It is not going to be helpful at all. This one factor alone does seem to be a very bad factor to divide these 1,000 data points into two groups. Correct. Let's say if I take another factor, let's say we don't use the gender, rather we use the domain of the learners. Now, if I change this factor from the gender to this domain, will that be a much better factor to divide these learners into groups? Will it be a much better factor? Of course, right? It will be a much better factor because now if 1,000 learners are divided into batches of IT, those who belong to IT domain and those who belong to non-IT domain, then in that case, Intellipaat will be able to serve the learners in a better way because they know how these learners have to be taught and how these learners have to be taught, how much technical things they know on the basis of that. So what I'm trying to show you here that there can be multiple factors on the basis of which you can make groups, but all the factors are not good enough. Like in the supervised learning, all the input columns are not equally important to predict the output. There will be some very important columns and there will be some very less important. Same way, we can have multiple factors and every factor will not be equally important for making the groups. Some will be very much important, some will be very less important. If instead of taking single factor, what if I combine two into one? Let's say I took IT, non-IT, that gave me very good cluster. But what if I take two of the factors, let's say their experience level and domain. So one group I make fresher IT, fresher non-IT, experience of IT domain, experienced learners from non-IT domain. If I have these 4 groups on the basis of these 2 factors, I can see the quality of the group increasing much just because of taking these 2 factors, which are very good factors of making the groups. And that way, you are understanding that whenever you have to do this kind of unsupervised learning task, then all the factors you don't have to take. You have to clearly understand out of given, let's say 50 input columns, 50 input factors, which of the input factors are good enough to make the groups. So out of 50 input columns, you can just use 10 of them or 12 of them, which seems to be the most important one. And you can discard totally the rest of them for making the final groups, right? And this is a ongoing experimental process. In this case, it is very difficult to identify those 10, 12 input columns, which will be very helpful for you. So this kind of task is not solved in, let's say, 2 months, 3 months, 4 months. This kind of task goes on for years. So you will be trying 10 first, then you try that for 6 months. Then you pick another 10 features, you try that for another 6 months. So after multiple trying, you will be finding out those 10, 12, or 15 features that were giving you the best result, right? When you divided the customers into that many groups, taking those factors, you were able to make very good quality groups. And what we do by making those good quality groups? What is the benefit? First, the benefit is that a company will be able to a company will be able to serve those customers better if they have made good quality clusters, right? And second, you see that if the Amazon has divided the customers into multiple groups, right? They know that one group is that kind of people who are young but less spenders, and one group is those customers who are young but high spenders. So Amazon can do a very proper targeted marketing. Any company can do a proper targeted marketing on the basis of those things that they know. Targeted marketing was what? If, let's say, Amazon has some sale going on or they have any offer going on. Now, they have to send notification about that offer or sale to some customers. Now, whenever you have your Amazon app installed, you will be getting a lot of notifications of Flipkart, Amazon, any of these applications that you have installed. Any means any startup who is selling some, let's say, beauty products or health related products. That also, if you have installed, you'll be getting notifications about the offer on your smartphone. Now, the same notification, same offer is not being sent to all the customers of that. You are being sent a very specific type of notification, which makes you spend more, right? Which makes you purchase that product, which is being sold to you, right? And this is known as a targeted marketing. So if those companies know what kind of customer you are, then they will be able to target you better. So all the people who are in this group, they are all young and high spenders. They like to spend high, they are young. So they have to be sent those kind of notifications, which will make them purchase those kind of products. So about any fashion product which is coming up, about any new smartphone which is coming up, and they are the people who like those kind of products and they're capable of spending that much. Correct. So they will be sent those notifications, which will make these people purchase that item. So targeted marketing is one of the most famous kind of application of unsupervised learning. So first, the companies will divide all the customers into group, then they will be serving them in different ways. Second, the second very famous example of this unsupervised learning is recommendation systems. Recommendation systems is a very famous thing now. It is there in the market from last 10 years, and it has improved to a very good extent as of now. The recommendation systems are what? When you go on any website and you're looking for a product, as you scroll down on the same page of that product, you'll see other items being recommended to you, which are similar to that product. So how something is being recommended to you, right? On what basis? So there are two types of recommendation systems that work in the real world market. Two types. Collaborative filtering content-based filtering. Correct. And you will be making, I think, a project of this recommendation system as you move forward. So recommendation systems are of two types, collaborative, content-based. And recommendation systems are an application of unsupervised learning only that you have been using on a day-to-day basis till now. So what is collaborative filtering? In collaborative filtering, this kind of thing happens. Let's say that this is person one, this is person two. And these both people are in the same group because these are similar type of customers. The company knows that these are both the customers in the same group. And now let's say this person one purchases a t-shirt from that company, Amazon, Flipkart, whatever, Walmart, anything. So let's say this person goes onto that platform, purchases a t-shirt. Now the company knows that this person is also very similar type of customer to this. So this person too will also be recommended this t-shirt on their homepage when they open that application. Somewhere they will be recommended this item. And why this item is being recommended to this person? In the hope that since these are similar type of customers, they might have similar type of likes somewhat or the other. And this person too will be more likely to purchase this t-shirt compared to any other t-shirt if we recommend them, or compared to any other product if we recommend them. There are low chances that this person might like them because we don't know what is the actual liking of this person. But if person one likes this t-shirt, the same t-shirt, if that is being recommended to person two, there are very high chances that this person two will purchase that. Now in this group, there will be other people also, person three, person four, person five. Lot of other customers are there, thousands, even millions of customers are there in a group. So if you are being recommended any type of product, one, it can be on the basis of your search history, what kind of thing you like. But apart from that, lot of recommendations you are seeing is on the basis of what other type of other customers purchased, which are very similar to you. Correct. That is the concept of collaborative filtering. The second one is known as content-based filtering. The content-based filtering happens very famously on Netflix, YouTube, Hotstar, right? These content-based platforms where you see this content-based filtering happens very much on those. Yeah, on Instagram, Facebook, Snapchat, obviously, in those social media platforms also. What is content-based? Content-based is nothing but, for example, if I talk about Amazon, so if person one likes this smartphone and they are looking at that, or they have added this smartphone one into their cart. Now this smartphone 2 will be also recommended to this person 1 because both the smartphones are in one group now. So in this case, the people are not in a group, but now the devices, the products are in a group. So if this person like this item, so this person might also like this item because these two items are very similar to each other. Same way, if you talk about Netflix or YouTube or Hotstar, and you have to think about the recommendation that is being done there. So if I like video 1 and I'm watching this video 1, I liked it, right? And there is another video 2. Now, you know, video 2 is either by the same creator or by the similar creators. And these two videos are very same. The audience are same, the kind of content is same, something is same, right? So if I like this video, then on the right side of that, the other videos that will be recommended to me will be similar type of videos, right? Which have some similarity. So now these videos are in a group, they are in a cluster, and this is now content-based filtering. If I'm watching something on Netflix, so on the same page, other videos are also recommended to us, right? On Netflix. So there also same thing is happening. If I'm watching a show, then other show which is very similar to that will be recommended to me. So these are some of the applications of unsupervised learning. And apart from that, there are other applications also which work on similar kind of concept. So wherever you are getting targeted marketing, targeted notifications or recommendations, anywhere where the company is putting their customers into multiple groups, there is a use of unsupervised learning. So every marketplace No matter if it is a small startup, bigger startup, if they are selling some sort of product, they will all do this kind of task, all of them, because they have to know what kind of customer they are dealing with so that they can launch product related to those type of customers. If let's say there is a new startup which is selling, let's say, whey proteins and protein bars, correct? And let's say some smoothies for your gut health kind of thing. They are selling that, right? And in those cases, they want to know what kind of customers are visiting our website a lot. What kind of people? So are those 25 to 35-year-olds more? And in 25 to 35, what kind of people? Are male customers more? Are female customers more? What kind of people are visiting our website more? On the basis of that, this company will be able to launch more products which might be liked by those kind of customers. So there are many applications of this unsupervised learning which you might have been interacting with on a daily basis, but you might not have known that these are the unsupervised learning things. So where somewhere you see the combos created by the company itself on the basis of what people are purchasing, correct? And then some places the combos are automatically also created, but I don't think that combos are like automatically created. The company sees that which kind of customer are liking that. On the basis of that, the company can make the combos itself, such as if you use Blinkit in India and uh, let's say food ordering platform. So, right. So both of them, they use this kind of information to club multiple items together. Let's say if customers are purchasing milk, bread, and butter a lot together, so they can be sold as a combo. So if any person is looking to purchase just a bread, if they see a combo, they might be more likely to purchase that entire combo, thinking that somehow I will use those other two products also, which I don't need. So these kind of combos are also created on the basis of these similar data points itself. Once you search in Flipkart, even got recommendation in Amazon as well. See, that is Milan, that's a different kind of thing. It is not related to machine learning. In Facebook, it's a social media marketing, or you can say Facebook ads thing. There's a tool in Facebook which is known as Pixel. So if you start marketing of your company, so there is a tool called as Pixel. Anyone who has to show ad on any platform, they register on this Pixel. Now, Pixel is a tool which tracks your movement on every single website. This is a tool which, without your knowledge, is tracking all your movements, whatever you do, anywhere. And on the basis of that, if you search something somewhere, that same recommendations or similar recommendations will be shown to you everywhere. This is the name of the tool, which is a Facebook's tool. And because of this tool, they earn a lot of money in revenue. If anyone who is working in marketing, who does this Facebook ads, Google ads, they will know this kind of tool. But this is a separate thing. Okay, so this was the introduction about the concept of unsupervised learning. Yes. So content-based filtering was what? In the content-based filtering, the content is in a group. Multiple videos are in a group. So if I like one video, other videos in that same group will be recommended to me. That is content-based. And collaborative is where the people or the customers are in a group. On the basis of the similarity between customers, they are in a group. And here in content-based, we have videos in a group. Right? On Netflix, YouTube, Hotstar, anywhere you see the videos are being clustered together so that if I like one video, other videos who are very similar to that, that is all recommended to me in some way or the other. Now, we will move forward and try to understand. We have seen an overview of all of these processes, how it is being done, how it is not being done. Now we will be talking about the algorithm. What kind of algorithm is being used to do all of this task? And in unsupervised learning, there are three very famous algorithms which is used most of the time. Three very famous. So let's get started about the working of. It's a very powerful algorithm which we are going to see, but it's very simple, very short, very simple, which you will be able to understand. Working of K-means clustering. Right. When you talk about the unsupervised learning approach, where we are making a model for a data set which does not have any output column. So that data we are trying to divide into groups. That is what the overall concept of unsupervised learning is. We always are trying to divide data into groups. And the groups will be on the basis of some sort of similarity. But how do we define a similarity? Correct. We'll be seeing all of that. Yes, of course. In the background, to put this kind of task into the background or on a seamless way so that customers can use that, lot of things are done. What you are studying here is just the tip of the iceberg. There are a lot of things which are very, very vast. If you get into the data science, you will see that whatever you learn in this course will be like the just a starting point, which a fresher knows. But apart from that, you have to take these projects, make them usable for a customer. So you convert this into an application form or a website form, and you have to constantly update your model, constantly update the data, constantly monitor the performance of your model. There are hundreds of things that you have to do in this field. That is why a lot of people are required to manage the entire process. But data science is one of the things which converts the effort of a data scientist into actual revenue, right? It is one of such things. If you do something very correct, if you're able to make a good model, or if you're able to make these good clusters, the impact of a data science project on the growth of a company, on the revenue of the company, is more direct, even more direct than the software development process. Correct. So because of that, this field has become so much important in the recent time. And this will become even more important as we move forward, because many companies have yet not started to use the data science actually. In India also, if you see, we can say that there may be like 10% companies who have been using data science properly, just 10%. 90% companies still have to use data science for their use case. Correct. So the expansion of the data science is going to be very exponential in the upcoming time. So you are kind of a very right time to learn all of these things and to take the full advantage of this. This is the golden period of the data science coming up. Uh, those who have joined around 2020, that kind of time, or before that, that was even better time, because the competition was not at all existent at that time. But now the competition is more, but it is not a problem because the expansion of this field is exponential. So let's see the working of k-means clustering. In unsupervised learning, there are three very famous algorithms. That's it, which you need to know, which are used most of the time. See, one is this k-means clustering. Second, we will be talking about hierarchical clustering, hierarchical. And third one is known as DB scan clustering. Three different algorithms are there: k-means, hierarchical, DB scan. These three are mainly used in 99% cases of unsupervised learning. Other algorithms, which are specifically designed by that company, might be used in different cases for a few particular cases, but these three are the famous ones which you have to use. Among these three, the most used is this k-means among these three, because the working of k-means is very easy. We understand it. We can modify that if we want, because understanding of the k-means is quite simple. Hierarchical DB scan are also very simple, but k-means is very intuitive, and it feels like we know what is happening in the background and we can explain the process. That kind of thing is there, which makes k-means very famous amongst the data scientists. But after k-means, the other one which is becoming very popular nowadays is the DB scan. Correct. So DB scan works in those kind of situation very well, where the groups are not very clearly visible to us. So if there is a confusion in how many groups exist, DB scan is a more advanced method which will be able to identify groups amongst a very complicated data. So let's get started. Now in this thing, what does K means? Okay, what does K represent? So K is the representation of how many groups that we will create in a data. So we don't know in any data how many groups are existent. We don't know by default, but there are K number of groups. That is the assumption that some number of groups exist. So we represent that with K. that there are some groups in every data set. And that is what we have to identify. Now, first, in the k-means clustering, we will have a data, right? And the data will have some n number of rows. N means it could be 10,000 rows, 5,000 rows, 20,000 rows. It can be any type of data which can have any number of rows. N rows are there and k number of columns are there, right? We can say n number of rows, m number of columns, anything you can say, just we are representing it with something. That n number of rows are there and k number of columns are there. Now this k does not represent this k. M number of columns are in any data set. So for example, it could be 10,000 rows and 50 columns. That is the data that we are working with. Now, all the columns that are given to us are all input columns. There's no output column that we have just seen. These are all input columns. So this is our data that we have to work with in unsupervised learning. Now, what is the assumption? Why are we using k-means clustering? How do we know k-means clustering will be used on this case? So assumption of ours is that there exist k clusters, right? There exist k clusters or groups in any data that we have to identify and then divide our data into those clusters. So we work with an assumption that in any data set which is given to us, there are some sort of groups. 1, 2, 3, 4, 5, more than one obviously will be there. So there exists some sort of groups, some number of groups in every data set, and that we have to identify given this. Now, if you talk about a supervised data set, so in supervised data set also there are some number of groups that exist. Like if I talk about classification and we have this data set of spam and non-spam, there are two groups that exist in that. If I talk about heart disease patient, non-heart disease patient, there are two groups. If I talk about regression data, like car prices, house prices, so there are less expensive car, more expensive car, mid-level cars, those kind of groups exist in the data. So any data that I work with, there are some sort of groups which exist. And in the case of unsupervised learning, that is what we try to do. Because in supervised, we have something else that we can focus on. We have an output that we have to predict, that kind of task we focus on. But in unsupervised, we don't have any output that we have to focus on. So what we are left with is identifying how many groups are there and then dividing our data into those many groups. So we will write it down in short words. So our task number 1 is identify the number of clusters, and then second, divide all the data into those clusters. Right, two main tasks. So identify the number of clusters, divide all the data into those clusters. Now, when we initialize the process of k-means clustering, when we start the process of k-means clustering, the k-means clustering has these two demands, or you can say better than demands, we should write requirements. Requirements to initialize the clustering process. There are two demands of the k-means clustering algorithm. The first demand is that give me the x variable. X variable is nothing but it is our data, entire data, all rows, all columns. We provide everything into this x variable. That is our entire data. Then second demand of the k-means clustering algorithm is the k value. Okay, k value is what? Number of clusters to be created. Now the first demand is okay, but second demand is weird. It's just saying that you give me the data and you also tell me how many groups I have to make in that data. This is a weird demand of the k-means clustering. And the problem is that how do I know how many groups exist in the data? How do I know? So you can say that we can plot the data and then we can identify that how many groups are visible, right? But the problem here is, I think I might have told you somewhere in linear logistics somewhere that if I have, let's say 20 columns, so then the graph will be 20 dimension. If I use 20 columns to make a graph, it will be 20 dimension, right? And because of that, we cannot plot the data. Anything above 3 dimension cannot be plotted. It is simply not possible to visualize any data which is higher than 3 dimension. Not at all. So the problem is that if I have a data set and if I cannot plot that data, how will I know how many type of groups are there? If I could see the data, then at least it was possible for me to identify the K value. But if I don't have the possibility of even seeing the data, then how do I know what is the K value or how many groups should be created in the data? And why this weird demand is there in K-means? This K-means clustering algorithm was created like 30 years ago, long ago in 1990 somewhere. And at that point of time, the data used to be so simple and basic that always we knew how many type of groups exist in the data. Like 100 rows were there, 200 rows were there, 300 rows were there. That kind of data used to be at that point of time. And on the basis of that only, the algorithms have been designed or created. So one reason for this kind of weird assumption or requirement by the algorithm is at that point of time, the data used to be simple. So people knew how many groups have to be created. So if I tell the data and the K value, then the work of K-means clustering is to make that many cluster more properly. And what do I mean by that? I'll be coming up to that. But you see, this is the weird demand of the K-means. Now, what is the solution? How do I provide the accurate K value? What can we do? So there is a technique which we will be seeing, which has been developed later. And that technique will help us to identify the K value. So before I run the main algorithm of K-means clustering, we have to do an experiment just before that to find out the most proper K value. So there is a very small, simple process, and it's very easy to understand how we can find out a very accurate K value for any given data set. But for now, let's start working and let's assume the K values as of now. How do we identify the proper K value for any given data set? Here, I'll be taking some data points. Let's say we have 3 data points here, 3 here, and let's say 4 here. So I have X variable, which is 10. 10 rows are there in the data set. And you know that for each row, there is a data point which represents that row. Correct. Whenever you visualize anything, then there is a data point which is representing a row. So for now, I'm assuming that we have just 2 input columns. One will be written here, one will be written here. Just 2 input columns are there on the basis of which we are making this graph. Because for 2 input columns, the graph will be 2 dimension. And this is how the 2 dimension look like. Now, why a point is called 2 dimension, 3 dimension? If you see, let's say we have a line here. Let's say we have just a line. So if I talk about a data set where it's a classification data set, suppose in the classification data set, we have one column which is income of a person, and second, loan approved or not. Loan should be approved or not. For that, one input column, one output column. So there is income of different customers given, and it is mentioned that for this person, loan was approved, for this no, for this yes. This kind of data set we have. And in this case, only one input column is there. One input, one output. So on the basis of the input column, we will be making the graph. So if just income is given to us, then I can represent income on one axis, just one axis. I don't need y-axis here. Just x-axis is enough. Because I can represent every income as a dot here. Right? Every income as a dot. Let's say these are all the people. And every dot is representing one income. That this is one person whose income is this much. This is one person whose income is this much. And on the basis of the output, we can color the data points that we have discussed in detail in the decision tree, I think. Right. So always in the classification, the coloring of the data points we can do on the basis of output, and the representation of data will be done on the basis of input. So one input, and you can see the graph is 1 dimension. There's only a single value which is representing a data point. Just a single value, it's income value. But if instead of income, if I take age of the person also, income also, 2 factors if I take now, So now you will see that the graph will not be one dimension. So now if I take a data, every data that I plot here will have two values. It's X value, it's Y value. So now I have taken age on this side and I have taken income on this side. That's why it is a 2-dimension. But if I talk about 3-dimension, so when will be a point 3-dimension? If I take another axis, which is Z axis, which is going in this direction. So think about it that you're standing in the corner of your room, corner. So one line is going upward in the corner of a room. You're facing the corner and there is a line going up. This is that corner you can see. Then one line is going on right side of yours, one is going on the left side of yours. So imagine that these are your 3 axes where you're standing in the corner of the room, correct, facing the corner. But this is how you can imagine that these 3 axes are there: X axis, Y axis, and Z axis. Now this point will be known as a 3-dimension point. Why? Because it has a X value, it has a Y value, and it also has a Z value. That is why, since this point is known by 3 values now, its age, income, and let's say CIBIL score. 3 input columns are representing this point. So this point is a customer, and this customer is represented by 3 of its values: their credit score, CIBIL score, or income, and the age. Correct, 3 things. And more than 3-dimension we cannot visualize. We cannot create the 4th dimension, and that is the problem that I was just referring to a minute ago, right? That is the main problem, that till 3-dimension we can represent the graph and we can represent every data point, but more than 3-dimension we cannot represent the data point. Correct. So that is what I was trying to explain a few minutes ago. It's not possible for more than 3-dimension. We can't represent. Coming back to the k-means part, we have some data points here. This, and this. Suppose this, and this, and let's say this, and this, and this. Right. So we have 10 data points. 10 rows are there, 10 data points are there, and all of these are 2-dimension data points. Correct. Now, in this case, the second thing that I have to give to the algorithm, one, I have provided the data, which is these data points. I am giving that to algorithm, k-means. But second thing is the k value. That also I have to give the algorithm. Only then the process of clustering will start. So for now, we will use the k is equal to 3 because I can clearly see 3 groups are there. I can clearly see that. For now, I will be using k is equal to 3. Now, what is the work of the k-means here? If I have given it the data and if I have given it the k value, then what is its work? What it is supposed to do? So the work of k-means clustering is to identify 3 clusters in the most correct way. Means one is this, one is this, one is this. If it does identify these 3 clusters like that, then it is good. Otherwise, it can identify one cluster like this, one like this, and one like this. Now also we have 3 clusters, but these are not correct 3 clusters. So main task of k-means clustering algorithm is to identify 3 clusters, or whatever clusters I'm telling it, in the most correct way. That is the main task of k-means cluster. Right. But in few minutes, we will also talk about how we can identify the most accurate k, that we don't have to guess a k value. And you see, first challenge was that we cannot plot the data point, and that is why we cannot tell the k value. The second challenge is also there, and that challenge is, what if you are able to plot the data point and the data points come out to be like this, right? What if your data point after plotting comes out to be like that? Here also, I won't be able to identify, right? I won't be able to identify how many groups are there. Not at all possible for us, right? So in this case, the algorithms will be able to do a better task of identifying this cluster. So we should leave this kind of task to the algorithm itself. We should not involve ourselves unnecessarily, because we know we won't be able to do a better task than them. Right. Now, on x-axis and y-axis, we have 2 input columns: income and age of the customers, like that you can say. So just 2 input, anything related to the customer I can have. Right. Now, so here, if you now see that we have 10 data points and we have given the data, we have given the k, and it will start. Now, when the k-means receive these two things, the k-means algorithm receive these two things, it now initializes, means it now starts working on this thing. And what is the step number one that it will perform in this process of identifying the clusters? Right. The step number one is it will create something called as centroid points. So in the step number one, this k-means algorithm tries to create something called as centroids. Centroids are also known as cluster means, or they are also known as cluster centers. Okay, centroids or cluster means or cluster centers, you can call it by any name that we are going to create now. But what is cluster center? See, if there are three clusters here, this is one cluster. Cluster means a group. Cluster is the technical name of a group which we will be using now. So if there are three clusters here, there must be a center point of these three groups. And why do we need to have a center point? We will talk about that also. But k-means work in this way. That first step number one is that according to the given k value, it will make that many centroid points into the graph. So it is going to make three new data points, which will be extra. These are our main data points, but it is going to create three new data points since k is equal to 3. If k was 10, then we would make 10 centroid points in the start additionally, right? So let's make the centroid points. One centroid point I will make will be of, let's say, this color. One centroid point I will make will be of, let's say, this color. And third centroid point, which I'm going to make, will be suppose of green color. We are going to make three centroid points because there are three clusters. And each one of them will be the center of one of these clusters. So pink one can be of this, the green one can be of this, and then the purple one can be of this. Three clusters, so three center points of those clusters. Now, initially, we don't know any cluster. Initially, we don't have any cluster created as of now. There are just data points, 10 data points, but there is no cluster existing as of now in the start. Because of that, they don't know where the center of the cluster is. So if the cluster itself is not formed, how do we know what is the center of the cluster? So initially, because of that reason, you can create them anywhere. So suppose I have created the pink one here, and I have created the green one somewhere here, and I have created the purple one somewhere here, right? The initial position will be randomly anywhere. Since there is no cluster at the initial point, they will be randomly scattered anywhere into the graph. All three can be here also. Initially, one can be here, one can be here, and one can be here. Anything. Their position can be anything. We don't have any control over that. So now, what we do with these points? See, these points are going to help us identify the clusters more easily. Using these three centroid points, we will be able to identify the clusters. Correct. And how we will identify that cluster? Let's see process one. Process one, very simple short. We take every data point. See, the blue points are our actual data points, and these three color points are not our data points. These are just three extra points we have created for helping us in the clustering process. So we take our data points, blue points, and one by one, we start with that. Let's say this is my first row number one. Let's say this is my row number one, my first data point, and we start from here. What we will do is we'll find out the distance of this data point with cluster mean 1, cluster mean 2, and cluster mean 3. 1, 2, and 3. These three. Right. So now we have our data points, and we have these three cluster means M1, M2, M3. I'm writing M1, M2 because this is cluster mean, right? That is why we are giving it a name M1, M2, M3. What we do now, we take our first data point and we find out the distance of the first data point with this, distance of the first data point with this, and distance of the first data point with this. And now we will see which is the minimum distance. This first data point is closest to M1 or M2 or M3. Where is it closest to? So it's clear that it is closest to the M1. Then the same process I will do for this data point also, second one. I'll again take the distance of this with this and with this, right? Then I'll take the third data point also, right? So for these three, I can clearly see that they will be closer to M1 for these three. No doubt about that. And when I come to this point, for this point also, I have to see the distance of this with this with this, and this with this. So according to that distance thing, I will clearly see that these three will be closer to M2 and these four will be closer to M3, right? According to our initial distances that we check, these 4 points, these are the 4 main points actually, right? So these 4 points are closer to M3, these 3 points are closer to M2, and these 3 points are closer to M1, according to our initial distances that we have checked. Now what we do, once we have created our initial clusters, we have created our initial 3 clusters as of now. What we are going to do now, M1, M3 randomly taken. So after we have done that, after we have identified these 3 groups, what we have to do now, we have to move this M1, M2, M3 at the center of those groups. So now the first group is these 3 points, this, and this. You take the average of these 3 values. This is one value, this is one value, this is one value. You take the average of these 3 values, wherever that average falls, it will fall in the exact center of this 3 group. At equidistance from all the 3 data points will be the center or will be the average of these 3 data points. Now what will happen? At this particular place, you will move your M1. Because M1 was what? M1 is a center point, cluster center. And initially there was no cluster, so they were randomly taken anywhere. But now we have a cluster 1. So now this M1 should be or is supposed to be in the center of your cluster 1. So it moves from here to here, and this is removed from here. Next what happens? The next cluster is like this, this, and this. And the M2, which is there, should move at the center of this. It's the mean point of these 3 data points, average point. That will fall here. So M2 is supposed to move there. And this is our cluster. And the third one, you can see that the green one will move in the exact center of these 4 points, and it will be removed from here. So after the entire updation, it will look something like this. After the entire updation, it will look something like this. After we have moved the center points, M1, M2, M3 to a new location, then we will again do the same process. Again, because the algorithm does not know that we have identified 3 proper clusters, we should stop. The algorithm does not know that because algorithm cannot see like us. So what it will do, it will try this same process again. So it will say that, now let's check the distance of this data point with the updated center points, with this pink one, with this green one, and with this purple one. Again, we will follow through the same process. But now the k-means will see that there is no change happening at all. The data points which were there are not moving at all, and they have become stable. There is no change happening. So when the k-means clustering will see that there is no change happening, it means that we have identified 3 best clusters, and because of that only, there is no change happening. And these are our 3 proper clusters with 3 centroid points. Now, what is the use of centroid points? We'll see that. But one example, we have seen that it is helping us to identify 3 clusters very easily. It's making this process very easy. So one use of them is that. Second, one more use is there, which we will see. So this was the most simplified example of the k-means clustering. Now we're going to talk about example. Okay, so just now we saw that there's a process following which we were doing this task. So here we have again some data points, right? And we'll take the example of something similar. Let's say we have 3 data points here, and we have 4 data points here, and we have 4 data points. Let's take this example now. In this case, the x is 11, right? In this case, x is 11 rows because I have taken 11 data points. And for this also, I'm giving the k is equal to 3 to the algorithm. As I provide these 2 things, then the algorithm is going to make 3 cluster points. Let's say one is pink, one is green, and one is of, let's say, this color. Yellow won't be visible. So we have taken these 3 colors, pink, green, and blue, right? Now, what we have to do with this pink, green, and blue, we will be putting that into here anywhere randomly. So one example I have taken previously where I took our initial points at some places. Now let's take the second example and suppose I put the pink point here and I put the green point somewhere here and I put this blue point here, right? 3 centroid points we have to make on the basis of the k value. So k I have taken 3 and on the basis of k is equal to 3, we have to have 3 initial centroid points. Now, since they can be randomly anywhere, they can be initialized anywhere randomly. Now, suppose what if their locations are like this, what will happen in this case? Now, what I'm going to show you will make it totally clear how this process is going to be followed through and how many repetitions we have to do. Why do we have to do multiple repetitions? You'll understand with this example. So I again start the same process of identifying all the similar closer points. So I start with this. I check its distance with this M1, this is M2, and this is M3. Let's say 3 centroid points are there, M1, M2, M3. We have to find out distance of the first data point with M1, with M2, and M3, right? We have to find out these distances. And as I take these things, I find it again, the first data point is closer to M1. Then I take the second data point, and let's say the second data point, M1, M3, M2, like that. So second data point is also closer to M1. But if I go to the third one and I check its distance with this, and with this. Now I think that this data point is more closer to M3 than M1 or M2. And same thing, if I check for this data point also, then I can see that it's more closer to M3 than M1 or M2, right? Now the scene has changed a little bit, and that makes it more interesting. So after checking all the distances, I found out that these two are closer to M1, so they're put into one group together. These are obviously closer to M2, they are put together. And now initially, because of these initial centroid points being initialized at these locations, this will be our third cluster. One this, and one this. Now, do you understand why do we need to repeat the process again? Because initially we have identified 3 clusters, but not the correct 3 clusters. So if we stop after doing one iteration, one repetition, there are very few chances that we will get actual 3 clusters. Very, very few chances of that, right? There are very high chances that 3 clusters will be created in the initial time, in the starting time, but that might be 3 incorrect clusters. And because of that, we have to repeat this process few more times. And after repetition, you are now just going to see that how we will go from this incorrect 3 clusters to correct 3 clusters. We just took the 3 centroid points randomly and checked the distance of the data point with these 3 centroid points. And whichever data point was closer to whichever centroid point has been put together into the clusters. But the thing is that we cannot stop here. We have to do the same process again, but not directly. We have to do some updation and then we have to repeat this process again. So what updation I have to do now is I have 1 cluster, 2 cluster, and 3 cluster. So if I talk about the first cluster, I can see that in this cluster, these are our 2 main data points. And the M1 is supposed to be the cluster center of this cluster. So in this cluster, only 2 points are there. And I take the average of these 2 data points, and the average will be in the middle of these 2, exactly. So we need to take the average of these 2 points, and average will fall in the center of these 2 points, in the exact center of it. Why it will fall in the center? Because mean is known as a measure of central tendency. It's the property of the mean value that if you take the average of multiple data points, it will fall in the center of that data. It's the property of that. That is why I'm not saying that it is my wish that it should be in the center or somehow magically. No, when you take the average of these 2 blue points, it will automatically be in the center of these 2 points. That's the central tendency. So this M1 moves from that location to the center of it, and now this cluster becomes like this. Same way, the M2 will be in the center of these 4 data points, and it will be moved from there to here. It will be updated from there to here. And now we have one group, this one. And now talking about the third one. So this M3, which you see, is supposed to be in the center of this entire group. So the M3 has to be at such a location where it will be in the center of this entire 5 data points. So I will move it somewhere here, and I think it should be good. Right. M3 will move from this point to this point where it seems to be like at the center of all these 5 data points. So after doing that, we remove these boundaries because there is no boundary that exists in the real scenario. I just make the boundaries to show you that there are 3 groups, but there is no kind of boundary that actually exists. So after updation, now the scenario is something like this. So after updating the centroid points locations, right? After updating the centroid points locations, we have to repeat the same process again. So now this is our M1, and this is our M2, and this is our M3 after their updations. Earlier there was location different, but now after updation, their locations are different, right? So now M1, M2, M3, M is cluster mean. That is why M1, M2, M3. It's a cluster mean. Because of mean, it is M1, M2, M3. Now what you do after this updated points, which you see, you will check the distance of all the data points again with the updated cluster means. Now, if I check all the distances, I will find out that now these all 4 points fall closer to the pink one, where in the initial step, these 2 points were with the green because they were closer to the green. But now since the green point has moved from here to here, because of that, in the second time when I repeat this task, I will observe that these 4 blue points will fall closer to the pink one. These 4 will be obviously same to this, no changes here. And these 3 points will now be with this blue. Correct. Now an updation in the shapes of the clusters can be observed if I repeated the same process again with the updated cluster means. Right, you can see a change in the shape. And as I change the shape again, we will update the cluster means again to be the center of those. So now this M2, which is the green one, will move where? Will move into the center of these 3. Because now in this cluster, there are only these 3 points. Earlier there were 5 points. Now after updation, there are only these 3 points which are closer to M2 after updation. So M2 will move in the center and it will be removed from here. Now this is one group. M1 will move from that. M1 is going to move from here into the center of this entire thing, and it will be somewhere here. And M3 will be as it is. No changes have to be done. Correct? So what we have done the same process 2 times, calculating the distance of each data point with the centroid, and then putting them together as a cluster, then updating the centroid point after making the first cluster, updating the centroid point. Now checking the distances again of all the data point with the updated cluster means or the centroid points. And then after that, when I did this second time, I can see the cluster shapes changed. Now, when I try to do it third time, we will not stop it here because we don't know. We have found the 3 base clusters. Okay, we can see, but algorithm does not know that we have found the 3 best clusters now. We should stop after the second time. It does not know. So it will try it third time again. Will any change be done after time? No change at all, because if you repeat this 10 times also now, 100 times also now, it will not change. The 3 clusters have become very stable. You will not observe any change in that. These 4 points will still be closer to red. These 4 points will still be closer to red after you repeat this process 10 times also. If these 3 will be closer to green one and these 4 will be closer to the blue one, no change will be observed at all. So the shapes are not going to change at all after any repetitions further. How this process is working and why do we need to do the repetitions? Because you can observe very clearly that initially we have 3 clusters, but they were wrong 3 clusters. And just by repetition of the process again and again, we are able to reach from a wrong 3 cluster to correct 3 clusters. And this process is so simple. Correct. This entire process is very, very simple. Now, in this entire process, what can go wrong? What can go wrong? Is there something we should be careful about where it should give us any sort of problems? Yes, there's a problem, of course, here. And that problem is known as initialization trap. Okay, initialization trap. Now let's see a problem. What kind of problem can the k-means clustering give us? Initialization trap is one of the problems, right? Euclidean Manhattan, I'll be telling you about that also. Euclidean is the distance formula which is used to find out the distance here. We will be talking about that. See, initialization trap, what it is. And if this problem happens, how do we avoid that? How do we overcome this trap? Now, how many clusters can you see in these two cases now? Means directly looking at that, how many clusters seems to be correct in this situation? So you can say 2 also, 3 also, 4 also, but the correct one seems to be 2. You see, all of these are 1, this as 1, and this as 1. The most accurate one, the most accurate k value that seems to be here is k is equal to 3, right? Because if you notice, there is no gap between any of the data points here. So this is all 1. This should be considered as 1 because there is no visible gap. There's no major gap in the data points. They are all supposed to be 1. Then I have these data points, and then there is a small gap. So I think that these are some other data points like that. So here we have k is equal to 3. So I have given my x, which is all these data points, and I have given k is equal to 3 to the algorithm. Now, what does the algorithm do? According to the k is equal to 3, the algorithm has to make the centroid points, initial centroid points. If k is equal to 3, then 3 centroid points. Centroid, cluster mean, cluster center are the same thing. So you should not be confused about that. That is what I written here. Centroid, cluster mean, cluster center. I've explained already so many times that I will be telling you the value of k. I've said it more than 5 times. We'll be seeing a process of that in few minutes. So according to k is equal to 3, what we have to do now, we have to make 3 centroid points. And you know that the centroid points can be anywhere. So let us suppose that if this happens, let's say the pink one of that is here, one of that is here, and one of that is here. What if my initial 3 points are here? Now think about it. In this case, will I be able to identify 3 correct clusters even after multiple repetitions? Will it be possible for me? No. And why no? Let's have a look at it. In this case, it is not at all possible to get to the 3 correct clusters. Not at all possible. Why not at all possible? Let's see that. So suppose I check the distance here, right? Suppose I check the distance of the data points initially with these 3 centroid points. I found out that these are the points closer to pink one. These are all the points closer to the green one. And these are all the points closer to the blue one, right? This blue. So we have centroid point here, here, and here. These are our 3 centroid points, M1, M2, M3. And initially, according to their initial position, the shapes comes out to be something like this, right? Now, after you have made these 3 centered, three clusters, first 3 clusters as you have created now, you have to move the green point, pink point, and the blue point to be the center of these clusters now. So pink one has to be at the center of these clusters, all the data points. So I think it will move from here to somewhere here in the middle of these 3, and it will be like that. Then green one will also move into the center of this group somewhere, suppose here, and it will be removed from here, right? So now the center points have updated, correct? And this, talking about this blue point, the blue point will just shift a little bit, I think somewhere here, and it will be at the center of this entire group, correct? Now, after I have updated the center means to be the center of those group, we will check the distance of the data point again with the updated center points. We'll do this process again. So now as the pink point moved from here to here, something like that, updated from here to here, now we have to check which points are now closer to the updated pink centroid point. So I think that these points are closer to the pink now, and these are closer to the green now, and these are all closer to this blue. Now blue one has become stable. no changes will happen into that. It has become stable. Whatever changes will happen now will be in green and the pink one. They will shift up and down a little bit in this case. So when I do this thing, I can see that they seem to be like at the center already. I don't need to update their locations further anymore. So this is one stable cluster, this is one stable cluster, and this is one stable cluster that we have identified. Now, if you repeat this process again and again, you are stuck. No updations will happen. So it has created 3 clusters for you, 1, 2, 3, but these are not 3 clusters. And you won't know because you can't visualize the data. So you won't be able to see whether it has made the 3 correct clusters or not. You won't be. So what to do about this situation? Because this situation can happen anytime in our data. And if this happens, then we will be getting a very wrong result, which we don't want to. So what should we do to avoid this trap? Right. Let us see what is the solution for that. But there is a tool which has been created inside the k-means algorithm, and that k-means algorithm, and that tool is known as k-means plus plus. Let me write that for you. To avoid the trap, we use a method. We use a method called k-means plus plus. Okay. To avoid this trap, we use a method called as k-means plus plus. And this k-means plus plus method we will be writing along with the code. When we will be implementing the k-means algorithm or k-means code, along with the code, we will be adding one extra parameter, which will be known as k-means plus plus. Okay, and we will see about that. But let's understand, what does the k-means suggest? How is it going to solve this problem? If initialization, if this trap happens, how can we make sure that we don't get stuck into this trap? What is the solution for that? So the solution, multiple solutions have been tried for that, and they came to a conclusion which seemed to be best in all the cases. What the people suggested in this case now, they suggested that if we use this k-means plus plus method, you have to do this. When you are making your centroid points, you have to make all the centroid points as far away from each other as possible. So you have to make your first one randomly anywhere. Let's say I make the first one here randomly, first one. The second one cannot be random. The second one has to follow a rule, which is it should be as far away from the pink point as possible. So let's say the green one I create somewhere here, maintaining a very huge distance from the first centroid point. So now the second one is not completely random. It can be created randomly anywhere, but it has to follow one condition, that it should be at a very far away distance from the first one, as far away from that as possible in the graph. And then the third one, which I'm going to create, third one also has to follow the same rule. Third one has to be farther away from both of them now, from the pink one also, from the green one also. So let's say I created that somewhere here. Now, after updation, can we say that we will be able to reach to the final 3 good clusters after updation now? So slowly with updation, what will happen? This green one will move somewhere here after a few updations. The blue one will move slowly here into the middle of this group, and the pink one will move slowly into the center of that after a few repetitions. So maybe it requires like 10 repetitions or 8 repetitions. More repetitions will be required. But your green one will definitely move from here to here after a few repetitions, pink one from here to here, and your blue one from here to here. And because of doing this, because of making all the centroid points as far away from each other as possible, the chances of initialization trap is reduced to minimum. Means it can still happen, and we cannot do anything about that. There are still chances that the trap can happen, but the chances is minimized to very little. That will be rare. Correct. So this is known as the k-means plus plus method, where we initialize the points in a way, in a particular way, so that they don't get stuck into the initialization trap. That's it. This is known as a k-means plus plus method. Okay. Now comes the final thing, last thing, which is finding the k. How do we decide the best k value? Now, till this point, I have been taking the k value randomly, right? Till this point, I have been taking the k value very randomly because I could see that uh, in my data points, there were 3 groups visible to me in all the situations. So till now, we were taking all the k values very randomly, right? And that is what I said at the start of this algorithm also. But given any data point, if I cannot plot it, so how would you know the k value? We don't have to make a guess. There is a proper measure or there is a process we have to follow to find the proper k value. Let us see what is that process. It's very simple, but again, see this thing, focus on this. The method name is WCSS. There's a tool again called as WCSS. WCSS means within a cluster, sum of squared distances. Okay. Now this WCSS is known by other names also. Somewhere people call it SSE, sum squared error, like we have seen in linear regression. Then some people call it SSR, sum squared residuals, right? So different names are there, but the most common name is WCSS, which has been proposed in the research paper of the K-means algorithm, right? Within a cluster, sum of square distances, WCSS. Now, what is WCSS going to do? How is it going to help us to identify the K or find the K given any data set? Let me explain you that process. Let's have some data points. Suppose these are my data points. These are some data points, and these are some data points. So we have again the situation where I take the X and 10 data points are there, but the K, I don't know. Here we are not going to assume the K is equal to 3 because we have to now see the process of finding the K. So can we say that we will try multiple K values and then we will see which one of them is best somehow? What is that method? We'll talk about it. But we have to go on a discovery process of finding the K. Means we have to try and experiment different K values, and one of that will be suitable. And that is exactly what we are going to do. Given any data set, you will be trying the K is equal to 1, means 1 will not be there. So generally we start trying from K is equal to 3 to K is equal to 15. Generally in this range from 3 to 15, you'll find your K value. You don't have to try more than 15 in most of the cases. But if you need to try more than 15, we will also see how we will know that we should try more than 15. But for now, the answer is that from 3 to 15, generally you will find your number of clusters. That is what we have to try. But how are we going to try that? Again, we will see theoretically, practically both. And after I show you practically, then it will be 100% clear. But now also 90% things will be clear. Let's suppose I start with K is equal to 1. I start with that. I don't know what is the perfect K value here. I have no idea. So I start with K is equal to 1. What I will do now, I will make a single centroid point because K is equal to 1. It can be anywhere. And then I will update the locations. And at the end, we will see that the pink one will be somewhere here after all the updations. And this is our one cluster. Correct. After all the updations, you will see that this is your one cluster and this is your centroid point of the entire cluster. Since K is equal to 1, put all the data points into K is equal to 1, right? What you have to now calculate is the distance of all the data point with your centroid point. This you have to do after, means you follow the normal process of clustering. You do that, complete that. But then you have, once you have got your final stable cluster, then you have to do one extra step, which we have not seen till now. We have to do one extra step where we have to find out the distance of all the data points with this centroid point now. All. And this is at the end. After finishing the clustering process, then at the end, we have to find this out. Okay. So now this. All these distances you have seen. And what you do now, you represent this with D1, D2, D3, D4, D5, like that. 10 points are there, so 10 distances will be there. What you have to do now, you have to write WCSS for K is equal to 1, right? K is equal to 1 means that you have put the entire data into one cluster and you have one centroid point, correct? So now you calculate the WCSS for K is equal to 1. When you have put the entire data into one cluster, what is the within cluster sum of square distances that we have to calculate? So how do we calculate that? You see, from D1 to D10, 10 distances we will have, and then we have to square the distances. That is what given in the formula here. We have to say D1 square, D2 square, D3 square, dash, 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 D10 square. So what are we doing now? Within a cluster, we are taking the sum of square distances. Square distances, sum, and it is all happening within a cluster. So that is why it is known as a within cluster sum of square distances. So let's say the WCSS for k is equal to 1 comes out to be something like 9, 2, 3, 4, something like that. This is the overall WCSS value, overall distance for k is equal to 1. Now what we will do, as we have noted this down, the WCSS value for k is equal to 1, we will remove everything. And what we will do now, we will now take k is equal to, now we'll try k is equal to 2. As I take k is equal to 2, then we will have two centroid points. Let's say one is here and one is here, something like that. We have two centroid points now initialized. Then we do the updations and we create two clusters. So let's say one cluster was identified, which was this, and one cluster which was identified was this. So now the green point moves into the center, and this also moves into the center. So after all the updations, this is here, and the green point is here in the center. So now we have these two clusters because the k is equal to 2, so it will stop here. No updations will happen further. Now, tell me one thing. If I check the WCSS value now, so what will be the WCSS for k is equal to 2? So WCSS for k is equal to 2 is that first we will check the WCSS for this, and then we will check the WCSS for this. Then we will add all the distances, and that will be the overall WCSS for k is equal to 2. So these all distances, then these all distances, and then sum up all these 10 distances now, and then you are going to get that, right? Now, when you have the WCSS for k is equal to 2, will it be lesser than k is equal to 1 or higher than k is equal to 1? The WCSS is going to reduce or it will increase. It will definitely reduce. Always it is going to reduce, because when you take the data points and when you put them into more groups, the data points come closer to each other. That's the property. That's the very common thing, that whenever you are taking 1,000 data points and you are putting them into 5 clusters versus 10 clusters. So when you are putting the same data points into more clusters, the data points come closer to each other, and always the distance between them will decrease. So for WCSS of k is equal to 2, when you have calculated that, let's say it comes out to be something like 7,926, let's say, for example. Some distances from that, some distances from this group. It feels like it might be increasing. But let's say when I go to k is equal to 3 now. So for k is equal to 3, the final situation that you will see will be something like that. For k is equal to 3 now, if I try one group here and one group here and one group here. Now something special will happen. When we try the k, which is best, yes, it is like the gradient descent, exactly. So when you try the k, which is the best one, for this data, we know that k is equal to 3 is the best one. And when I try the k is equal to 3, for that you will notice a special thing. What special will happen? The decrease in the WCSS value will be massive. From 9,200 to 7,900 it went, because the decrease was not that much. But as you go from 2 to 3, it will be drastically reduced, because you can now observe that the data points have come closest that they can be. Correct? Like this one seems to be the best one. So from 2 to 3, as we go to the best one, you will always observe a very drastic reduction. So let's say from 7,900, it went to 2,733, something like that. A very drastic reduction, major. And for that, we can try some other WCSS value also for k is equal to 4. When I go from 3 to 4, then there will be a small reduction now happening from 2,700 to, let's say, 2,418, something like that. Now, If I have 10 data points, then k is equal to 10 maximum I can go. Because at k is equal to 10, the total WCSS value will become 0. Because when k is equal to 10, then all the data points are a cluster in themselves, and each data point is the center point also of that group. Correct. Each data point will be the data point also, will be the center of the group also. So distance between the data point to the centers will be all 0. So WCSS for k is equal to 10 will be 0. So maximum we can go in this data is equal to 10. But if our data point has 40,000 data, so you can go till k 40,000, but of course we don't have to try till k 40,000. Like I said, till from 3 to 15, you will generally get your answer. But if you need more than that, we will see all the process. Okay, we will see all the process, how we know where to stop. I will show you. It's a very simple process. I will show you that. Okay, so we don't need to go till 0. We don't need to. Like I said, whatever number of data points are there, if 40,000 data points are there or 4 million data points are there, generally you will get your answer from 3 to 15. But how do I know from where to where we should try? How do I know? It is very simple. I'll show you with the code. It's very, very simple. It's intuitive. It's simple. So you will see that also. Leave that to me. You'll see that also. How do we know where to stop? I'm just going to show you this process, this one process practically. We were taking the different k values and we were calculating the WCSS for different k values. Now, after receiving the k and their WCSS, what I'm going to do now is I'm going to make a graph between a particular k value and its WCSS value. So for k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5, k is equal to 6, k is equal to 7, like that. Now I will just represent those. K is equal to 1, what was the WCSS? Let's say very high, somewhere here. Then for k is equal to 2, where was the WCSS? Somewhere little low. Let's say somewhere here. Then what was the WCSS for k is equal to 3? Drastically reduced, somewhere here. Then 4, then 5, then 6, then 7, like that. It will go towards 0. Now we just have to connect them. Something like that, it will go. Right, let's make this one somewhere here. It will be on the line. So now I just have to connect all the WCSS values for different k. And what I am going to observe, this will be called as a elbow point graph. It's a line plot. It is nothing but it is a line plot. You have scatter plot, histograms, everything. You're just taking the k value and their WCSS value. You're just plotting them as a line plot. I'll show you this also. And the property you will see in this kind of graph will be, there will be a very major bend that you will see. And it will be like an elbow. You have your hand, there's a bend here, and you can see that from here at the shoulder it is starting, and then it is going towards the wrist here, and there is an elbow in the middle. Wherever you observe this major bend, this elbow kind of thing, that is your k value. That's it. But this is how we identify the most proper k value for our data set. For any given data set, this is the process we will follow. We will take the data, we'll try multiple k values, we'll note down their WCSS. And when we make the graph of that k with that WCSS, we'll see this situation, which will tell us the most proper k value. Now, should we see the practical of just this process? Rest we will see later. Just this process, let me show you the practical so that you will be more clear about that, right? Okay, so for this, it's a k means unsupervised. The data will be, yeah, this one. Just running all of it. Let me show you this process. So here, after taking our x, we have to perform a process of finding the k value. See, in this code, what we are doing now, in the machine learning process, we take x. There is no y because there is no output column, just x. In x, I'm taking the input columns. And then after that, we have to run this code. After taking the x, we have to apply the k-means clustering on the x, on the data. But the problem here is that this is our algorithm And this algorithm has a parameter known as n clusters. So n clusters is this k. We don't know what is the cluster. So I cannot run this code directly. So we have the data. And the second step, the next step we have to perform is this. But we don't know this number of clusters. For that, we have to perform a process in the middle. After taking X and before applying the algorithm, in the middle of these two, we have to run a process, run an experimentation to find out our K value. So once I got the K value, then we will try that K value one last time and we'll run the final algorithm. Let's see how do we do that. A very simple process. I'll explain that in depth. So first we make a list of WCSs. We make an empty list by the name of WCSs. And then we say that for I in range of, let's say 1 to 6, means I'm going to try the K value from 1 to 5. 1 to 6 means that it will go from 1 to 5. Range function goes till end -1, stop -1. So we'll go from 1 to 5 and I'll try 1 to 5 initially. How do I know 1 to 5 is where I will get the answer? I don't know. I'll update. But what we need to run in the loop? In the loop, we are going to call the k-means algorithm. The actual k-means algorithm, we are going to repeat the algorithm multiple times. We are going to run the actual algorithm for different k values with a for loop. And what I'm going to write here, I'll be writing n clusters. N clusters is equal to I, and there's a parameter in it. Here I have to mention k means plus plus. Init is the name of the parameter where we have to mention k means plus plus so that it does not get into the initialization trap. This is where you have to mention that. And this is our k means algorithm with n cluster is equal to I. Now, since it is a class, we have to make an object of that. This. Now, after making the class, what we do? After making the object of the class, what we do next? So we take that object and say dot fit xtrain ytrain. That's what we do, right? We take that object and we say dot fit xtrain ytrain, but we don't have any xtrain ytrain. Only thing that we have is x. That's it. So we have to provide that here. Now, as I do this, then something I can print. K means dot inertia. And let me show you what happens after this. See, what we have done, simple thing. These are our 2 lines of code, which is for the algorithm. Take the algorithm, put it in, make an object of that, then using that object fit x. So here we are doing that clustering. We are putting the data points into k is equal to 1, then k is equal to 2. This is running in loop. So first time n cluster is equal to 1. Second time n cluster is equal to 2. Then 3, then 4, then 5. And what we have here is there's a class by the name of k means. Correct? This will make it totally clear. And in this class, there is a function by the name of fit. You know that the object of the class, right? You know that the object of the class can only object of the class can access the function of that class. You know that, right? So this is the object of this class, and that has the means access of this function. So this object is accessing this function. That function takes something, does the process. This is that. But in this class, there will be some variables also, self dot something. So in this class, there is a variable known as inertia. Inertia with the underscore. This is a variable that exists in this class by default. It's written code. And what is stored into this inertia value? The WCSS. So WCSS is automatically calculated. We don't have to calculate it manually. When you perform this process here what you're doing, you're putting the X, you're putting the data points into the K, into different clusters at this line of code. So when you put the data points into different clusters, then inertia value is automatically calculated, which is nothing but our WCSS. So in the first time when the loop runs, I is equal to 1 and this is 1. So for k is equal to 1, we are putting the entire x into k is equal to 1. As I do that, then I can access k-means dot inertia. That object can access that variable also. So inertia I'm able to access where this is the WCSS for k is equal to 1 we have printed. Then this is the WCSS for k is equal to 2. This is for k is equal to 3. This is for 4. This is for 5. So inertia is a variable where WCSS is automatically calculated and stored. So we have to do one last thing, just that we have a WCSS list where we will append all these inertia values which we were printing. K-means dot inertia. I'll just append that so that when I have a list of these WCSS value, I can make a graph. Let me show you. So now as I did that, WCSS list is ready and I can make a graph of that. Let me show you how that graph will be created. See, what we are doing now is we are saying plt.plot. And you know that in the line plot, we have x and y value. On the x, we have to represent the k. So multiple k's are there. So I'm using range function from 1 to 6. Whatever range value you use here, the same range value you have to use here also. So range 1 to 6 and WCSS means k is equal to 1 to 5 and its corresponding WCSS value. This line of code is going to make that graph, that line plot. And the labels on x-axis and y-axis are these, and then plt.show, that's it, run it. Now you can observe we have got that graph which I was talking about. And now we have a bend here at 3. But the question is, how do I know if I have tried from 1 to 5, here I got the answer, how do I know that? Let me tell you that. How do I know that when I tried from 1 to 5, I have got the answer here and I don't have to try for further k? How do I know? So answer for that is, if your graph is still decreasing fast till that last value, it means that you have still not got the answer. You have to try further. If you got your answer, then your graph will become almost flat, right? Almost like this till that last point. So my graph at this point has not become flat as of now. My graph is still decreasing very fast till 5. So I know that I have to try more than 5. This is the method of finding that. Let me show you how. So from 1 to 5 I have found, and I got a bend here also. I got a bend, but this is not our k value. Correct? This is not. Why it is not? It is a bend, but this is not our k value because the graph at this point has not become flat. It has to become flat. Means it should have become like this at this point. Then only we can take that this is our k value. Right? Now, not. So my graph is still reducing, means WCSS is still reducing. Let me show you something interesting. This final thing will make it totally clear. Let's say I increase from 1 to 8. 1 to 8. 1 to 9 as I say, 1 to 8. Correct. And then I run it. I will also change the same thing, 1 to 9, because we have calculated WCSS from 1 to 8 now. And now you will see the answer. Now what is your k value? Here, as you can see at 8, has it become flat, which I was talking about? Yes, it has become flat. And then which is our best k value? The lowest one, which we have. Here also there is a bend. Here also there is a bend. But we have to take the lowest one, which is our final answer. So whatever is your final k, after that you will observe that your graph will become flat after that point. See, from 3, it is still reducing very fast. So this is not our optimal k. The k5, after which the graph becomes almost flat, that is our optimal k. Now, do you think that I have to try more than 8? Will the answer change if I try more than 8? What do you think? No. Obviously, no. Because we already got the graph flat. And if I try even further till 20, 200, whatever, it will go further flat only. We won't get any other final answer. This is our final answer. So this is the method. Some of you have this question, and how do you know where to stop the K? Now you know the answer, where to stop the K. So we tried from 1 to 8. Initially, we initialized that. From 1 to 5, we tried. Then 1 to 8, we tried. If I did not get the answer, if the graph was still something like that, if it was still decreasing fast at this point, if it has not become flat, then we would say that we have to try further, right? That is the point. If our graph would have been decreasing very fast till 8 also, then I would have known that 8 is not the best. I have to try more than 8. But as our graph has become flat, reaching 8, it means that we don't have to try more than that. It's an here we have to stop, right? Now, this is the simplest explanation of the K-means algorithm and also discussing all the points. There is only few formulas which I have to tell you, that how were we calculating the distance. There is a Euclidean distance formula. That's it. You don't have to remember those formulas because you are not going to do any calculation. Apart from that, whatever we needed to know, I have explained that to you in the most simplified manner. No, you have to see the elbow graph. This is the method. You have to see the elbow graph. Without that, you won't be able to identify that. It's a method. So there are two major flaws of K-means algorithm that were discussed. One, we have to predefine a K value, which we have to provide to the algorithm. Second, we have option of only making spherical clusters when using the K-means algorithm. Spherical means you can make a circular shape of clusters if you use the K-means. So if your data set has any other shape of cluster, like a diamond shape or square shaped or any other shape, then K-means is not suitable to identify that shape of cluster, right? So that is where, keeping these two flaws or limitations in mind, the hierarchical clustering approach was created. Okay, so it's another algorithm which is to be used when K-means is not giving us the desired results. Now, to implement the hierarchical clustering, there are two methods, two approaches that we have. One is agglomerative and one is divisive. In agglomerative and divisive, you see that agglomerative works in a certain way that you take multiple data points and those data points are combined together to make clusters, right? Agglomerative is this. Agglomerative says that you start with single data point till you make bigger and bigger and bigger clusters. And at the end, you should be having one big cluster where all the small clusters are there, right? That is what you should have. The exact opposite of that you will do. You will be able to do that with divisive clustering. So divisive is exact opposite from the last to the first. If you do that process, then you will be able to do the divisive, right? So exact opposite of agglomerative you have to do, and divisive will be performed. But you don't need to know about the divisive. No one uses that. No one will be asking anywhere in the interview. You just need to understand the agglomerative approach. This is the only one which is used. And this is more easy to understand, intuitive to explain also what is happening. So that is agglomerative one is used, right? So what agglomerative says, understand this thing. Agglomerative says that we have to start with single data points, right? Agglomerative says that in the start, all the data points that you have, they are a cluster in themselves, all the data points. Now, at this point, what are you doing now? You found out that 1 and 2 are closest, you put them into one cluster. Then you found 3 and 4 are closest, you put them into one cluster. Then 5 and 6 were closest, you put them in one cluster. Then you put them into one cluster, and then you put them into one cluster, right? So this approach where you are starting with single data points, and at the end you are putting everything into one big cluster, this is known as agglomerative, right? You are combining your, you can say, bringing all the data points together into one big cluster, but not directly, stepwise. So this is called as agglomerative. What is divisive going to say? Divisive is going to say that in the start only, we will put everything into one big cluster, then break it down into smaller, right? So in agglomerative, we go from smaller to bigger. In divisive, we just do opposite. We start with one big cluster and break it down into smaller, till the point where we have all the data points as single. How the process of hierarchical clustering work, this is how it works. But what is the benefit of doing this thing? We said that whenever we have to identify which clusters to combine when, in which step, so we use a concept of distance matrix. Distance matrix helps us to understand that which 2 points are closest to each other that we should be merging first. Distance matrix is going to help us in that. So what are the ways to find the distance between the clusters to identify close clusters? What are the ways, right? So we have 4 ways, which is single linkage, complete linkage, average linkage, and word linkage. These linkages are something which help us to understand what? They help us to understand that if I'm combining or if I'm finding out the distance between 2 clusters, so how we are going to define a distance between 2 clusters. So we'll particular point here, have a look at this. So this is one and this is one. What the linkage concept says, what the linkage concept says. So there are 2 things that you will be confused about: the distance, Euclidean distance, and the linkage. So which one is doing what? So see, Euclidean distance is a formula which will help us to find out distance between 2 things or 2 points. This is going to be used for calculating distance. But we should know first what distance are we calculating. Between what we are calculating the distance, we should know that first. First, if I know that, if I know that I have to calculate the distance between this to this, then I will be using the Euclidean distance formula to calculate this distance. But who will help us to understand what distance I have to calculate? Linkage. So linkage concept says that if there are 2 clusters here, if let's say this is my cluster and this is my cluster, if 2 clusters are there, we have to find out the total distance between these 2 clusters. Correct. We have to find out the total distance between these 2 clusters. But distance of what? How will I know the distance between these 2 clusters? So there is no boundary that exists between them. So I cannot calculate the distance from here to here because there is no boundary. Boundary to boundary distance cannot be calculated. So what are the methods using which we find out the overall distance between these 2 clusters? Keep this in mind. We are trying to represent a method which will help us to find out overall distance between 2 clusters, overall distance. So what the single linkage concept says? Single linkage concept says that the overall distance between these 2 clusters is the distance between the closest points. That is the single linkage, right? Single linkage says, if you want to know the overall distance between these 2 clusters, so you have to calculate the distance between the closest point of them. That will be the overall distance between these 2 clusters. The complete linkage says that if you want to know the overall distance between them, you have to take the farthest point, the farthest between both. So you have to take that. Then average says that you have to take this also, you have to take this also, you have to take this also, and you have to take this also. And then you have to do the average of all these 4 distances. And when you get that average distance, that will be the overall distance between these 2 clusters. And word method says what? Word method says that if you have D1 here, D2 here, D3 here, and D4, 4 distances are here. So D1 square plus D2 square plus D3 square plus D4 square, you have to add them up. That is what word linkage concept says. So I hope everyone is clear with this concept. What is linkage doing? And then when linkage has decided that thing for us, then we are using the Euclidean distance formula to calculate that distance. This is very, very important. Now see, I will be telling you how do you decide which linkage to use. In any data set, when you are using the hierarchical clustering, you will be using only one of them at a time. But you have to check which one is giving you best result in any given data. So directly you cannot decide that I will be using single or complete or average or what. You cannot decide that directly. I will be telling you a very simple or intuitive method using which you have to identify which one of these linkages you have to use. Now, if you try to search the answer of this on the internet, you will rarely get a good answer related to that. So that is why whatever I'm going to explain to you, try to understand that, because that is going to be the best answer to understand which linkage to use in what scenario, right? That I will be explaining with all the visualization and everything. We'll be trying to see that in detail. But for now, let's see the example of how these linkages are going to work. So example of agglomerative approach using linkages. Let's see how does the agglomerative approach work. When I say agglomerative, it means that hierarchical clustering. Correct. So we are trying to see how does the agglomerative approach is going to do hierarchical clustering for us. So let's get started from this point itself. A quick revision kind of thing will happen. So what I have done here, I have taken an example that suppose there are 5 data points available to us, A, B, C, D, E. So I'm naming them A, B, C, D because if I give them 1, 2, 3, 4 number, then you'll be confused between the distance and the data point names. So I'm using the names as A, B, C, D, E. 5 data points are there with us, means that we have taken 5 rows of the data set. That is why 5 data points are there. Now I am representing the distance between these 5 data points with each other. So 5 data points are there and total you can see 25 distances are there, which means that we have the overall distance between each other, right? So this is the Euclidean distance concept we have used to find out the distance between each other. Single data points were there at the start. Now these numbers I have given as an example for you. This is our starting point. Suppose our data is spread like that they have these kind of distances in the start. So now we need to understand, we need to start the clustering process and we need to see how are we going to combine the points together. Okay. Now here there will be 1 or 2 confusing points. So that is why with focus, we'll be able to understand. See, when you have made this distance matrix, okay, in this distance matrix, you always have to pick the smallest value, always in this distance matrix. So the concept of single, complete, average, ward, that will be used outside. I'm going to show you where that will be used. But in the distance matrix, whenever I will make a distance matrix, I always have to pick the smallest number from the distance matrix. So here, if you see that we have 1, and no matter which linkage approach you are using, complete, single, average, ward, no matter which linkage approach you are using, whenever you have to look at the distance matrix, you always will be picking up the smallest number in the distance matrix. Okay, so I have A and E here, and when A and E is there, so you can see that they have the smallest distance between each other. Correct? They have the smallest distance between each other then. Okay, I said just now that these are all the values that I have given as an example for now, such that just assume that there are 5 data points which are this much away from each other. These are example values. See, so A and E are having a distance of 1. And you can see that the data points A and E initially are closest to each other. These are the initial distances between them. And you can see that initially, when we are starting the clustering process for the first time now, we can see that A and E are closest to each other. So what I'm going to do now, I'm going to do my first clustering here, which is A and E. I'm going to put them together. Then we have B, C, and D. Now, after having this AE and BCD, then I will be writing the same thing at the top here also, AE and BCD. Now, when I have to represent the distance between AE to AE, it will be 0 because it's the same thing, it will be 0. So what has happened now, there was 2 data points A and E, now they are in a group, right? So AE to AE means that we are checking the distance of this group to this group itself. So that will be 0. And now the main part comes up when we have to find out the distance between AE to B, right? So how are we going to find out AE to B? If I use the single linkage approach, then what I will be doing, let's look at that. If I use the single linkage approach. So linkage concept will be used outside in the outside calculation, which I'm going to show you now. So now I have to find out the distance between a group to a data point, right? And that is not given here. I am given the distance between A to B and E to B, right? I'm given a distance between A to B and E to B. This is given, but AE to B is not given to us. That we have to calculate. So if I use the single linkage concept, then the calculation will be like this. If I say AE to B, then it will be A to B, then check E to B, right? So A to B is how much? A to B is 4, E to B is 3, right? So A to B is 4 and E to B is 3. Whichever is the smallest number here, out of these two, whichever is the smallest number, that will be the overall distance between AE to B. right? That will be the overall distance between AE to B. So our final distance is 3, correct? Same way, if I use the complete linkage approach, if instead of single, if I use the complete linkage approach, then it would be 4. Same thing, just I will be taking the maximum value, which is going to be 4, right? Then if I use the average linkage approach, see, nothing else will change, just that for single, I'll be taking the smallest one. For complete, I'll be taking the biggest one. And for average, I'll be taking average. Yeah. So in the previous table, we have A to B, and distance between A to B is this 4. And distance between E to B is this 3. This is the distance between E to B. So 4 and 3 are the values which I'm using here for the calculation. Okay. So if I use the average linkage, so I will be saying 4 plus 3 by 2, that is 3.5. That will be the distance between them. And if I use the word approach, right, so in the word approach, it will be 4 square plus 3 square, that will be 25. So let's take an example of the complete linkage. Okay, we'll take the example of complete linkage for now to do all the calculations. Now, whichever linkage you decide once, then you have to follow the same linkage throughout the entire calculation. You cannot change the calculation in the middle of that. So you have to initially decide which one you want to use, complete, single, average, or what, and then you have to follow it completely for the entire calculation. But how do I decide that? Don't worry, I'll be coming to that. How are we going to decide that? No, I have not explained single to be used in this case. So now AE to B is, I'm going to say 4 because I'm using the complete linkage approach. So AE to B. What is the value of AE to C according to complete approach? AE to 4. Sorry, AE to C. So A to C is 7 and E to C is 6. So maximum out of that will be 7. Then I have to take AE to D. So A to D is 9. E to D is 8. Okay. A to D is 9 and E to D is 8. So I have to take the 9. Right. Remaining ones are given to us. Just the difficult part was calculating these 4 because it was not given to us. We had to calculate. But B to AE is 4. That I know here. And B to B is 0. B to C is given to us. B to C is 3. And B to D is 5. Then C to AE is 7. C to B is 3, 0. C to D is 2. Okay. And D to AE is 9. D to B is how much? 5 to 0. 5, 2, and 0. Correct. Now this is our updated one. So we started with single. Now in the updated one, we have one group and 3 single values. Now what are we going to do in this? In the distance matrix, what we have to see now? The smallest value. Remember it always. In the distance matrix, you always have to see the smallest value, right? Here, you will never take the bigger value or average value or word value. In the distance matrix, you always have to take the smallest. So smallest is, so which is now going to be combined together. C and D are going to be combined together next. So we are going to write like this. We are going to write now AE was one group. Then we have B and then we have C comma D. And then I'll be writing the same thing, AE, then B, and then C comma D. Now comes the interesting part. So AE to AE is going to be 0. AE to B is also calculated here, 4. No, not to initiate. Every time I have to do the clustering, so I have to take the closest points, no matter what is the linkage, not just to initiate in the entire calculation. So you know that AE to AE is 0, AE to B is 4. Correct? Now AE to that is that. So now see that here we have AE to CD. Now how are we going to calculate the distance of AE to CD? Now this is the another concept, AE to CD. How that will be calculated, right? So one thing that you might think is we will check A to C, then A to D, then E to C, then E to D, right? But no, that is not right. You don't have to calculate all the 4. Why you don't have to calculate the 4? Because are you not given already the value now between AE to C and AE to D? See, why would you now calculate A to C, and A to D, then E to C, and E to D, right? Why would you calculate these four? Because now if you see in the previous thing, already A and E has become bigger. So can we say that it will be AE to C and it will be AE to D? Can we say that? Because we now already know the distance of AE to C and A to D. So why would you not use that, right? Why to just do extra calculation? We already know the distance of AE to C and A to D. We have just calculated that. We have to use that. Otherwise, it will be wrong, right? So now AE to C is how much? 7 and AE to D is 9. So we are using the complete linkage. So we'll be using the maximum one, which is 9. Perfect. So B to AE is again 4, B to B is 0, and B to CD now we have to calculate. Now we have to calculate B to CD. So B to CD, right? How I'm going to calculate B to CD? So simple thing, B to C, B to D, right? B to C is how much? 3, B to D is how much? 5. So maximum out of these two will be 5, and that will be my overall distance, 405. And then CD to A is going to be 9, CD to B is 5, and it is 0. Perfect. Now, as I have made the updated distance matrix now, so which value we have to pick now, as I've got the updated distance matrix? Okay. So we are now going to combine this 4. You see that? 4 and 4. So what is now going to be combined? AE to B. AE is going to be combined to B. No. How is AE CD will be combined? How are you saying AE to CD? AE to CD is 9. Correct? 9 is not correct. You are going to combine what? AE to B. That is the value 4, which is the smallest one now. Right? AE to B, you are going to combine. Right. So now we are going to write it like that. We have A, E, and B. See, how am I writing that? I'm not writing AEB directly. I'm writing like this to represent how they have been clustered. First, A and E has been combined together. Then B has been combined together into that cluster. So you have to write it like that. Right? That will be the correct representation of how they were combined together. And C and D are 1. So that is the same thing you're going to write at the top. AE to B and CD like that. Now, this is going to be 0. But now the main part is, this is 0. But now AEB to CD, that is what we have to check. This is now little powerful. AEB to CD. So how are you going to calculate this thing? So take a look at it. You have to calculate this, the value of this from this matrix. This is your reference point. So whenever you are calculating the distance values now, refer to the previous one that you have made. How this will be calculated? So the calculation will go through like this. First, you will calculate the distance of AE to CD, and then you will be calculating B to CD, right? Why? Because AE to CD is 1 and B to CD is 1. Why I'm calculating like that? Because these are the values which we have already calculated in the previous one. We know these values. That is why I'm able to utilize that. AE to CD, do I know the value of that? AE to CD is 9. Yes, I know the value of that. Then do I know the value of B to CD? B to CD is the value 5. I know both of them. So I'm not going to calculate A to C, then E to C, then A to D, then E to D. No, nothing like that. See in the previous one, what are the things that you know? See in the previous one, that what are the distances we have to calculate. So 9 and 5 are the two distances. This one is 9 and this one is 5. So the maximum one is 9. We have to take that. So this will be 9, this will be 9, and this will be 0. So finally, what will be combined? Finally, everything will be in 1. So we will be saying AE, then B, and then CD, and then like that. Okay, this is how they are going to be combined together. So when you are going through this example, when you solve this thing, try to use the single linkage, average linkage, and word linkage, that examples also. I have shown you an example of the complete linkage. You just have to replace the complete linkage thing with the single, average, and word. And remember this thing, whichever you pick, you have to follow through that only in the entire calculation. Means if you're using the complete linkage, then you can't say that here I'll be using average linkage, right? And you can't say that here I'll be using the single linkage. Whichever you pick, you have to use that only from the further one, right? That is the thing. So, so now we have two clusters. Let's see what are we having here. Previously, we did not combine AE and CD, while this we are combining AE and B, AE and B. Because the smallest distance, you always have to see the smallest distance. Whichever have the smallest distance, you have to combine that. So in our initial, see, we started from here. In this thing, which is the smallest distance overall? So the smallest distance overall is 1, which is between A to E. So first we combine that. There is no other smallest distance, right? This is 1, this is 1. So they both are representing A to E or E to A, same thing. So we are going to combine first A and E, correct? Now, so after combining A and E, we again calculated all the distances. And what we found in these distances, which was the smallest value, this 2. So 2 is representing what? C to D, or you can say D to C, same thing. Either you combine C to D or D to C, same thing. You are putting them together. So in the second step, we combined C to D because that was the smallest value here. Then here we took what? Here we checked the smallest value, 4. So in this case, we found that AE with B is closest. So what is getting combined? AE with B, right? So now we have AE with B, then CD, and then only one distance is remaining. So we combine all of them together into 1. So this is the only mathematics that you need to know. That's it, right? That's it. There's nothing apart from that. So when you do the when you work on this example once, when you see the video, so I'm saying that instead of using the complete linkage approach, try the single linkage also, average linkage also, word also. One example of all, you try that. Okay. Once you do the entire calculation with single linkage, once you do the entire calculation with average, and once you do the entire calculation with the word method. What are you going to observe here? When you change the linkages, you will observe this thing is the way we are clustering the data points, that will change. So in this case, A and E were combined together, then B was combined with that, because we were following the complete linkage. So it gave us a cluster like this. But if I change these linkage approach, so obviously the result will also change. Obviously, it is definitely going to happen that this is going to change. So if I use the single linkage, it might happen that A and D get combined together and C and E get combined together. That can happen totally. It is going to change. The structure of the clusters are going to change when you change this linkage approach. Because if all the linkage approaches are giving you the same cluster, then it will not be beneficial to have multiple of them. Correct. Then we would be having only one linkage approach, right? If all of them are giving the same kind of cluster. But when you change the linkage approach, you will see that they will change. Okay. Now, yes, I'll be coming to that. Should I use this for the large data set or not? What are the challenges that will happen? But now let me show you why we did that. Okay. We understood how we are doing this thing, but let's now go through that and try to understand why we did this thing. What is the benefit of combining these in step by step? What is the benefit? Let me take you through that. So let me take you to the coding process now, and let me show you how these processes is going to be helpful for us in the practical scenario. We have understood what are the terminologies that you need to know and what are the calculations being done, but how we have to make sense of that. I want to show you that with the practical, because with practical, it will make sense. And at the end, you have to use it with the practical itself. Now, in this Colab notebook, most of the code is exactly same as what we have in the k-means. Just there is 1 or 2 lines of code which is new. So we'll be talking about that. But apart from that, everything else is exactly same. You can open up the Colab notebook and just see for now. Don't write any code for now, because all the code is same. Whatever is new, I'm going to first explain that to you, and you can run that later. But first, try to understand this thing. Let me run this file first. Now, what I was showing to all of you is there's a dendrogram. Dendrogram is what? Dendrogram is a structure that will be created once you do the clustering. You see, if I open one of the examples, have a look at it. So if I have the data points, A, B, C, D, E, 5 data points were there. So how they are being combined together, we are representing that exact thing with a diagram known as dendrogram. Okay, this diagram is known as dendrogram. This is the name of the diagram. Now, as soon as you do this process, as soon as you tell to the hierarchical clustering that you have to do the clustering using agglomerative approach, and you want to do the linkage using complete linkage. Suppose you tell that the linkage will be done like this, that this example I was showing you. Now, as you have done this, as you got this result through the calculations, then you are going to represent this exact thing as a dendrogram. Correct? You're going to represent this. So how it is working now in this case is you have 5 data points, A, B, C, D, and E, right? So first, which are the points getting combined together? A and E. They are getting combined. Then what was combined after that? B. Then what was combined after that? CD, and then totally into one. So let me bring that closer so that it will be more easy to understand. We have A, E, B, C, and D. C. So in the first step, A and E were combined together. Then in the second step, C and D were combined together. That is what happened, right? A and E, then C and D, then A, E, B, right. So first A and E were combined together, then C and D were combined together, then AE was combined with B, then this entire thing was combined with this entire thing, right? And this is known as hierarchical. You're going from start to the top, bottom to the top. In a hierarchy, you are moving up, right? So what are we representing with this diagram? We are representing how the data points were combined. So first I have written A and E because these were the 2 points combined first. Then second, C and D were combined. Then third, AE with B was combined. Then finally, AEB with CD was combined. So these are the lines which are telling us how and which are the data points that has been combined together one by one, step by step. Correct. So this structure will be created when you perform the linkage process. When you complete the linkage process, then this structure will be representing this thing. Right? This structure will represent what? This thing that we have created with the calculation. But what is the benefit of this? Why we even bother about this structure? What is the benefit? I'm going to explain you the benefit now of this structure. Yeah, let me show you some of the practical things. AE, B in cluster 1 look like and CET in another cluster. Now, I'm uploading the mall customers.csv dataset that we used in the practical of the k-means. Exact same dataset. Right now. So here we have pd.read.csv, we have mall customers.csv. Correct. And then we have this customers.head. If you look at it, then you have all these 5 columns as your input column. Then we have to drop the customer ID column because it was not important. Then, but for now, I'm not encoding it because I'm not using the gender column for now. I'm just using the last 2 columns, the annual income and spending score. So because of that, I'm not encoding it for now because I want to show you the final visualization of the clusters that will be created. So till this, all the steps are same. We took the data, checking for the duplicates, missing values, then encoding the data, all the things are same. And then we come to this point where we take the X. In X, we store the last 2 columns value in array format. I have explained this thing to you. Now, as you take the X, you have to perform one process, which is known as the process of making those linkages. Correct. So how should we choose the number of clusters in hierarchical clustering? That is what we are going to talk about here. First, you remember that when we took the X value in k-means clustering in the last practical, what we did with the k-means clustering. So we took the X value. X value was all the input column. Then after taking the X value, this was our step 1 in machine learning process. After taking X value, what we did an experiment, right? In experimentation, we used the k-means algorithm. The main algorithm we ran multiple times in a loop with different k values. We ran the main algorithm. And then after that, we used the final k value, correct? So the problem here is that we are running the k-means algorithm multiple times. The main algorithm itself, we are running multiple times to find the k value, correct? And what is the problem with doing that? If your data set is very large, if you're running the k-means algorithm first for k is equal to 1, then for k is equal to 2, then for k is equal to 3, if your data set is very large, it will take too much time. A lot of time will be required and a lot of computational resource also will be required. If you're doing this thing, if you're using a very large data set and you're running the algorithm with different k values. Correct. So you can imagine if you are going from k is equal to 1 till k is equal to 15, imagine that how much of the process will be required or how many resources will be used for doing that. But this is the only option we have in the k-means clustering, that you run the main algorithm and then you find out the WCSS value, then you plot the k value with its WCSS to get the proper k value. This was the problem. Using the main algorithm to find the k value was the problem, because using the algorithm is a intensive process. It will take much time, it will take much resources. It's an intensive process, right? So we are saying that we will not do this. In hierarchical clustering, what are we going to do? Step number 1 is going to be our x. We'll take our x, which is our data. Then in step number 2, what are we going to do? We are going to do the linkage in step number 2. We are not going to run the algorithm, our agglomerative clustering algorithm. We are not going to run algorithm to find out our k value. Correct. So we are going to do a much simpler process, which is known as a linkage. Linkage is nothing but what we were doing with the mathematics. Linkage is that. In the linkage, we are not using the algorithm. We don't have to use the concept of agglomerative clustering or the main algorithm. We don't have to use. We just have to do the linkage on the basis of distance calculation. Correct. If I use the single linkage, I'll be using the smaller value. If I use the complete linkage, I'll be using the bigger value to represent the overall distance. We don't have to use any machine learning algorithm to do the linkage. Linkage is the very basic distance calculation that we are doing between them. Correct. So when I do this, then I'll be able to find out number of clusters through this linkage process. Then in the third step, we will be running agglomerative clustering algorithm. The main algorithm we are going to run in step number 3 only once. Only once. Just we are going to run the linkage once, and this will help us to understand the number of clusters. Once I got the number of clusters, then I will be running my main algorithm once. Correct. So it will be taking much less time compared to what we were doing in that case, in the k-means clustering. But it also has its own challenges. So let's understand how we are going to do all of these things. Let me show you something interesting now. So ignore this code for now. I'm going to show you the same thing in a simpler way for now. See, so first I'm taking the entire data and I'm using the single linkage for now. Because what I told you, we don't know which linkage approach we have to use. We don't know that at all. We will never know which linkage we should be using. So what we need to do here is we need to try all the linkage approaches, and then we will be able to find out which linkage approach is best on that data set. So you will never know, by default, you will never know that on this data set, whether the single linkage will work or the complete will work or the average will work or the odd will work. You will not know that, correct? So you are going to use the linkages one by one, and you are going to see which linkage is giving you the correct answer. So first, let me make the single linkage approach and let me show you this. So remember that the work of algorithm is what? Either you use the k-means or you use the hierarchical clustering. What is the main work of algorithm? The main work of algorithm is to make sure that if you have told it to make 3 clusters, so it should be making 3 right clusters, not 3 wrong clusters. That it has to make sure, right? It is this much. The main work of algorithm is to make sure that if I'm giving it the number of clusters, so I am giving it the number of clusters in both the cases. But if I'm giving it the number of clusters, it has to make sure that the number of clusters which it is creating should be correct. Okay, if I say make 5 clusters, so it should not be making 5 wrong clusters. It should be making right clusters with 5 of them. That is its work. Now, look at this single linkage and look at what it has done. And now, let me go through the complete linkage and let me show you what the complete linkage is doing. Now, can you see that the entire structure changed as I changed this? You see, this is the structure getting created when I'm using the single linkage. And this is the structure getting created when I'm using the complete linkage. So can you see now that the way the data points are getting combined together is totally different, very, very different from each other, right? This structure and this structure, totally different. So obviously, when you are going to change the linkages, the structures will be very different, very, very different, correct? Some of them can be very similar to each other, but generally what you will see that the structures will be very different. Now you have to decide whether this one is better or this one is better. You have to decide that. But coming to that point also, let me show you the other two also, the average and word. Average is doing this and the word method is doing this. Okay, now, so single, complete, average, word, average and word. So single, complete, average and word, correct? So I hope you are able to see this thing that they have a very different structure. But now look at this word method. If you see, word method is something similar to complete. Word method has done something similar to complete. So it can happen that two of them can have little bit similarity in them, what they are doing, but there will be still differences between them. It will never be exactly same. There will be still quite a significant difference in them. Correct? Now see this. So do you think that the single linkage is doing a good task in this case? Now, before you answer that question, you have to keep this in mind that I was writing a concept for all of you. So the similar points should be as close to each other as possible, right? And the dissimilar points should be as far away as possible. Now look at these both the things. We have to make sure whenever we make clusters, we have to make sure both of these things are being followed, both at the same time, not just one of them, both. So similar points should be as close to each other as possible, and dissimilar points should be as far away from each other as possible. Now see this. What is it doing in this graph? So do you think that this graph is making this or following these two things? Is this graph following these two things at the same time? So you will observe that no, it is not following, because if you see, there is in the start the orange color and green color structure. In the start, there's an orange color cluster and the green color structure that is getting combined with this side. You see, there is a connection coming up on this side with this blue color cluster, with this pink color cluster, then there is a blue color cluster. So are the similar data points close to each other in this case? No. The single linkage is not able to combine the similar data points in a closed structure together. And you see that you don't even have to go to that. What you have to see, is this structure easy for me to understand or not? Will I be able to interpret what is happening in this entire thing or not? You will see that it is so much of mess that you won't be able to understand what is happening here. It is total mess. So if you see like that, this kind of structure, that it is totally mess, you don't even understand what is happening here, that is totally bad, and single linkage has done a very bad task in making the clusters. Correct. So single is very bad. We don't have to use that because I am not able to see any structure clearly here. Okay, what do I mean by that? Let me show you other examples. Now this is of complete. So can we say that complete linkage has done a much better task compared to single linkage? Because here I can understand very clearly that this is one, this is one, this is one. I can understand it very clearly, very, very clearly. And I can make sense of what is happening here. And the structures which are also created, I can see that they are very clear. So all of these, you see, all of these data points which were closer to each other have been put together. And now these data points and these data points were away. So they have been put away from each other. Correct. So now complete linkage is following both of these things in this data set. So complete is doing a better task compared to single linkage in this data set. It does not mean that it will always do a better task than single. In this data set, when I'm visualizing this thing, complete linkage seems to be doing a better task compared to single. Okay, it is not complete yet. Just let me show you a few more things and then you'll understand what I'm trying to explain. Now, this is for the average. Is average better to use? So as I can see that, again, this is complicated. So it is not as bad as single linkage, but it is still very bad, right? It is not as bad as single linkage. Single linkage was doing a very horrible task of making the structures, but average is doing not that much worse, but it is doing a better task. Correct? So average also is not good. Complete, we have seen that it is better, but average is also not better. Then coming to the final one, which is what, right? Coming to the final one, which is what. So Word has done something quite similar to the complete. So Word is also very simple, very clear, very easy to understand what it is trying to do. Very easy to understand, right? So now, uh, when we have looked at single, complete, average, and Word, right? When we saw all of these things, four, so in all the cases, you have to do this thing manually. In all these cases, whenever you take a data set, you will never know which linkage is best for you. You always have to do this experimentation exactly like what I'm showing you. You try all the linkages, see the graph of all the linkages, then compare which one is doing a better task for you. This is how you have to do it always. There's no formula which is going to help you find out this. This is a manual task which you have to do like this. But now, between Word and complete, which one I should be picking? That is the interesting point. So average and single gone. Those are not the correct options for this data set. Okay. Now I have to decide between Word and complete. So which one I will be using between Word and complete? That is dependent upon a concept. You need to know a principle before you decide that. See, what you need to see is, first, let me show you the complete. So in the complete one, see, so in this example, if you notice that point number 2 and point number 3 are getting combined. Point number 1 and 5 are getting combined, and 4 and 6 are getting combined. But the height of these dendrogram is different there. If 2 and 3 is there, their combination is being shown with this much height. But when 1 and 5 are getting combined together, their combination is shown with a taller height of this bar. Then 4 and 6 is even taller, that is being shown. Is there a significance of this height? Obviously, if there is a different height, so obviously it would have a significance, correct? So what is the significance? Let's understand that with this. Okay, let's understand with this. The point number 1 and point number 2, you see that point number 1 and point number 2, are they very close to each other? So if I say point number 1 and point number 2, I'll be making a very small bar to represent that they are connected. I'll be mentioning a very short bar, very small bar, because they are very, very close to each other. But if I combine 3 and 4, if I combine 3 and 4, but they have a little more distance compared to 1 and 2. So I'll be making a little longer bar, a little taller bar to represent that 3 and 4 are closest to each other, but they are not as much close as 1 and 2 were to each other. Correct? Then if I combine 5 and 6, so I'll be making even taller bar, that 5 and 6 are closest to each other compared to any other data point. 5 is not closer to any other data point. 6 is not closer to any other data point. They are closest to each other. So of course, 5 and 6, I have to combine and put them together. But when I show this combining part, when I show that 5 and 6 are getting combined, I'll be making a taller bar compared to 1 and 2 and 3 and 4, because the distance between 5 and 6 is more than the distance of 3, 4 and 1 and 2. Correct? But why am I telling you this? Is there a significance of that? Is there an importance of this thing? Exactly. There's a importance of that. Otherwise, this height would not be there. Otherwise, we would be having the same height for all of the clusters which are being made. This height is something important for us. See, here you have to see. In the complete linkage, what is happening? This is one cluster and this is one cluster. And the distance between them you have to observe here is, are these two clusters very, very away from each other? So you will see that not much. These two clusters are definitely away from each other, but not much. Okay. And coming to the Word method, what is Word doing here? So can you see that this and this is very far away from each other? These two clusters have been made very far away from each other. Yes, clearly it is visible that compared to the complete approach that we were using, the Word is making these two clusters very far away from each other. If you remember one statement I have given you, that the good clusters are those clusters which are very far away from each other. So if I have a cluster here, if I have a cluster here, and if I have a cluster here, very, very far away from each other, it means that these are good quality clusters which we are making. Correct? Why did I tell you that? So suppose one cluster is here and one cluster is here. So don't you think that instead of making these two clusters separately, we might have combined all of this into one because they are very close to each other. So they might be almost the same data points, not very big difference in them to represent them as two separate clusters. So can I say that we should have represented both of these into one, and we should not have represented them separately? They should have been into one because they are overall almost same, very, very similar to each other because distance represents similarity. The same way, if I say that one cluster is here and one cluster is here, which means that these two clusters are good quality clusters. Means obviously these data points are very different from these data points, and we should make two different clusters to represent these two data points. We should make, because these two clusters are having two very, very different type of data points, not the similar type of data points, very different from each other. So a huge distance between the clusters represent that we are making good quality clusters, because the similarity between them is not at all there. They are very dissimilar from each other. So if dissimilar clusters are very away from each other, that is a representation of good quality clusters. Why am I saying that? Let me show you one example so that you never have confusion in this thing. As far away from each other as possible, good quality cluster. But why am I saying that? Let me explain that to you. Why am I saying that? If the clusters are very far away from each other, it's a good quality cluster. Why am I saying that to you? So in this example, you notice that this is one cluster, this is one cluster, and this is one cluster. They are at a good distance from each other. But if the distances would have been even farther away from each other, it would have been even better. The farther the clusters are from each other, the better it is for us. But why? See, so if I have these points, and suppose I am representing these data points with the values of income and age. I'm taking two input columns. So every dot is representing income of a person, age of a person. Now see here, if I take a data point here, and if I take a data point here, these both are into the same cluster. Now, are they very similar to each other? We have seen, yes, of course, they are very similar to each other. And because this person has this much income, this much age, this person has this much income and this much age, right? So they are very similar to each other. So we should be, of course, putting them into same cluster. Now, suppose if I have some more data points here, right? Suppose I have one more data points here. So can I say that instead of making them into another cluster, can we say that we should be overall putting all of them into one? Because these data points are not very different from these data points. Not that much different that we should be putting them into another group. These are not very different type of customers than these type of customers. Why am I saying that? Because if you notice their income and their age, they are not very different from these type of people. Their income and age is very, very similar to these people. Not that much similar, but overall, these are similar to each other. Means you are saying that these type of customers and these type of customers are very similar in their property, in their behavior. So why to keep these customers into two different groups? They should be put into one group, correct? So if there are some data points which are very close to each other, we should not be putting them into two different clusters. It is not going to be helpful if I put them into two different clusters. I should be rather putting them into one big cluster, correct? Are you getting the point? Now, so you see that what was the complete linkage doing here? Complete linkage was saying that this is one cluster, this is one cluster, but it was making two clusters which were very close to each other. You see that? What was the complete linkage doing here? Complete linkage was making two clusters. It was making two clusters which are very close to each other. So can't we say that it has identified two clusters which were not good quality clusters? So it has tried to divide a data point of one clusters into two clusters. It has not identified actual good clusters, correct? Because they have a very closeness with each other. These two clusters have a very closeness with each other. So we are saying that these are not good quality clusters that the complete linkage has identified, right? Now, instead of that, if I go through the word linkage, so can I clearly see that it has identified two clusters which are obviously very far away from each other, because this tower represents the distance between them. So this cluster and this cluster were very far away from each other. And if they were far away from each other, then they are very dissimilar from each other. And we should obviously not be putting them into one group. They should obviously be put into two different groups, as is being done by this word method. Keep in mind, whichever linkage is making multiple clusters very far away from each other, that linkage is best for us. So in this case, out of all four, we have to use which one? The word method, right? We have to put word method in this. So this is a tower which is representing how far away from each other they are. This tower, the taller the tower, the farther they are from each other. Correct. This is a cluster. This is a cluster. So this tower, the tallness of this tower is representing how far away from each other they are. And before explaining this, I explained this also. That you see this one. I said that 2 and 3 are getting combined, but this is having this much taller tower. Then 1 and 5 is having this much taller tower. So 1 and 5 are getting combined together, but the tower which is representing this linkage is taller than this one. So what does it mean? That 2 and 3, point number 2 and 3 are, let's say, this much away from each other, but 1 and 5 are little more away from each other. Correct. So 1 and 5 are closest to each other compared to any other data points. 1 is not closer to any other data point compared to 5. And 5 is also not closer to any other data point compared to 1. But the way they are closer to each other, they are not very close to each other. They have this much of distance in them. Correct. That is what these distances are representing. So that is why what matters to us here is we have to see that this and this are very far away from each other that we have identified, right? That is the thing. Perfect. So we have identified the word method as of now. But now what to do? We have finally identified the word method, and I have not explained this code for you. Let me explain the code. See, so what are we doing now? After taking the X variable, which is our data, we took the data. Then after taking the data, we have to run this linkage process where we will be able to identify the number of clusters. So just after taking the data, we have to follow this linkage process. And through this linkage process, we will be able to find out number of clusters. How? Coming to that. But now see, what is the code I've written for that? Code is very simple. I'm importing this package as this alias name. When I say import pandas as PD, so this is the name of the package whose alias name is SCH I'm using, right? So import scipy.cluster.hierarchy as SCH as this alias name. Then what we are doing now is we are doing a simple thing. We say SCH.linkage. Correct. Using this package, we are calling a linkage function from that. And what are we providing to the linkage function? Our data and what? Method. Method is equal to what? So when I provide the data and the linkage method, it will start linking them together. Correct. It will start to link them together. Then when it is linking them together, it will be making this particular code will be making what? AE, then B, then C, comma D. This example that I was showing you, the way they are getting combined, this particular code is going to make this code. But now when you have this thing, then you have to represent it as a visualization. You want to see it as a visual form. So then it becomes easy for you to make further decisions. So what I'm doing now, take this entire code, put it into a bracket. So whatever this entire code is going to give to us, what are we going to do on that? We are going to make sch.dendrogram on top of that. Correct? Simple thing, right? So first we are taking our data and the method, linkage method, giving that to linkage function. It will do the linkages. It will make that graph, that A, comma E, comma B, those combinations it will do. Then whatever combinations are being made, you are visualizing that exact combination with a dendrogram plot. Correct? So whatever it is making, I'm storing that into a variable dendrogram so that I can print it, or whatever I want to do, I can print it. And then the method, word method, why did I pick the word method? That also should be clear to all of you. Now coming to the last part in this case, why did we even care about the word method? Correct. Why did we even care about the word method? Let's take a look at that. So first, we have to take our data, which is X, then we have to go through the linkages, single linkage, complete linkage, average linkage, and word linkage. All of these things we have to see what? Manually visualize them or manually check them, you can say. So after manual visualization, what we have done, we will take a data, we will take our data set and we will try all the linkages on the data set. I'll say method is equal to single, method is equal to complete, method is equal to average, method is equal to word. Where? In this code. You see, there is a method is equal to word I've written. So you will be trying all 4 of them on every data set because you will never know which one is going to give you the best answer. So by default, you will not know. You always have to try all the linkages on a data set. Correct? Now, so when I tried all the linkages on the data set, I found out in this case, this one, right? The word linkage, we found out that it is the best one that we have applied on that. Correct? Now, third one, using that final linkage graph, right? You have to use the final linkage graph to decide the number of clusters. So number of clusters. Now see, now you should be able to understand the flow. Take the data, manually try or manually visualize all the linkages. Then when you manually visualize all the linkages, then you have to pick the one which is best representing. In our scenario, it was word linkage. And don't worry about it. As we move forward, we'll be working on multiple examples. And you will see that in some case, single linkage will be better. In some case, complete linkage will be better. But I've explained to you how do you decide that. So if your graph looks very random, very, you can say, messed up, it is very complex to understand, totally discard that. That is not doing a better clustering, correct? In this case, complete and word gave us very clear picture. But complete was not very good because it was not following one of the principles of identifying the clusters very far away from each other. Word did a better task of identifying the clusters very far away from each other. That is why we are picking the word method in that. Clear till now? Now, as we have defined the word linkage and as we have defined that this is our final graph that we have to use, what to do with this graph? Using this graph, we are going to decide the number of clusters now. Correct? We are going to decide the number of clusters now. Correct? That is the thing. Right? That is the thing. So should we go forward to that? Your input columns, whatever input columns you take, 2, 3, 5, 10, 15, 20, whatever input columns you take, you'll be able to visualize this dendrogram structure, right? You see that on the bottom, what is being represented? Our data set has 200 rows. Correct? Our data set has 200 rows. So we are not plotting the data. If I was plotting a data like that, then I would be limited to 2 input columns or 3 input columns. But I'm not plotting the data here, you see. I'm plotting the distance between the data points. So no matter how many input column you use, the distance will be visualizable. Correct? So that is not a problem here. We have the distance between the data point. So you will be able to use as many input column as you want. Now, let me show you what is the final thing we have to do here. Because what is left for now, we have not yet understood how this thing will give us the number of clusters. That is what I'm going to show you now. That will be our final thing. So now what you all have to see is this. Yeah, these represent cluster, but you can even break down into further more clusters, which I'm going to show you now. So by looking at these, you can say that this is one, and this is one. So number of clusters is 3. You can say that also. That will be correct. That will not be very wrong. But the people have said that you should not be using this as the final answer. You should rather use another method that will give you an even better answer. What we do now, look at these junction points. So there is a line coming up and joining this line. So wherever this point is happening, this joint, that is our junction point. Now, this is my junction point. This is one of my junction point. Then second one is here. And third one is here. Then fourth one here, fifth one here, sixth one here. Then seventh one here, eighth one here, ninth, like that. We have multiple junction points. But you see, you don't have to go to those bottom things. In bottom, you'll never get your answers. So you don't have to see all the junction points. only the ones which matters are, that will be at the top. Yeah, you can call it T point, you can call it junction point, connecting point, whatever you can call. So these are some of the points I have mentioned. So let's say this is my connecting point 1. This is my connecting point 2. This is my connecting point 3. Okay, this is my connecting point 4 and 5 and 6 and 7 and 8 and 9, like that. Like these are my connecting point, correct? Now, so what you have to see now is, as you have represented these connecting points, you now have to travel, you have to start making line, a straight line you have to make. And from the point of 1, here we have one connecting point, one T point. We have to start from here. You have to start making one straight line here. Now, how much you can travel? You can travel that much so that you don't cross this layer of another junction that is there. So this is the level of junction number 2 or point number 2. You cannot cross that level, correct? Then from 2 to 3, how much you will be able to travel? From 2 to 3, only this much you will be able to travel, because if you go further, then you will be crossing the level of 3. You can't cross the level of the other junction point. Then from starting from 3, how much you can travel? Starting from 3, you see that this 4 is little above this thing. That is why I've given this 4 and 5, because 4 and 5 are on the same level and they're just above this 6 one, right? So use from 3, we can travel this much, then we'll be on the level of 4 and 5. Then from 4 and 5, we can just travel this much, then we'll be on the level of 6, right? So now what you have to see here is where we are able to travel most. Between which two junction points we are able to travel most. So I can see that here also and here also, both seem to be the same distance which I am able to travel, which are two maximum distances which I am able to travel, correct? Now, you can pick any one of them as the final one, but let's say I am saying that this is the distance which is maximum I am able to travel between two junction points, correct? So as I have decided this here, then I will be making a straight line passing through this, and this straight line should be between these two junction points where I'm able to travel most, correct? Now, this line is crossing this line which I have created just now randomly is intersecting our actual graph at 5 different places. See, whatever I'm explaining you here is the actual method, how it has to be done. And this is the simplest example regarding this, you will see. Now, our line which I created here is intersecting our actual graph at 5 different places, 1, 2, 3, 4, 5. 5 different places. So what is the value of k now, or the number of cluster is equal to 5, correct? If I would have used this, correct? If I would have used this one, then if I would have passed the line through that, so it will be 1, 2, 3, and your answer will be 3, correct? Your answer will be 3 because it is intersecting 3 of our lines which are of our actual graph. Now, both the answers I'm getting, 3 also, 5 also, then which one should be my final answer? Because in this scenario, you can see a special case where this one is there and this one is there. Both are having equal maximum distance that we can travel. So I'm getting 5 also, I'm getting 3 also, but which one is our better answer? So now, there I'm going to tell you one important one, whether you have to pick 5 as the number of cluster or 3 as the number of cluster, which one is the correct one? See, here what you are going to do, right? Here what you are going to do now is this. When you will be working on the unsupervised data set, unsupervised learning data set, then this will not be done by a fresher. You as a fresher will never be making these final decisions about the number of clusters. Through this calculation, through this entire practical which I'm explaining to you, you will be able to find out the number of clusters. But will this be your final number of clusters which you are going to use in practical? You don't have to make that decision. That final decision will be made by some person who is experienced and who knows about that company. Now, what I'm going to say to you now in 5 minutes, important, very important point. So I'm working on, let's say, a data set of, let's say Amazon, for this example. Let's say I'm working on the data set of Amazon. Now there is a person who is working in Amazon for quite some time. They have a good experience working in Amazon. Now they know how many type of customers exist in Amazon, right? On Amazon, how many type of customers are there which are very distinct? Are there 5 type of customers, 6 type of customers, 7 type of customers, 4 type of customers? How many type of customers are there? So since they have experience on working on Amazon, they have already worked on different projects. Through those projects, they would have found out that there are 6 type of customers or 5 type of customers, right? They know this thing very well because they have worked on the data set of Amazon and different projects, and they have somehow this information, a very correct information, that in Amazon there are 6 or 5 type of customers. So if they are very sure, then they would have used this answer directly. We would not have to do this entire practical. But they are saying that I think it should be 6 or 5, but I'm not very sure about that. But I think it is 6 or 5, something like this. Then the actual number of clusters would be 6 or 5. Now you have done the practical on the data set. You found two numbers, let's say 5 and 3. So which answer is more closer to what they knew? The 5 is the answer which is more closer to what they know. Correct. So they were saying that either the number of customers are, or type of customers are 6 or 5. I'm not very sure, but I'm sure that it will be 5 or 6. With your practical, you are just confirming the fact. Okay, they have a knowledge of this thing, but with your practical, you are confirming which one is correct. You're confirming the fact. So if your code is giving this output as k is equal to 5, so then you are confirming the fact that whatever they knew were correct, and the actual number of clusters would be 5, right? Now, suppose if you would have got, if your manager would have said that the number of customers are 4, correct? So your answer 3 and 4 both are closer to 4. So either you can go with 3, or you can go with 5, or you can go with 4. Any of these answers will be correct. There is no concept of right and wrong. There is just a concept of more efficient, less efficient. So you can either go with 4 because that person knows that, and our code is also confirming we are getting two k values which are closer to 4. So I can say that 4 might be the correct answer because my code is also saying that, right? Correct? Because my code is also confirming the fact that the number of clusters could be 4 or are closer to 4. So you can go with 3, you can go with 5, or you can go with 4 also. Because your code is confirming that the number of clusters can be 4. Because both the number of clusters are very close to 4. Is that clear to everyone? So you have to go through either 5 or 3 or 4. You have to go through that. I hope this is clear, right? So you don't have to make sure that, or you don't have to just stick to your final answer, which is given by the code. You don't have to say that 5 is given by the code or 3 is given by the code. So I'll use that one only. I can't use anything else. No, it is nothing like that. If you have any other answer, which your some experienced person knows, you can go with that value also. But you have to see that is the code telling us the same thing or not. So code was telling us the same thing, that if my manager says that 4 should be the number of clusters, and my code is also confirming that both the number of clusters I found was close to 4, 5 and 3. So I can go with the 4 as the final answer. That will be the. So basically you can say that overall you can say that with the code we are confirming. So someone who is a manager who will know this thing, whoever is experienced in this data set, they will have an idea in their mind that the number of clusters should be 3 or 4 or 5 or 6. They will have a number in their mind that they are pretty sure. But with the code, you are just confirming which is that number, which is the better. You are confirming that thing. So this is the thing you will do finally. In k-means clustering also, in the hierarchical clustering also, this is the thing you have to go through. So I hope this is clear, and this is simple. If it is having any giving you any confusion, or don't worry much about it, when you go through the theoretical and practical both together at the same time, then it will make sense more. Now, after finding out your final number of clusters, you just run this final code, which is of your algorithm. So agglomerative is the class which we are importing from this package. Then we say agglomerative clustering, take the class, mention these values which it is asking from us, and then make an object of it. Then you do the same thing which you have done in the k-means clustering.
Just a quick info, guys. Intellipaat offers a data science course which will help you master Python, SQL, machine learning, AI, and Power BI. Get a data science certification from IIT Empower, an innovation hub of IIT Madras. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given in the description and take the first step towards the career growth with the data science course.
Talk about a concept called as PCA, Principal Component Analysis. So now we have a principal component analysis, and this topic is going to help us understand something, help us to do something. See, what is the situation here? When you talk about the number of input columns, the input columns are also called as features. So whatever is the number of input column, we have that dimension, that much of the dimension in the data set, right? If I suppose take a one single column and I try to make a graph of that, we will be having one dimension data set or one dimension graph, you can say. If I take 10 input columns and if I try to represent that as a graph, or if I try to work on that, it's a 10 dimension. 30 columns, 30 dimension, 500 columns, 500 dimension, right? So whenever you work on different number of input columns, so you have that many dimension in the data set, right? And the thing is that there is a problem that happens when you start increasing the dimension and you try to increase the dimension more and more and more. There's a problem that start to come into picture. So first, let me give you an idea about why do we call it dimension? How I am saying that if I have one column of data, I can call it one dimension data set. Why am I saying that? How do you have to make sense of that? So here we have a data set and we'll try to understand that. Let's say I take a data set in which income of the people are given to us and then their loan approved or not is given. Okay. You see, suppose I have one input column and one output column, right? In this case, if you talk about the input column, if you talk about the column in input column income. Now let's say I have this income column, right? In this income column, I have 0, 1, 2, 3, 4, 5. These different rows are given to us. And there is some income of the first person, second, third, fourth, fifth, sixth. These are different people whose income I have in a data set. And whether their loan was approved or not, we have that on as an output column. So we have yes, yes, no, yes, no, yes. These kind of things are there. Okay. So I have a data set in which one input column is there, one output column is there. And in the case when you have one input column, then whatever data you plot, that will be one dimension. So if I suppose have to plot these income values, all the income value of the different customers that is given to us, if I plot that, you will see a graph like this. You will see a graph like this. Okay. And in this graph, you'll see that there will be multiple dots on a single line. Let's say like this, like this, like this. Now each dot is representing what? Each dot is representing one income value, right? And this is income here. And this is our x-axis. You know, we have seen already a lot of graph and we have a graph like this. We call x-axis, y-axis. These kind of things are there. But see, when I take a classification data, suppose here, and I have one input column, if I plot a single input column, you'll see that these dots will be created on a single line. Okay, single input column. So you have a single axis here on which you have the dots. So this is a customer whose income was this much. This is a customer whose income was this much. Let's say it is starting from 0 here and it is going in this direction. Correct? So now we have start from here, right? We have a value starting from here. It is 0. And as we are moving forward, we have different income values like that. Correct? And every dot you see is a certain income value of let's say a person. Correct? So if I have 1000 income values, then I will have 1000 dots like that, but on a single axis, one axis. Correct? Now, if I take this data, copy and say paste here. Now let's say I take this data and I add another input column into this. I'm going to add another input column to this, which is, let's say, the CIBIL score we were talking about, the CIBIL score of the people who were applying for a loan and income of the people. So now I have two values that I'm going to take, right? So when I take two values, I have to represent a row with two values, their CIBIL score, their income. For every dot, there will be two values attached to that. Correct, for every dot, because every dot is a data point and every data point is basically a single row that we are representing. You see, there are different dots like these. And what are these dots? Every dot is a row, right? Every dot is a row. Now see, so when I take here, when I take a single row, every row has two values, correct? A person's CIBIL score and a person's income. A person's CIBIL score, person income. So if I have 1,000 rows now, every row has two input values. So here I'm representing the income and here I'm representing the CIBIL score, correct? And you see all the dots are representing a row, right? And since every value has two values, or every data point has two values, right? The income value and the CIBIL score, that is why it is known as a two-dimension data, because every value is having two different values. There is something called as a scalar, and then there is something called as a vector. Now, whatever data you provide to machine learning or machine learning related algorithms, what we are going to study at PCA is also a machine learning related algorithm. Okay, so whenever we provide the data to machine learning related algorithms, they understand the data or they work with the data in the form of scalar, vector, matrix, or tensor. Okay, so they work with one of these type of data. So scalar is a very small unit. Scalar is basically a single number. Let's say I have a 35, 42, 1.9, 0.008, something like that. If I have a single value that I'm taking, just a single value, not a row, not a column. So scalar is just a single value that you have. Okay, it can be any value, just a single value. But now when I take a collection of scalars, that becomes a vector. Right. If I take a collection of scalar values, if I take multiple values and I put it as a collection, then it becomes a vector. And vector is basically a one-dimension array. Okay. You have studied the NumPy concept, and in NumPy you would have seen one-dimension array. One-dimension array is an array which is in single line. It is not having multiple rows, multiple column. Just a single row is there. That's a one-dimension array, and that is called as a vector. Okay. Now, when you take a collection of vector, you make a matrix. So matrix is nothing but it is called as a 2D array. 2D array means you have multiple rows and columns. So if I have a array of shape 5, 7 or shape 100, 250, right? Anything, if I have some rows, some columns, that data is known as a 2D array, and that is also called as matrix in the field of machine learning. Correct. And what is a tensor? Tensor is 3D or higher array, right? When I talk about tensor, tensor is a 3D array or higher dimension array, right? Now, why am I telling you about these terms? Because you see, whenever you provide a data frame or a single column or a single row or multiple rows, you are providing the data in the form of rows and columns to the machine learning algorithms, right? But when machine learning algorithms receive the data, they are going to convert that data into one of these forms, and it will understand them in the form of vectors, matrices, tensor, scalar, in form of these. We are providing rows and columns. We are providing a data frame to the algorithm, but they don't work with the data frame or rows and column structure. They first convert a data to that, and they are going to use that, right? So till now, whatever data we have used, all of the data was in the form of vector and matrices. Till now, we have not touched the tensor. Correct. Till now, whatever data we have worked with, that was either a vector we were working with or a matrix we were working with. Most of the time, we have been working with matrix. Okay. Now, tensor is what? Tensor is a array representation of images, videos, signal, that kind of thing. So we have not worked on image data, video data, audio data. So tensors, we have not dealt with that for now. Tensor you are going to deal with in deep learning concept. After machine learning, the advanced part of machine learning that you will study, there you will be dealing with tensors. We have not studied about tensors at all till now. Most of the time, we have been dealing with vectors and matrices. Basically, all of the data that we have been using were kind of vectors and matrices. Let me explain. So let's say I have a customer whose CIBIL score is, let's say, 700 and their income is 75,000 per month. Okay, a person is there whose CIBIL score is 700 and income is 75,000, and they applied for a loan and their loan was approved, right? Now see, in this case, 700 and 75,000, these are both scalars. This is a scalar, this is a scalar, correct? 775,000, these single individually, they are scalars. But if you take them together and if you put them as a list, or if you put them as a one dimension array, 700 comma 75,000, if you put them like that, 700 comma 75,000, so it is going to be called as a vector. Okay, now you are going to call it as a vector. So what is a vector for us? Vector is nothing but every single row that we have been using till now. Every single row is a vector. Correct. Till now we have been using that, but some of you knew, some of you did not know that all of the rows are vector for us. Correct. First row, second row, third row. So if I have 10,000 rows in my data set, I have 10,000 vectors. Correct. And these are called as row vectors because see, I have made a vector out of row values. So these are called as row vectors. Row vector. Correct. Yes. Now see that in the case of vectors, we have a column vector also. Column vector. So what is a column vector? You see, the output column that we use generally in the form of column vector. We make a variable y, right? And in the variable y, we provide the output column. So output column that we provide we are providing the output column basically in the form of a column vector. So this is our column vector, and the rows that we use, these are row vectors. Now, if I show you an Excel file, let's say I open the data set for heart disease related data set. Correct. So this is our heart disease data set. Now, from here to here, from this to this, we have our input columns, and target is our output column. Target column is our output column. So target column, we are going to treat it as a column vector. And this is going to be stored into y variable. Correct? But every single row that you see in the input columns, this is going to be called as a row vector. This is a row vector. This is a row vector. Every single row is a row vector for us, is a vector for us. Now, if I take two values in a vector, it's called as a 2D vector. If I take three values in a vector, it is called as a 3D vector. If I use four values in a vector, it is called as a 4D vector. Correct. So the number of values which are there in a vector, that much is the dimension of that vector. How? Let me show that to you. See, so in the case of this data set, I have taken two input columns. You see CIBIL score and the income, right? For now, I have taken two input columns, CIBIL score and income. So basically this vector has two values, and this is going to be called as a two-dimension vector or two-dimension data set that we have been saying till now. But it is basically a two-dimension vector, which gives us a two-dimension graph. How? Let me show. So let's say this is a dot representing our first row or first vector, this dot. Then I have second row. So there will be a dot for that. There is a third row. There will be a dot for that. There's a fourth row. There will be a dot for that. Fifth row, sixth row, seventh row, eighth row. Every dot that you see is a vector which has two values. Okay. So now if I take one of these points for now. So here, let's say this point is representing our first row. What is the value here? 700 for CIBIL score and 75,000 for income. So first I have x-axis. So I'll be representing x-axis value first, 75,000 and 700. This is the value. Correct. So now this dot is a vector for us, or you can call it as a 2D vector for us. Correct. Single dot is a 2D vector. And when I'm representing a 2D vector as a graph, it will make a 2D graph that you're seeing here. X-axis and y-axis you have. So 2 dimensions are there, 2 axes is there. It's a 2D graph because we are using a 2D vector. Now, what if I take a third column also? What if instead of these, I take a third column, let's say age of the customer, CIBIL score of the customer, income of the customer, and age of the customer. Now, let's say for the first person, the person who has a CIBIL score of this much and income of this much, their age is, let's say, 28. And this is my first customer. So now this vector has how many values? 3 values. And now this will be called as a 3D vector. And when I represent a 3D vector, it will make a 3D graph for us. Why it will make a 3D graph for us? You see that. So now I have a point here. Now, to this point, I can give its income value and CIBIL score value, but how do I represent its age value? So for age, I have to make another axis here. And this is our z-axis, and this is age, which I'm representing here. So now for this person, its income value 75,000, CIBIL score value 700, and age 28. You see, now this point will be represented by 3 values, and it is now nothing but a 3D vector. Now, when I'm representing a 3D vector as a graph, so now it will be making a 3D graph. Why? Because you see that its X value, income value, its Y value, CIBIL score value, and its Z value, which is its age value. So I have to make a 90-degree line here. So that is why we are making a 90-degree angle line. Right. Now, like this dot, there will be other dots also. And each of these dots are 3D vectors, each of these dots. And that is why what overall the graph that is going to be created to show 3D vectors, to visualize 3D vectors, that is a 3D graph for us. Correct. Now, we cannot see anything more than 3 dimension. Maximum we can visualize in the real world possibly is 3D. So very similar to that, there will be another axis created, and you will have 4D vector, 5D vector, 6D vector, 7D vector. Correct. So here I am taking 3 values. I'm just going to take 4 value, 5 value, 6 value, 7, 8, 9, 10. Whatever number of input columns are there, that many number of values will be there in a vector. Right. You can see here that I have 3 columns. So 3 input columns are there. That is why a vector has 3 values. If I would take 10 columns, the vector will have 10 values and it will be 10-dimension vector. And to represent a 10-dimension vector, we will have a 10-dimension graph. No, that is what I'm saying. Above 3 dimension, we can never visualize anything. So how do we work on data which we cannot visualize? See, so the thing is, this concept called as linear algebra. Right. See, linear algebra that you see here, linear algebra is such a beautiful and such a powerful concept that says that you can visualize the data till 3 dimension only. Means if you want to see how the data looks like visually, you can see till only 3 dimension. But above 3 dimension, if you want to work with the data, you want to make a best fit line in a 10 dimension, if you want to make a sigmoid curve in 100 dimension. So you cannot see that, but linear algebra says that leave it to me. I will be able to make that best fit line in 100 dimension or a sigmoid curve in 500 dimension. It can do that. Correct. So linear algebra is capable of representing the data in higher dimension, and it can make the machine learning model for us, but we cannot see what it is doing. It just gives us a formula, which is the final machine learning model, we call it. So in the case of decision tree, there is a tree and those decision boundaries. So it gives us that. It makes all those connections and relationships in a higher dimension, but we cannot visualize anything above 3 dimension. Mathematically, it can be drawn, or you can use a mathematical equation to see that relationship in the data, but you cannot visualize that as a graph. Mathematically, we can visualize that. So why I was trying to explain this thing to you, because it is a very important concept. And you see that we deal with vectors when we are dealing with a data set. Now, one another interesting thing is every row will be a 3D vector for now, every single row. And every single dot that will be created will be representing a row, which means that all these dots are 3D vectors for us, every single data point. Now, the interesting part here is if I take a collection of all these vectors into one. What this becomes? If I have 5 vectors, I have 6 vector here, 6 rows I have taken, 6 vectors are there. For those 6 vector, a single data point will be created. But a collection of vector is called as what? It is called as a matrix. Okay, it is called as a matrix. So matrix is always a collection of vectors taken from the data set. So when you provide this kind of data to machine learning algorithm, when you say to the algorithm that I will be creating this X variable, which will store all the input columns. So in this X variable, what you store? Age, civil score, income. Input columns you store. But what machine learning does? Machine learning takes your input columns, convert them into matrix first, and then it will be working with that. So even though I'm providing columns and rows and data frames, it will take that, convert to matrix in the background, then it will be working with that, and it will giving you those equations of the ML model that we have been using. Right. Now, so that is how you can understand when we take a certain number of input column, then that is the dimension of the data always. Right. Now let's understand why we are talking about these dimensions. If I have just a single input column and a single output column will be single, but let's say I have one input column and one input column and output column. Now, if I have to predict the price of a house with just one feature of the house, which is area, how much accurate we will be in predicting the price of the house. So we can say that I just have one feature about the house. So predicting the price of the house just with the area of the house will be very difficult for us. And we will be very inaccurate in that, right? Very, very inaccurate. Because one feature has only a certain amount of contribution in the final price of the house. Correct. It can be a very important feature, but still it has only a certain amount of contribution or effect in the final price of the house or in the final output. So with a single column, we cannot do a very good task in predicting the price of the house. So we say that, what if I increase the column? What if I take the second input column, which is the number of floors in the house? Right? Number of floors in a house. So now the thing is that if I have two input columns, so I'll be able to predict the price of the house better compared to one input column. If I take three input column, let's say number of rooms, how many rooms are there? So I will be able to predict the price of the house even better with three input columns. Then if I go and if I see age, I take the fourth input column. So age will be, if I take four input columns now, it will be helping us to predict the price of the house even better. Correct. So what I'm trying to explain to you is, now see here, if I have four input columns, so for four input columns, we'll be predicting the price of the house much better compared to one input column or two input column or three input column. Correct. So the idea is that when I have more and more input column, so our accuracy of predicting the output increases as much as we take the input column, right? We go on increasing our accuracy, or the performance of our ML model improves as I take more and more input column. But there's a problem that happens if you do that. And that problem is called as curse of dimensionality. Okay, that problem is known as curse of dimensionality. What is this curse of dimensionality? Correct. See, what is this curse of dimensionality? Curse of dimensionality says that, everyone please focus here, very important. Curse of dimensionality says that when you increase the number of input column, so along with that, accuracy of your model also improves. If you increase your input column again, so accuracy of your model will improve again. So you are increasing the number of input column, and with that, the accuracy of your model is also improving. But there comes a certain point after which, if you increase the input column more, then what will you see? You will see that your accuracy is decreasing, not increasing with that, with the increase in number of input column. But what is the reason for that? So the curse of dimensionality says that you should be definitely taking more and more input column, but till a certain point. You should not just keep taking more and more input column blindly. You just take the input columns which are actually important for you, or till a certain amount, you should collect a number of input columns. But after that, you should not take more and more input columns because it will be harmful for your model. But why? To understand that, we'll see a simple reason why this happens. Why after a certain point, if I increase the input column more, the accuracy decreases. What is the reason for that? Let's say if I have 5 input columns I have taken in a data set and I'm making a model with that. I am just working with 5 input columns. Since I'm working with 5 input columns, so definitely I would have collected 5 important input columns because the number of input columns are very less. So whatever input column I would have collected from somewhere, that all the 5 input columns would be important 5 input columns. Now let's say I increase it to 10 input columns. So 10 input columns are also such that if I'm increasing the input column, 10 input columns are also the number of columns that I would have been very careful. And these 10 input columns are important. All the columns would be important in this 10 input columns. But let's say I now kept collecting more and more input column, and now I have 50 columns, 50 input columns. So will there be chances of some unimportant columns that I would have collected in this? Since I'm collecting more and more and more input column, and now I have 50 input column. So is there chances that if I'm taking 50 input columns, so I would have collected 1 or 2 unnecessary columns because I was just focused on collecting more and more columns. So it can definitely happen that if I'm taking 50 input columns, some of my columns would be unimportant. Possible, right? I'm not saying that it will always happen, but the possibility is very high. Same way, if I, let's say, go to 100 columns, if I go to 100 columns, so now the chances of taking more, if I'm talking about 100 input columns, so the chances of lot of unnecessary columns will be even higher in this case. So this is the situation which causes the curse of dimensionality. The curse of dimensionality says that till a certain point, you would be collecting good input columns. Correct? Till a certain point, till a certain number of columns, you would be collecting good input columns. But after that point, since you are focused on collecting more and more input columns somehow, so you would end up collecting some of the unnecessary columns. Okay. And if I have a data set which has 300 columns, 700 columns, 1000 columns, so the more is the number of input column, the more is the chances of unnecessary columns in that. So if I have 700 input columns, so it can happen that 100 of the input columns are unnecessary or very, very less important. If I remove that also, there will be no problem with me in the model. Correct. Now, what kind of problem will come up when we collect these kind of things? But let me explain few more things. What kind of problem we are going to see here? What kind of issues can come if I take more and more input column? So when you have too many input column, then there are high chances that some or many of these columns are unnecessary. Because of this, we start to see overfitting in the data set. The first problem that start to come up because of lot of unnecessary columns is overfitting issue. Why overfitting happens? You see, let's say if I am taking 100 columns, okay, in this 100 column, we have 70 columns which are important for us. 30 columns are there which are either very less important or totally unnecessary. They have nothing to do with our machine learning model. They are either very, very less important or they are totally unnecessary. Now, the problem that will happen because of these 30 columns is that machine learning will think that if you have provided these columns to the algorithm, right? You see, if you have provided these 30 columns to the algorithm, it will unnecessarily try to use this into the final model. Correct. So whether it is making a best fit line equation or if it is making a decision tree. So those algorithms will do what? They will try to use these 30 columns also in the final model. But the thing is that they should not have been used. These are totally unnecessary. They have nothing to do with the output column. They are not helping me to predict the output column. But since you have given these 30 unnecessary columns to the algorithm, it will try to use that in the final model making process. So don't you think that if 30 different columns are used in your final ML model, in your best fit equation or in your final decision tree, that will cause a lot of problem or that will cause a lot of output to become wrong because of these 30 columns involved in the machine learning prediction? Obvious, right? It is very obvious that if I'm using this 30 unnecessary columns in my final ML model, so definitely the predictions made by the ML model will become wrong. A lot of predictions will become wrong. And this is the situation which will cause overfitting, right? So our machine learning model is trying to forcefully create a lot of connections with those columns in the machine learning model. And this is called as overlearning or overfitting in the data set. Correct. And this problem is what we refer to as a curse of dimensionality. Dimensionality means what? The number of input columns. So the curse of dimensionality says that till a certain point, the number of input columns are good. But after a certain point, the chances of having a lot of unnecessary columns increases. And because of that, we will have a curse of dimensionality. Now, see, the second issue that comes into picture, one, overfitting comes into picture. And the second issue that comes into picture is multicollinearity. So when I'm taking more and more input column, there are very high chances of multicollinearity in the data. Very, very high chances of that. Correct. So why multicollinearity chances increases in a high dimension data? See, if let's say I have a data set of house price prediction, and in the house price prediction, I'm taking a lot of input column. Now there is one column which is called as area of the house. And then there are these two columns, which is length of the house and width of the house. Now, the thing is, when you do this length into width, you get the area of the house with length and width. So this column and these two columns are exactly same, right? These are telling the exact same thing about the data set. And why this happened? This issue is called as multicollinearity. When there is a very high correlation between input columns, this is called as multicollinearity. And you should have very, very less correlation between input columns. See, input columns are called as independent variables. Correct. Input columns are called as independent variables because all the input columns are supposed to be unique, right? Then only they will be bringing unique features into your data set and the algorithm. If the input columns are dependent upon each other, then multiple input columns are telling the same thing. And that is a bad thing for us. Why would you take two input columns which are telling us the same thing? No reason. Correct. It is not going to help in that. It is just going to take unnecessary computational power to process these things. Now, so the thing is that when I'm taking more and more input columns, the chances are there that I would collect some input columns which are very highly correlated to each other. And this will cause a problem of multicollinearity, which is nothing but high correlation between input columns. So two main problems happen. Overfitting start to come up when we have too many dimensions, and multicollinearity comes into picture when we have too many dimensions. See, so till now we have understood few things. Now let's see a few more examples of that. So let's say we have a data set of 200 column, right? I have a data set of 200 columns, suppose. Now in this 200 columns, we use some formulas and some concept, and we found out that 28 columns are unnecessary in these 200 columns. For example, right? For example, if I have a data set of 200 column, it is a 200 dimension data. Now, in this data set, let's say we found out when we were studying the data, we found out that 28 columns are unnecessary for us, right? Now, if I get these 28 columns are totally unnecessary, I can delete them, right? I can go ahead and delete them. Now remaining, we are left with 172 columns. 28 we found unnecessary, we deleted that. So 200 minus 28, that gone, now left with 172. Now 172 columns which are remaining to us, in these 172 we found out that 56 columns are very less important. Means they are not unnecessary, they have some importance, but their importance is very less. Now, one thing you can do is you can delete these also. And 172 minus 56, you can do that also. And whatever is left, we are going to work on that. You can say that. But see, individually, these 56 columns individually might not be very important or are having very less important. But can we say that 56 columns combined together definitely would have some important features stored in that? or definitely would have been helpful in predicting the output if I talk about 56 combined. Individually, they might be very weak. But if I take weak features also, and if I combine multiple of them, so that will be powerful, or that would have some important details hidden into that, which might help us to do the prediction. That is the thing here. So think of it like if I have one thin stick, I can break it easily. It's very thin, it's very weak. But if I stack multiple thin sticks together, and now you have 56 thin sticks together, you won't be able to break it. Now they are strong and they are capable of doing something. They are now strong. Correct. So same thing I'm trying to explain here, that if I talk about, let's say in 172 remaining columns, 56 columns I'm left with. Individually, 56 columns I found are very less important individually. But together, if I'm able to use them together, they would give us some very important information, or they would definitely help us in predicting the output if I'm able to use them together. Now, how can I use them together? Right. So one thing is I can delete these 56 columns because they were individually very less important. I can delete them. But now I have a solution here. The solution is if we have some method which can reduce the number of input column in a smarter way. So rather than deleting 56 columns, you see, rather than deleting 56 columns, we are saying that if I have a smarter method of reducing the number of input column, then that would be a very good solution. Correct. Again, if we have some method which can reduce the number of input column in a smarter way, rather than deleting them, that would be a good solution for us. Correct. Because instead of deleting this 56 column, I'm saying that we will try to utilize them in some way, not individually, but some way, which I'm going to explain to you. But I'm saying that if some way I'm able to use these 56 columns, then that will be helpful for us instead of deleting them. That is what a solution that we are going to see now. And this is where the concept of dimensionality reduction technique comes into picture. So there is a concept of dimensionality reduction. Dimensionality means number of input columns. Reduction means reduce the number of columns. So one simple method, keep in mind, one simple method of reducing the number of columns is to delete that. Simple. But second method, which is called as dimensionality reduction, what we are going to do, we are going to combine multiple into one. Okay. Dimensionality reduction technique says that if there are two columns which are less important, let's say column 1 and column 2, don't use them individually, combine them and create a new column. Okay. Take column 1, take column 2, combine the data of column 1 and column 2, make a new column, and this column will be better than in using them individually. This is the concept of dimensionality reduction. That is what we are going to study. So what we were able to do with this, we were able to reduce the number of columns. 2 were there, and we were able to reduce it to 1. And this one column that you have here, you see, this one column that you have here is more powerful than those two. So we are able to do two things. We are able to reduce the number of column also, but in such a way that the new column that is getting created is more powerful than the one we have deleted. Correct. So this is the concept of dimensionality reduction that we are talking about. Okay. No, deletion is deletion. Deletion is not reduction. That is what I'm explaining. So one method of reduction is called as deletion. That is not proper reduction. That is not dimensionality reduction. So here I'm just randomly deleting them, means totally deleting them, directly deleting them, right? I'm not trying to use them into my model. But these ones I'm saying, these 56 columns, I'm not deleting them. I'm going to combine them into one. Now let us understand what is this dimensionality reduction, and in a few minutes you will understand what I'm trying to say. So if I have to do dimensionality reduction, keep in mind whenever I say this thing, dimensionality reduction, that we are taking multiple columns and we are combining to create new column. This technique says that we are going to take multiple columns and we are going to combine them into one. Somehow, how we will combine, I'm going to explain everything. But somehow we are going to combine them together and we will create new columns with those columns. Okay. And then as I have created this new column, I'll be then deleting these columns and I'm going to use this one, because this one has the information of these two stored in that. So now we have a single column instead of two, and this is more powerful than C1 and C2. So this is obviously a very smart approach, or this is obviously better than deleting the columns. So I'm able to reduce the number of column also, but in such a smarter way that when I'm reducing the number of column, I'm creating new columns which are more powerful. So less columns, but powerful columns compared to more and weak. See, so there are two dimensionality reduction techniques available in the field of data science. One is called as PCA, Principal Component Analysis, and second is called as LDA, Linear Discriminant Analysis. This one we will be studying today, and this one we will be studying tomorrow. Okay, see, PCA can be applied on all type of data. PCA can be applied on regression data, classification data, unsupervised data, any type of data you can apply it, because its main task is to reduce the number of columns by combining multiple into one. So it can be applied on any type of data. Now, this PCA is called as an unsupervised method. This PCA is called as unsupervised method. Now, why is it called as an unsupervised method? It says that if I have to reduce the number of input column, I don't have to use the output column for that. Let's say I am given C1 and C5. These two columns are there, and I have to reduce these two columns to make one column. Correct? Two columns are there for now, and I want to reduce that. So it says that if I want to reduce the number of input column, I don't have to use the output column for that. Right? I will not be even looking at the output column because there is no output. There is no need of output column for me. I will just be combining them. Let's say I add them, and I will be able to create a new column. Right? New column 1, I can call it. Correct? So since this PCA is not using the output column for this kind of reduction task, that is why it is known as a unsupervised method. And if it would be using that output column for that task, then it will be called as a supervised method. This LDA technique that we are going to study, it's a supervised method, because for data reduction, it will be using the output column also. So this is a supervised related task, and PCA is a unsupervised method or unsupervised task. Correct. But how it will do that? Don't worry. Okay. The LDA is a method which will be applied only on classification data, and PCA will be applied on all type of data. If PCA can be applied on all type of data, regression, classification, all, so why we have LDA, which is specially used for classification? It is only applied on classification, no other type of data. So if I already have PCA, which can work on classification data, then why do we have LDA? Principal component analysis. The main working of PCA we are going to understand from here. Till now, I was just explaining to all of you that what is this concept and why we are worrying about this concept. So there was a problem called as curse of dimensionality. I was trying to explain this thing to you as of now. That the curse of dimensionality says that if you increase the number of input column further from a certain point, then it causes a problem instead of helping us. So we should be taking more input column, but not too much. Okay. So more higher dimension data is better for us, but it should not be too much dimensions. That is going to cause a problem. So this is called as a curse of dimensionality, or a problem of dimensionality that we are going to face. Okay. Now let's see. So how is this principal component analysis work? We understood what it is going to do. It is going to combine multiple column into one, but how? PCA help us to reduce the dimension of the data, or PCA help us to reduce the number of input column in such a way that we lose very little information while reducing the number of column. If I have 56 columns, which are less important individually. Now, if I delete all these 56 columns, so individually they had very less information in them, but 56 column together might have a lot of important information together. So if I'm taking a decision to delete them, then I lose a lot of information, loss of data will be there. But if I'm saying that instead of deleting this 56 column, I'm going to combine them into 2-3 new columns. Correct. So that way, I will not be losing that much information that I will lose if I delete them. Right. So that is the thing, that is the benefit of using PCA, that we are able to reduce the number of column also, but in such a way that we are retaining the information. We are keeping the information. We are not losing the information while doing that. Let's say I have a column 1, let's say column 5 and column 7. So I'm combining the data of column 1 with column 5 plus 2 into column 7. And this is going to create a new column for us. Let's call it new column 1. Now, when I'm going to combine multiple columns into one, so I have to combine them into such a way that you do a linear combination of multiple columns. Linear combination means you add them, you subtract them. You can't multiply, you can't divide, you can't square them. You always have to combine them in such a way that it's a linear combination. And linear combination means you subtract multiple columns, you add multiple columns. Some of them you subtract, some of them you add, but you have to do only subtraction and addition. You can't do multiplication, division, squaring, anything like that. Correct? So we have to do linear combination of that. Now, I can do this. I can say that 3.5 into C1 means take the values of the column 1, multiply every value of column 1 with 3.5, every single value. Then add those values with the value of column 5. Then add those values with the 2 into column 7 values. So you can multiply a column with a number. This is not a problem, but you should not do that. That C1 into C5 into C7, this kind of thing you can't do. A feature you can multiply, you can scale a column with some number. Correct. So when you are adding them, you are going to get a new column 1. Now, the benefit is that I can now delete these columns. I can say that I am not going to use this 3 column. Instead of those 3 columns, I am going to use this one single column. So 1 instead of 3. But the way it is created, I have the information passed on from these 3 columns into 1 column. So even though I'm saying that I will not be using those columns, but I'm not losing that information. I already have extracted the information from those 3 columns and saved into new column. So this new column is single compared to 3 columns. So 1 column I'm using, but it is powerful because it has the information taken from, extracted from all these 3 columns. But what will be a problem with this? It is a very good, or it is a very powerful concept. If I'm, and you can see use 1 column instead of 3, definitely it is very powerful. But there is one problem when I'm trying to do that. What is a problem that you think will happen? There will be one drawback of doing that. See, something comes to your mind. What can be the drawback here? Okay, another kind of very simple problem will happen. No, column C, we don't have to choose the columns. See here, we'll get high score for each card in the column. No, you see, the problem that will happen is, correct. Let's say this C5 was number of rooms. Okay, this C7 was number of floors in a house, and this C1 was the age of the house. So C1 is the age of the house, column 5 is number of floors in a house, and C7 is number of rooms in a house. Now, individually, was I able to understand what kind of data is there in column 1? Yes, I was. If I was looking at the column 1, it is the age of the house. So when I look at the values of the column 1, I was able to understand that this column is talking about age of the house. If I'm looking at this, so I would be able to understand this column is talking about number of floors of a house. And if I look at this column, I would be able to say that this is talking about number of rooms. But if you're combining the data of these 3 and making one, would you understand what is this data talking about? Would you be able to interpret this new feature that we have created? No, right? No, because it is a combination of age of the house plus number of floors plus number of rooms. So this column does not make sense to us, right? So then whatever model is going to be created, I won't be able to interpret that. It will be working very fine. It will be doing all the predictions very fine. It will be a usable feature. But only the thing is, I won't be able to tell what is this column about. I won't be able to interpret that. So that is the biggest drawback with PCA, that it does solve a problem, but it creates another problem for us, that after using PCA, all the new columns which will be created will not be interpretable to us, because those are combination of multiple columns into one. Okay. Now see, so let's say I have these 100 input columns. Correct. You see, if I have 100 input columns, in this 100 input column, if I was giving these 100 original input column to decision tree, it was causing overfitting issue, let's say. So I said that instead of using original 100 input column, and instead of using that to a decision tree, that with a decision tree, I'm saying that let's transform our data. Let's transform our existing input column using what? Using PCA algorithm. Now, when you give the data, when you give your existing input column to PCA, it is going to transform that and it will create new input columns using the existing columns, or combining multiple existing columns, it will create new columns. And all those columns are going to be called as principal components. So first new input column will be called as principal component 1, principal component 2, principal component 3. So each principal component is a combination of multiple existing columns. And how the input columns have been combined to make PC1, you won't be able to tell that, or you won't be able to find out which columns have been combined to create PCA. That you won't be able to find out, because the columns are combined in a very complex manner and we have no idea how they are being combined. That is totally a task of algorithm. But you see that the new input columns that are going to be created, the benefit is that those will be powerful and less than the number of actual columns. But the problem is, the only big problem is that I won't be able to understand what these new columns mean. So I can just use this with the algorithm and I will be able to do everything. Just that I won't be able to understand which column is what. That I have these 100 existing columns, which I'm giving to PCA. PCA says that let's combine multiple columns into one, and it will create new columns using existing 100 columns. Now we will say that we will not be using these, because now we have created new input columns. Let's say we have now created 28 new columns using 100 existing columns, because we combined multiple into one. So these new 28 columns will be called as principal component 1 to principal component 28. These new input columns will be used and it will be provided to the decision tree. I will not be using them. Okay, I will not be using them. Correct. See, but when we are doing this transformation, PCA gives us a very good power to us to control something in this entire process. Okay, so till now see, when PCA does this, when PCA transform your existing column into new columns, and we are saying that we will not be using them now, we will be just using this new input columns. When we are transforming the data into new input column, PCA gives us a power to control something in this process. In this transformation process from old to new columns, in this transformation process, PCA gives us a power, or it gives us an ability to control something in this. What it gives us to control. Now think about it. If you're combining multiple existing columns into one to create new columns, would you be able to extract all the information into new column? If I'm saying that I'm combining column 1 plus column 5 and I got a new column. So will I be able to transfer 100% information to new column? Of course not, right? So I can transfer like 99% information, 97% information, but I can never extract 100% information from those two columns and put it into new column. But we don't have to extract 100%. If I'm able to extract 95% information also from these two, more than enough. It is too good. So that is the thing, that we won't be able to extract all the information. Some information will be lost during transformation, but it is very less that it does not matter much to us. Now, in this process, the PCA gives us a power to control this thing, that if you are combining the existing columns to make new columns, how much information you want to keep in this process, that power also I have. Let me explain. Now, let's say I have the existing data and this data has 100 columns. So imagine that you are in an old house and you have a very big box, a carton kind of thing. You have a very big box in which you have been putting a lot of items into that, and you have been living in this old house. Now, you have been living in this house for, let's say, 2 years, 3 years, and you have collected a lot of items in this box. Whatever you thought was important, you kept in this box. Now you have to move into a new house. Okay. And the new house is very new, very clean, new painted, and everything is all new. Now you want that I have to take this entire box into new house. Correct. This box we have to take to new house because a lot of items I have put here. So you are saying that if I take this entire box into new house, it will take a lot of area in one corner, and I don't want to take that much area to keep this box. Okay, I want that there should be a small box and it should be kept somewhere that it does not bother us. So you are saying that instead of taking all the items, from this box into new house, we will take a small one. Okay, we will take a small box. So let's say instead of that big box, I took a small box. Now, since you have a small box compared to this box, would you be able to transfer all the items into that? No, you won't be. So, but I'm saying that I am okay losing 5% of the products or 5% of the items. I will either throw it away or I will sell it somewhere. The 95% important items which are there, I'll be only transferring that. Correct. So in this box, there were some very big boxes, or there were some like teddy bears which were very big. And I'm saying that there were some items which were taking too much space. So I will sell those big items, and all the small important items which are there, I'll be transferring that into new small box. So I'm transferring 95% important items into this new box. So it is small and it is having almost all the items, just 5% of the items. I have to throw it away or I had to sell it. Now, if I take even smaller box, instead of this box, if I take an even smaller box, now in this, I can, let's say, transfer 85% in important items and I'm throwing away 15% items. And I'm saying I'll just transfer 85% of our important items or important products into that. So this exact thing happens in PC also. PCS says that if you have your existing data, in your existing data, there are 100 columns and those 100 columns has 100% information for now. That is your data set. Now, when you are combining these 100 columns into new columns, you're combining them to make new columns. So it can happen that since you want to transfer 100% information, you can't, but let's assume that you are saying that if you want to transfer 100% information into new columns, so let's say we have to make 82 new columns to keep 100% information or to transfer 100% information from existing to new. Let's say we need 82 columns. So were we able to do proper reduction that we wanted? So I can say, yes, 18 columns we were able to reduce, but not much, right? It is not that much beneficial for us if I'm saying that all the 100% of the information I want to keep. So if you want to transfer all the 100% information from your existing data to new data, you will need more columns to store that much of information. Correct. So a lot of pain, but little gain. Correct. Perfect. So what I'm saying that is if I reduce this information, if I say that, no, I just want to keep 95% information. So when I'm combining the columns, I'm okay losing 5% information. I'm okay. No problem with that. 5% if I lot, no problem. Still, I'm able to extract 95% important information. The benefit of that will be instead of 82 new columns, you'll just need, let's say, 54 columns. A drastic reduction will happen if you are saying that I am okay losing some information and I want to keep, let's say, only 95%. A reduction. So you now reduce from 100 column to 54 column. That is now obviously beneficial. Then you say that I will keep only 90% information, 10% I'm okay to lose. So now you will be able to store everything in just 31 new columns. So you see, when I'm saying that I want to retain a certain amount of information, that many, or on the basis of that, the number of new input columns will be decided. So the more the information you want to retain, the more the columns will be required. The more the new columns will be required to store that much of information. The lesser and lesser as you go, and lesser the number of new columns will be required to keep that much information. Now, one thing to keep in mind here, when I'm saying 95% information I want to keep, it does not mean that our accuracy will also be 95%. Or when I'm saying I just want to extract 90% information, it is not that our accuracy will also be 90%. So it can happen that you are extracting just 80% information from old to new, still your accuracy is 93%. Okay, so this has nothing to do, or this is not directly telling you what will be your accuracy. It depends upon if you are keeping 80% information, was it most important 80% information or not? Correct. So this is the thing we have to decide. Now the question is, how do I decide this percentage? Should I use 99%, 95%, 90%, 85%, 80%? How do I decide that percentage? I'll be explaining that to you with the practical. But this is a power which PCA gives us to control the amount of information you want to retain when you're doing this transformation. Depending upon how much information you want to keep or you want to retain, the number of new principal components will be decided on the basis of that. You see now, let's say I decided to retain 95% information, let's say. So from 100 input columns to retain 95% information, 28 principal components were created, for example. So these are known as PC1 to PC28, and these are our new input columns, which are a combination of multiple existing columns. Correct. Every principal component has been created through combination of existing columns. Right. Now, there's a property here in this principal components. When these new input columns are created, they have a important property. The property is that your first principal component is the most powerful or the most important principal component. Correct. And as you go forward, the importance of these new input column decreases. They become weaker and weaker, right? They become weaker and weaker. So now that is the thing. We have multiple principal components. And when we talk about this principal component, the first one is most powerful. And as we go till the end, that is the least powerful. So they become weaker and weaker as we go from the start to the end. This is one of the most important property of this principal component. So let's talk about the mathematical working of PCA. Till now, whatever I've discussed, if you understood that much, that is enough to understand how PCA is working overall and what is PCA doing overall. But one last thing I have to show you is mathematical working of PCA. If I'm combining multiple columns into one, mathematically how that is being done. That if you have one input column in classification, you can represent it as a one-dimension data. If you have two input columns, you can represent it as a two-dimension. Three input column, three-dimension. That kind of thing we have, right? Now, let's take a look at this two-dimension data set. And what I'm going to do now, with PCA, I'm going to reduce this two-dimension data into one dimension. Let's work on that. So how to reduce the dimension using PCA? I'm taking an example of two-dimension data, which I'm going to reduce to one dimension. If you understood that, same way, a 10-dimension data can be converted to 9-dimension, 8-dimension, 7-dimension. Everything will work like that. Just we need to understand this example, how things are going to be done. So I'll take this example, 2D, and convert it to one dimension or transform it to one dimension. So this concept of PCA says that if you want to reduce the number of columns by combining them, you have to do it like that. It says, take the data, income, CIBIL score, you have two input column, and all these dots are your input data. Every dot is a vector, is a row. So you have your data points that you have plotted here. That's it. Now what you need to do, you need to reduce them so that this two dimension becomes one dimension. But how am I going to do that? The concept of PCA says that if you want to combine a 2D data, or if you want to combine the values of this column and this column together to make a new column, you have to do it like this mathematically. It says, make a new line. Okay, anywhere in the data, make a new line. Where we have to make, we'll see. But it says that make a line in the data. Anywhere, it can be here, it can be here, it can be here, it can be here. But we have to find out the best one. But we have to, let's say, create a line somewhere. Say I created a line here. Now this line is not our best fit line. This line is not a decision boundary, which is separating my data into two sections. It is not a best fit line. It is not a decision boundary. But what it is a new axis. It is a new axis. So this is our x-axis and this is our y-axis. So it is saying that when you combine the data of these two columns, when you combine them, so CIBIL score has CIBIL score of different customer and income column has income of different customer. When you combine the data of these two columns, after combining, you make a new column and this line is that new column. Okay. So this line is a representation of your new column or new principal component that we are going to create. So I'm saying that to transform the data to make this data 2D to 1D, first make a line. And that line is a new axis, correct? Axis like this is x-axis, y-axis, z-axis, those kind of things are there. So it's a new axis. What you do now, once you have created that new axis, then what you need to do is you need to make a mirror image of your data points, and you have to put this data point onto the line, correct? So what you do, you make a 90-degree line from your data point, take your data point, make a 90-degree line and touch this line. Wherever it touches that new axis, you have to make a mirror image of this data point here. But it says make a 90-degree line wherever it the line of dot touches this new axis, there you make an image of this dot. Okay, same way you have to do for all the data points. So you take this data point, it says take this next data point, make a 90-degree line here, touch this new axis, wherever it touches, there you have to make a image of this point on the line. Then same thing you need to do for this also, for this also, for this also, for this also, for this also. For each of the points, we have to do the same thing. Now, some of the points can overlap, no problem with that, no issue with that, it can overlap. So it can totally overlap. It will be rare that 2 points are overlapping at the same point. It will be rare, but if it is overlapping, no problem with that. Okay, so we have 1 point here, 1 point here, 1 point here, 1 point here, 1 here, 1 here, for this here, for this one here, and for this one here. For each of the existing data points, which are our green data points, so I made a mirror image of that onto the new axis, right? And as I made the mirror image of those on the new axis, then remove, delete all of these things. Now see, so I have total these many points, these many points. For each of the point, I have made a image or a mirror image on the line. How do I make a mirror image? Coming to that. But as I made the mirror image of the existing data points onto the line, then you can see that I have an axis on which I have the data points. So can I show it separately like this, individually, separate from that? Can I show it like that? Yes. So I can show the same data points as an individual graph like that, where we have one axis and we have all the mirror images of the data point that we created here, right? So when I did that, when I took a new axis in the data and when I made the mirror image of existing data points on that line, so what we got a new axis on which we have the transform version of a 2D data as a 1 dimension. So this data that you see here, it is a transform version of your existing green points. Your green points originally were in 2 dimension, but now you did a process and after that you have your green points on this line, which is a transform version of that, and this is 1 dimension. So from 2 dimension, you got a data into 1 dimension. But the question is now, how did you make a mirror image of those dot on the line? How do I make a mirror image? Mirror image is nothing but, right? You see, mirror image is also called as projection. When I'm making a mirror image of a dot on the line, it is also called as projection. I'm projecting a data point onto a line or onto a new axis. It's called a projection. So projection of data points onto the new axis is nothing but linear combination of existing columns or existing data points. So what we are doing now, here each data point was representing the income of a person, let's say 25K, or it is higher. Let's say income of a person is 45,000 INR, Indian rupee, and CIBIL score is, let's say, 800. Okay, credit score is 800, credit score, right? Now, what I'm doing now, I'm combining these two values to make a new value. So as of now, this dot is being represented by the income of the person and credit score of the person, two individual values. Correct. So it's a 2D vector for now. But now I'm going to combine them into one. Means in simplified sense, you can say that we are adding them. So 45,000 plus 800, 45,800, let's say. So when I combine these two values, then what happens? The combination of these two values is going to make a mirror image of that data point onto the line. So mirror image or projection of the data point is nothing but a combination, a linear combination of the existing data points together. Correct. So this is how we are going to make a projection. And as I have projected, as I made the mirror image of the data points onto the line, then I can represent it individually. So here your green points were in 2D. Here your actual data points, your green points are in 1 dimension. Correct. So mathematically, this is how the combination of two columns is being done to make a new column. Correct. But what is one difficulty here? This is the entire mathematical process that you have to know, but there is just one small problem. Small. What do you think is a small issue in this entire process? So we just have to make a line which is a new axis, and then we have to make a mirror image of those points onto the line. Done. That's it. But small problem. What is that problem? What do you think? We can't interpret the data, this new data that is created, that we already seen. So the problem here is that, like in the linear regression, we had to try multiple lines to find the best fit line. What we were talking about in linear regression, we saw that if I have some data points like that, so a line can be like this also, line can be like this also, line can be like this also. So there can be multiple possible lines passing through the data. What we have to find out? The best line, and that is our best fit line. Correct. So on a data set, there can be multiple lines possible. We have to find out the best line, which is having the least error, or which is closest to all the data points. This is what we were talking about in linear regression. Same way, I also have to find out what, right? In the same way, we have to find out this new axis. So this new axis should be here, it should be here, it should be here, it should be here. Where it should be, that we have to find out. Correct. Because if I don't find out the best new axis, then the combination of the column will be bad. Right. So if I want to combine two columns most efficiently, then I have to find out the new axis, which is the best one for us. So like the concept of best fit line, we have a concept of best axis also. So axis should be here, or it should be here, or it should be here. If you change the axis, the way the transformation is done is also going to change. Okay. And the best axis is the one axis where the transformation will be most efficient. Means when you're transforming two columns into one, so you will be able to keep, or you will be able to retain most information if you find the best axis to do the transformation. So the process of this PCA is just that much. The mathematical process of PCA is just that much. Make a new axis, make a projection of those data points onto the line. Correct. But the problem is, one slight problem, small problem is that where this new axis is, how do I know? We don't know that. So we need to talk about how do we find out the best new axis? Because once we found out the best new axis, I just have to project the data points onto that, or I have to make a mirror image of the data points onto that. That's it. Correct. So that is the last thing in this we are going to talk about. How to find the proper new axis. This will be our last thing. Let us have a look at how we are going to find out the best new axis. Because you see now, I have a new data set here. I have an example here. Let's say I am taking some data points, and I have 6 data points, 3 here, 3 here. 6 data points are there in total. Now, when I have these 6 data points, then what I need to do, I need to find out that the new axis which I'm going to make should be here, should be here, should be like this, should be like this, should be like this. Where exactly it should be? Okay, because there is a possibility of multiple lines. Correct. There is a possibility of multiple lines. Yes, that line is exactly going to give us the principal component. That new axis which I'm telling you, this is our principal component. Correct. So principal component 1, principal component 2 that we are going to make. So this line itself is our principal component. Because what you're doing, this line is a representation of two columns being combined. So this is our principal component, and that is what we have to find out. Correct. Now see, so we have 3 data points here. We have 3 data points here. And when you see the 6 data point, we need to find out our best new axis. Correct. See, so the concept of PCA says that if you want to find out the line, you start with this step first. First, it says find out the centroid of the data. Like we were doing in k-means, we are saying centroid. Okay, centroid of the data we have to find out. What is the centroid of the data? Centroid of the data is the center point of this group. So I have 6 data points, which I'm putting into one group. And what is the center of that? So center point is, suppose here, the average of all these data points is the center point here. Correct. How center point is decided? This dot should be at equidistant from all the points, average distance from all the points. So this is our centroid point. In the K-means algorithm, we have seen that we have to create a center point. But now I'm going to show you how that centroid point is created. So if you see that we have these 6 data points, and if I have to find out where the center of this 6 data points is there, how do we do that? So first we do it like this. You see, I have, or first let me talk about these 3 points. Focus on these 3 points. I told you that the center of these 3 points will be here in the middle. So if I have these 3 points, 1, 2, 3, the center of this will, or the centroid will be exactly in the center. But why did I say that? Why? First, mean is called as measure of central tendency. So when you calculate the mean of anything, it will automatically fall into the center. It's called as mean of measure of central tendency. But now let me tell you why we were putting that into the center. Simple reason. Let's say I have these 3 data points. To find out the centroid point of this cluster, we need to first take their x values. Okay, let's take x value of this, x value of this, and x value of this. Then y value of this, y value of this, and y value of this. Correct? Now, when I have the x value of these 3 data points, I'll be taking this x value, this x value, this x value, add them up, divide by 3. So when you add these x values and divide by 3, you will see that there will be a value somewhere here. There will be a value somewhere here in the middle of these 3 values, in the center. Correct? It will be average and it will be center of from here to here. Same way, if I take these y values, if I add this y value, this y value, and this y value, and divide by 3, this plus this plus this, divide by 3. So you'll find out that their average will fall somewhere here. Okay, in the middle of this point to this point, center. Now, what you have found out? You have found out the average x and average y for this cluster. For this group, you have found average x value, average y value. Now you just have to do this simple thing. You have to stretch this data point like this, and you have to stretch this data point like this. And wherever they meet, that is your centroid point. Correct? It is little wrong because I am roughly making it. But see, wherever this average of x and average of y meet, that is the point of your centroid. Correct? This is how the centroid is calculated. In any case, when you're calculating the centroid, this is how. So you take the x values of that group, y values of that group, average of x, average of y, wherever they meet, that is your centroid point. Now the same way, what we need to do, we need to find out the average of entire data here, not just group wise. So how much data points are there? 6 total. Okay. See, the 6 data points are there. 3 here, 6 data points I have. Now to find out the center of these, I will be taking the x value of all these 6 points and y value of all these 6 points. So x, this y and x, these are the average of x and average of y for the 6 data point. It is calculated like that. Take all these x values, take all these x values, and when you take the average of all these, they will fall into the center. So this is the average of x for these 6 data point. Same way, when you calculate the y values and when you take the average of all these y's, you'll find out that this is the average of y value of all these 6 points. Correct. So now I took the average of x, average of y, and these are your average points. Now wherever they meet, that will be the point of centroid. So if I take line like that, and if I touch it like that, this is the point where our centroid will. Again, it is roughly designed, roughly made, so it is not very accurate. But you get the point that you calculate the average of x, average of y, wherever they meet, that is your centroid point. Correct. Let's remove that. And I'm going to make it somewhere here because it seems like here it is the actual middle of the data. Now the question is, why am I calculating the centroid? I was trying to find a line, right? But why am I trying to calculate the centroid point? So the reason I am calculating the centroid point is this PCA says that if you want to find out your best axis, we are trying to find out best axis where it should be. So the PCA says that if you want to find out the best axis, what you need to do now, after making the centroid point, you have to make sure that whichever line we make, that should be passing through this centroid point. Okay. So one thing you are fixing now, that the that best axis will be there. It will be passing through this. Correct. It will not be going from here. It will not be going from here. It will not be going from here. It will not like that. So what we are doing now, we are structuring this process. We are making this process easy for us. So we are now saying that if I want to find out my best new axis, it will be passing through the centroid point. Correct. So at least we are making that entire process little short and efficient, because now I don't have to try these kind of lines which are going randomly anywhere. I don't have to try those lines. I now know that every line will be passing through the centroid point. So now I have to focus only on those lines. Correct. Okay, so this is one point. That is why I was trying to calculate the centroid, because our best axis will always be passing through this centroid point. Now, what we need to do before we find out our best line, it says that we have to move the data in such a way that its center is at origin. We are saying that in this data, before we find out our axis in this data, let's do a simple transformation here, or let's make this process more simplified. It says that do a process where you move this point here. Okay, do a process so that your centroid point moves to this point, which is a point of origin. This point is called as origin because here x value is also 0, y value is also 0. The entire middle of this graph, exact corner of this graph. This point is called as the origin point. Correct. So what we need to do now, we first calculated the centroid. Using this, we have to find out our best axis. But before we start the process of finding our best axis, it is saying that let's move the data in such a way that the centroid points moves at this point, which is called as origin point. Now, if you're moving this point here, if you're moving the centroid point here, then the remaining of the data point will also move. So this entire graph will move in this direction. So you see, if my centroid point moves from here to here, so these green points will also move into this place on the left side of the origin point. So I'm moving the data in such a way that the position of the data point will be maintained. Okay, the position of the data points according to the centroid point will be maintained. So whatever is the distance between these, see, this point and this point are at a certain distance. This point and this point are at a certain distance. So these will not change. Correct? These will not change. The distance of the data point from each other will stay same. How much away these data points are from the centroid point, that will also be maintained. Just I'm moving the data from here to here. Why we are doing that, you'll just understand in 1 minute. But we are saying that we are going to move the data point here. This process is called as mean centering or scaling. And see why this is done, because when you do the mean centering of the data or when you do the scaling of the data, your calculations become simple. Which calculation? We will see all of that. So this process of moving your centroid point to the origin and also all the points along with that. So these points will move here and these points will move somewhere here. So entire this data point will move. And after moving, it will look something like this. Your data points are going to look something like this. So I have the mean point here, you see. So earlier it was like that, right? Earlier it was here, your data point was like this. But now as I move the center point here, correct? So from here, the centroid point moved here. Same way, if I move the centroid point from here to here, so the 3 green points which were here, they also moved, correct? And whatever green points were here, they also moved here. So according to all the values, the data points will move so that the orientation of the data points will not change. The properties stored in the data will not change, only they are being moved from one place to another place. This process is called as scaling. So the benefit of this is some calculations will become simple, but you see that I'm not changing the properties of the data by doing that. This data point was the rightmost data point earlier also. It is the rightmost data point now also. This data point was leftmost earlier also. It is leftmost now also. So property of the data is maintained. Just we move it from somewhere to this place. But the question is, How did we do that? This process is called as mean centering or scaling or standardization. Okay, you can call it mean centering, scaling, or standardization, whatever you want to call it, you can call it. But the question is, how did we do that? It is simple. So let's say I have two columns. I had income column and I had CIBIL score column. Correct? Yes. Proportionality of the data points will be maintained. Yes, all the properties of the data point will be maintained when I'm moving that. Just something will change. What will change? Let's see. So I'm saying that we had income values and we have CIBIL score values or credit score. Those who don't understand CIBIL score, see, this is financial score given on the basis of how you have been doing financially when you're taking loan, when you are taking credit card. So your credit points are there. In different countries, different names are given. In India, it is CIBIL score, credit score, you can call it, right? So what we did, the centroid point, how we are calculating the centroid point? Original centroid point was nothing but the average of income and average of CIBIL. That was our centroid point. So let's say average income is 30K and average CIBIL score is 650. When I took the average of all these, I got these two numbers. So this is going to give us our centroid point, original one, right? Original one. Now, when we do the mean centering, how do we do the mean centering? So for that purpose, I'm going to use this formula called as your data point minus mean divided by standard deviation. Correct? Data point minus mean divided by standard deviation. What we are saying that when we do the mean centering, when we do the scaling, how the scaling is done, how the mean centering is done, we use this formula for that. This formula is used to do standardization. So you call it standardization, you call it scaling, you call it mean centering. It's all the same thing. So what I'm saying is we take our actual data points, right? This data point, this data point, this data point. We will scale them. Scale means if let's say my first income value is 65K, correct? We say my first input value is, first data point is this. Take your first income value. How are you going to scale the first income value? You take that income value, subtract the mean from that, divide by standard deviation. Let's say 5K is the standard deviation of income column. Let's say mean is 30K of that income column. So take your data point, subtract mean from that, divide by standard deviation. That will give you a number. Okay. So 35 divided by 5 is 7. Correct. So 35K divided by 5K, 7. So what you did, your income value was, the first income value was 65,000, but after scaling, it becomes 7. Okay, it becomes 7. So value changed, but the property of the data will not change. So if suppose this 65,000 is the highest value in this column, let's say it is the highest value, 65K, correct? So its scaled value also will be highest. If let's say this value is the smallest, let's say it is 10K. So after scaling, its scaled value also will be the smallest. Correct. So the data is being changed. It is being scaled down from original value to something smaller. It is being scaled down, but the property of the data is being maintained. Correct. The property of the data is being maintained. Now see what will happen to these values. If I do this process with our average values, don't you think that they will become 0 and 0? Because you see if I find out what is the Z value of our average, will they not become 0? Because it will be 30K, which is our data point, and 30K is the average also, and 5K is the standard deviation. So after scaling, this average of income and average of CIBIL score, both will become 0 respective to their column. Correct. They both will become 0 after scaling. So other numbers are becoming small. Same way, your income average and CIBIL score average, they will also become 0 after scaling. Correct. Now, so you see that earlier, you see this thing. Earlier, let's say this was your data point where average was 30K and your average CIBIL score was 650. Correct. Earlier, your data point was here. After scaling, what happened? It became 0, 0. Your this also became 0. This also became 0. Correct. Now, average of income column, you understand? how do you calculate average? Average of all these values, 30K, correct? I'm saying, let's take the average of this CIBIL score column, 650. Now I'm saying that we are going to scale entire data, scale, or you can say mean centering. What do I mean by mean centering? What do I mean by scaling? So for scaling, we use this formula. Okay, when we do the scaling of the data, this is the formula which is used, right? So data minus mean divided by standard deviation. So our data is what? Our data is, let's say, this value, this value, this value. How will you scale them? From each of the values, subtract the average of the column, divide by standard deviation. So let's say average of this column is 30K, standard deviation of this column is 5K. After calculation, I got these two numbers. How do I scale this number? 65K is our data point, minus 30K is the average, divided by 5K, it becomes 7. So 65 got scaled to 7, correct? Then if I have a value which is 10,000, I have a value which is like 5,000, I have a value which is like 52,000, they will also be scaled. 52,000 minus 30K divided by that. This is the formula, correct? So you are scaling all the values. Now, what will be the scaled value of your average? What will be the scaled value of this average, which is 30K? If the scaled value of 65K was 7, because 65K minus 30K by 5K, 7. If 7 was the scaled value of 65, for example, what will be the scaled value of 30K? So it will be 30K minus 30K divided by 5K. So to find out the scaled value of your average point, it will be 0, because 30K minus 30K is 0 by 5K. It will be 0. Same way, if you talk about the CIBIL score column, so this value, this value, this value, this value, they are also being scaled. So let's say the average of the CIBIL score column, average of this column is 650, correct? And let's say standard deviation of this column is 50, for example, correct? When I calculated the average of this column and standard deviation of this column, it was 650 and 50, right? Now, so I'm saying that when you take the average of this and this, then say our first CIBIL score is how much? Let's say our first CIBIL score value is 710. What will be the scaled value of this 710? So 710 will be 710 minus mean, which is 650 divided by 50. Okay. So it is 60 by 50, correct? 60 by 50, or you can say 6 by 5, like that, correct? And it will become 1.2. So 1.2 is the scaled value of 710, which is our first CIBIL score value. Same way, I have 580, 800, 850, different values are there. I'm going to scale them. So they will become like 1.2, 2.8, 5.6, those kind of number they will become. Now, if this, let's say this is the highest CIBIL score value, so its scaled value also will be highest. Property of the data is being maintained. They're just converted to some other numbers, but the property of the data is being maintained. After scaling, the maximum value will still be maximum, minimum will be still minimum. Now, what will be the scaled value of 650, which is the average of this column? It will be 650 minus 650 divided by 50, 0, right? The scaled value of your average of the CIBIL score will be 0. So earlier, what was the average? 30,000, 650. But now can I say it is 0, 0? The scaled value of your average, is it not 0, 0 after scaling? Exactly. So it is now 0, 0. Correct. So this is the thing. How we are moving it here, we are doing a process called as scaling of the data. And scaling of the data is nothing but we are going to take all the data points. These data point, and our centroid also, we'll take all the data points and we will take them through this formula called as data minus mean divided by standard deviation. Why we are doing this, I'll explain now. But see, when I apply this formula on the entire data, they will be scaled. So when you apply this formula on your data set, you will see that your mean value will move to the origin. It will become 0, 0. Whatever is the mean, whatever, it will always move to 0, 0. and the other points also will move according to that. Okay. Now the question is, why did I do that? See, if I did not do that, still no problem. I will still be able to find out our best line, no problem. But why did we do that? So scaling of data is always done to reduce the time taken to do any calculation. Correct? Our calculation become faster. What calculation? This. See. So let's say if I have to find out the distance between these 2 points. If I have to find out the distance between these 2 points. So, or if I have to find out the distance between these 2 points. Let's say. So what is this point now? Let's say this is income of 18,000 and let's say CIBIL score of 250. Correct. This point is 18,250. This is X1 and Y1. What is this now? This is 0, 0. So can we say that it will be 8? How the distance between 2 points are calculated? I think I would have explained this thing to you in the K-means. The distance between 2 points are calculated like that. X2 minus X1 square plus Y2 minus Y1 square. This is how the distance between 2 points are calculated. Correct. So if I need to find out this, if I need to find out the distance between these two, so I'll say X1 and Y1 is this, and X2 is, and Y2 is this. Okay. So for this second data point, its X value and Y value is called X2, Y2. For this first data point, its X and Y value called as X1, Y1. So to find the distance between 2 points is X2 minus X1 plus Y2 minus Y1. Now, when you have moved this centroid point at the origin, so can we say that now the calculation becomes simple? Correct. The calculation becomes simple because 18,000 minus 0, simple. 250 minus 0, simple. Correct. So your calculations become simple because one of the value becomes 0, 0. And whenever I have to calculate these distances, it will become very simple. And also, remember that these points also have been scaled. We are not just scaling this point. All the points have been scaled. So can we say that now it is not 18,000 and 250? Correct. These are not 18,000 and 250. These are like, it will be 2.8 and 0.9, something like that. So instead of using 18,000 and 250, you are using what? 2.8 minus 0, 0.9 minus 0. So is our calculation becoming faster? Yes, it is becoming much faster because I have to do subtraction of smaller number. So smaller number calculations are obviously simple. This is the reason. Just to make our calculation faster, we have done the scaling. Just for that. There is no change that is going to happen. If I don't do the scaling, still everything will work fine. Still, I will be able to find out our best access. But we did this process just to make this process faster. Everywhere, wherever we do this scaling, it is always to make the calculation faster. Always. No other reason of scaling. Now, final thing, the very final thing. So we need to find out our best access. But the thing is, your algorithm does not know where that best access is. It has no idea because it cannot see like us. So it says that to find our best access, first let's make a random access somewhere here. Okay. First, we are going to make a random access anywhere. So initially, we are going to make a random access anywhere. Let's say I made it here. I could have made it here. I could have made it here. I just made it here. The only thing is you have to pass it through the centroid point. Wherever you initialize it, you have to pass it through the centroid point. That is the important point. So this is our first one that is initialized. Now to find out whether it is our best line or not, what the PCA does, the PCA says that let's calculate the distance of the data point to this line. Okay. We say, let's find out the distance of the data point to this line, the first line that we have created. How much far away from the data points this line is. So let's say this is D1 distance, this is D2 distance, this is D3 distance, D4, D5, and D6. 6 points are there. So this line is how much away from the data points overall. That is what we are going to calculate. Then after calculating the distances, we square them. And that is why this is called as sum of square distances, SSD. Right? Why squaring? Because it is said in the algorithm. Let's square all the distances. So D1 to D6 square, we are going to calculate for now. At this point, let's say overall distance between the data points to this new axis is 6,427, for example. Suppose, okay, just example, that overall distance between the data points to the line is, let's say, this much, because we are squaring the distances also. Let's say overall it is this much. Now what your PCA will do to find out our best axis, it will say that let's make a new line. Okay. Now you can make the second line on this direction, or you can make the second line in this direction, either right side of the first one or the left side of the first one. You see, if suppose the algorithm makes the next line here, left side of that. Okay. So what will happen? Will the distances increase or decrease? The distance of this second line to all the data points, will it increase or decrease? So you can obviously see it is going far away from that, right? Obviously. So it will become like 7,100, 109, something like that. Because as I made this second line in the left side of the first line, the distance increased. And as the distance increased, the PCA will understand that I should not go in this direction. I don't have to increase the distance. I have to decrease the distance. Means I have to bring that line closest to all the data point. So this works exactly like the concept of best fit line. Best fit line also was the concept which was closest to all the data point. Here also we have to do exactly same. So as I made the second line, right? As I made the second line here, its distance increased from the data point. So then we understand, no, we don't have to go into this direction. Means we don't have to go into this direction. It's wrong. So then the third line that will be made, on the right side of the first one, somewhere like this. But see, all the line has to be passing through the centroid point. That is important. So I made the third one on the right side of the first one. Now the distance will decrease because it came closer to the data points more. So the distance decreased. Let's say it became 5,111. Let's say it became that much, for example. So now your algorithm will say that, okay, as I made this third line, the distance decreased. It's a good thing. I should keep moving in this direction. Then I made the fourth line, right? I made the fourth line now. So fourth line is also in this direction itself. I have to go in the right side only. So I now have fourth one. You see, the fourth one is even more closer to all the data points. To make it easy, see, these are your data points. So fourth line is more closer to the data points. It is closer in this side also, to these also. And you see, the tail is also closer to these points. So overall, this line is going closer to our data points. Now, slowly, I will be moving this again. I make the fifth one. So I update the line and it became fifth one like this. Then still the distance decreased. Then I made the sixth one. So as I made the sixth one, so it is, let's say, passing from somewhere here. Correct. Now, as I came to the sixth one, let's say our sixth one is the best. Correct. Sixth one is best because it is now closest to all the data point. Let's say our sixth one is best. How will your PCA know that sixth one is best? It has no idea that this is best. How it will know is, as it make the next line, as it is going to make the next line now, and the seventh one. So from 1 to 6, when I had 1, then third, then fourth, then fifth, then sixth. So 1 to 6, it was decreasing. Correct. From 1 to 6, it was decreasing. But as I am going from 6 to 7, now it start increasing again. So then the PCA will know that as I'm going away from 6. So if I'm going away from 6 in left or right side, both the sides, the distance is increasing, both the sides, which means that the sixth one must be the point of minimum distance, right? That is why when I'm going left or right, both the side, the distance is increasing from the data point. So it must be your best location, correct? And then finally, you are going to remove all the other points and your sixth one is your best one that you're going to use. So overall, the last part of this mathematics is that any line which minimizes this equation will be our new axis. So we are saying that any line which minimizes this formula will be our new axis. Means whichever line is closest to all the data point, that is our best new axis. That's it. So as I got the new axis, then what I have to do with that new axis, I just have to project my data points onto that. Done. That's it. Correct. So only difficult part was to find out where my best access is. For that, we talked about this concept, and whichever line minimizes this formula, that will be our best access. That is the last thing about this. Okay. That what is curves of dimensionality, how PCA work theoretically and mathematically, how it is going to work. And when we find this new axis is nothing but our principal component. Correct. So we were saying that principal component 1, principal component 2. So this line is our principal component. The question now is, how do I know whether I should apply the PCA on the data or not? Is there a requirement of PCA on a certain data or not? How will we know that? Problem here is, if I have 100-dimension data, I cannot plot it. If I can plot this 100-dimension data, then by looking at it, I still might be able to tell whether I need PCA on this data or not. But the situation is I cannot plot it. So how can I know whether we need the PCA on a data or not? You don't have to apply PCA on every data, because the problem is your original columns were like area of the house, age of the house, number of floors of a house. Your original columns were understandable. But as you combine them, you get PC1, PC2. These are not understandable. Your new columns are not understandable. They are solving a problem, but the issue is that we are making a trade-off. We can't explain what is happening after we do the transformation. So these had a problem of multicollinearity or overfitting. That is why we did a transformation. Now these data are less, these columns are less in number. They will not be having overfitting multicollinearity after transformation. But the trade-off here is we are losing the explainability. We can't explain what these principal components are, how they have been created. We can't explain. Right? Now see, so how will you know that you need the PC on that or not? How do you know? Because you see that you can say that if I'm not able to explain, why does it matter? It is better. It is having less columns. It is doing a better task. That is okay for us. Why do I need explainability? As a data scientist, explainability is more important for you. Very, very important for you. Okay, why it is important? Because let's say someone gave you a task to make a machine learning model on house price prediction dataset. So you have to tell them, right, that the price of a house is affected this much by the number of floors, this much by the number of rooms, this much by the age of the house. You have to find that out, right? This is your main task as a data scientist. You have to find out how your features are affecting the final output. It is important. If you're not able to tell that, then you are like a machine. This you have to explain. So when I'm applying PCA, I'm losing the explainability. So should I be taking this trade-off or not? How do we decide? The answer is this. Let's say that you took a data set, you took a data, and you, for example, it's a classification data set. It's a classification data set, and you took that. Now the situation is you are giving it to logistic regression or random forest or decision tree. You're giving it to any of the algorithm. And the problem that you're facing is they are giving very bad accuracy score, because higher dimension, or when a data is having too much dimensions which are not required, if there is a curse of dimensionality in the data, what you will see, it is giving 62% accuracy, 68% accuracy, 67% accuracy. You're getting these kind of scores. Now you tried everything. You tried cleaning the data. You tried this, that, everything that you know. You tried everything. But still, the accuracies that you're getting on your machine learning models is coming out to be bad. So one of the problem might be that your data is having a very high dimension. And because of a very high dimension, these accuracy problems are coming up. Your model performance is being impacted. So what you do now, you say that, okay, let me try PCA on that. Let me try. So you took the data, you gave it to PCA. PCA gave you a PCA transformed data, right? You are not giving it to algorithm first. Now you say that let's take a data, give it to PCA first. As you give it to the PCA, PCA gave a PCA transformed data, right? Now you took the PCA transform data and now you are giving it to decision tree, random forest, logistic regression. And what you observe that now it became 78%, 90%, 87%. You started getting scores like that. So then you will understand, right? Then you will understand, okay, PCA was required in that. PCA reduced the dimension in a smarter way. And now my data is having less dimension. And because of that, now our models are working very well. So when you apply a PC on a data, and if the scores improve significantly, then you get an idea that PCA was required on that. So directly you can't tell. You will apply the PC on that. Before and after you can compare. So before the scores were like that, and after the scores were like this, are like this. That gives you an idea that you have a problem. First, you will directly do this process. Then you got bad scores. Then you will say that, okay, let me try PCA. Then you tried PCA. So you compare the previous scores with the new scores. And if this is having a very big difference, that gives you an idea that your data required PCA. Okay, this is the answer. Now, it does not mean that still you will be using PCA. If explainability is not important for you in any project, then you will use PCA. But if explainability is important, you'll try other methods. You will still not use PCA for that. So PCA is not to be used in all the situations. It is only to be used in that situation where other measures are not working, like a backup option, right? That is the thing, right? So in the case of PCA, what happens? You are going to make multiple principal components, right? So here, if you have, let's say, a data set, this is your data here. And in the case of a data, when you make a new principal component, correct? So we were saying that we have original columns C1 to C100, let's say, right? And then what we do, we give this data to PCA. And as I give this data to PCA, what PCA will do? PCA will give us principal components, PC1, PC2, PC3. It will give us principal components. Principal components are nothing but these are new columns that we are getting from the original columns, correct? So multiple of the original columns are combined together and we get new principal components, correct? Now the thing is, we took a 2-dimension data that we converted to 1 dimension or that we transformed to 1 dimension. But if you have a data of, let's say, 100 dimension, so 100 dimension can be transformed to a smaller dimension depending upon how easy it is to combine different columns. Okay, so if multiple columns are very easy to combine, then PCA will combine multiple columns in very few number of columns. Okay, and if it is very different, or if multiple columns are very different or difficult to combine together, then it would be creating more columns after doing the transformation. But you can be sure that it will be significantly lesser than your original number of columns. The new columns that will be created will be significantly lesser. And in this case, we can also control how much information you want to retain when you're doing the transformation. So if you're transforming your original columns to new columns, you want to keep 95% information, or you want to keep 90% information, 80% information, how much information you want to keep, you can tell that also. On the basis of that also, principal components will be decided. We will never be converting, let's say 10-dimension data to 1 dimension in PCA. It will not make sense to convert 10 dimension to 1 dimension. But yeah, you can say 10 dimension, we can convert to 8 dimension, 7 dimension, 6 dimension, something lesser than 10. But we will never be converting like 10 dimension to 1 dimension or 50 dimension to 1 dimension. That we will never do. So in this case, if this is your data set, what we saw here, we will be making a principal component, correct? We will be making a principal component. Now, principal component that you see here that is what I'm going to explain. How does the system know, or how does the algorithm know which columns have to be combined together? It happens like this. All of you now see, we saw that multiple columns are going to be combined, but how the columns are going to be combined, how does your algorithm understand that? This is what I'm going to explain to you here. You see, when I took two columns, column 1 and column 2, two different columns I have taken, and this is a 2D data. Now this new line which I have created is a new axis for us. And what we were doing, we were making a mirror image of the existing data points on this axis. Now this new line that we were creating, when you put the data points onto this line, when you make a mirror image of your data points onto the line, then you can say that we can represent this line individually, and that will become our one dimension data. Because all the points are on the line, so it is a one dimension data. This is nothing but your principal component 1. Okay, this line that you're making, this axis that you're making is nothing but your new input column, principal component 1. But how am I saying that it is our new input column? Because you see, if I have one column, existing or original input column, let's say income column, do we not represent the data on one of the axes here, like on x-axis? So when we have to represent, let's say, income column, we represent the value on one axis. If I have another column, another input column, let's say CIBIL score. So we represent the value of the CIBIL score on this axis. Correct. So what I'm trying to tell you, whenever you have an input data, and if you have to represent it as a graph, you represent the data on axis, x-axis, y-axis, z-axis. Yeah, you represent the data on that. If you need two axes, you say that it is two-dimension data. If you need one axis, you say that it is one-dimension data. If you need 10 axes, you say that it is a 10-dimension data that we are using. Correct. So now see that this is a line which is not a normal line. It's an axis. Correct. It's an axis on which what I'm representing the data which has been transformed on this axis. So this axis is nothing but our principal component 1, because it is only one line. And this is nothing but our new input column that is getting created, principal component 1, right? And in mathematical terms, this concept of PCA uses some mathematics in the background. So this principal component 1 in mathematical terms is called as a eigenvector. Okay, so there is this word that you should know. Sometime it will be used somewhere, that what is an eigenvector in PCA? Eigenvector is nothing but that new axis that you're creating, that principal component that you're creating. It is a eigenvector for us. It's a kind of word which is being used, right? So this is mathematical name for this principal component 1. It's called as a eigenvector. It's a eigenvector. Okay, just that much. Then there is something called as an eigenvalue also. I'll explain what is an eigenvalue, but for now, you have to know that this principal component 1 is an eigenvector. Okay. Now, this is one thing. Now, when the principal component 1 is created, you see the principal component 1 will be created in the direction of maximum variation of the data. You see, we have these ping points, and our points are having a variation, means spread of the data points. So our data points are spread in two directions. One, if you see that they are spread in this direction, correct. One of the points is here and extreme points are here and here. So if you see that your data points are scattered in this direction, right? One is this direction. What is the second direction in which they are scattered? This direction. Correct. This direction. So the first principal component that will be created will be in the direction of maximum variation. Okay. The first principal component, when it will be created in that direction where you have maximum variation in the data. Means your data points are spread in that direction. In that direction only your principal component 1 will be created. And where will be the principal component 2? Principal component 2, if I make, it will be made in the direction of second maximum variation, right? So in this data, only two variations are there. One in this direction, one is this direction. So PC1 will be created in the direction of maximum variation, and PC2 will be created in the direction of second maximum variation. PC3 will be created in the direction of third maximum variation, like that. Correct. This is the thing that we have to understand, right? That is the thing. So PC1 is created always in the direction of maximum variation, PC2 in the direction of second maximum, PC3 in the direction of third maximum variation, like that. Now, if I show you this in a 3-dimension, how does it look like in 3 dimensions? So let me show you PCA in 3D. That is why PC1 has maximum importance. And I'm coming to that, why PC1 has the maximum importance. What is the benefit of making a principal component in the direction of maximum variation? What do we get out of that? So I'm coming to that. Now see, in the 3-dimension, if you see this graph, correct, you see, your 3-dimension data will look something like this. The data will be spread into the graph, something like this. So wherever you see there is a maximum variation, in that direction, your first principal component will be created. So if you see here, in this kind of 3D data, if you see, this is the direction. If you're noticing here, this is the direction of maximum variation, correct? And same thing is there. If you see, this is the direction of maximum variation. So this is our PC1. PC1 will be created in this direction because here we have maximum variation. Right, so your PC1 will be created something like this, and this is going to be your first principal component. Your second principal component will be created, let's say if this is the direction of second maximum variation, so PC2 will be created in that direction, correct? And then one direction you see, PC3 I can create where you see that these data points are focus on this. So can I say that the data points are also in that direction, going from our side into the screen, right? One direction can be that also, a line starting from outside the screen and going inside the screen, right? Towards the back side of this data. So that can also be one direction, right? So PC1 is this maximum direction, PC2 is the second maximum direction or second maximum variation, and PC3 in the direction of third maximum variation, like that. That is why PC1 is the most important principal component. PC2 is the second most important component. Now, what do I mean by the direction of maximum variation? So direction of maximum variation says that that direction has presence of most important information. When I say the direction of maximum variation, or when I say the direction of maximum spread of the data, why that is important for us and why PC1 is created in that direction? Because you have maximum amount of information stored in that direction where you have more variation. Okay, understand this thing. In whichever direction your data points are spread, that direction has more information for output prediction or whatever you want to do. That direction always have more information stored in that. Correct. So more variation is equal to more information. Exactly. So this is the thing. That is why your first principal component is created in the direction of maximum variation. Now, what is the reason for that? Can we have, right? It is going to be diagonal. So now see, why am I saying that in the direction of maximum variation, we have more information? Why am I saying that? Let's take a data set, and I have a data set for car price prediction. Okay, you see, I have a data set for car price prediction. In the car price prediction, we have multiple input columns on the basis of which the price of a car will be determined. And let's say it is a second-hand car price prediction. I have a data set of second-hand car price prediction. Okay, now see. So suppose I have a feature of the car, which is number of doors in a car, correct? And then we have another feature, which is kilometers driven. It's a second-hand car, so I have information about how many kilometers that car has been driven. Let's say these are the two input columns. Now, in the number of doors, you will see the cars have 2-door, 4-door, 2-door, 2 doors, 4, 4, 5. Let's say these are the number of doors in different cars. Okay, either it will have 2 doors or it will have 4 or 5. These kind of things you will see. But in kilometers driven column, you'll see that a car can be driven for 100 kilometer, another car can be driven for 565 kilometer, another car can be driven for 27,328 kilometers. A car can be driven for any number of kilometers here. Now, which of these features is better helping you to predict the price of the car? Which of these features is a more important feature for you, which is helping you to predict the price of the car? So of course, you will see that kilometers driven is much more of a informative feature for us, right? Much more. Because you see, if I talk about number of doors, in the number of doors, what is the variation of the values? 2 to 5, right? The variation of the values in number of doors column is just 2 to 5. But in the kilometers driven, if it is a second-hand car, it can be driven anywhere from 100 kilometer to 100,000 kilometer, right? It can be driven anything like that, maybe even more than that. So now this column has very high variation. The spread of the values are very, very high. And the more the variation we have in any of the input column, that input column, you will see that generally will be very helpful in price prediction. Because you can see that a car which has been driven very less will obviously be having a more price because it has been driven very less. It's a, you can say, comparatively new car, even though it is a second-hand car, but comparatively new because it has been driven only 100 kilometers. Compared to that, if a car has been driven 27,000 kilometers, so its price will be much lesser than that car which is having 100, which has been driven 100 kilometers. What I'm trying to explain you here, I said few minutes ago that the direction in which there is a maximum variation is more important, or more information is hidden in that direction which has more variation. So I'm trying to explain that exact thing with a example here. Why did I say that? So you can clearly see in front of you, this column, number of doors has very less variation, 2 to 5. The spread of the data is just between 2 to 5, a very small spread, very small. And because of that, it is not very much helpful for us in predicting the price of the house, correct? Or price of the car, sorry. Then we have kilometers driven. It has lot of variation. And because of this variation, you can see that I can definitely predict the price of the car much better with this kilometers driven column, which has more features. So it happens in all the machine learning data. If there is any input column which has more variation, you'll see that generally it is more important in predicting the output or making the machine learning model. Correct? So I hope this thing is clear, that principal component is in the direction of maximum variation, second maximum, third maximum. And that is why, since PC1 is in the direction of most variation, in this direction, we have most important information stored. And that is why PC1 is the most important principal component that is getting created. Now let's get to practical. And with the practical also, we'll try to understand few more things in the theoretical aspect that we will see. Overall means if you think that there is an outlier in the data, then you can remove the outlier, right? If there is any outlier, you can remove the outlier, then you can check. So we will not be considering outlier as a variation. Outlier definitely I'll be removing. After outlier, whatever the normal data which is left, the standard data which is left, that I will be checking. Of course, outliers can give us the wrong answer. So I won't be using outliers in that. But for now, I have to just explain few things with you. Our step number 1. So step number 1 is for Google Colab users. So when the data comes, it will always be having like many columns. So when you give the data to PCA, it will be the task of PCA to identify how many dimensions it will create after doing the transformation. So how the columns have to be combined together and how many columns have to be created or how many principal components have to be created at the end, it will be the task of PCA totally, right? So how does it do that? I was just trying to explain you that. Means how the principal component analysis PCA algorithm is deciding how many of these principal components have to be created. So it will see that in how many directions there is a variation of the data. If there is a variation of the data in only 3 directions, it will make only 3 principal components. If there is a variation of the data in 20 different directions, it will make 20 different principal components. If the variation of the data is happening in 30 different directions, so it will be making 30 principal components like that. Okay, so for now, it will not seem to be like how this data will have 30 directions, but we are not talking about a 3D data. This is just a 3-dimension data. That is why it has a 3 directions. But when you talk about 100-dimension data, so 100-dimension data can have multiple directions, which it is going to capture, right? So it totally sees that in how many of the directions our data is spread, and on the basis of that, that many principal components will be created. That is the thing. The first thing is for the Colab users, every single column, every single principal component is called as a eigenvector. PC1 is our first eigenvector, PC2 is our second eigenvector. Every principal component is a eigenvector. The first line of code that we write in Google Colab is just to upload the data set, and that is what we'll do from google.colab import files. Say uploaded is equal to files.upload. Now, after uploading the data, you see, you just have to click on this choose files button and it will let you to upload. Now, this code is just for Google Colab, as we have already seen multiple times. Let me upload the files. Okay, so you have to click on the choose files button and then you have to go to the folder where you have your data. Right, my data is present in this location and this is nbafinal.csv. For you, the data will be in the downloads folder. You can get it from there. Now you have to import the required, right, import the required packages. Now in this, I'll just be uploading some of the normal packages which are required for reading the data and machine learning related tasks. I'll be just importing that. So first we have import pandas as PD, then import numpy as np, then from sklearn.linear model import logistic regression. Then we have from sklearn.model selection, we'll import this trend test split. Okay, now why am I importing these machine learning related packages? Because I will be applying logistic regression normally on this data set first. Then we will see what is the accuracy score coming up. After that, we will apply PCA. And after applying PCA, when we have transformed the data, we'll apply logistic regression again on the transformed data. So before and after, we'll see the result, what our model is giving as an accuracy. Okay, so from sklearn.metrics, import accuracy score, comma, ROC AUC score. And one last thing is from sklearn.preprocessing, we have to import the standard scaler. You have the file so that you can focus on the other explanations. So in the step number 2, what we do, we are going to do the reading and exploring the data. Right. Now let's bring in our data set. So our data is this. Data is equal to pd.read CSV, and we have NBA final.csv. Okay, and if you look at the data here, it is like this. Okay, now see. So here we have multiple columns, and what is the amount of column we have? We have data.shape, and we are dealing with 45 columns. Correct. So this data set has 1408 rows and 45 columns. Okay. See here, we have the data here, and we have multiple columns. 45 columns are there in total. Now, this is a classification data set I've taken for just example purpose. You can take any data set and you can apply PC on that, right? So PCA you can apply on a classification, regression, or unsupervised. Anywhere you can apply the PCA. That is the thing. Okay, and one example we are going to see here. Now, have a look. We have 45 columns, and this data set is about NBA final. NBA is a basketball championship, and the finals of that, we have a data set of that, and we are using it for now, right? Now, originally we have 45 columns here. Out of 45 columns, we have 44 input columns and 1 output column. You see, this play is our output column, and rest of the columns are our input column. Now, we don't have to study this data too much for now, because our main task is not to study this data. Our main task is to see that how we can combine 44 input columns to make less number of columns or principal component. So our main focus is just that. You don't have to worry much about the data for now in this case. Right. Now, why I have taken this data? Because it is a data which I have seen it is very suitable for PCA, and you will see significant results when I apply PCA. Right. Now, after checking the shape of the data, there are different things we check. The very first thing we check after checking the shape is the D types. This D types is a variable which is going to print the data types of values in each column. Right. And why we are checking this data.d types? Because of the reason that we want to just verify whether any column is object type or not. Right. We just want to see that. If there is any column of object type, we will need to encode that. So here we have some columns which are of the object type, and we are going to see a code how we are going to encode that. We will be talking about that. Right. So with the verification, we have just now seen that our data has this object column, this object column, this object column. Multiple object columns are there, which is nothing but column with text values. Object means that that column has text values, and we are going to encode that. Because any machine learning algorithm or PC also, they don't work directly with the text data. So we have to first encode that, and then only we can provide this data to algorithm. Either it is machine learning algorithm or it is PCA. Correct. Now, so data types we have checked. The next thing that we are going to check is the number of missing values. Right. Now here, so we have data.isnull.sum. This is going to print the number of missing values in each column. This is what it is going to do for us. So if you now run this code, in this data set, we have a lot of missing values that we have to deal with. We have to do something about those missing values. Now see, the POS2 column has 1396 missing values. Then we have 99 missing value, 4 missing value, 15 missing values. Different amount of missing values are there for now. Now, how to deal with the missing value? There is an entire science behind that. You cannot just say that I will be deleting this or I will be filling something at the place of this about the missing value. For the missing value, there will be an in-depth discussion about how do we decide when to delete something or when to fill something, right? How to decide that. So for now, I'll just give you a small idea about it. But in this case, see, so in this case, you can see that multiple columns are there and they have multiple missing values. Now, in this case, we have this POS2, 1396, right? So POS2 has 1396 values. Let us see what kind of values we have in POS2 column and why we have so many missing values here. Because if you now observe, we have total how many of the rows? Total 1408 rows are there. Total. So out of 1400 rows, if you have 1396 values missing, so it is like more than 95% of the data is missing from one of the column, which is POS2 column. So if you have 1408 rows in the data set, every column will be having that many values. Correct. So the number of values in a column is always equal to the number of rows in your data set. So POS2 column also should be having 1408 values, but 1396 out of 1408 is missing, right? So it means that only 12 values are available, 1396 missing. Correct. Now, what is the reason for that? When you look at this column, in this column, more than 96% data is missing. So a direct decision you can take is to delete this column. Okay, because if a column has more than 90% data missing, what will you fill it? So it is obviously a very direct thing that we can delete this column. But before I delete it, let me show you that we can also do something else. Before deleting that, we should be looking at the data. What is that data first? Let me show you first. Okay. So deleting it would be like obviously a correct thing to do, but let me show you what else could be done in this case. See, POS2 column. What is this POS2 column? Or here you won't be able to understand. Let me show you here in the main data set. See, so every row is talking about one player who played finals of NBA championship. Now here, the first player, there is something called a rank. RK is the rank of the player. Then this is the name of the player. This is the ID of the player. And you have POS1 and POS2. See, POS1 is the primary position from which the player plays. Correct. In football, in basketball, there are some primary positions from which a player plays, which is their main strong position, right? Then POS2 is the backup position where they will play. If suppose there is another player who is playing as this primary position, so that player can also take a backup position and they can play from that, right? Now here, if the POS2 value is missing, what does this mean or what does it represent? So it can be representing here that this player does not play with any other position. If this C is a center position, if this center position is not available, then they will not be playing with any other position. They will be out of the team. They will not play with any other position. So all the NaN values that you see here, they are all representing that those players don't play with any other backup position. They only play with their own primary position, which is center, PG, SF, PF. These are their positions from where they play. Correct? Now I can delete this. This column has more than 96% data missing. I can definitely delete that. But can I also fill this, all the missing values with a word none? Can we do that? Will it also be okay thing to do in this case? Can we fill it with none? None would mean what? This none as a string, not as like this, but you'll see we will be filling it with none. Now, what will be the benefit of filling it with null? No, NULL, it is already that. You see, if I'm having a NaN here, NaN is nothing but it is null. So I don't have to fill with the word null. It is not going to help us. I'm saying another word none, None, none. Right? What is none? You see that Na is this only. This Na is a representation of Na or null. So whenever you see NaN, NaN means Na, null, they are all the same thing. So you are not going to represent it that. They are all the same thing, and machine learning or these pandas related data, they deal with the same kind of thing. Correct. Now see, what I'm telling you here is, can I fill it with this word none? Now, if I fill it with the word none at all the places, with a word, it's a string value. And what will happen if I fill it with the word none? So now when I look at the data, then I can understand that this player does not play with the position 2. Earlier, this value was empty. NaN means this value was blank, empty. But now I'm saying that I'll fill a word none. Right? None means what? This player does not play with the second position. None as a word being present there will help us to understand that, okay, this player does not play with the second position. And that is the idea I'm trying to give it by putting this string none. Correct. So NaN here means that this word is not present there. This NaN word is not present there in that cell. It is empty. NaN is a representation that this value in our data set is empty, blank. But I'm saying that instead of blank value, I'll be filling it with the word none. So now when anyone look at the data set, they will understand that, okay, whichever players have the position 2 as none, they don't play with that position. That will help us to understand something about the data, right? Because if it is null, if you say that I'll fill it with null, or I'll fill it with NA, or I fill it with NaN, it means that the data is missing from that location. And if the data is missing, it can be because of any reason, right? Someone did not fill the values here, or the data got corrupted, and because of that, the data was lost. Correct. So the data being empty, or you are saying that it is null or NA, you are basically telling that the data is not available from this place. At this place, the data is not available, and the data can be not available because of multiple reasons. Let's say this player, which you see the third one, let's say this player plays with the first position and they play with the second position also, which is center. But someone by mistake did not fill the value C here and it was left blank. And because of that, you are seeing null. So what is this blank value representing? That it can be missing because of any reason. It does not represent that this player is not playing from the second position or they don't play with any second position. Blank value means directly that for some reason, the value is empty, but I don't know what reason. Do they not play with that position, or by mistake it is empty? Correct. So that is the thing that I'm trying to explain. That if I put the word none here, that also will be very beneficial in this case, because I will be able to understand that the players don't play from that position. Correct. So what I'm trying to explain you with this concept is that before you delete a column, you have to go through that column and you have to try to understand what type of values are supposed to be in that column. And even though 90% of the values are missing in that, should I delete that? Or can I do some other step and can I fill it with some other value, which seems to be like a very good value to fill in those blank locations? Just an idea. If you delete the PS2 also, perfectly fine, no problem. We will not be having much issues in that. But I'm just giving you an alternative idea that in this such extreme situation also, if you take a decision to fill the values with something, that also seems to be a good option for you, right? So that is the thing. Now there are different things or different kind of decisions we have to take depending upon how much values are missing and how important a column is. Correct. So that is the thing. And on the basis of that, you're going to take the decision. So we have just now decided that we are going to fill it. How we fill a missing value? So I'll say the name of our data frame is this data. Then POS2 is the column name. Now we will say dot fill any. The name of the function is fill any. Fill any function says that I will go to each location where the value is not available. Means I will go to each locations in the entire data frame and we will see where the values are not available. NA means not available or missing. And we will fill those locations with whatever you give. Now, if I give 100, let's say, as I say, data pos2.fill NA 100. So wherever the values are not available in my pos2 column, because I have written pos2 here, if I remove this and I just say data.fill NA, so data is my entire data frame. All the columns, all the rows come into that. Now, if I say data.fill any of 100, so in my entire data, wherever the values are missing, it is not available, it will fill those locations with this word, with this value 100, this number 100. But now I'm saying that I don't have to deal with all the columns for now. I'm just focused on POS2 column. So in the POS2 column, this function will first go and search where the values are null or which is not available, then fill those locations with this value that I provided. But I don't want to fill it with 100. I want to fill it with this word none that I'm providing it. Now it is going to fill that. When we are going to fill the null values with this word none, I'm going to store it back into the right. I'm going to store it back into the same POS2. Okay, right. POS2. That is the thing that will be done. And if you now look at the POS2 column, you will see that it is having this word none at all the places where the values were not available, or NaN. Now we have filled it with that. Correct. Now, other decisions also you can take. If you have another column which is missing a value, you can also do something about that. Let's say I have a column which is called as this POS2 column. This POS2 column has object type of data in this column. And let us say that I try to fill the POS2 column with this word, with this number 100, right? 100. Now, if you fill this word 100, you see that in the POS2 column, some of the values, whichever values are available, that is in string format. Okay, a lot of values are missing, but whatever values available in this column, it is in string format. And whichever values are missing, you are saying that I'll fill it with 100, which is an int value. Now the same column POS2 will have some string values and some int values, which is not possible. Right? Every single column will be homogeneous. It will have homogeneous data. Either it will be all string or it will be all integer. Now, in which they will be converted? If I have some values in string and some in integer, in which they will be converted? They will always be converted into string. The priority of the values flow like that. Integer, and bigger than that, that is float, and more important than that, it is string. Okay, this is how the priority flows. String is the most, you can say, a value which is given highest priority. So if you have three values, one string, one float, and one integer in the same column, everything will be converted to string. But the question is why they will be converted to string? Why not to integer? Why not to float? Suppose I have a number 100 here. If there are some values 100, and if in the column there are some values in float, let's say 56.20, something like that. Now, if you say that we will convert these values into integer, what will happen? This value will be lost from the float value. If I am converting both these numbers all into integer, then from the float values, some data loss will be there. Whatever was there after the decimal, that data loss will be there. Okay, and 456 and 456.20 are not the same value. They are different. Correct. But if I say that let it be 456.20 and let's make this integer as float, will there be a problem? Right. No, if you round off also, then also it is wrong. You see, if I say that don't change the float value, let's change the integer values. Right. So if I convert an integer value 100 to 100.0, now I make it float by adding 0.0. Will there be a problem? No problem. Right, no problem. Because if you say 100 into 2, or if you say 100.0 into 2, they are going to give the same value, just it will be in another format, but the value will be same. On the other hand, if you say 456.20 into 2 versus 456.2, they are the two different values, right? They are the two different values. So that is the reason why they are converted. If integer and float both are there, more priority will be given to float conversion, means everything will be converted to float. Because when you convert integer to float, you don't have data loss in that. Now, the thing comes up, what if I have integer and float and a string in the same column? Or this word none, let's say. What if I have this situation? A column can have only one type of data. Why a column has to have only one type of data? Because if you try to do any operation on the column, and in the column you have string also, float also, integer also, so your any process will get confused what to do with this column. Okay, it will get confused what to do with this column. So if a data has all the three values, like if you have some float, some integer, and some string, what will happen? They will all be converted to one type of data. Which one? So if you say that we will convert everything into integer, what will be a problem? If I say let's convert everything to integer, then in this one there will be a data loss, and this one we can't convert. So your process will fail if you try to convert everything to integer. That we can't do now. Just now we saw. Then we say let's convert everything into float. All the three values, let's convert everything into float. So this will be done. This will be done. This is also okay. But this will not be converted into float. But when I talk about, let's say now convert everything into string, can we convert everything into string? Yes, because we just have to put them into quotes and we can convert everything into string. This process will be carried forward. So there will be no failure in that. That is why string will be given as a priority, right? So that is what you have to remember. Integer least priority, then float, then string, like that. That is the thing. Now, converting a number to string, is it correct? No, technically it is not correct. But when I'm talking about a conversion of the values in one of the format, then this is how they are given priority. But if after conversion, if some of the values are becoming wrong, then you have to be careful in that. If you did not want a number to be getting converted to string, you have to be careful in that. But the code will do its task. It will see that where I can convert, which is the most suitable format, it will convert into that. Right? It is right, not right. That is for you to check as a data scientist. Now, so POS2 column, we have filled with the word none. Now, there are other columns also which have a lot of missing values. What to do in that now? So let's now talk about if there is another column. So let's say there is another column, which is again an object column in which some missing values are there. So how do we fill this object column if it has some missing value? This was also an object column. So we saw that I can fill it with a static value. It is not a dynamic value. I just filled it with a particular word, none. It's an example of filling it with static value. But how did I decide that I should be filling it with this word none? Because I was pretty sure by looking at the data, I was pretty sure that if I fill this column with the word none, it will be a very suitable thing to do. I was pretty sure of that. That is why I decided to fill it with this word none. But what if I'm not sure with which word I should be filling the missing values? And I have to fill. I am not going to delete, let's say, but I have to fill the column. So another option I have is you take the mode of the column, you calculate or you find out the mode of this column, and you fill the missing values with that. So either with a single value or with the mode. If you try to fill that, if you want to delete, you can delete a column or you can delete the rows in which missing values are there. But talking about the object data type, if you have any missing value in your object column, you are going to fill it with either a particular string, particular word, or the mode of that column. Mode is what? Mode is nothing but the most occurring value or the most occurring word in that column. You are going to fill it with that. Correct. For example, if I have a column which is types of loan. In a bank data set, one of the column is types of loan. In this types of loan column, there are some values missing. So let's say this is personal loan, car loan, personal loan, car loan, and there is a value missing here in this place. It is NaN, value missing. Now, in this case, you can see that we have more people taking personal loan compared to car loan. So if I have to fill this missing value, what will be a most suitable value to fill will be personal loan, because most of the people are taking personal loan. So this person also, let's say, or we are just making an assumption that this person will also be taking a personal loan or would have taken a personal loan, and for some reason its value is not missing. Correct. So this data set is about the loan only. All the people in this data set have taken a loan, but I'm saying that if this value is missing, so either at this place, it will be a car loan or personal loan. So I'm saying that since most of the people are taking, let's say 70% of our customers have taken personal loan, so filling this value with a personal loan will be a most suitable thing to do, which is nothing but the mode value of this column. So that is how you decide for the object column. But now talking about the numerical columns. So in the numerical columns, this is the situation. Let's say I have a column called salary in which the values are missing. So in this salary column, when I'm talking about a numerical column, two things I have to see. First, importance of that column. Correct. Importance of that column. And then second thing is whether this column has outlier or not. Whether this column has extreme values, outliers or not. Now let's say this salary column, first let's talk about importance. What importance? Let's say this salary column is there and this column has, let's say, 60% of the missing values. 60% missing values there in this column. Now, if a column has more than 30% missing value, you can delete that column. Entire column you can delete as an idea, but there are again other decisions to make in that. Let's say this column has 60% values missing. Now I have to decide whether I'm going to delete the entire column, or I'm going to delete those rows in which the values are missing? Yeah. Let's say in this case, what you have to decide is, should I delete the entire salary column, or should I delete the rows in which values are missing? If let's say in row number 0, the salary value is missing, should I delete the entire row, or should I delete the, or should I fill the values? So 3 options are there: delete the column, delete the row, or fill the values. 3 options are there, correct? So first you have to see whether I can delete the column or not. So if this column is very important, if I don't want to lose this data, if 40% values are also available, let's say that is also enough important for us. I don't want to delete this column. So I'm not going to do that. I'm not going to delete the column. Second option, should I delete the rows? You see that if I delete the rows, you have to talk about the trade-off. If you delete the rows, you're getting rid of missing value of this column, but you are also deleting a lot of other values which will be present in that row. That is also bad. If you delete the row, I know that salary value is missing in that row, but that row could have other values also which would be present, and those are important values. So do you want to take that risk or not? Do you want to make that trade-off or not? That I want to remove the missing values, but along with that, a lot of other data will also be gone if you delete the row. And third thing is fill the values. Are we going to fill the values? So if I'm going to fill the values, then with what? So again, 3 options. With a constant value, I will be filling the salary, all the missing values in the salary column with a constant number, or mean of the entire column, or median of the entire column. 3 options are there with you, using which you can fill the values. So in the salary column, filling with constant will not be very suitable because you don't know which value will be most suitable for that. So you are going to pick mean or median as the most suitable option for most of the numerical cases if you want to fill it. Now, you see that I'll be giving very good example one for when you should be deleting a row. But now say that I have to fill the salary column for mean and median, right? And in the case of mean and median, you have to decide which one. We try to take this mean as the first option. But if outliers are there in that column, then I will not be taking mean, then I will be taking median. So if I have to fill it, if the salary column has all balanced value, no outliers, not even one. So if our salary column has balanced value, no outliers at all, then I will be taking mean of that column and I'll be filling the missing values with the average of that column. If outliers are there, then I will not be using mean, I'll be using median. Correct. Or you can say that we will first delete the outlier, then take the mean. Correct. So with the presence of outlier, you can't take the mean. That will be wrong. So then median for that. Okay. So column part understood, that if a column is not important, you can delete the column. But if the column is important, you can't delete the column. Then you have to decide the rest of the 2 options. If you decide to delete the row, then you have to consider the trade-off that I will be removing the missing, but along with that, a lot of other important values will be also lost if I delete a row. Then in this case, you thought that both I'm not going to do. So last option left with is fill the values. So fill the values, and then you are going to decide which one. Again, in this also, some other things are there, which we'll be talking about. But now let me give you one example of where I'm going to delete a row. Okay, see, suppose I have a house price prediction data set. House price prediction data set I have, and I have a price column, which is our output column. Correct. In the price column, if some values are missing, let's say if first value is available, second value is available, third is missing, fourth is available, fifth is available, this is missing. Now in the price column, the situation is now this column has also 60% missing value. And it is the output column of this house price data set. 60% values are missing in this case. What should I do? Should I delete this column? No. You can't delete the output column. Otherwise, you will not be able to run the machine learning algorithm in that if you delete the output column. Correct. So obviously, no matter how many values are missing in that, I can't delete this column. It is the most important column for our use case, which is our house price prediction data set. Okay, I can't delete it. No matter how much percentage of data is missing, I can't delete that. Second option. So if 60% values are missing in this price column, does it make sense in this case to fill it with mean or median? If 60% values are missing, see the amount. Okay. Will you take this decision of filling 60% of the values with an assumed number? See, mean or median is what? Mean or median is not the accurate value. It is closer to accurate. We are just making an assumption that if I fill this value, if I fill this value with average or median, then I'm filling it with a value which is supposed to be closer to actual. But am I sure that it is closer to actual? Right? Am I sure that it is closer to actual? I'm not sure. So if I fill the output column with 60% of the synthetic values, that will also be dangerous. Okay, remember that you are not going to fill with mean or median every time, because you have to first see that mean or median is not the accurate answer. This is close to accurate. And I'm not sure that whether all the values are okay or not. This is just an assumption I'm making that average is a good option to fill the missing values. But see, these are not actual values. These are assumed values. Even though they are close to accurate, these are not actually accurate. So if I fill my most important column, the output column, if I fill with 60% assumption values, then there is a danger that you are making your entire data synthetic. And whatever machine learning model you make, you are predicting assumed prices. So your machine learning model might be wrong because of this thing that you're doing. So filling also is not a good option in this case for this scenario, and deleting this column is also not a good scenario. So what is the only option you are left with? Right. What is the only option you're left with? Row deletion. Okay, row deletion. So now let's see whether row deletion will be a good option in this case or not. Now, if I have a house price data set and this price column has some missing value, let's say I know the features of this house, but I don't know the price of this house. So does this row help you at all? If I know the features of a house, but I don't know what was the price of the house, will it be helpful for me in the model making? No, right? If I go to certain houses and I know that that house has 4 rooms, this much area, this much floors, but I don't know the price of the house. So how will I utilize that information in model making process? I can't. Correct. So what I'm trying to explain you here, in this situation, row deletion will be the best option, because anyway, for this row where inputs I know but output I don't know is not at all important for me. What will I do with of this row whose input I know but output I don't know? Correct. So that is how we have to take a decision whether I should be filling or deleting, because whatever you do, there will be a trade-off. A trade-off you have to keep in mind, which one is more dangerous for me, which one I don't want. On the basis of that trade-off, you have to take the decision. So what I'm going to do now, the remaining columns which are there are other rest of the columns also apart from POS2, which has a lot of missing value. For now, I'm just going to fill all the other columns with a value 0. I know this is wrong. It is not most accurate. But for now, we'll do the discussion about rest of the columns. How should we deal with them? But for now, I'm just filling the rest of the columns with this value 0 so that we can do the further process. Okay, now, so the missing value situation also we have understood. Now let us see the duplicates, whether we have some duplicates or not in this case. So I'll say data dot duplicated dot sum. Okay. And if you see now, we have 0 duplicates for now. And if the duplicates were there, we can use this drop duplicates function to do that. In place is equal to true. Okay. Now this column will delete all the duplicate rows. Okay. Now, so duplicate also done, missing value also done. Now coming to the data type part. We had object data type, and we are going to convert those object column into numerical column. And this is how we are going to do that. So there is a code here. Okay, and before we write a section dealing with object data type columns. Now there are no missing values, because what we have done here, we have filled the rest of the missing values with 0. All the other columns which were having missing values, we have filled every one of them with 0 for now. Okay, this is not very correct thing to do, very right thing to do, but for now, so that we can go through the further process, we have now filled the entire data with 0 wherever the missing values were there. Okay, in the entire data. Now, how are we going to deal with object data type columns? So there is a function here where you say the name of your data frame and say select d types. Okay, name of your data frame dot select d types is a function here in which you are going to mention object. And before we come to this part, we'll do one small thing. In our data set, right, you see that in our data set, there are few unnecessary columns for now that I'm going to drop. Which columns are unnecessary? These columns. So for machine learning related purpose, the player's name and player's ID is not important. So these columns might be important for data analysis purpose, but when I'm going to machine learning process, so these two columns will not be helpful for me. The name of the player and the ID of the player is not going to be helpful in machine learning related process. So I'm going to delete these two for now before we go to further process. So I'm going to say data.drop and we'll say columns is equal to these two, player.x, and another is player.x, player underscore ID, player underscore capital I, capital D. So here I'll be mentioning in place is equal to true, so that they are deleted permanently. Now, so there is this function called as select d types. In this select d types function, if I mention this word object, right, and if I run it, so when I mention here data.select d types of object, it is going to print all the columns which are of the object type in our data set. If I mention here number, right, in this case, if I mention here number, sorry, not as like this, I have to mention number as a string. Okay, and if I run that, so when I mention here number as a string, so it will select all those columns for us in which we have either integer values or the float values, right? So like this, it will give you the name of all the column, or it will show you all the columns which have numerical values in that if you mention number here. And if you just want to see the column name, not the entire column data, just you want to see the column name of those columns which are having those numerical values. So you can just mention dot column at the end, right? So from the data frame, select those columns whose data type is number, and dot columns will show you only the names of the column, not the values of that column. Now you see that you are getting a list of those column names. And what you can do now, you can save them into a variable numCols, and whatever you want to do with that, you can do whatever you want, right? NumCols. So I'm storing this names of those columns into this variable numCols. And if you see numCols, this variable, it is storing only the names of the column. If you want to see those columns, you can say the name of the data frame, square bracket, and in this numCols. So now you will be able to print all the columns here, which are whose names are being stored into this variable. Correct. Same way, I can make a variable object calls, and what I can say data.select d types. Correct. And here in a bracket, I will be mentioning object, and I'll say dot columns. So this code is going to give us the name of the columns. Sorry, this is going to show us all the columns which are of the object type, And when I mention dot columns, it is going to do what? It is going to just show us the names. And that list of names I want to store into this variable object calls. Correct? Now, why did I store the names of those columns into this object calls variable? So that I can do the encoding of all the columns directly using that list of names. Correct. So for now, if you see object calls variable, then it is nothing but a list of all columns whose data types are this categorical. Now what I will do, I will be doing a simple thing. For the data processing, we have from, it requires like that because number is not like an keyword kind of thing. Object is like a keyword. So without the codes also it understood that. But number is not a keyword. So when I just mentioned number directly, it was thinking that I'm giving a variable name whose name is number. So that is why I had to give it in the string format. That is how they accept that. Now here, what I'm going to do, there's a package called as from sklearn.preprocessing. We are importing label encoder. Okay, we are importing label encoder. And when I import this label encoder is a class which is going to do the encoding for us. So I take this class label encoder, and what I'm going to do, I'm going to make an object of that. You make always an object of a class. As I make an object of this, you can use one-hot encoder also, but I'll tell you there are again some things to decide which encoder we should be using. I'll talk about that also, which one to use in which case. But for now, I'm using a label encoder. Label encoder is good for most of the situations, and you can use that. It is going to do what? If your if a column is gender column, male and female is given, so it will give 0 to one category, 1 to another category, right? That is called label encoder. If 3 categories are there, it will be giving 0 to one of the category, 1 to one of the categories, and 2 to one of the categories. So this is how the numbering is done. This is how encoding is done using the label encoder. But there is one problem that happens when you use label encoder. Some drawbacks are there, because of which you have to use another encoders in some situation. So I'll be coming to that. What is the problem? But see, why did I make a list of this object column? Because I can now say for each column in object columns, right? I can now say for each column in object columns, do what? Take that column of a data frame, and what you should do now, you should do here le.fit transform data of that column. Means using this label encoder, using this object of the label encoder, call this fit transform function of the label encoder class, give it a column one by one, right? Give a column one by one because we are running a loop. 7 columns are there in that. So 7 times this loop will run. First time this call will be POS1, this POS1. So first time data POS1 is equal to le.fit transform data POS1. So now with this loop, I can do the encoding of all these 7 columns in just one line of code, because I've stored that into a list, and I can go through all the values of this list and I can do the transformation, correct? Or encoding, you can say. So with this just 2 lines of code, we are able to do the encoding of all the columns. We don't need to write the same code again and again. So for this situation, making a list of all the column names on which I want to do a certain task, I can use that. This is beneficial. Our data for now is this. When I say data play is our output column, and this is a classification data set. So before we now go to machine learning process, we have dealt with object data type, we have dealt with missing values, we have dealt with duplicates and all. We have seen that. But what we should do now, one last thing before we start the machine learning process, it is a classification data set, and we know that a classification data can be balanced or imbalanced. So we have to check whether our data is balanced or imbalanced. That is what we have to check. So which column we check for that? The play column. Play is the output column. So output column's value counts thing that we have to check. This is for imbalance, right? You see. So in the data set which is given to us, we have 1335 no, and 73 yes. Means if you go to this thing here, you see that play column has no and yes. So no has been converted to 0 or encoded to 0, and yes has been encoded to 1. Okay, so what is the situation in our output column? Out of these 1408 rows which are given, 1400 and player information is there, 1408 player information. So out of 1408, 1335 players did not play the final, only 73 players played the final. So is our data set imbalanced? Of course, our data set is clearly imbalanced, and we have to do something about that. We have to deal with in the machine learning process. So by changing the type of the column, but changing the column, if you are now doing that, you see, when I mentioned the data and column name. So when you mention like this, you are not selecting column name, you are selecting the entire column data, right? What the method of column selection is this. So I'm not changing the data type of a column name. I'm changing the data type of the column. That is the thing. See, so this is the name of our data frame. And in this, whatever I mentioned, it selects that entire column, not just the column name. It selects that entire column. In this machine learning process, you see, after dealing with the normal situations in the data set, we now come to the machine learning process. And it is a classification data set, so we'll be applying any classification algorithm. I just took logistic regression for an example for now. In the machine learning process, you know that you make first X and Y variable. Then second, you split the data into 4 parts. In this data, what you have to make sure when you're splitting the data, you have to make sure of this stratify is equal to Y. Whenever our classification data is imbalanced, then we have to use this parameter stratify is equal to Y. Exactly this, nothing else, right? But for now, X and Y variable, then splitting the data into 4 parts, and you have to just make sure that you mention this definitely because it is imbalanced data set. Now, in the PCA, what I have explained to you that we were doing a mean centering process. Before we were finding out our best axis, we did a mean centering. We moved our centroid point to the origin point. That was mean centering. So how we are doing the mean centering? There is a class called a standard scaler. Okay. And standard scaler is a class. We are making an object of that. And then doing this, we are doing the mean centering. That our calculations become faster when we do the scaling, because bigger numbers are converted to smaller numbers, and scaling is beneficial for fast calculations. But there is one more benefit of that, of the scaling, which we need to talk about, and I'll explain that in a few minutes. But see, what I have to do now, when I have to do the scaling, I have to do it like that. We take a class, we make an object of that. Then using this object, SC, which is the object of the standard scaler, using that, we have to use fit transform and xtrain, and then we have to say SC dot transform xtest. So with the xtrain, we have to use fit transform function of this class, and with the xtest, we have to use the transform function. This is how you have to work with these two. Now, why different? Why we are using fit transform for xtrain and Y transform for xtest? See, there is this thing. In the fit transform, fit means learn, transform means transform. So you are learning something, then transforming your xtrain data. In the case of xtest, you are just transforming, you're not learning. But what is the difference between them? See, when you do the standard scaler, its formula is your data minus mean upon the standard deviation. So data is what? All the values of a column. So if you have 10 columns, you are going to scale all the 10 columns. So whichever columns are in your xtrain, you are transforming those columns, correct? So now you are saying that you take the data, subtract the mean, and divide by standard deviation. This you have to do for every value of a column. And that is how the entire column is going to be scaled. And this is the formula of the standard scaler that we use, correct? So when you do that, you do the mean centering of the data or scaling of the data or the standardization of the data. In this case, when you are doing this thing, what you are now calculating in this first, First, you're calculating the mean of a column and standard deviation of a column. Correct. For every column, you are first calculating the mean and standard deviation of those columns. Then you are subtracting the mean from every data point in that column and divided by standard deviation. So you are learning this for each column. That is why fit. Now, once you have learned that, you are going to use the same mean and standard deviation for different columns in the X test also. So one of the column is my salary column in this data set. So for salary column, using the extend, I found out its mean and found out its standard deviation. The same mean and standard deviation I will use to transform the X test data. That is why only transform for the X test, because we are not calculating mean and standard deviation again of those columns. We already calculated that here in this step, and we are just using the same mean and standard deviation for X test also. That is why just transform, not fit transform. So this is how you have to use that, right? So we are calculating mean and standard deviation for each column. Now, after scaling the extend and X test, you have to store it back. Now you can store this scaled data back into the same extend variable and back into the X test. But what I did, I made another variable, extend scaled and X test scaled, two new variables I created, where I'm storing the scaled version of extend and X test, so that these are safe for now. If I need them later for some reason, then they should be safe. Otherwise, if I would have saved that into the same variable, then my data will be permanently modified. These two variables will be permanently modified. Now, so taking this scale data, I now apply the logistic regression. Same thing, make an object of this logistic regression, say logred.fit. Here I'll mention extend scaled y-train, not the extend scaled version I'm going to use, right? So extend scaled y-train. Then we are using x-test scaled for predicting, and we got this vibrate. Now see this data set, right? This data set is imbalanced. That is why we are using ROC AUC score. So we have studied in the random forest that if our data set is imbalanced in classification, we should not be using accuracy score, correct? We should be using ROC AUC score. So you now see that we are getting 92% accuracy in this data set before PCA. Now, what are we going to do? We are going to apply PCA, and after PCA, we will see what is the result. So let me show you that final part of the code in PCA, and that is, so we say from sklearn.decomposition, we are going to import this PCA class. PCA is also written for us in a class, and we just need to import it, and we just need to use that. So we imported this PCA class, then we are going to make an object of that class. Okay, we are going to make an object of this class, PCA. I told you one important thing. When you use PCA, you have the option to mention how much information you want to retain, correct? So that is the thing you can mention here in this PCA class. There's a variable called as, or there's a parameter, sorry, called as n components is equal to something, right? So you are saying that I want to retain 95% information, you can mention 0.95. If you mention 100%, you can mention 1.0. Okay, 100% you should never use, but 0.95 is the most common. And if you mention 90%, you can mention 0.9. If you have to retain 85%, you mention 0.85, like that. So now I'm going to use, let's say, 95% information I want to retain. So one thing that you can give in this n components variable is how much information you want to retain. On the basis of that, it will make certain number of principal components, right? How many it will make, I don't know. But on the basis of this percentage, certain number of principal components or new columns will be created. So in this case, we have another option also. In this n components, I have another option also. So originally, we had 44 input columns in our data, and we deleted 2 of them. Player.text, player.id, we have deleted 2 columns. So for now, we have 42 input columns. And I can do one more thing here in n components. I can tell a number of principal components that I want. I'm saying that you have to create only 10 principal components. You can't go more than that. So I have option to do this also. if I know how many principal components I want, or I'm limited to the number of new columns I want, I can mention that also. I can just say 10 I want. So somehow it will try to fit them into 10. But how much information you will be able to retain, that is not guaranteed. So in creating 10 principal components, if it is able to just keep 70% information, that only it will be able to do. So here now you don't have control over how much information you will be able to retain. It will just say that, okay, I'll make 10 principal components, but how much I will be able to retain, that I will see. You don't have control over that. So better one is we try to do this because this is more better for us and we use that. Now, as I make an object of this, then we have to just transform our data using this PCA. And how are we going to transform that? Simple. So we'll say PCA.fit transform, and which columns I have to transform? Input columns, not the output column, just the input column. So I say PCA.fit transform, in which variables our input columns are stored. We have two variables, xtrain and xtest. Correct. But now we have another two variables. One is xtrain scaled and xtest scaled. So which one are we going to use? These scaled version of xtrain and xtest we are going to use, not the normal one, because we have to do the mean centering. After that, we have to do. See, there is no difference in that. You can use xtrain and xtest. Just that when you use the scaled version of train and test, the calculation will be faster and you will be able to do this process faster. That's it. The speed matters. Okay, so I'll say PCA.fit transform, and with the fit transform, I'll give the xtrain scaled, and then I'll say PCA.transform, just transform with the testing part, xtest scaled, right? Xtest scaled. Now, as I have done that, what I'm going to do, I'm going to store the result into two new variables, xtrain PCA is equal to this, and I'm going to store this into another variable, xtest PCA is equal to that, right? So basically we have three different variables related to xtrain and xtest. One, we have normal xtrain and xtest. Then we have xtrain scaled, xtest scaled, and now we have xtrain PCA, xtest PCA. So this is my final version of xtrain and xtest where we have done the PCA transformation. So you are going to run that xtrain PCA and xtest PCA. After that, what we should do now, after we have done that, let us check the shape of how many new principal components have been created here. So I'll say xtrain PCA dot shape, right? So you now see that 22 new columns have been created with that. Correct. 22 new columns have been created. So these are my 22 principal components that has been created. Now what I will do, I will now run the logistic regression again on the PCA scale data. So I'm going to say this xtrain PCA ytrain, and then we are going to say xtest PCA with this and see the result here. Correct. So ytest and y predicted to. So see what has happened, right? See what has happened here. So take a look at it. We now have 92.58% before PCA. Correct. Before PCA. And how much we are getting after PCA? How much we are getting? We are getting 92.77% after PCA. Right. This is something that I wanted to show you. That is why I picked this data set. You see that what is happening? When I had 42 input columns, okay, 42 input columns were there originally. We scaled that and I explained how the scaling is done, why we did the scaling. So now 42 input columns we have taken and we have scaled that. And now when I applied the logistic regression on this data, logistic regression, what is the accuracy we are getting? 92.58% before applying PCA on the data set, right? Till now, the data is only scaled and we applied the logistic regression on the scale data. We got 92.58. Now we take this scale data and what we did on this scale data, we did the PCA transformation. Because before doing the PCA transformation, we do the mean centering and then we do the PCA transformation. So we take the scale data, X trend scaled and Y trend scaled. We took that and we created PCA transformed data. Correct? Now, as I created this PCA transformation data, then when I applied logistic regression on that, on this PCA transform data, how much accuracy we are getting? 92.77%. So we are getting a 92.77%. So 92.77% we got as an accuracy after PCA. So you can now see that after the transformation, we had just 22 input columns or 22 principal components, right? And we have reduced the number of columns, but the reduction was done in such a smarter way that our accuracy even improved by reduction of the columns. So which means that earlier these 42 columns were weak and normal, but after combining, we created such powerful input columns that it is giving almost the same result, or you can say little bit better itself we got with less number of columns. So I hope now you're able to see that before and after result. Before we had 92.58, after we have 92.77. So it is not that it will always be same as the original one. It can be lesser than that, it can be higher than that, it can be same. But you will see that after PCA, whatever result you are going to get will be almost the same. Now, why did I do the scaling before logistic regression? It was just that I took a scale data. Scale data you take anywhere, it is not an issue. With any algorithm, with any process in entire machine learning, if you take the scale data, it is beneficial always because it will make all the calculations easy. So with logistic regression, if I use that, it will make it just faster. So no problem if I use it anywhere. With PCA, it is very important to do the scaling for faster calculations. But if I did the scaling and I use it with logistic regression, it will also become faster. So scaling is not a problem anytime. You can do it anytime. Now, okay. And one important thing, I'll explain one more importance of doing the scaling on the data set. I'll come to that. But you see, scaling you should always do after doing the split of the data. Okay. You should always do the scaling of the data after you have split it into this training and testing. Always after that, never before, right? Always. That is the important thing you have to keep in mind. There is some issue happens if you do it before. So for now, just keep in mind, scaling should always be done after splitting that. And you will be doing it on extend and extest after splitting. Okay, right.
Just a quick info, guys. Intellipaat offers a data science course which will help you master Python, SQL, machine learning, AI, and Power BI. Get a data science certification from IIT Empower, an innovation hub of IIT Madras. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given in the description and take the first step towards the career growth with the data science course.
LDA concept. Why do we need this LDA concept if PCA is already there? Because when I talk about dimensionality reduction techniques, two techniques are there. One is PCA that we understood and one is LDA. Two concepts are there, PCA and LDA, right? Now see that if I said already that PCA can be applied on all type of data, then why do I need LDA? Because PCA can be applied on classification also, right? So that is the thing now you have to understand. Why do we need LDA? LDA is a concept that is used for dimensionality reduction like PCA. But LDA is only used for classification. You can't use it for any other data like PCA. It is only for classification. Now let's understand, why do we need LDA? What is the problem with the PCA? Why do we need LDA? That is the thing. Let's see. So we have income and CIBIL score. The same example I'm taking for LDA explanation also that we have taken for PCA. Now see, when we work on a classification data, then there are some situations. In the classification data, if you have one column called as income, one is CIBIL score, two input columns are there and one output column. So whatever data you plot it using the input columns, correct? Input columns. So if you see here, as I took this data set, which has two input column, and as I plotted that, you see the data set look like this. And it is a classification data set. When I plotted that, you see that it looks like this. What you do in classification, you are going to make a decision boundary that separate these two categories of data into two separate sections, correct? The main task of classification is what? The main task of classification algorithms is what? It is to make a decision boundary. So either you use logistic regression or decision tree or random forest, any classification algorithm you use, it will do what? It will be separating the data points into two separate sections by making a decision boundary. This is one situation. Now, when you have a data like this, you can just use one decision boundary to separate them into two sections. Correct. Now, some scenarios can be like this, where you will need more than one decision boundary. To do the classification, you need more than one decision boundary. Some situations can be like that. But in the classification, you can have one situation like this. Okay. You can have one situation like this in classification, right? So you plotted the data and you see that your data points are totally mixed with each other. There is no separation point that is visible to you. Okay, there is no separation point visible to you. So now take a look at it. In this case, in this scenario that you see here, your classification data, this is your classification data. Okay, I'm working on a classification data set, and one scenario is like this. The data set, when I plotted, it is such that you can separate it with one decision boundary. One is enough. And now this data is very much separable with each other. So now, for now, it is two-dimension classification data and it is separable for now. Correct. Originally, it is separable into two sections. I can clearly see that. If I apply PCA on this, will PCA be able to convert this into one dimension, and will it be able to work on that? So I can say yes, if I apply PCA on that. So what PCA will do, PCA will make a line like this. PCA will make a line like that, and it will just do it will project the data points on that, right? After it projects the data point on that, how will you see this one dimension data? How will your new axis look like? You see that on this part of the line of this new axis, you will have the green dots, and on the bottom part of the line, you will have all the red dots, right? Being mirrored on that or being plotted on that. So it will look like that. After doing the transformation, you will see that on the bottom side of this line, you have a lot of these pink points like that. And on the higher side of this, you're seeing that this is the case. What I'm trying to explain you here, when I took the classification data, original classification data, it was two-dimension and it was separable. Means I can clearly see that there is a separation in this data, and this classification data is 2D, which is separable. I can make a PCA, I can apply PCA on this data set, and I will see that this line will look something like this, and I can make a decision boundary here, right? I can make a decision boundary here. So I took a 2D data, represented it as one dimension, transformed it to one dimension, and then I can make a decision boundary, and you can clearly see that there is a separation. So in 2D also, I can make this decision boundary to do the separation. In 1D also, I can make a decision boundary here on this data set, and there is a separation, correct? Now, same thing, in this case also, if I give this data to PCA, so this is 2D separable. PCA will be able to work in this case also perfectly fine. So this data, this classification data, which is originally separable, okay, originally it is separable. So if I provide this data set to PCA, somehow it will be able to convert that to one dimension, and it will also be properly visible to us. I can make a decision boundary and I'll see that left side and right side will have the data. In this case, you now see that we have a situation like this. In this situation, do you think PCA will work? Right. The data which is in two dimension, this classification data which is in two dimension originally, it is not separable. It is a inseparable data. Means if I make a decision boundary now, will the decision boundary will be clear to us in this case? So you see that no matter where I make a decision boundary, no matter here, no matter where I make decision boundaries, it will not be able to separate this data set, right? And now I'm saying that if I have a classification data set like this, which is inseparable, if I give this data to PCA, what will be the situation? So let's say I make a new axis here. This is not our decision boundary. This is our new axis, the principal component I'm trying to make. So now if I represent it like this as a one dimension, after you make the projections on this line, so will it not be like this? It will be right. And you'll see that the green points also will be totally mixed in that. Correct? So your two-dimension data was also inseparable. And if your original data is inseparable, if you give that data to PCA, the PCA will try to project that onto one axis. And if you look at that line like this, you will see that the transformed version of that data is also inseparable. So now, can you provide this data to any classification algorithm? Can you provide this data to any classification algorithm to work on that? No. Correct. Because anywhere you make a decision boundary, you see anywhere, you are not going to see a clear type of data on any side of any decision boundary. Correct. So now I hope you're getting the point here. I'm trying to explain in classification, there is a situation like that. Only in the classification data set, there comes a situation like this, that your original data, which is in, let's say, 2D, 5D, 10D, original data is inseparable. Means you can't make some decision boundaries to separate the data. Your original data is inseparable or very difficult to separate into two sections. So that data, which is 2D in this case for now, which is totally inseparable in classification, if I try to make a decision boundary, it will not work. Now, if I say that if originally it is inseparable, what if I try to transform this to one dimension? This type of data, if I try to transform to one dimension, so will I be able to transform it correctly or not? So I will be able to transform it. I will be just able to make all the projection of all the data points onto this line, right? But you'll see that it will look something like this. So on 2D, you can't make a decision boundary in this case because it was not separable. When you converted that to one dimension from this to this is also being created in such a way that you can't give it to any algorithm to work on that, right? So what you see here in this specific case, PCA fails. It can do the conversion. It can transform a 2D data to one dimension data. But the problem is not with PCA. The problem is that your original data is inseparable. So after transformation also, it will be inseparable and any of the algorithms will not be able to do the classification on that, right? For this particular case, you are going to need LDA, right? For this specific situation where PCA fails in this specific situation, so then you are going to use LDA. LDA will do the transformation for you, correct? This part you should all understand. You should be clear about that. Why do we need LDA? If I already have the PCA, which was doing the transformation for us, which was converting a higher dimension data to lower dimension, why do we need LDA? We need LDA only in the classification, only for this specific scenario. Otherwise, everywhere else, PCA will be helpful for us. But in classification, for this specific situation, we need LDA. Now, so if you're clear with this thing that why do we need LDA? Where do we need LDA? So LDA is not to be used everywhere. It is only to be used in this specific situation of classification. So let's understand now how LDA will do this thing and the working of LDA, because that is the only thing we have to understand. Rest every concept is same as the PCA. To solve the problem of inseparable classification data set, we use the LDA. LDA will do what? LDA will project the data onto new axis to make the data easily separable. Now the thing is, LDA was mainly created for the purpose of making your classification data separable, right? The main reason why LDA algorithm was created, this LDA method was created, LDA was not originally created to be a dimensionality reduction technique. Okay, LDA by default, it was not supposed to be a reduction technique. But what it was designed to do, it was designed for this specific situation. It was designed that whenever your classification data is something like that, which can happen in many situations, if your classification data you plotted and it is inseparable, it is totally mixed with each other. So for that situation, we can make inseparable data separable by doing some sort of transformations in the data. So LDA is mainly responsible for making a inseparable classification data separable, to separate them into two sections so that we can make a decision boundary easily. But the thing is, while it is doing that, while it is making a non-separable data into separable data, while doing so, it automatically reduces the dimension of the data. Automatically, correct? It is automatically going to reduce the dimension of the data. This is the main thing that you have to understand. So LDA does the dimensionality reduction, but it was not specifically designed to do that. It does something else, but when it is doing that thing, it automatically does the data reduction or dimensionality reduction. Okay, so this is the only theoretical thing that you have to know. No, you will be either applying PCA or LDA, not both, one of that. So let's now understand the mathematical working of LDA. Theoretical thing is clear. Why do we need it and what it is going to do? That is clear. But let us now see how it will do that thing. How it is going to make inseparable data separable, and then how do we do the data reduction, dimensionality reduction? How do we recognize that the data is inseparable? Because the issue is we can't see. In this case, the new axis that the LDA will create, LDA does the exact same thing which the PCA does, just with another technique, another style. LDA also says that if you give me a data set, I will be making axis in the data, and all the data points will be projected on top of that, same like PCA. But the way I will decide the best axis, that is different. Correct. The difference between PCA and LDA is that we were using this formula, D1 square plus D2 square dash dash dash. This was the formula used in PCA. And this helped us to understand which axis is our best axis. Okay, or where our best axis is. This formula helps us to find out that. Correct. And whichever line gives us the smallest value of this overall distance, that is our best axis in PCA. But in LDA also we have to find out the best axis, but we have to do it in another way with another formula. That is the difference. Otherwise, once we found out the best axis in LDA, we just have to project the data points on that. The difference between them is in the formula we use to find out our best axis. But once we got the best axis, then we just have to project the data points onto the line. That is it. That part is same, but the formula is different to find out our best axis. Okay, now see. So the new axis that LDA will create should follow these two criteria. The new axis that the LDA will create should follow these two criteria both simultaneously. Means at the same time, we have to follow two different formulas or two different criteria on the basis of which we'll be able to find out which is our best axis. So is our best axis here, or is our axis here, or is our axis here? So which is our best axis? To find out that, the LDA says that we have to consider two situations. What was the PCA saying? We have to only consider this situation. Whichever line has the least value of this formula is our best axis. PCA was saying that only one formula. But LDA says that we have two things, two conditions that we have to focus on at the same time together to find out the best axis. Correct. Now, you see, the decision boundary and axis is two very different things. Decision boundary is to separate the data point, and axis is to project the data points on that. Now, so new axis is going to be created in the LDA following these two methods, right? How it will do that, you see here. The first criteria in the LDA, which we have to see, is used to maximize the distance between the means of two classes or categories. When I create a new axis using the LDA, we have to maximize the distance between the means of two classes. One criteria is that. Second criteria, minimize the variation or spread within each class or category. So when I focus on both of these conditions together at the same time, then I will be able to find out our best axis. Then once I found out our best axis, we just have to project the data points on top of that. That's it. Right. Now see. So what do I mean by maximizing the distance between means of two classes or categories? And what do I mean by minimize the variation within the class? What do we mean by class here? I think I might have told you what does this class means. Class means nothing but if I had the play column has yes and no, right? Play is our output column, and this output column has yes and no, two categories. So this is called as one class. This is called as second class. So two classes are there, which means that two categories are there in our data. And what we do in the classification, we take a future input and we predict the value of that, whether it is going to be yes or no. So what are we doing? Every future input value, we are putting into either yes class or we are putting into no class after prediction. This is why it is called as classification. Okay. So class nothing but the categories in the output column, those are called as classes. If two categories are there, two classes are there. Three categories are there, three classes are there. That is what the class means in this case. Okay, now see. So the situation is we have to minimize the distance between the means and maximum the variation. To understand that, we are making some symbols here. So we have mean of the red points, or if let's say red is our all the yes points. So mean of the red points and variation of the red data points or the yes data points, for example. Then we have another class, which is no. So mean of the no data points or the points which are no, I'm representing that with green color. So why am I writing green with no? Just as an idea that in classification, what we do, the dots are being created using what? Input columns. Means if I create a dot here, a dot represents these input values. The coloring of the dot we do on the basis of output column in classification. Coloring, right? So that is what I'm saying. If let's say red point is representing your yes data points, correct? And green point is representing suppose your no points. That is the thing. So we have to take the average of all the red points, correct? And we have to say the average of all the green points. Now, then here we have variation of the green points or variation of all the data in which are the green points. So you have mu r and SR square, and you have mu g and SG square. This symbol that you have here is called as mu. It's a Greek symbol and it is called as mu, which is representing the mean of the red points, mu r, mean of red points, and mu g is the mean value of green point. Using these four symbols, mu r, mu g, SR square, SG square, we create this formula. So this is the formula which we have to see. This is the main formula of LD. Whichever line maximizes this formula, that is our best axis. Okay. So we are trying to understand which line is our best axis. And once we identify our best axis, that's it. So our main concern is to find out our best axis in this case. In the PCA, we had this formula, d1 square plus d2 square plus dash dash dash. This was our main formula in PCA. And what were we trying to do? We were trying to minimize. Minimize means what? Whichever line gives us the smallest value of this formula, that is our best axis. Correct. Best axis we were finding out, that was that line which is having the smallest value of this formula in PCA. Same way, in whichever line gives us maximum value of this formula, we are maximizing it. Whichever line gives us the maximum value of this formula, that is our best axis. This is the main formula, right? So in this main formula, we have to maximize the above part, minimize the lower part. And when we are able to do that, overall, we are able to maximize this above formula. So what I'm saying, suppose this is our data set in classification, correct? Suppose this is our data set in classification. And in this data set of classification, I want to make an axis which will help me to reduce the dimension, right? So this data set is a 2D data, and this data is separable, correct? You see that this data is separable. I can directly make a decision boundary here, and it is separating my data into two sides. This is my decision boundary. The work of decision boundary is to separate them into two sections. But I'm saying that I don't want to make a decision boundary now. I first want to separate the data into two sections. I first want to convert this data or transform this data from 2D to 1D. Then I will make the decision boundary. This data is a classification data. If I want to make a decision boundary now, I can make it because it is clearly separable. I can make this decision boundary and it will separate my data into two sections. Perfectly fine. You can do that. But what I'm saying is, I'm saying that I don't want to do the classification on the 2D data. I first want to reduce the dimension. Then I want to, then I want to do what? Then I want to make a decision boundary. First reduce the dimension, then make the decision boundary. So who will reduce the dimension? LDA. Who will make the decision boundary? Logistic regression. Okay, this you should not be confused about. So reduction, dimensionality reduction with LDA or PCA, and the decision boundary with logistic regression. So PCA is working, we have understood. But let's say, how does the LDA work? How does it know where that best axis should be created, which will do the separation very properly? Let's understand that. Suppose I make one of the axis here. This is not my decision boundary. This is our axis for data reduction or dimensionality reduction. Let's say this is my new axis that I have created. Is this good, or should I create it somewhere else? So now we have a axis here. Now this axis, is this the best axis, or should I create another axis here? Right? Should I create another axis here? Should I create another axis here? Should I create it here? Should I create it here? Where that axis should be created, we are trying to identify that. So I'm saying, suppose I take this as an axis. How do the algorithm know whether this axis is good for the data separation or not? How will it know? Correct. So I'm saying that if I make this, then what happens here? So when I take this new axis, we are going to make a projection of all these points on this line. Project all the data points onto this new axis. Don't confuse this with the decision boundary. On decision boundary, we don't project the data points. Decision boundary is created to separate them into two sections. Axis is supposed to project the data points on top of that. Major difference in that. Okay. So now, as I took this new axis, I'm just going to make a projection of those points on the line. Now, when I make the projection of all the dots on the line here, then how will LDA know whether this is the best axis or not? How will LDA know? So in this case, if you now see, we have this situation. We have projected the data points on top of that, and now they look something like this, right? You see here. So after projection of the data points on top of that, when I represent this line individually, it looks something like this. Because you see, on the bottom part of the line, we have all the red point projections, and on the top part of the line, we have the green point projections. So this is the top part of the line. This is the bottom part of the line. We are representing that individually after this projection. So now how will your LD algorithm know that this is the best one or not? How will it know? So it has to use this formula to find out whether this axis is best, or is there another axis which is even better than that? How will it know? So there are few calculations you have to do. First thing you have to optimize, or first thing you have to keep in mind, is the distance between means of two classes or categories should be maximized. What do I mean by that? Is this. See here. See this example. So after projection, these are my green points, which is one class or one category. Then this is another green points, which is another category, right? So what I have to do now, I have to now find out the average of the green points. We have to find out the average of the green points, and you know that average of the green point is the center point, measure of central tendency. So this point, if you notice here, it is your mu r. Okay, mu r. Then if I talk about the green points, the average of the green points will be what? Average will be also in the center of these 5 points. And let's say it is this. So now this is what? This is the mu of the green points, average of the green points. Correct? So mu of red points, mu of green points, that is what we have. Right? Now see. So what we have to do, the distance between these two have to be maximized. Correct? We have to maximize the distance between the average of these two groups. Clear? This is what we have to maximize. At the same time, what we also have to do, at the same time, you see that the spread of the data points, the spread of these red data points is represented by SR square. The spread of the data point have to be minimized. SR square should be as low as possible, and at the same time, SG square also has to be as low as possible. So overall, what I have done now, See what I did? I took the actual data points that we have all the actual data points, right? The green points and the red points, we took the data points. Those were my actual classification data points. I took that. What I did then, I made an axis, right? Now I'm trying to understand whether this axis is the best axis or is there any other axis better than that? Which is the best one? So I'm saying, let's say, for example, if I took this axis, how will LDA identify whether this is our best axis or not? How will it identify what it is calculating? So it is doing that. After taking that axis, you projected the data points onto that axis. Then you are going to calculate 4 things: the average of the red points, average of the green points, then the variation of the green points and the variation of the red points. So variation of red point is this SR square. Variation of the green point is this SG square. Variation means what? Variance. Variance you are calculating. SG square and SR square is the variance of those two groups. You don't have to calculate. Everything will be done by the algorithm, but this is what we are calculating. Clear? What we will do now after calculating that, we will use this formula. Mu R minus mu G square, SR square plus SG square. This is a fixed formula we have to use. So what will be the first part? The distance between mu R to mu G square, that divided by this value plus this value. So you now notice that we have this formula that we have. Now, after calculating that, suppose we found out that this is 980, mu R minus mu G square, for example, is 980, and SR square plus SG square is, let's say, this is 422 and this is 475. Because what are these values? These are nothing but the overall spread, the variance of those groups. Correct. So for example, we had this 980 by 422 plus 475. What we have to do in this case, we have to find out such a new axis which is having a very high value for the above part and very low value for the bottom part. For the numerator, we should have as high value as possible, and the denominator part should be as small as possible. Means, what does it say? That the distance between the mean of red and green should be as high as possible, and the variation in each group should be as low as possible. What do we mean by that? Let me show you another example that will make it even clear for you. So now, what we are now going to do, let's say I take another axis like this. The first axis, how I have taken that? The first axis was taken like that, this one. And when I took that, let's say I got the values like 980 by 422 plus 475, right? Let's say I take another axis, this line, right? In this one, we have another line here, which is another axis here. And you see that you will be projecting the data points on that. So let's project the data points on that, right? Let's project the data points on that. And you project all the data points on this, correct? After projection, how do they look like? They look something like this. When I show this line here as an individual line, how does it look like? So you'll see that all the green points which are here are very close to each other, and all the red points are also very close to each other, correct? So if you now see that there is a line here, there is this axis here, which is having this kind of situation. What we will do now, we will calculate again the mu R, mu G, SR square, SG square for this situation, for this case now. Then what we will do, we will use this formula, mu R minus mu G square divided by SR square plus SG square. Now, in this case, if you see that these are not very far away as earlier. In this case, the mu R and mu G were very far away from each other, but they are, let's say, not very far away. So let's say the distance overall between them is 520. This distance between them squared is 520. But you now see that the variation in the S red group and the variation in the green group is also less. So let's say variation in the red group is overall 98 total spread, and the total spread in green group is overall 122. Correct. So we have 520 divided by this. So now, is this line doing a better task? Right? Is this axis doing a better task of dimensionality reduction, or is this line doing a better task of dimensionality reduction? Which axis is better for reducing the dimension? That we have to find out. So what we will now compare this 980 divided by 422 plus 475. Correct. This is the one and this is the one. So we have how much? 980 by 422 plus 475. You see that which line is fulfilling this criteria overall? Which line is fulfilling this criteria overall? The first line or the second line? If you will see that what we had to maximize, overall, this equation has to be maximized. Whichever line gives the maximum value or highest value of this formula, that is our best axis. So out of these two lines that we are comparing here, which is doing that task, so you'll see 980 divided by this is overall 900 something. So 980 divided by 900 and 520 divided by 200 something, right? So 520 divided by that, this is a bigger number compared to this. So which is our best axis now? Out of these two comparisons, the second one is our best axis. So similar to that, if let's take 4 different axes, they are giving these kind of values. Correct. They are giving this kind of values. So which is our best axis out of these 4 lines which are giving these kind of values? This fourth one will be best because the fourth one is maximizing the numerator value and minimizing the denominator value. This should be as low as possible. This should be as high as possible. So out of these 4 lines, the fourth line is maximizing the above part and minimizing the bottom part that we have to do. And that's it. The entire mathematical concept of this LDA is just that. We have only a one simple small formula which says that make an axis and check this formula for that axis, right? How much is the distance between the means and how much is the overall variation in the group? So whichever line is maximizing this formula, that is going to be our best axis. So what did I tell you about the LDA? LDA main focus is what? LDA's main focus is to make your data separable. It is not focusing on reducing the dimension. LDA's main focus is that I will be transforming the data in such a way that your classification data will become more separable. It will be clearly separable. And while it is doing that, it will automatically reduce the dimension. Correct. It will automatically reduce the dimension. This part should be clear to all of you. This is something you have to remember. LDA is not focusing on reducing the dimension directly. It is focusing on making the data separable. And while it is doing that, it is automatically reducing the dimension. But how? You see, once I found out that this axis is best, so I will now be projecting all the data points on that. And this is now a one-dimension representation of this two-dimension data. So this is our original two-dimension data. As I found out this is the best axis for me in this data set, I project all the data points on that, this best axis. And once I project it on that, then this is how the data will look like. So now you have reduced the dimension from 2 dimension to 1 dimension. This is 1 dimension data. So this 1 dimension data is separable also and also having less dimension. Correct. So this is what we are able to achieve with LDA. I know some confusions will be there, but you watch PCA and LDA means sequentially, then you will be able to get this point easily. This SR square that you see here, it is the spread of the data in that group. Red group and green group, 2 group of data points are there. Yes and no, 2 classes of data are there. So SR square is the variation or spread of the data in one group, and SG square is the variation of the data in another group. Correct. You can call them S1 square and S2 square to say that one group, second group. That also you can say, but I just use SR square, SG square. So to represent that, the green group and red group. The entire mathematical process of LDA is just this much. That is the thing. So PCA, when you have to use, PCA you have to use on all the data, right? PCA you have to use on all the data. LDA when you have to use, LDA you have to use on the specific part. Yes, LDA you have to use on only inseparable classification data. Okay, remember this part. LDA to be used on inseparable classification data and PCA to be used on all the data, right? Now, both we have to use only when it is required. PCA, LDA, whichever I'm using, we have to use them only when they are required. Otherwise, I don't have to use that. Correct? That is the thing. But PCA can be applied on all the data, any data, and LDA only on inseparable classification. You can say that is what I answered just in few minutes, that if you are using PCA only when other options are not working well for you. It is not that you have to apply PCA, right? PCA is not something that we have to definitely apply. It is very optional thing. If you think that other things that you are using are not working, and only a final option left with me is I should apply PCA, then only you apply PCA. Otherwise, no need for that. If you are able to remove the overfitting, or if you are able to control the multicollinearity with other options, other measures, so then you don't have to use PCA. PCA is saying that when you tried other options and still you could not control the overfitting and multicollinearity, then PCA is the last backup option you should try. That is the thing. But for now, remember that PCA is to be used as a last backup option when other options are not useful for you. Why? As a backup option? Because after applying PCA, your data is not explainable. You can't explain the data, what is happening in the data. There is no understanding of that. The question is, how do I know my classification data is inseparable? How do I know? Because we can't plot the data to see that it is separable or not separable. How do I know? It is going to be done like that. It is very simple. You take your data, which is your classification data. Your data is classification. And to know whether your data was inseparable or not, you will be doing that. Let's say you took this classification data, you did all the process, everything, cleanings and everything you did, and you give it to logistic regression, you give it to again decision tree, you give it to again random forest, right? You are giving the classification data to multiple of them, and you say that these are giving very bad scores. This example I've related to PCA. Same situation is here in this also. Percent with that, 71% with that, and 73% with that. I took a classification data, I gave it to different algorithms, and they are giving this much of accuracy. Now I tried all the other methods and I'm not able to improve their accuracy from this. This is the final that I'm getting. What I can do now, I can apply PCA on that, right? PCA on that. Now, if the problem of this was because of a high dimension, you see that the problem of this low accuracy, if it was because of high dimension, then PCA will be able to solve that. So when you give it the data to PCA, and after that, again, if you give it to logistic regression, you'll see that earlier it was 68%, but now it will be, let's say, it came up to 83%, something like that. So when you gave a data to these algorithms and you saw that these are giving very low scores, so you said that let's give it to PCA. When you gave it to PCA, if the problem of less accuracy was because of high dimension, then your PCA will solve that problem. It will give you now a higher accuracy after PCA transformation on that data. But now the thing is, if the issue in this classification data is because of inseparability, right? The problem is because of inseparability, not because of high dimension. So PCA, when you apply the PCA on this data, which is inseparable, so what you will see that after PCA transformation also, you're getting like 69% or 68%, same score you're getting. Means PCA is not able to solve. What might be the reason of that? PCA was not able to solve this classification, was not able to improve this score because the problem is not of this in that data, the problem of this. So you will take it and you will apply LDA on that. And LDA, if it improve the score to 83%, let's say from 68, then you will know that our data did not have this problem, our data had this problem. So only way to know whether your data is inseparable or having a dimensionality issue is checking the scores before and after. That is the thing. Otherwise, there is no such tool which can tell us this kind of situation is there. But only way is that you have to use this, right? Only method of finding whether these issues are there is this. Okay. Again, understand this, that we have a data. When you provide it to the algorithm, if they are giving bad scores and you tried everything else, it is not working, you'll try PCA first. If the problem was of high dimensionality in the data, PCA will be able to transform the data in such a way that your accuracy will improve. But if After PCO also, if the accuracy did not improve, then you will say that let me try LDA. If LDA was able to improve the accuracy from 68% to 83%, then you will say that the problem was not of high dimension, it was of inseparability. And that is why LDA worked on that data, PCA did not work on that. So eigenvalue, right? I was talking about, say this PC1, PC2, PC3, PC4, correct? So now, in the case of principal components, these principal components which are there, they are called as eigenvectors. They are called as eigenvectors. Okay, these all the principal components. This is the mathematical name of this principal component. Now, in that you said that when you have your original data, right, your original columns, you gave your original columns to PCA, and you got what? You got those principal component PC1, PC2, PC3. And in this process, you also were able to mention how much information you want to retain while doing this transformation. You said 95%. The thing is, there is this property of this principal component that your first principal component, PC1, will be able to keep most information after extracting that. Means out of this 95% data that we are keeping in these columns, the PC1 will be able to hold most of that alone. So let's say PC1 is able to keep, or PC1 is able to explain 27% of that 95% data. I wanted to keep, while I was doing the transformation of the data, I wanted to retain 95% information, right? So out of this 95%, the PC1 is the most powerful or the most important principal component. This alone will be able to retain most of the information from the original data. So this percentage, the amount of data it is able to extract from the original data, this is called as our eigenvalue. Eigenvalue. So 27% can be represented with 0.27, which is 27%. So this number is our eigenvalue. Let's say PC2 is able to explain 18% of 95%. It is able to extract that. So this is eigenvalue of PC2. So we have multiple eigenvalues and multiple eigenvectors in LTA. Yeah, eigenvalues are just numbers. Those are scalars. These are just numbers. And eigenvectors are your columns. Okay, because what is a vector? Vector is either a column vector or a row vector. So PC1, PC2, PC3, these are columns. So that is why they are vectors. These are eigenvectors. And these values are just single values. Those are scalars and they are called as eigenvalues. Right. No, we can't visualize it for now because we have 28 principal components. You can't visualize them. Fit transform we use because when we do the transformation, this is the formula used, data minus mean upon standard deviation. So you calculate the standard deviation and mean value of each column when you are working with xtrend. Okay, so mean and standard deviation you calculate of each column when you are working on xtrend. That is why fit means learning these values of each data. Then transformation means doing the actual transformation, scaling the data actually, right? But in X-test, we don't need to learn. Whatever mean and standard deviation we have already calculated, using that we will do the data transformation. So for X-test only transform, and Xtrend, fit and transform both.
So moving on with our first question. Explain the types of data science problems along with the datasets used for each problem. Data science problems can be grouped based on what we are trying to solve. For example, one common type is classification problems like fraud detection. Here the goal is to categorize data into classes such as fraudulent or non-fraudulent. The datasets here are usually highly imbalanced, meaning there are far more non-fraud cases than frauds. Sometimes these datasets can even have a time series structure. Another type is regression. This is where we predict a continuous value. For example, predicting house prices. Datasets here might have features like the number of bedrooms, location, and property size, and the target variable would be the price feature. Then there is time series forecasting. This is used to predict future values based on historical data. A common example is stock price prediction or sales forecasting. Another type is recommendation systems. This is where we suggest items like movies, products, or songs. The data sets often include user preferences, item characteristics, and sometimes behavior logs like clicks or purchase history. Lastly, we have clustering problems like customer segmentation. Here we group similar entities based on features like age, income, or spending habits. These datasets don't have labels, so we look for patterns. Each type of problem has its unique dataset structure and challenges, but it's all about understanding the data and the problem we're solving. Moving on to the second question. What are the common issues in raw datasets that require cleaning? One common issue in raw datasets is missing values. Some rows or columns might be incomplete. For example, in a dataset of customer records, you might not have some records in the contact number feature column. This can be solved by the following methods. For numerical columns, we can fill them with the mean where there are no outliers, whereas median in case of outliers. And for categorical data, we can fill with the mode. Another issue is duplicates. This is where the same data point appears multiple times. This often leads to skewed analysis. The duplicate function can be used to identify the duplicates. There could also be outliers in the data, like a few incomes could be way too high or way too low compared to the rest. This would again lead to inaccurate prediction. You can use scaling methods like standardization or normalization to deal with outliers. I have a separate video on standardization versus normalization. You can check it out in the description. Inconsistent formatting is another big one, like dates in different formats or text fields with varying capitalization. And then there's incorrect data where entries are just wrong. So say for example, a negative value in a column for age. All the above issues can be taken care of at the data cleaning stage itself. The data needs to be accurate, consistent, and reliable for analysis. Moving on to the third question. What are the different learning mechanisms in data science? So there are 4 main types: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. In supervised learning, the model is trained on labeled data, meaning we already know the outcome. It's like teaching a child with examples. So say in email spam detection, we know which emails are spam, so the model learns from those examples. Next is unsupervised learning. This is where we have data but no labels. The model tries to find patterns or groupings by itself. A good example is customer segmentation, where the algorithm groups customers based on their purchasing behavior without knowing what each group represents. And then there is something known as semi-supervised. This is a mix of both. There will be a small amount of labeled data and a large amount of unlabeled data. The model uses the labeled data to learn and then generalizes to the unlabeled data. It's useful when labeling data is costly. Finally, we have reinforcement learning. Here the model makes decisions and gets feedback in the form of rewards or penalties. It's commonly used in gaming or robotics, where the model has to learn to improve its actions through trial and error. Moving on to the fourth question. Why is standard deviation often preferred over variance when analyzing data? Both variance and standard deviation measure how spread out the data is. But the key difference is that variance is in squared units, while standard deviation is in the same units as the original data. Let's say we're looking at the test scores of a class of students measured on a scale from 0 to 100. If we calculate the variance, it would give us the number in the units of squared points, say something like 25,000. Now, this is not easy to relate to the actual scores. However, when we calculate standard deviation, it's in the same units as the original data. In this case, just points. So if the standard deviation is 50, it's much clearer because we can directly understand it as the spread of scores around the average score. Standard deviation just makes it easier to relate to real world values. Moving on to the fifth question. What is overfitting and underfitting, and explain how you can detect if your model is overfitting or underfitting. So overfitting happens when the model learns the training data too well, even the noise and the random fluctuations. It performs great on the training set, but struggles with new unseen data because it's too specific to the training data. It's like memorizing answers to a practice test without truly understanding the material. On the other hand, underfitting happens when the model is too simple to capture the patterns in the data. It fails to perform well on both the training set and the test set. It's like studying just the basics and missing out on the important details. In order to detect underfitting or overfitting in your model, you need to look at performance metrics like accuracy or error rates and compare them between the training and the test sets. To deal with overfitting, you can either reduce the number of features or use techniques like regularization or cross-validation. Whereas for underfitting, you would want to make the model more complex. This might involve adding more features and increasing the model's capacity. Moving on to the sixth question. Explain the concept of regularization in machine learning and why is it important for improving model performance. Regularization is used to prevent overfitting by adding a penalty to the model for being too complex. Essentially, it discourages the model from relying too much on specific features or learning noise in the data. There are two types of regularization techniques. First is L1 regularization or lasso regularization. It adds a penalty based on the size of the model's coefficients, making some of them shrink to zero. This way, it automatically selects only the most important features and ignores the rest. For example, in house price prediction, if the number of garage doors has little impact, L1 regularization might set its weight to zero and exclude it from the model. The next one is L2 regularization or ridge regularization. It adds a penalty based on the square of the coefficients. This reduces their size but doesn't make them zero, so all features are kept but none dominate too much. For example, in predicting house prices, if the area feature has a large impact but the number of rooms has a smaller impact, L2 regularization will ensure that both are considered while preventing the area feature from overpowering the model. Regularization is important because it helps the model generalize better to unseen data by controlling complexity and preventing overfitting. Moving on to the seventh question. If a model performs well on training data but poorly on unseen data, what technique could you use to understand its generalization ability? This is a classic case of overfitting. To understand the model's generalization ability, we can use cross-validation. With cross-validation, we will split the data into multiple smaller sets or folds. The model is trained on some folds and tested on the others. This process is repeated multiple times and we average the results to see how the model performs across different subsets of data. It's a great way to check if the model is consistently good across various splits or if it's just memorizing the training data. Moving on to the next question. What is the role of activation functions in machine learning models like linear regression and logistic regression? Activation functions are used to introduce non-linearity into a model, which allows the model to learn complex patterns in the data. In linear regression, there's actually no activation function because the output is simply a linear combination of input features. It's used for predicting continuous values. In logistic regression, however, we use the sigmoid activation function, which squashes the output between 0 and 1, making it suitable for binary classification problems like predicting the yes or no outcomes. So the main role of activation function is to help the model make more accurate predictions by capturing complex relationships in the data. Moving on to the next question, what is the confusion matrix, and describe a situation where false positive is more important than false negative and vice versa. A confusion matrix is a tool that is used to evaluate the performance of a classification model. It shows how well the model's predictions match the actual outcomes by displaying the number of correct and incorrect predictions. It's basically a table with 4 values. One is true positive. These are the correctly predicted positive cases. Then there are true negatives. These are the correctly predicted negative cases. Third is the false positives. These are the incorrectly predicted values as positive, also known as type 1 error. Lastly, we have false negatives. They are incorrectly predicted values as negative, also known as type 2 error. From these values, we can calculate other performance metrics like accuracy, precision, recall, and F1 score, which give a clearer idea of how well our model is performing. False positives are more important than false negatives in cases like a medical test for a rare disease. A false positive that is incorrectly saying someone has a disease might lead to unnecessary tests, but it's safer because it ensures we do not miss any actual cases. Whereas for a spam filter, a false negative, which is a spam email getting through, is less risky because you can always delete it. But a false positive, where important emails are marked as spam, could cause you to miss important messages. Moving on to the 10th question, why do we prefer a decision tree over a random forest? A decision tree is a simple model that splits data into branches based on features, making decisions based on these splits. It's easy to understand and visualize and works well for smaller, less complex problems where interpretability is key. A random forest, on the other hand, is a collection of multiple decision trees where each tree is trained on a random subset of the data. It combines the results from all these trees, which usually gives better accuracy and reduces overfitting. You'd prefer a decision tree over a random forest when you need a simple, interpretable model or when computational resources are limited. But if you need better accuracy and robustness, especially for complex datasets, random forests are the better choice. Moving on to the 11th question, what is naive in naive Bayes theorem? Basically, what we're trying to understand here is what does the term naive stand for in this naive Bayes theorem? So, the word naive in naive Bayes basically refers to the assumption that all the features in a dataset are independent of each other. But if you consider real life scenarios or real life data sets, this assumption does not really apply. Why? Because, say, for example, you have a house price prediction data set. You will have feature columns like number of bedrooms, number of bathrooms, balcony, the area of the house, and so on. Now, in real life, if you consider the area and number of bedrooms, number of bathrooms, so are supposed to have some sort of correlation between each other. But what naive Bayes theorem does is it is going to consider that these features are independent of each other, that is, they have zero correlation between each other. Now, this assumption will not apply in real life, but surprisingly, it works really well in many situations, especially for classification problems, right? So, naive Bayes has a major application in classification problems. Alright, so naive Bayes basically calculates the class probabilities based on feature likelihoods, assuming no dependence between them. Clear? So, this is the formula for naive Bayes theorem. This is the posterior probability of the hypothesis. This is what the naive Bayes is trying to calculate. This is the likelihood probability, which basically is the estimated value for each feature, assuming that all the features are independent. Alright, so this is the assumed value. And then we have our hypothesis probability and our evidence probability. Alright, before we move to the next question, let me take you guys to my notebook and show you guys the implementation of naive Bayes. Alright, so the implementation in Python is very easy for any naive Bayes. So basically we have 4 types of naive Bayes theorems. First one is Gaussian naive Bayes. So this works well for continuous data. So the Gaussian naive Bayes basically calculates the mean and the variance, and then it goes for the probability. Then we have multinomial naive Bayes. So this works for the discrete data set. Like it is going to count the data and then it is going to go and calculate the probability. Then we have Bernoulli naive Bayes. This works for binary or Boolean features like yes, no, true, false. Then lastly, we have categorical naive Bayes. So the name itself suggests that it works for categorical data sets. So you can easily import your naive Bayes theorem, whichever one you want to apply, from sklearn.naive Bayes, and then you have to call your function and simply train it using the fit method. Alright, so once that is done, you can go ahead and predict it, and this is what your output is going to look like. Alright, so basically this is how it has classified it as 0 and 1. So that is all about the naive Bayes theorem. Moving on with our 12th question, what is imbalanced data and how do we handle them? So I have already made a video on this particular topic and I have explained each and every concept in a lot of detail. So you guys can go ahead and check it out. But right now I'll just cover this concept in brief so that you guys get a basic idea. Alright, so imbalanced data basically happens when one class in a dataset has a lot more samples than the other. Now what does that mean? So consider this example over here. So this is a balanced data set. Now why is this a balanced data set? So we have 2 classes over here, female and male. Let's call them A and B. Alright. Now class A, that is female, has 51% of samples in a data set, whereas class B, which is male, has 49% of samples in the data set. Now this is a pretty, you can say, balanced situation. Why? Because we have almost equal number of samples, right? 51% and 49% are not that far away. But if you consider this particular scenario, we have 98% of samples in class A, which is our normal, okay, so this imbalanced data is basically for the fraud detection data set. Okay, so we have a fraud detection data set where we have 2 classes, which is normal transactions and fraudulent transactions. Now, our normal transactions are obviously going to be in a higher ratio compared to a fraudulent transaction. So we only have 2% of transactions which were fraud, which is our class B. Alright. So the number of samples of class B is comparatively very less as class A. Right. So this is going to lead in poor performance in the minority class. Basically, our model is going to be biased towards the majority class, right? So say for example, my model predicts not fraud or say normal each time. My model is going to be 98% accurate. Isn't that right? So now with a 98% accuracy, I can say my model is working pretty well. But the cases I am most interested in. Now the entire purpose of training a model on fraud detection dataset is to detect the fraudulent transactions, right? But if my model is failing to do the one goal it was trained for, and it is giving me 98% accuracy, I can say my model is practically useless, right? So this is why we need to handle the imbalanced data sets using techniques like undersampling, oversampling, and lastly we have SMOT, right? So in undersampling, basically we take random samples from our majority class till they are equal in size with our minority class, right? So basically we are making our data smaller. So say we had 1000 samples over here in our majority class and 100 samples over here. Our final data set is going to contain 200 samples, right? We are randomly going to pick 100 samples from our majority class. Whereas in oversampling, if we have 1000 in our majority class and 100 in our minority class, we are going to keep duplicating these samples in our minority class until and unless they are equivalent to the size of our majority class. That is, initially we had 1100 samples, now we are going to have 2000 samples in our entire data set, right? So this is how undersampling and oversampling works. Now over here in oversampling, we are simply duplicating the data randomly in our minority class, right? We are not exactly performing some sort of calculation. Now in our next technique, which is known as SMOT or synthetic minority oversampling technique, over here instead of randomly duplicating the data, we are going to perform some sort of calculation using this particular formula, and we are going to create synthetic data points, and these data points have one rule. That is, they are always going to lie between the axis of two existing data points. Alright, so this is basically what SMOT does. So these are some of the techniques that you can use to handle your imbalanced data. Moving on to the 13th question, state the scenarios when the different tests can be used and also explain the p-test. So now the different tests that we have are z-test, t-test, f-test, chi-square test. Like these are some of the tests that we'll be covering in this particular question. So the first one is z-test. Now this is used for the large samples, generally greater than 30. So whenever we have more than 30 samples, we will be using z-test. Now keep this condition in mind. I'm sure some of you guys must be having a doubt regarding 30 samples. We'll be talking about this in a few minutes, but first let's cover all the tests, right? And your population standard deviation should be known. So say for example, you want to compare the average heights of two cities. So this is a scenario where you would preferably be using z-test. So this is the formula for finding the value of z-test. So you subtract your population mean from your sample mean and you divide it by your standard deviation divided by the total number of observations. Alright. Then the next one that we have is a t-test. This is used for small samples, preferably less than 30, and you don't know your population standard deviation. So say for example, you want to test a new teaching method, whether it improves your test scores in a class or it doesn't, right? So this is the formula for your t-test. So the next one that we have is an f-test. This basically compares the variances of two data sets. So say for example, you want to check the variability in scores from two teaching methods. This is when you'll be using an f-test. So this is the formula. You divide your larger sample variance by your smaller sample variance, and then you can look up the f-test table to find the value. Then we have a chi-square test. This is used for categorical data to test relationships between your features. So say for example, you want to analyze whether genders impact the product preference, right? So for cases like that, you would be using a chi-square test. This is the formula for your chi-square test. C is your degree of freedom, O is your observed value, and E is your expected value. Alright. Then lastly, we have our p-value. Now, the p-value is not particularly a test. Rather, it is used to determine whether the result of a statistical test is significant or not. Right? So basically, a p-value is a decision rule that compares with alpha. Now, alpha is generally 0.05. Right? This is the standard value of alpha. It could vary based on the problem, but in general, we keep it 0.05. Now, if our p-value is less than or equal to 0.05, we reject our null hypothesis. But if it is greater than 0.05, we fail to reject the null hypothesis. That is, we accept our null hypothesis. Alright. So, say for example, we want to test a new drug, right, and its effects. So, we'd be using a p-value in this case. Now, before we go ahead, let me quickly take you to my Google Notebook. Alright. So, we know the general rule of using a t-test and a z-test is whether a sample size is greater than 30 or less than 30. But if you take practical scenarios or real life scenarios, our data set usually has around 1000 samples, right? Whenever we go to train a model and we pick a data set, it is going to have at least 1000 samples. Now, out of those 1000 data points, if we try to take out only 30 samples, it does not make sense, right? Our data set is going to have at least 500 or 600 data points to be able to learn and have an accurate output, right? So in a problem statement, whenever there is mean or average mentioned, we use a t-test, and whenever there is a percentage or proportion mentioned, we use a z-test. Clear? So theoretically, we take the 30 sample rule, but when it comes to practical scenarios, this is the condition that we follow. Alright, so let me quickly show you how it is implemented. So I am going to implement t-test. So this is my data set and I have taken a sample size of 1000. I have decided my new sample data. And what I'm going to do is I'm simply going to perform a one sample t-test. So I'm going to import my t-test from scipy.stats. I've declared my variables t-stat and p-value. And I've passed my column purchase. And I've given the sample size over here. And after performing that, I have got my p-value as 2.8. Right? Now this 2.8 is clearly greater than 0.05. This means we have to reject our null hypothesis. And over here we have given a conclusion, that is whatever was our alternate hypothesis has become our conclusion now. Alright, so this is basically how we perform any test in Python using the libraries. So moving on to the 14th question, what are eigenvalues and eigenvectors and why are they important? So let me quickly explain a scenario where we have a data set which is in a 3D form. Alright. Now if I want to make my model simple and understand the data better, my goal would be to transform this 3D data into a 2D data, while also being able to retain the maximum information out of this particular data. Now in order to do that, I can compress my data from any one of these dimensions, either from my height, my width, or my breadth. But if my goal is to retain the maximum information, I'm definitely going to compress it from an angle that has the largest area. And if I feel this particular side is going to give me the maximum information out of my data, I'm going to compress my data set from this particular angle. So now what eigenvalues and eigenvectors are? Eigenvalues are basically going to tell me how much my data set has shrinked or stretched during my transformation. Whereas my eigenvectors are going to define the direction from which my data sets have been shrinked or stretched, right? And the direction is always going to remain unchanged during that transformation. So I hope this is clear, and this is the basic formula that is used to calculate the eigenvector, which is represented with the x vector, and we have eigenvalue represented by lambda. Alright, so let's quickly look at the example. So we have a matrix denoted by A, which is 2, 0 and 0, 3. Now in order to calculate the eigenvalue, this is the formula that we'll be using. Alright, we need to calculate our matrix A minus lambda into I. Now I is the identity matrix and it is represented using this particular matrix. Alright, so now we know the determinant of this particular matrix is going to result to 0. Alright, now this is going to help us give the final values of the lambda. Alright, So now to calculate a minus lambda I, this is the kind of calculation we'll be performing. We've already multiplied lambda with our identity matrix, and this is going to be the resultant matrix after multiplication, right? So after subtraction, this is going to be our final matrix, 2 minus lambda and 3 minus lambda. Once we equate it with 0, we get the values of lambda, which is 2 and 3. Alright, so we get two eigenvalues, which is 2 and 3. Now, in order to calculate the eigenvectors, we are simply going to multiply x with a minus lambda I. Alright, now we know the values of lambda, which is 2 and 3. So we are going to substitute these values in lambda, and once we do that, we're going to get a matrix like this, and after we multiply this matrix with x, our x value is going to be somewhat like this. Alright, so basically these are the steps that we follow in order to calculate the eigenvalues and eigenvectors. Alright, now why are they important in data science? So eigenvalues and eigenvectors are used for principal component analysis. Basically, they reduce the dimensions of large data, and they're used to identify the important features using eigenvectors. Then they're used for graph analysis and stability analysis also. Alright, moving on to the 15th question. How do you ensure that the sample chosen for a study truly represents the entire population? Now, in order to answer this particular question, first we need to understand what is sampling. So whenever we're conducting a study, it is not always going to be possible to include everyone in the population, right? So we're going to use sampling to study a smaller, more manageable group. So the first step is to define who or what you are studying. That is, we need to define the target population. So say for example, we want to know the opinions of college students for a particular study, right? So our target population is going to be only the college students, not their parents, not their siblings, right? So that is how we define the target population. The next step would be to choose the right sampling method. Now we have over here 4 different types of sampling methods. So the first one is simple random sampling. Over here, everyone in the population is going to have an equal chance of being selected, right? There is not going to be any particular bias towards any person. The next one is systematic sampling. So over here, every nth person or nth member from a list or sequence is going to be selected. So basically over here, we're going to apply some sort of algorithm or some sort of system that every third person that we meet or every third person that we interview is going to be part of our data set. Alright. Then what we have is a stratified sampling. Over here, we divide the population into groups, that is our strata, and take a random sample from each group. Alright. So say for example, I am interviewing college students. I'm going to divide the college students into groups, say depending on their streams, right? So maybe I make groups of computer science and MBA and other fields like that, right? So once I have divided the college students into groups, I'm randomly going to pick a student from each group. Alright, so this is what is known as stratified sampling. Then lastly, we have cluster sampling. Over here, we divide the population into clusters, randomly select the clusters and include all the members from those clusters. Alright, so over here, I'm not going to select an individual from a group, rather I'm going to select the entire group randomly. Alright, so this is known as cluster sampling. So depending on our problem statement, we need to choose the right sampling method. Then third is to ensure sample size is adequate. What this means is larger samples are better because they reduce the likelihood of errors. So say for example, if we are polling 10 people to understand a city's preference, we are going to miss the diversity of opinions, right? A sample of 1000 is going to be much more reliable and much more adequate. So this is what ensuring the right sample size means. Then lastly, we need to avoid bias. Bias occurs when certain groups are favored over the others. So say for example, we only survey people from urban areas and we ignore the rural areas. So our result is going to be completely skewed, right? Obviously, the opinions of urban people are not going to match with the ones of the rural people. So this is basically how bias enters the sample. So we need to avoid bias in order to have a sample that truly represents the entire population. Alright, moving on to the 16th question. What is a gradient and gradient descent? So gradient basically measures the slope or rate of change of a function. Alright, this is the formula for gradient. Basically, we have a function and we have a gradient with respect to x and with respect to y. Basically, all the independent variables of a function. So we perform differentiation and we get the final value. Alright, so gradient basically points in the direction of the steepest increase. Alright, so if in this case we had our y value as say positive and x value also positive, then this gradient would be signifying that in whatever direction we are moving so far is the direction of the steepest increase. That is, we are going in the increasing direction, right? It is leading us to the maxima. Alright, but say in case one of these value was negative instead of positive, this particular value was negative. Now this would indicate that the direction that we are heading to is the opposite of the direction of our increase. That is, we are leading to towards the minima. Alright, so basically gradient tells us how much the function is increasing or decreasing as we move in different directions. Alright, then we have gradient descent. Now this is a method to find the minimum of a function by moving in the opposite direction of the gradient. Now we already discussed gradient is going to lead us in the direction of maximum value. And now gradient descent is a method to find the minimum of a function. So obviously gradient descent is going to move in the opposite direction of the gradient. Alright, so say for example this is our function. Alright, now in order to reach the minimum point which lies over here, what we are going to do is at every point we are going to calculate the gradient. Alright, now if the gradient is telling us that this particular direction is going to lead us to the minima and this particular direction is going to lead us towards the maxima, we are obviously going to move in the direction that is leading us towards the minima, right? And we are going to check that at each particular point until and unless we reach a point which is the global minima. Alright, so basically we are trying to reach towards the bottom of a valley. Now this optimize the models by minimizing error. Alright, so this is basically what gradient and gradient descent means. Okay, moving on to the next question, define confounding variables. Now confounding variable is something that influences both the independent and the dependent variables. Alright, so confounding variables are often referred to as hidden variables, and they can make a relationship appear between an independent variable and a dependent variable even if there is none. Alright, so this is basically what confounding variables do. Now say for example you're studying the relationship between exercise and weight loss. You find that people who exercise tend to lose more weight. But if you don't account for people's diet, it could be the diet causing the weight loss as well, right? And not just the exercise. So in this case, diet becomes our confounding variable. Alright, so this is basically how confounding variables work. Moving on to the next question, define bias variance trade-off. Alright, now in order to understand bias variance trade-off, we need to understand these terms separately. So bias is basically an error due to oversimplistic models that don't capture all patterns in the data. Alright, so this is an example of high bias in our data. So these are our data points, and since we have a high bias in our data, we are not really trying to understand all the data points. Rather, due to the simplicity of our model, we are just going to fit a straight line where we assume that most of our data points are being touched. But this is a case of underfitting. Alright. Then the next thing that we have is variance. Now this is an error due to models that are too complex and overfit the training data. Now this is the opposite of high bias. So basically when we have a high variance or low bias, what we do is we try to learn each and every data point in the data set. This leads to overfitting, and this is also a case where the model performs really well on the training data but very poorly on the unseen data. Alright. So a simple example or simple analogy of a high bias would be a person studying for an exam, and the person is not really trying to understand the definition and the examples of each concept. Rather, he just looks at the headings of each concept. Right? This would be a case of underfitting. But if that same person tries to memorize each and every detail of a particular concept, so he even memorizes the numericals, the exact value of each numerical, the person is going to perform extremely well if the exact same questions appear in the data. But if the values of a particular numerical or a particular question are changed even slightly, the person is going to fail in that particular case. So this is an example of overfitting. Alright? And overfitting happens when there is a low bias or a high variance And underfitting happens when there is a high bias or low variance. Alright. Now the entire goal of bias variance trade-off is to find the right balance between bias and variance. Now if we have a low bias and a high variance, our model is going to fit the data well, but it is not going to generalize it. Alright, which basically means overfitting. But if we have a high bias and low variance, our model is going to be too simple and it is going to miss important patterns or even the general patterns, the basic learnings of the data. Alright. So the goal is to find a spot where the model is complex enough to capture patterns but simple enough to avoid the overfitting. Alright. So this is basically what it means. This is the kind of point that we're looking for, which gives us the optimal solution. Moving on to the 19th question. When do we use deep learning in a project? So in order to answer this question, we need to answer what is deep learning. The deep learning is basically a subset of machine learning which uses neural networks with many layers. Alright, so it can handle complex data which includes images, text and audio. Alright, so here is an image that indicates machine learning and deep learning. So in machine learning, we have an input data. Then we perform feature extraction and then we perform classification and then we get an output. But in deep learning, we have an input data and our feature extraction and classification are performed all together with the help of neural networks and we straight away get the output. Alright. Now, when do we use deep learning in a project? So, we use deep learning if we have a very complex and large data set. So when our data is large and unstructured, that is, our data includes images and videos, right? So this basically makes our data complex and it would be better to use deep learning in such cases. Alright, so say for example, we need to analyze the medical images. Alright, so say it is a cancerous cell data set. Alright, and we need to define whether the cell contains cancer or not. So we can use deep learning and basically neural networks in cases like this. Then comes the need for feature extraction. So whenever we need to automatically learn useful features from raw data, say for example, we need to identify objects in a photo. Alright, so we can use deep learning again. Then when our model needs high accuracy, so when a high level of accuracy is crucial for the task, we would go for deep learning. Alright, so say for example, self-driving cars will need precise object detection and in real time, right? So we would go for deep learning. So some projects that use deep learning would be image classification, speech recognition and natural language processing. Some other would be a chatbot, traffic sign classification, newspaper summarizer, image caption generator, human age detection and so on. Moving on to the 20th question, what is OOB error and how is it useful? So OOB error basically stands for out of bag error, which is a concept in random forest models. Now, this is a way to estimate the model's accuracy using the leftover data that isn't used during the training. Alright. Now, we have an original training data of size 5. Now, we are going to do sampling with replacement. So, we have multiple decision trees and we are going to use the sample size of 3 for each particular decision tree. Now, OOB error is basically when random forests build multiple decision trees, they train each tree on a random subset of data called a bootstrap sample. During this training, some data points are going to be left out. Now, these are called the out-of-bag data points or OOB error. Alright. So, once the random forest model is trained, the out-of-bag error or the out-of-bag data is going to be used to test the predictions. By aggregating the errors from all the trees, we calculate the OOB error. This is an estimate of how well the model performs on unseen data. Alright. So OOB error is useful for internal validation, which basically provides an unbiased accuracy estimate without needing to separate validation data. Then it also saves resources. So it is going to eliminate the need completely to split the data set into training and testing sets. Right? Since we are already leaving out some data to be tested on, we do not need to split our data set separately. Then it also provides performance check. So it is going to help identify if the model is overfitting or underfitting. Right? So some examples of OOB error are suppose a random forest model trains on 70% of the data, which is a bootstrap sample, and the remaining 30%, which is our out of bag data, is going to be used to test each tree's prediction. Now we aggregate these predictions to compute the OOB error in total. Alright. Moving on to the 21st question, define and differentiate between convex and non-convex functions. Now as you can see in this image, we have two graphs. Let me tell you, this is a convex function and this is a non-convex function. Alright. Now in order to understand convex and non-convex, let us recall gradient descent. Right. Now the purpose of gradient descent was to find the minimum of a function, right? This was used to minimize the error or loss of a model, correct? Now, if we talk about this particular function, if we start from any point, say initially we have a point over here, or you can say we start from this particular point, we know that our minimum point or a minima lies somewhere over here. Is that correct? As you guys can see, this is going to be, or somewhere over here, this is where the minimum of our function is going to be located. Now, if we start from this particular point and we calculate the gradient, we are going to be led into a direction somewhere over here, correct? Then when we calculate the gradient over here, we are going to be again led in this particular direction. And this process is going to be continued until and unless we reach this particular point. Now, in a convex function, it does not matter what our starting point is, because no matter from wherever we start, we are somehow or the other going to be led to the minimum point of our function, right? So convex functions are said to have one and only one global minima. Right? Now if we talk about non-convex functions over here, so say my starting point is somewhere over here. Now if I try and calculate the gradient, I could be directed in this particular direction or this particular direction. Right? Or I could be directed towards this particular direction depending on the exact slope of the function at that particular point, right? So say if I'm directed in this particular direction, then I calculate the gradient in this particular point again, I'm going to be led somewhere over here. And once I reach this particular point is going to be considered my global minimum. But is that correct? Is this my global minimum? No, it is not. This point is supposed to be my global minimum. But since I do not have any lower point than this at this particular point, this point is going to be considered my global minimum. So basically, convex functions are said to have multiple local minimas. Alright, as you can see over here, this is another minima, this is another minima, this is another minima. So whether or not you reach the global minima depends completely on your starting point. Alright, so say if you start somewhere over here, there is a higher chance you reach the global minima rather than some other local minima. Alright, so these are your local minimas. Alright. So this is a basic differentiation between convex and non-convex functions. So a convex function is where the line segment between any 2 points on the curve lies above or on the curve. There is only one and only one global minima, and it is easier to optimize. Alright. A non-convex function is a function where the line segment between any 2 points on the curve may lie below the curve. Alright. It has multiple local minima and maxima, and it is much harder to optimize. Moving on to the 22nd question, what is collaborative filtering? So collaborative filtering is basically a method that is used to make recommendations based on user behavior. It relies on similarities between the users or the items. So collaborative filtering is again divided into two types. First is user-based and second one is item-based. Alright, so user-based collaborative filtering is basically when items are suggested based on users with similar preferences. Alright, and item-based collaborative filtering is basically when the items are suggested similar to what the user has liked previously. Alright, let's understand this with the help of an example. So there are two users, user 1 and user 2. So both these users have several movies in common. That is, they have both liked these movies or they have highly rated these movies. Now, if user 1 has watched a particular movie that user 2 has not, there is a high chance that this particular movie is recommended to user 2. Alright, so this is basically how user-based collaborative filtering works. Then we have item-based filtering. So basically we have three users who go shopping. So user 1 has shopped for these particular items, whereas user 2 has shopped for these particular items. Now, if a third user has shopped for this particular item, this user is going to be recommended items from the similar category. Now, if this is not clear, let me give you another example. So, say if you buy a book about machine learning. Now, what the system is going to do is the system is going to recommend similar books in the same category to you as well. Maybe you get recommendations of deep learning as well, right? So, this is how item based filtering works. Based on your previous preferences, based on your previous likings, you will be recommended items in the future. Clear? Moving on to the 23rd question, what is a lazy learning algorithm? Now, lazy learning basically refers to algorithms that postpone generalizing from the training data until they receive a query that is a new data point. Now, they don't process the data during training, but instead they store it for later use. Alright? So, basically, they delay generalization data until a query is made. Alright? So, in the training phase, a lazy learning training is almost instant because the algorithm is going to store the data set without building a complex model. Whereas in the prediction phase, when a new query comes in, the algorithm is going to compare it to the stored data to make a prediction. This step is going to take time because this is going to involve looking through all the stored data. Alright. So one example of lazy learning algorithm is the k nearest neighbors algorithm. Alright. Now what k nearest neighbors does is, so say you have 5 data points about fruits. Alright, let's say these are apples. Some are apples, some are oranges. Alright, they're already classified. Alright. Now say you have a new data point, which is basically a new fruit. Now in order to classify this new fruit, what KNN is going to do is, it is going to compare it to the stored data. Right, these are your stored data points. Right, all these are your stored data points. Now KNN is going to compare the stored data point and check the k closest neighbors for the new data point. Alright, so say if most of the neighbors of this new data point are apples, KNN is going to classify it as apples, otherwise it is going to classify it as oranges. Clear? So this is how KNN works, and this is basically what lazy learning algorithm works. Alright. Moving on to the 24th question. Describe the differences between bagging and boosting algorithms. Alright. So bagging basically works by creating multiple subsets of the training data. So bagging and boosting are basically two powerful techniques in machine learning that are used to improve the performance of models. Alright. So both of these models are basically going to combine multiple models, but their approach and goals are completely different. Okay. So first let's see bagging. Now what bagging does is, it is going to create multiple subsets of the same training data, and it is going to train independently on each subset. Alright, so basically bagging works in parallel, whereas boosting trains the model sequentially, where each new model is going to focus on correcting the errors made by the previous model. Alright, so the final prediction is going to be a weighted combination of all the models. Clear? The basic difference is clear. So let's look at the approach. So bagging basically follows a parallel model training, whereas boosting follows sequential model training. The goal of bagging is to reduce variance, whereas boosting has the main goal of reducing bias and variance. Alright. The basic method of error handling in bagging is to have equal weights for all the models, whereas boosting corrects errors of the previous models. Alright. So bagging has a lower risk of overfitting, whereas boosting has a higher risk of overfitting if not controlled. Alright. So basic example of bagging would be random forest, where we have multiple decision trees working parallelly on each subset of the training data. Whereas boosting algorithms would be AdaBoost, gradient boosting, and XGBoost. Alright. Moving on to the 25th question. Explain the central limit theorem and its importance in data science. CLT, or central limit theorem, basically states that the sampling distribution of the sample mean approaches a normal distribution as the sample size increases. Alright. So as you can see over here, as we increase the sample size, the distribution of our data approaches a more normal curve. Alright. So this basically enables the use of statistical methods that rely only and only on normal distribution. It's going to help make inferences about the population using sample data, and it is used in hypothesis testing, confidence intervals, and many more such inferences. All right. So, a basic example would be, say you want to measure the average height of students in a school. Now, the individual heights might vary a lot and may not follow a normal pattern, right? But if you repeatedly take random samples of students, calculate the average height for each sample, and then plot these averages, the graph will eventually form a normal distribution as the sample grows. All right. So, the importance of CLT in data science is mainly the foundation for statistical analysis. So, stats plays a major role in data science, and CLT is a basic foundation of stats, right? Many statistical methods assume normality, and CLT is going to ensure that we can apply these methods even when the original data isn't normal. All right. Then comes sampling and efficiency. All right. So instead of analyzing the entire population, we can work with smaller and more manageable samples and still get reliable results. Finally, we have hypothesis testing. All right. So CLT is used to calculate confidence intervals and perform hypothesis tests, which are essential for making data-driven decisions. All right. So this is the importance of CLT in data science.
Just a quick info, guys. Intellipaat offers a data science course which will help you master Python, SQL, machine learning, AI, and Power BI. Get a data science certification from IIT Empower, an innovation hub of IIT Madras. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given in the description and take the first step towards the career growth with the data science course.